Hey everyone, welcome to our AI full course by Simplilearn. What if you could teach machines to think, learn, and even create just like humans? Now that's the power of AI, and you are about to unlock it. Welcome to a hands-on, future-ready course where you will explore how AI is transforming everything from business to creativity. First, we'll start with the basics and quickly move into powerful concepts like machine learning, deep learning, reinforcement learning, and Gemini agents. You'll get comfortable with cutting-edge tools like N8N, Langchain, and even learn how to build your own AI websites. And as you progress, we'll dive into agentic AI, multimodal system, and tackle real-world challenges like AI bias and model evaluation. And by the end, you won't just understand AI, you'll know how to use it, build it, innovate, and lead. So let's get started. Now, before we commence, if you're interested in growing your career in AI and machine learning, this course is your great way to start. The Professional Certificate in AI and Machine Learning by Simplilearn, Purdue University Online, and IBM will help you master key AI skills like ChatGPT, LLMs, deep learning, and agentic AI through live classes and hands-on projects. So in just 6 months, you will work on real-world industry projects, use 18+ popular tools like Python and TensorFlow, and you can earn certificates from Purdue and IBM. You'll also get career support including resume help, mock interviews, and job assistance. So whether you're switching careers or upskilling, this course will give you the latest AI knowledge and practical experience to stay ahead. So guys, hurry up and enroll now, and you can find the link in the description box below.
Liam, a 19-year-old freshman, recently joined an Ivy League college to study history and political science. While reading about thinkers and scholars of the early 20th century, he stumbled upon a name, Alan Turing. Liam was fascinated by Alan and realized that the computer that he knows of today, Alan is considered to be the father of modern computer science that eventually led to the invention of his computer. But there was something that was even more fascinating about Alan. Although Alan Turing was famous for his work developing the first modern computers, decoding the encryption of German Enigma machines during the Second World War, he also built a detailed procedure known as the Turing test, forming the basis for artificial intelligence. Liam had his mind blown by this fact. He realized that AI is not a modern phenomenon, but rather more than a thought experiment existing since the early 90s. Liam used AI tools like ChatGPT, Perplexity, and Consensus on a daily basis for his research. He had a smartphone that he used for multiple tasks, like using Siri or Google Assistant to find local food places, using autocorrect on multiple apps like Instagram and WhatsApp, and even AI photo editing features. He realized that AI has seeped into almost every aspect of his life, from making trivial decisions like where to have his morning coffee, to complex AI tools like ChatGPT for his research, to even his father's self-driving Tesla that he used whenever he got a chance to. Artificial intelligence, or AI, in the 21st century has become a very subtle technology that exists in every human's life without them even realizing it. But what is this AI? Does this mean robots in a completely dystopian AI warlord future? Not really. Let us dive a little deeper into understanding everything about AI. Artificial intelligence, or AI, is like giving computers the ability to think and learn much like humans do. Imagine teaching a friend how to solve puzzles, and then that friend can solve different types of puzzles on their own. AI works similarly. It helps computers understand and carry out tasks that typically need human intelligence. These tasks include recognizing faces and photos, chatting with us through smart assistants like Siri or Google Assistant, and even driving cars. Think of AI as a smart helper that makes our daily lives easier. It can learn from data, make decisions, and improve itself over time. This means that AI isn't just about robots taking over the world, it's more about using smart technology to assist us in various ways, making complex tasks simpler and everyday routines smoother. AI has found its way into many areas of our lives, often making things easier without us even realizing it. In healthcare, for example, AI helps doctors by quickly analyzing medical images like X-rays to detect issues faster than the human eye might. In finance, AI works to keep our money safe by spotting unusual activities in our bank accounts that could indicate fraud. When you stream shows on Netflix, AI suggests movies and series based on what you've watched and liked before. In retail, AI manages stock and predicts what items will be popular, ensuring that store shelves are filled with what customers need. Even in our homes, AI is at work through smart devices that learn your schedule and adjust the temperature automatically, or lights that turn on when you enter a room. AI touches so many parts of our daily lives, making things more convenient and efficient. One of the best AI applications today, which is very widely known and used, is ChatGPT, an advanced AI developed by OpenAI that can chat with you just like a human would. Imagine having a friend who knows almost everything and can help you with any question or topic. That's what ChatGPT does. But how does it work? ChatGPT is powered by something called a transformer model. This is a type of machine learning model that learns patterns in language by looking at a vast amount of text data from books, websites, and other sources. Think of it like reading millions of books and remembering important information from all of them. When you ask ChatGPT a question, it doesn't just pull out a random answer. Instead, it looks at the words you used, understands the context, and predicts what a good response would be based on what it has learned. For example, if you ask about the weather, it understands you are looking for current weather conditions and gives you relevant information. If you ask it to help with homework, it draws on its knowledge to explain concepts clearly. ChatGPT uses a process called deep learning, which is a bit like how our brains work. It breaks down sentences into smaller parts and looks at how these parts fit together. This helps it understand not just the meaning of individual words, but also how they combine to convey a complete idea. This is why ChatGPT can handle complex questions and give answers that make sense. To make sure it provides useful and accurate information, ChatGPT was trained on a diverse range of topics. This training helps it recognize and generate text on anything from science and history to entertainment and daily life. It's like having an encyclopedia and a friendly tutor rolled into one. Similar to ChatGPT, there are a plethora of other tools and applications being developed every day that are trained for various purposes using varied kind of data sets. For example, DALL-E, which has been trained on a diverse data set of text and images from the internet. Stable Diffusion, which has been trained on a variety of images and corresponding text descriptions. Tesla Autopilot, which has been trained on sensor data from Tesla vehicles and driving data, and so on and so forth. AI is a remarkable technology that holds great promise for the future, offering solutions to some of the world's most pressing challenges. Imagine a future where AI takes care of routine tasks, giving us more time to be creative and focus on what we love. AI can help in many ways, from improving medical treatments to making our daily lives more efficient. However, it's essential to use AI responsibly. This means creating guidelines and rules to ensure AI is developed and used in ways that benefit everyone. By embracing AI and understanding its potential, we can look forward to a future where technology and human creativity go hand in hand. AI is not just about smart gadgets. It's about opening new possibilities and making our world a better place. The future of AI is bright, filled with opportunities for innovation and progress, helping us achieve things we never thought possible.
Today, we'll take you through the exciting roadmap of becoming an AI engineer. If our content piques your interest and helps fuel your curiosity, don't forget to subscribe to our channel. Hit that bell icon so you never miss an update. Now let's embark on this AI journey together. As artificial intelligence continues to revolutionize various industries, AI engineers stand at the forefront of this technological wave. These professionals are essential in crafting intelligent systems that address complex business challenges. AI projects often stumble due to poor planning, subpar architecture, or scalability issues. AI engineers play a crucial role in overcoming these hurdles by merging cutting-edge AI technologies with strategic business insights. So in this video, we'll guide you through the essentials of becoming an AI engineer. Let's start with the basics. What does an AI engineer do? An AI engineer builds AI models using machine learning algorithms and deep learning neural networks. These models are pivotal in generating business insights that influence organizational decision-making. From developing applications that leverage sentiment analysis for contextual advertising to creating systems for visual recognition and language translation, the scope of an AI engineer's work is vast and impactful. So to succeed as an AI engineer, you need a blend of technical prowess and soft skills. So now let's break down this 8-month plan. Month 1, Computer Science Fundamentals and Beginners Python. So before we delve into AI, it's crucial to establish a strong foundation in computer science. This month, you should focus on the following topics. Data representation. Understanding bits and bytes, how text and numbers are stored, and the binary number system is foundational for everything in computing. This knowledge helps in comprehending how computers interpret and process data. Now next comes computer networks. Learn the basics of computer networks, including IP addresses and internet routing protocols. It's essential to understand how data travels across networks using UDP, TCP, and HTTP, which form the backbone of the internet and the World Wide Web. Next comes programming basics. Begin with the basics of programming like variables, strings, numbers, conditionals, loops, and algorithm basics. These fundamentals will allow you to write and understand simple programs. Simultaneously, you'll also start with Python, the preferred language for AI. So learn about variables, numbers, strings, lists, dictionaries, sets, tuples, and control structures like if conditionals and for loops. And then move on to functions and modules. Understand how to create functions, including Lambda functions, and work with modules by using pip install to add functionality to your projects. Next comes file handling and exceptions. You should also practice reading from and writing to files, as well as handling exceptions to make your programs more robust. Finally, grasp the basics of classes and objects, which are crucial for writing organized and efficient code. So this comprehensive overview sets the stage for more complex programming tasks that you'll encounter in the following months. Now in month 2, you'll move on to data structure algorithms and advanced Python. So building on the foundations from month 1, we'll now delve into data structure and algorithm. So familiarize yourself with the concept of big O notation to understand the efficiency of different algorithms and data structures. Learn about arrays, linked lists, hash tables, stacks, queues, trees, and graphs. Mastering these structures will allow you to store and manipulate data effectively. Now next comes algorithms. You should explore algorithms such as binary search, bubble sort, quick sort, merge sort, and recursion. These are essential for optimizing your code. And parallelly, you'll advance your Python skills. So you can dive into inheritance, generators, iterations, list comprehensions, decorators, multi-threading, and multiprocessing. These topics will enable you to write more efficient and scalable code. So this month's learning prepares you to handle complex data operations and enhance your coding efficiency. Now in month 3, you'll move on to version control, SQL, and data manipulation. So in the 3rd month, the focus shifts to collaboration and data management. Number 1, version control. So understand the importance of version control systems, especially Git and GitHub. So learn basic commands such as add, commit, and push. You should also learn how to handle branches, reword changes, and understand concepts like head, diff, and merge. So these skills are invaluable for tracking changes and collaborating with other developers. Next, pull requests. Master the art of creating and managing pull requests to contribute to collaborative projects. Next, we'll dive into SQL for managing databases. So first, we'll start with SQL basics. So learn about relational databases and how to perform basic queries. And then you'll move on to advanced queries. Understand complex query techniques such as CTEs, subqueries, and window functions. And then comes joins and database management. So study different types of joins like left, right, inner, and full join. You should also learn how to create databases, manage indexes, and write stored procedures. Additionally, you will use NumPy and Pandas for data manipulation and learn basic data visualization techniques. This comprehensive skill set will be crucial as you move into more advanced data science topics. So now in month 4, you'll deal with maths and statistics for AI. So mathematics and statistics are the backbone of AI, and this month is dedicated to these critical subjects. So first, learn about descriptive versus inferential statistics, continuous versus discrete data, nominal versus ordinal data, measures of central tendency like mean, median, mode, and measures of dispersion like variance and standard deviation. After that, understand the basis of probability and delve into normal distribution, correlation, and covariance. After which, you should move on to advanced concepts. So you can study the central limit theorem, hypothesis testing, p-values, confidence intervals, and so on. In parallel, you should also study linear algebra and calculus. So in linear algebra, learn about vectors, matrices, eigenvalues, and eigenvectors. And in calculus, cover the basics of integral and differential calculus. So this mathematical foundation is essential for developing and understanding AI models, setting you up for success as you transition into machine learning. Now in month 5 comes exploratory data analysis, which is EDA and machine learning. So with a solid foundation in math and statistics, you are now ready to delve into machine learning. Number 1, pre-processing. Learn how to handle NA values, treat outliers, perform data normalization, and conduct feature engineering. You should also understand encoding techniques such as one-hot and label encoding. You'll also explore supervised and unsupervised learning with a focus on regression and classification, and learn about linear models like linear and logistical regression and non-linear models like decision tree, random forest, etc. And then understand how to evaluate models using metrics such as mean squared error, mean absolute error, MAPE for regression and accuracy, precision recall, etc. Then comes hyperparameter tuning. Learn about techniques like grid search CV and random search CV for optimizing your models. After which you'll move on to unsupervised learning. Here you can study clustering techniques like K-means and hierarchical clustering and delve into dimensionality reduction with PCA. So this month's focus on EDA and model building will prepare you for more complex AI applications. Transitioning to the next phase, you will begin to work on deploying these models and real-world scenarios. So in month 6 comes ML Ops and machine learning projects. So this month will cover the operational aspects of machine learning and work on practical projects. So in ML Ops basics, learn about APIs, particularly using Fast API for Python and server development. Understand DevOps fundamentals, including CI/CD pipelines and containerization with Docker and Kubernetes. You should also gain familiarity with at least one cloud platform like AWS or Azure. Now in month 7 comes deep learning. So in this month, we delve into the world of deep learning. So number 1 comes neural network. So learn about neural networks, including forward and backward propagation, and build multi-layer perceptrons. After which we'll move on to advanced architectures. So here explore convolutional neural networks, which are CNNs, for image data, and sequence models like RNNs and LSTMs. So this deep learning knowledge will be crucial as we move into specialized areas of AI in the final month. Now in the final month, the 8th month, comes NLP or computer vision. So the final month, you have the option to specialize in either natural language processing, NLP, or computer vision. So first we'll level NLP track. So here you should learn about regex, text representation methods like count vectorizer, TF-IDF, Bow, word2vec, embeddings, and text classification with naive Bayes. And familiarize yourself with the fundamentals of libraries like Spacy and NLTK and work on end-to-end NLP project. And talking about computer vision track, focus on basic image processing techniques like filtering, edge detection, image scaling, and rotation. Utilize libraries like OpenCV and build upon the CNN knowledge from the previous month. Practice data preprocessing and augmentation. So by the end of this month, you should have a solid foundation in your chosen specialization, ready to embark on your AI engineering career. So in conclusion, adopting AI is more than just a trend. It's a strategic move that can transform your organization's approach to machine learning. So do check out our professional certificate course in AI and machine learning, which is designed to equip you with the skills needed to excel in this dynamic field. Through live classes led by industry experts, masterclasses from IIT Kanpur faculty, and hands-on projects, you'll gain a competitive edge in AI. To enroll in this program, candidates should have a bachelor's degree with a 50% or higher average, preferably 2 or more years of work experience and foundational knowledge in programming and mathematics. Check out the course link in the description box below. So that's all for today's video on becoming an AI engineer. We hope you found this guide valuable and informative.
Let me take you back to a factory floor in South Korea. Every day, workers used to spend hours inspecting thousands of smartphone parts by hand. It was slow and tiring, and even the smallest human error could cost the company millions. Then they introduced an AI-powered camera system. Overnight, that changed. Now, these machines catch defects instantly, once the human eye can't even spot and the workers. They have shifted to safer, more creative roles. This isn't science fiction, it's happening right now. And that's the power of AI most people never see. When we hear AI, we always think ChatGPT, Midjourney, maybe a few more smart assistants that answer questions and write stuff. But here's the truth. That's just the surface. Behind every chatbot, every voice assistant, every cool AI demo, there's a massive hidden world working behind the scenes. And today, I want to show you that world. In this video, we are not just talking about tools, we are peeling back the layers. What powers these tools, how they learn, what makes them smart and sometimes biased, and why understanding this is a key to anyone who wants to be future ready. So let's start with what's most popular to know. You've probably used ChatGPT, Bard, Jasper, or even AI tools built into your phone. They are impressive. They talk like humans, write like authors, and sometimes even think like strategists. They feel magical, but they are not magic. They are powered by something much bigger underneath. At the core of these tools is something called an LLM, which is a large language model. Think of it like the brain behind the chatbot face. An LLM is trained on huge amounts of text from websites, books, code, social media, and learns to predict what words come next in a sentence. It doesn't understand like a human does, but it's brilliant at patterns. You type a prompt and the model predicts most likely next word again and again, millions of times per second. But even that brain needs fuel, and that fuel is data. We are talking about massive web archives like Common Crawl, curated information from Wikipedia, code from GitHub, opinions and trends from Reddit and Twitter. This is where the model gets its knowledge, and also sometimes it flaws, because data isn't always clean or fair. Let's talk about the risk. Just like real people, if AI is trained on biased or toxic content, it can repeat that back to us. That's why ethical AI development is a big deal. Developers have to clean, test, and constantly fine-tune these models to keep them safe, fair, and useful. Talking about the real-world impact, so where's all this AI power going today? It's transforming manufacturing, logistics, finance, education, and more. In factories, AI predicts demand months ahead. Smart machines check product quality in real time. Sensors alert teams before machines break down. Robot assist, not replace humans on the floor. And the numbers back this up. Back in 2020, the manufacturing industry spent over $6.2 billion on AI. And by 2030, that number is expected to hit around $181 billion. That's not a trend, it's a revolution. Nearly 97% of CEOs now say AI is going to be a big part of their future operation. And over half are already investing more in AI than in robotics, cloud, or any other technology. They are seeing the real results: better performance, lower cost, and faster growth. So the next time someone talks about how cool ChatGPT is, remember it's just the tip of the iceberg. The real story is hidden underneath. That is the massive data sets, the deep learning models, the ethical decisions, the engineering work, and the massive impact across the industries. That's where the future is being built. If you want to truly understand AI, not just use it, but shape it, start exploring the full picture. Learn how it's made, understand how it learns, dive deeper than the surface level tools. Because the more you know what's under the iceberg, the more powerful you become above it. Also, just a quick information, guys, if you're interested in mastering the future of technology, then the professional certificate course in generative AI and machine learning is the perfect opportunity for you. Offered in collaboration with the ENICT Academy, IT Kanpur, this 11-month live and interactive program will provide you hands-on expertise in cutting-edge areas like generative AI, machine learning, tools like ChatGPT, DALL-E 2, Hugging Face, and many more. So hurry up and enroll now, and find the course link in the description box below and in the pinned comments.
We've looked at a lot of examples of machine learning, so let's see if we can give a little bit more of a concrete definition. What is machine learning? Machine learning is the science of making computers learn and act like humans by feeding data and information without being explicitly programmed. And we see here we have a nice little diagram where we have our ordinary system. Your computer, nowadays you can even run a lot of this stuff on a cell phone because cell phones have advanced so much. And then with artificial intelligence and machine learning, it now takes the data and it learns from what happened before. And then it predicts what's going to come next. And then really the biggest part right now in machine learning that's going on is it improves on that. How do we find a new solution? So we go from descriptive, where it's learning about stuff and understanding how it fits together, to predicting what it's going to do, to post-scripting, coming up with a new solution. And when we're working on machine learning, there's a number of different diagrams that people have posted for what steps to go through. A lot of it might be very domain specific. So if you're working on photo identification versus language versus medical or physics, some of these are switched around a little bit or new things are put in. They're very specific to the domain. This is kind of a very general diagram. First, you want to define your objective. Very important to know what it is you're wanting to predict. Then you're going to be collecting the data. So once you've defined an objective, you need to collect the data that matches. You spend a lot of time in data science collecting data, and the next step, preparing the data. You got to make sure that your data is clean going in. There's the old saying, bad data in, bad answer out, or bad data out. And then once you've gone through and we've cleaned all this stuff coming in, then you're going to select the algorithm. Which algorithm are you going to use? You're going to train that algorithm. In this case, I think we're going to be working with SVM, the support vector machine. Then you have to test the model. Does this model work? Is this a valid model for what we're doing? And then once you've tested it, you want to run your prediction. You want to run your prediction or your choice or whatever output it's going to come up with. And then once everything is set and you've done lots of testing, then you want to go ahead and deploy the model. And remember I said domain specific. This is very general as far as the scope of doing something. A lot of models, you get halfway through and you realize that your data is missing something and you have to go collect new data because you've run a test in here someplace along the line. You're saying, hey, I'm not really getting the answers I need. So there's a lot of things that are domain specific that become part of this model. This is a very general model, but it's a very good model to start with. And we do have some basic divisions of what machine learning does that's important to know. For instance, do you want to predict a category? Well, if you're categorizing things, that's classification. For instance, whether the stock price will increase or decrease. So in other words, I'm looking for a yes-no answer. Is it going up or is it going down? And in that case, we'd actually say, is it going up? True. If it's not going up, it's false, meaning it's going down. This way, it's a yes-no, 0, 1. Do you want to predict a quantity? That's regression. So remember, we just did classification. Now we're looking at regression. These are the two major divisions in what data is doing. For instance, predicting the age of a person based on the height, weight, health, and other factors. So based on these different factors, you might guess how old a person is. And then there are a lot of domain-specific things, like do you want to detect an anomaly? That's anomaly detection. And this is actually very popular right now. For instance, you want to detect money withdrawal anomalies. You want to know when someone's making a withdrawal that might not be their own account. We've actually brought this up because this is really big right now. If you're predicting the stock, whether to buy stock or not, you want to be able to know if what's going on in the stock market is an anomaly. Use a different prediction model because something else is going on. You got to pull out new information in there. Or is this just the norm? I'm going to get my normal return on my money invested. So being able to detect anomalies is very big in data science these days. Another question that comes up, which is on what we call untrained data, is do you want to discover structure in unexplored data? And that's called clustering. For instance, finding groups of customers with similar behavior given a large database of customer data containing their demographics and past buying records. And in this case, we might notice that anybody who's wearing a certain set of shoes goes shopping at certain stores, or whatever it is, they're going to make certain purchases. By having that information, it helps us to market or group people together so that we can now explore that group and find out what it is we want to market to them if you're in the marketing world. And that might also work in just about any arena. You might want to group people together, whether they're based on their different areas and investments and financial background, whether you're going to give them a loan or not. Before you even start looking at whether they're a valid customer for the bank, you might want to look at all these different areas and group them together based on unknown data. So you don't know what the data is going to tell you, but you want to cluster people together that come together. Let's take a quick detour for quiz time. Oh, my favorite. So we're going to have a couple questions here under our quiz time. And we'll be posting the answers in the part 2 of this tutorial. So let's go ahead and take a look at these quiz times questions, and hopefully you'll get them all right, and it'll get you thinking about how to process data and what's going on. Can you tell what's happening in the following cases? Of course, you're sitting there with your cup of coffee and you have your checkbox and your pen trying to figure out what's your next step in your data science analysis. So the first one is grouping documents into different categories based on the topic and content of each document. Very big these days. You have legal documents, you have maybe it's a sports group documents, maybe you're analyzing newspaper postings, but certainly having that automated is a huge thing in today's world. B, identifying handwritten digits in images correctly. So we want to know whether they're writing an A or capital A, B, C. What are they writing out in their handwriting? C, behavior of a website indicating that the site is not working as designed. D, predicting salary of an individual based on his or her years of experience. HR hiring set up there. So stay tuned for part 2. We'll go ahead and answer these questions when we get to the part 2 of this tutorial. Or you can just simply write at the bottom and send a note to Simplilearn, and they'll follow up with you on it. Back to our regular content. Now these last few bring us into the next topic, which is another way of dividing our types of machine learning, and that is with supervised, unsupervised, and reinforcement learning. Supervised learning is a method used to enable machines to classify, predict objects, problems, or situations based on labeled data fed to the machine. And in here you see we have a jumble of data with circles, triangles, and squares, and we label them. We have what's a circle, what's a triangle, what's a square, and we have our model training, and it trains it so we know the answer. Very important, when you're doing supervised learning, you already know the answer to a lot of your information coming in. So you have a huge group of data coming in, and then you have new data coming in. So we've trained our model. The model now knows the difference between a circle, a square, a triangle. And now that we've trained it, we can send in this case, a square and a circle goes in, and it predicts that the top one's a square and the next one's a circle. And you can see that this is being able to predict whether someone's going to default on a loan, because I was talking about banks earlier. Supervised learning on stock market, whether you're going to make money or not. That's always important. And if you are looking to make a fortune in the stock market, keep in mind it is very difficult to get all the data correct on the stock market. It is it fluctuates in ways really hard to predict. So it's quite a roller coaster ride. If you're running machine learning on the stock market, you start realizing you really have to dig for new data. So we have supervised learning, and if you have supervised, we should need unsupervised learning. In unsupervised learning, machine learning model finds the hidden pattern in an unlabeled data. So in this case, instead of telling it what the circle is and what a triangle is and what a square is, it goes in there, looks at them and says, for whatever reason, it groups them together. Maybe it'll group it by the number of corners. And it notices that a number of them all have 3 corners, a number of them all have 4 corners, and a number of them all have no corners. And it's able to filter those through and group them together. We talked about that earlier with looking at a group of people who are out shopping. We want to group them together to find out what they have in common. And of course, once you understand what people have in common, maybe you have one of them who's a customer at your store, or you have 5 of them are customer at your store, and they have a lot in common with 5 others who are not customers at your store. How do you market to those 5 who aren't customers at your store yet? They fit the demographics of who's going to shop there, and you'd like them to shop at your store, not the one next door. Of course, this is a simplified version. You can see very easily the difference between a triangle and a circle, which might not be so easy in marketing. Reinforcement learning. Reinforcement learning is an important type of machine learning where an agent learns how to behave in an environment by performing actions and seeing the result. And we have here where in this case, a baby. It's actually great that they used an infant for this slide because the reinforcement learning is very much in its infant stages. But it's also probably the biggest machine learning demand out there right now, or in the future, it's going to be coming up over the next few years, is reinforcement learning and how to make that work for us. And you can see here where we have our action. In the action in this one, it goes into the fire. Hopefully the baby it was just a little candle, not a giant fire pit like it looks like here. When the baby comes out, and the new state is the baby is sad and crying because they got burned on the fire. And then maybe they take another action. The baby is called the agent because it's the one taking the actions. And in this case, they didn't go into the fire. They went a different direction, and now the baby's happy and laughing and playing. Reinforcement learning is very easy to understand because that's how as humans, that's one of the ways we learn. We learn whether it is, you burn yourself on the stove, don't do that anymore. Don't touch the stove. In the big picture, being able to have a machine learning program or an AI be able to do this is huge, because now it's starting to learn how to learn. That's a big jump in the world of computer and machine learning. And we're going to go back and just kind of go back over supervised versus unsupervised learning. Understanding this is huge, because this is going to come up in any project you're working on. We have, in supervised learning, we have labeled data, we have direct feedback. So someone's already gone in there and said, yes, that's a triangle. No, that's not a triangle. And then you predict an outcome. So you have a nice prediction. This new set of data is coming in and we know what it's going to be. And then with unsupervised training, it's not labeled. So we really don't know what it is. There's no feedback. So we're not telling it whether it's right or wrong. We're not telling it whether it's a triangle or a square. We're not telling it to go left or right. All we do is we're finding hidden structure in the data, grouping the data together to find out what connects to each other. And then you can use these together. So imagine you have an image and you're not sure what you're looking for. So you go in and you have the unstructured data, find all these things that are connected together. And then somebody looks at those and labels them. Now you can take that labeled data and program something to predict what's in the picture. So you can see how they go back and forth, and you can start connecting all these different tools together to make a bigger picture. There are many interesting machine learning algorithms. Let's have a look at a few of them. Hopefully this gives you a little flavor of what's out there. And these are some of the most important ones that are currently being used. We'll take a look at linear regression, decision tree, and the support vector machine. Let's start with a closer look at linear regression. Linear regression is perhaps one of the most well-known and well-understood algorithms in statistics and machine learning. Linear regression is a linear model. For example, a model that assumes a linear relationship between the input variables x and the single output variable y. And you'll see this if you remember from your algebra classes, y equals mx plus c. Imagine we are predicting distance traveled y from speed x. Our linear regression model representation for this problem would be y equals m times x plus c, or distance equals m times speed plus c, where m is the coefficient and c is the y-intercept. And we're going to look at two different variations of this. First, we're going to start with time is constant. And you can see we have a bicyclist. He's got his safety gear on, thank goodness. Speed equals 10 meters per second. And so over a certain amount of time, his distance equals 36 kilometers. We have a second bicyclist who's going twice the speed, or 20 meters per second. And you can guess if he's going twice the speed and time is a constant, then he's going to go twice the distance. And that's easily to compute. 36 times 2, you get 72 kilometers. And so if you had the question of how fast would somebody who's going 3 times that speed, or 30 meters per second is, you can easily compute the distance. In our head, we can do that without needing a computer. But we want to do this for more complicated data. So it's kind of nice to compare the two, but let's just take a look at that and what that looks like in a graph. So in a linear regression model, we have our distance to the speed, and we have our m equals the VE slope of the line. And we'll notice that the line has a plus slope. And as the speed increases, distance also increases, hence the variables have a positive relationship. And so your speed of the person, which equals y equals mx plus c, distance traveled in a fixed interval of time. And we could very easily compute, either following the line or just knowing it's 3 times 10 meters per second, that this is roughly 102 kilometers distance that this third bicyclist has traveled. One of the key definitions on here is positive relationship. So the slope of the line is positive. As distance increase, so does speed increase. Let's take a look at our second example where we put distance is a constant. So we have speed equals 10 meters per second. They have a certain distance to go, and it takes them 100 seconds to travel that distance. And we have our second bicyclist who's still doing 20 meters per second. Since he's going twice the speed, we can guess that he'll cover the distance in about half the time, 50 seconds. And of course, you could probably guess on the third one, 100 divided by 30, since he's going 3 times the speed. You could easily guess that this is 33.333 seconds time. When we put that into a linear regression model or a graph, if the distance is assumed to be constant, let's see the relationship between speed and time. And as time goes up, the amount of speed to go that same distance goes down. So now your m equals a minus VE slope of the line. As the speed increases, time decreases, hence the variable has a negative relationship. Again, there's our definition, positive relationship and negative relationship dependent on the slope of the line. And with a simple formula like this, and even a significant amount of data, let's see with the mathematical implementation of linear regression. And we'll take this data, so suppose we have this data set where we have x, y, x equals 1, 2, 3, 4, 5, standard series, and the y value is 3, 2, 2, 4, 3. When we take that and we go ahead and plot these points on a graph, you can see there's kind of a nice scattering, and you could probably eyeball a line through the middle of it. But we're going to calculate that exact line for linear regression. And the first thing we do is we come up here and we have the mean of xi. And remember, mean is basically the average. So we added 5 plus 4 plus 3 plus 2 plus 1 and divide by 5. And that simply comes out as 3. And then we'll do the same for y. We'll go ahead and add up all those numbers and divide by 5. And we end up with a mean value of y of I equals 2.8, where the xi references it's an average or means value, and the yi also equals a means value of y. And when we plot that, you'll see that we can put in the y equals 2.8 and the x equals 3 in there on our graph. We kind of gave it a little different color so you could sort it out with the dashed lines on it. And it's important to note that when we do the linear regression model should go through that dot. Now let's find our regression equation to find the best fit line. Remember, we go ahead and take our y equals mx plus c, so we're looking for m and c. So to find this equation for our data, we need to find our slope of m and our coefficient of c. And we have y equals mx plus c, where m equals the sum of x minus x average times y minus y average, or y means and x means, over the sum of x minus x means squared. That's how we get the slope of the value of the line. And we can easily do that by creating some columns here where we have x, y. Computers are really good about iterating through data, and so we can easily compute this and fill in a graph of data. And in our graph, you can easily see that if we have our x value of 1, and if you remember the xi, or the means value, is 3, 1 minus 3 equals a negative 2, and 2 minus 3 equals a negative 1, so on and so forth. And we can easily fill in the column of x minus xi, y minus yi, and then from those we can compute x minus xi squared and x minus xi times y minus yi. And you can guess it that the next step is to go ahead and sum the different columns for the answers we need. So we get a total of 10 for our x minus xi squared, and a total of 2 for x minus xi times y minus yi. And we plug those in, we get 2/10, which equals 0.2. So now we know the slope of our line equals 0.2. So we can calculate the value of c. That'd be the next step, is we need to know where it crosses the y-axis. And if you remember, I mentioned earlier that the linear regression line has to pass through the means value, the one that we showed earlier. We can just flip back up there to that graph, and you can see right here there's our means value, which is 3, x equals 3 and y equals 2.8. And since we know that value, we can simply plug that into our formula, y equals 0.2x plus c. So we plug that in, and we get 2.8 equals 0.2 times 3 plus c, and you can just solve for c. So now we know that our coefficient equals 2.2. And once we have all that, we can go ahead and plot our regression line. Y equals 0.2 times x plus 2.2. And then from this equation, we can compute new values. So let's predict the values of y using x equals 1, 2, 3, 4, 5 and plot the points. Remember, the 1, 2, 3, 4, 5 was our original x values. So now we're going to see what y thinks they are, not what they actually are. And when we plug those in, we get y of designated with y of p. You can see that x equals 1 equals 2.4, x equals 2 equals 2.6, and so on and so on. So we have our y predicted values of what we think it's going to be when we plug those numbers in. And when we plot the predicted values along with the actual values, we can see the difference. And this is one of the things that's very important with linear regression in any of these models, is to understand the error. And so we can calculate the error on all of our different values. And you can see over here we plotted x and y predict. And we draw in a little line so you can sort of see what the error looks like there between the different points. So our goal is to reduce this error. We want to minimize that error value on our linear regression model. Minimizing the distance. There are lots of ways to minimize the distance between the line and the data points, like sum of squared errors, sum of absolute errors, root mean square error, etc. We keep moving this line through the data points to make sure the best fit line has the least square distance between the data points and the regression line. So to recap with a very simple linear regression model, we first figure out the formula of our line through the middle, and then we slowly adjust the line to minimize the error. Keep in mind this is a very simple formula. The math gets, even though the math is very much the same, it gets much more complex as we add in different dimensions. So this is only 2 dimensions, y equals mx plus c, but you can take that out to x, z, I, j, q, all the different features in there, and they can plot a linear regression model on all of those using the different formulas to minimize the error. Let's go ahead and take a look at decision trees, a very different way to solve problems in the linear regression model. Decision tree is a tree-shaped algorithm used to determine a course of action. Each branch of a tree represents a possible decision, occurrence, or reaction. We have data which tells us if it is a good day to play golf. And if we were to open this data up in a general spreadsheet, you can see we have the outlook, whether it's rainy, overcast, sunny, temperature, hot, mild, cool, humidity, windy, and did I like to play golf that day, yes or no? So we're taking a census. And certainly I wouldn't want a computer telling me when I should go play golf or not. But you could imagine if you got up in the night before, you're trying to plan your day, and it comes up and says tomorrow would be a good day for golf for you in the morning and not a good day in the afternoon or something like that. This becomes very beneficial, and we see this in a lot of applications coming out now where it gives you suggestions and lets you know what would fit the match for you for the next day or the next purchase or the next whatever, next meal out. In this case, is tomorrow a good day for playing golf based on the weather coming in? And so we come up and let's determine if you should play golf when the day is sunny and windy. So we found out the forecast tomorrow is going to be sunny and windy. And suppose we draw our tree like this. We're going to have our humidity, and then we have our normal, which is if you have a normal humidity, you're going to go play golf. And if the humidity is really high, then we look at the outlook. And if the outlook is sunny, overcast, or rainy, it's going to change what you choose to do. So if you know that it's a very high humidity and it's sunny, you're probably not going to play golf because you're going to be out there miserable, fighting off the mosquitoes that are out joining you to play golf with you. Maybe if it's rainy, you probably don't want to play in the rain. But if it's slightly overcast and you get just the right shadow, that's a good day to play golf and be outside, out on the green. Now in this example, you can probably make your own tree pretty easily because it's a very simple set of data going in. But the question is, how do you know what to split? Where do you split your data? What if this is much more complicated data where it's not something that you would particularly understand? Like studying cancer, they take about 36 measurements of the cancerous cells, and then each one of those measurements represents how bulbous it is, how extended it is, how sharp the edges are. Something that as a human we would have no understanding of. So how do we decide how to split that data up? And is that the right decision tree? So that's a question that's going to come up. Is this the right decision tree? For that, we should calculate entropy and information gain. 2 important vocabulary words there are the entropy and the information gain. Entropy. Entropy is a measure of randomness or impurity in the data set. Entropy should be low. So we want the chaos to be as low as possible. We don't want to look at it and be confused by the images or what's going on there with mixed data. And the information gain. It is a measure of decrease in entropy after the data set is split, also known as entropy reduction. Information gain should be high, so we want our information that we get out of the split to be as high as possible. Let's take a look at entropy from the mathematical side. In this case, we're going to denote entropy as I of P of and N, where P is the probability that you're going to play a game of golf, and N is the probability where you're not going to play the game of golf. Now, you don't really have to memorize these formulas. There's a few of them out there depending on what you're working with. But it's important to note that this is where this formula is coming from, so when you see it, you're not lost when you're running your programming, unless you're building your own decision tree code in the back. And we simply have a log squared of P over P plus N minus N over P plus N times the log squared of N of P plus N. But let's break that down and see what it actually looks like when we're computing that from the computer script side. Entropy of a target class of the data set is the whole entropy. So we have entropy play golf. And when we look at this, if we go back to the data, you can simply count how many yeses and no in our complete data set for playing golf days. In our complete set, we find we have 5 days we did play golf and 9 days we did not play golf. And so our I equals, if you add those together, 9 plus 5 is 14. And so our I equals 5 over 14 and 9 over 14. That's our P and N values that we plug into that formula. And you can go 5 over 14 equals 0.36, 9 over 14 equals 0.64. And when you do the whole equation, you get the minus 0.36 log root squared of 0.36 minus 0.64 log squared root of 0.64. And we get a set value. We get 0.94. So we now have a full entropy value for the whole set of data that we're working with. And we want to make that entropy go down. And just like we calculated the entropy out for the whole set, we can also calculate entropy for playing golf and the outlook. Is it going to be overcast or rainy or sunny? And so when we look at the entropy, we have P of sunny times E of 3 of 2. And that just comes out how many sunny days yes and how many sunny days no over the total, which is 5. Don't forget to put we'll divide that 5 out later on. Equals P overcast equals 4 comma 0 plus rainy equals 2 comma 3. And then when you do the whole setup, we have 5 over 14. Remember I said there was a total of 5? 5 over 14 times the I of 3 of 2 plus 4 over 14 times the 4 comma 0 and 514 over I of 2, 3. And so we can now compute the entropy of just the part that has to do with the forecast. And we get 0.693. Similarly, we can calculate the entropy of other predictors like temperature, humidity, and wind. And so we look at the gain outlook. How much are we going to gain from this? Entropy play golf minus entropy play golf outlook. And we can take the original 0.94 for the whole set minus the entropy of just the rainy day and temperature, and we end up with a gain of 0.247. So this is our information gain. Remember, we define entropy and we define information gain. The higher the information gain, the lower the entropy, the better. The information gain of the other 3 attributes can be calculated in the same way. So we have our gain for temperature equals 0.029. We have our gain for humidity equals 0.152, and our gain for a windy day equals 0.048. And if you do a quick comparison, you'll see the 0.247 is the greatest gain of information, so that's the split we want. Now let's build the decision tree. So we have the outlook. Is it going to be sunny, overcast, or rainy? That's our first split because that gives us the most information gain. And we can continue to go down the tree using the different information gains with the largest information. We can continue down the nodes of the tree where we choose the attribute with the largest information gain as the root node and then continue to split each subnode with the largest information gain that we can compute. And although it's a little bit of a tongue twister to say all that, you can see that it's a very easy to view visual model. We have our outlook, we split it 3 different directions. If the outlook is overcast, we're going to play. And then we can split those further down if we want. So if the outlook is sunny, but then it's also windy, if it's windy, we're not going to play. If it's not windy, we'll play. So we can easily build a nice decision tree to guess what we would like to do tomorrow and give us a nice recommendation for the day. So we want to know if it's a good day to play golf when it's sunny and windy. Remember the original question that came out? Tomorrow's weather report is sunny and windy. You can see by going down the tree, we go outlook sunny, outlook windy. We're not going to play golf tomorrow. So our little smartwatch pops up and says, I'm sorry, tomorrow's not a good day for golf. It's going to be sunny and windy. And if you're a huge golf fan, you might go, uh-oh, it's not a good day to play golf. We can go in and watch a golf game at home. So we'll sit in front of the TV instead of being out playing golf in the wind. Now that we looked at our decision tree, let's look at the third one of our algorithms we're investigating. Support vector machine. Support vector machine is a widely used classification algorithm. The idea of support vector machine is simple. The algorithm creates a separation line which divides the classes in the best possible manner. For example, dog or cat, disease or no disease. Suppose we have a labeled sample data which tells height and weight of males and females. A new data point arrives and we want to know whether it's going to be a male or a female. So we start by drawing a line. We draw decision lines, but if we consider decision line 1, then we will classify the individual as a male. And if we consider decision line 2, then it will be a female. So you can see this person kind of lies in the middle of the two groups, so it's a little confusing trying to figure out which line they should be under. We need to know which line divides the classes correctly, but how? The goal is to choose a hyperplane, and that is one of the key words they use when we talk about support vector machines. Choose a hyperplane with the greatest possible margin between the decision line and the nearest point within the training set. So you can see here we have our support vector, we have the two nearest points to it, and we draw a line between those 2 points. And the distance margin is the distance between the hyperplane and the nearest data point from either set. So we actually have a value, and it should be equally distant between the two points that we're comparing it to. When we draw the hyperplanes, we observe that line 1 has a maximum distance. So we observe that line 1 has a maximum distance margin, so we'll classify the new data point correctly. And our result on this one is going to be that the new data point is Mel. One of the reasons we call it a hyperplane versus a line is that a lot of times we're not looking at just weight and height. We might be looking at 36 different features or dimensions. And so when we cut it with a hyperplane, it's more of a three-dimensional cut in the data, or multi-dimensional. It cuts the data a certain way. And each plane continues to cut it down until we get the best fit or match. Let's understand this with the help of an example. Problem statement. I always start with a problem statement when you're going to put some code together. We're going to do some coding now. Classifying muffin and cupcake recipes using support vector machines. So the cupcake versus the muffin. Let's have a look at our data set. And we have the different recipes here. We have a muffin recipe that has so much flour. I'm not sure what measurement 55 is in, but it has 55, maybe it's ounces? But it has a certain amount of flour, a certain amount of milk, sugar, butter, egg, baking powder, vanilla, and salt. And so based on these measurements, we want to guess whether we're making a muffin or a cupcake. And you can see in this one, we don't have just two features. We don't just have height and weight as we did before between the male and female. In here, we have a number of features. In fact, in this, we're looking at 8 different features to guess whether it's a muffin or a cupcake. What's the difference between a muffin and a cupcake? Turns out muffins have more flour, while cupcakes have more butter and sugar. So basically the cupcake's a little bit more of a dessert, where the muffin's a little bit more of a fancy bread. But how do we do that in Python? How do we code that to go through recipes and figure out what the recipe is? And I really just want to say cupcakes versus muffins, like some big professional wrestling thing. Before we start in our cupcakes versus muffins, we are going to be working in Python. There's many versions of Python, many different editors. That is one of the strengths and weaknesses of Python, is it just has so much stuff attached to it, and it's one of the more popular data science programming packages you can use. In this case, we're going to go ahead and use Anaconda and Jupyter Notebook. The Anaconda Navigator has all kinds of fun tools. Once you're into the Anaconda Navigator, you can change environments. I actually have a number of environments on here. We'll be using Python 3.6 environment. So this is in Python version 3.6. Although it doesn't matter too much which version you use. I usually try to stay with the 3x because they're current, unless you have a project that's very specifically in version 2x. 2.7 I think is usually what most people use in the version 2. And then once we're in our Jupyter Notebook editor, I can go up and create a new file. And we'll just jump in here. In this case, we're doing SVM muffin versus cupcake. And then let's start with our packages for data analysis. And we almost always use there's a few very standard packages we use. We use import numpy. That's for number Python. And they usually denote it as NP. That's very common. And then we're going to import pandas as PD. And numpy deals with number arrays. There's a lot of cool things you can do with the numpy setup as far as multiplying all the values in an array, in a numpy array, data array. Pandas, I can't remember if we're using it actually in this data set. I think we do as an import. It makes a nice data frame. And the difference between a data frame and a numpy array is that a data frame is more like your Excel spreadsheet. You have columns, you have indexes, so you have different ways of referencing it, easily viewing it, and there's additional features you can run on a data frame. And Pandas kind of sits on numpy, so you need them both in there. And then finally, we're working with the support vector machine. So from sklearn, we're going to use the sklearn model. Import SVM, support vector machine. And then as a data scientist, you should always try to visualize your data. Some data obviously is too complicated or doesn't make any sense to the human. But if it's possible, it's good to take a second look at it so that you can actually see what you're doing. Now for that, we're going to use two packages. We're going to import matplotlibary.pyplot as PLT, again very common, and we're going to import Seaborn as SNS. And we'll go ahead and set the font scale in the SNS right in our import line. That's what this semicolon followed by a line of data. We're going to set the SNS. And these are great because the Seaborn sits on top of matplotlibary, just like Pandas sits on NumPy. So it adds a lot more features and uses and control. We're obviously not going to get into matplotlibary and Seaborn. That'd be its own tutorial. We're really just focusing on the SVM, the support vector machine from sklearn. And since we're in Jupyter Notebook, we have to add a special line in here for our matplotlibary. And that's your %sign or ampersand matplotlibary in line. Now, if you're doing this in just a straight code project, a lot of times I use like Notepad++, and I'll run it from there. You don't have to have that line in there because it'll just pop up as its own window on your computer, depending on how your computer's set up. Because we're running this in the Jupyter Notebook as a browser setup, this tells it to display all of our graphics right below on the page. So that's what that line is for. I remember the first time I ran this, I didn't know that, and I had to go look that up years ago. It was quite a headache. So matplotlibary inline is just because we're running this on the web setup. And we can go ahead and run this, make sure all our modules are in. They're all imported, which is great. If you don't have them import, you'll need to go ahead and pip, use the PIP or however you do it. There's a lot of other install packages out there, although pip is the most common. And you have to make sure these are all installed on your Python setup. The next step, of course, is we got to look at the data. You can't run a model for predicting data if you don't have actual data. So to do that, let me go ahead and open this up and take a look. And we have our cupcakes versus muffins. And it's a CSV file, or .csv, meaning that it's comma-separated variable. And it's going to open it up in a nice spreadsheet for me. And you can see up here we have the type. We have muffin, 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 cupcake, cupcake, cupcake. And then it's broken up into flour, milk, sugar, butter, egg, baking powder, vanilla, and salt. So what we can do is we can go ahead and look at this data also in our Python. Let us create a variable recipes equals, we're going to use our pandas module, .read CSV. Remember, it's a comma-separated variable. And the file name happened to be cupcakes versus muffins. Oops, I got double brackets there. Do it this way. There we go. Cupcakes versus muffins. Because the program I loaded, or the place I saved this particular Python program is in the same folder, we can get by with just the file name. But remember, if you're storing it in a different location, you have to also put down the full path on there. And then because we're in pandas, we're going to go ahead and you can actually, inline you can do this, but let me do the full print. You can just type in recipes.head in the Jupyter Notebook. But if you're running in code in a different script, you need to go ahead and type out the whole print recipes.head. And pandas knows that that's going to do the first 5 lines of data. And if we flip back on over to the spreadsheet where we opened up our CSV file, you can see where it starts on line 2. This one calls it 0, and then 2, 3, 4, 5, 6 is going to match. Go and close that out because we don't need that anymore. And it always starts at 0. And it automatically indexes it since we didn't tell it to use an index in here. So that's the index number for the left-hand side. And it automatically took the top row as labels. So pandas using it to read a CSV is just really slick and fast. One of the reasons we love our pandas. Not just because they're cute and cuddly teddy bears. And let's go ahead and plot our data. And I'm not going to plot all of it. I'm just going to plot the sugar and flour. Now obviously you can see where they get really complicated if we have tons of different features. And so you'll break them up and maybe look at just 2 of them at a time to see how they connect. And to plot them, we're going to go ahead and use Seaborn. So that's our SNS. And the command for that is sns.lmplot. And then the two different variables I'm going to plot is flour and sugar. Data equals recipes. The hue equals type. And this is a lot of fun because it knows that this is pandas coming in. So this is one of the powerful things about pandas mixed with seaborn and doing graphing. And then we're going to use a palette set 1. There's a lot of different sets in there. You can go look them up for seaborn. We'll do a fit regular equals false, so we're not really trying to fit anything. And it's a scatter, KWS. A lot of these settings you can look up in seaborn. Half of these you could probably leave off when you run them. Somebody played with this and found out that these were the best settings for doing a seaborn plot. And let's go ahead and run that. And because it does it inline, it just puts it right on the page. And you can see right here that just based on sugar and flour alone, there's a definite split. And we use these models because you can actually look at it and say, hey, if I drew a line right between the middle of the blue dots and the red dots, we'd be able to do an SVM and a hyperplane right there in the middle. Then the next step is to format or pre-process our data. And we're going to break that up into two parts. We need a type label, and remember, we're going to decide whether it's a muffin or a cupcake. Well, a computer doesn't know muffin or cupcake. It knows 0 and 1. So what we're going to do is we're going to create a type label. And from this, we'll create a numpy array, np, where, and this is where we can do some logic. We take our recipes from our panda, and wherever type equals muffin, it's going to be 0. And then if it doesn't equal muffin, which is cupcakes, it's going to be 1. So we create our type label. This is the answer. So when we're doing our training model, remember we have to have a training data. This is what we're going to train it with, is that it's 0 or 1. It's a muffin or it's not. And then we're going to create our recipe features. And if you remember correctly from right up here, the first column is type. So we really don't need the type column because that's our muffin or cupcake. And in pandas, we can easily sort that out. We take our value recipes dot columns. That's a pandas function built into pandas. Dot values, converting them to values. So it's just the column titles going across the top. And we don't want the first one. So what we do is, since it always starts at 0, we want 1 colon till the end. And then we want to go ahead and make this a list, and this converts it to a list of strings. And then we can go ahead and just take a look and see what we're looking at for the features, make sure it looks right. Let me go ahead and run that. And I forgot the S on recipes, so we'll go ahead and add the S in there and then run that. And we can see we have flour, milk, sugar, butter, egg, baking powder, vanilla, and salt. And that matches what we have up here, right where we printed out everything but the type. So we have our features and we have our label. Now, the recipe features is just the titles of the columns, and we actually need the ingredients. And at this point, we have a couple options. One, we could run it over all the ingredients. And when you're doing this, usually you do, but for our example, we want to limit it so you can easily see what's going on. Because if we did all the ingredients, we have, that's what, 7, 8 different hyperplanes that would be built into it. We only want to look at one so you can see what the SVM is doing. And so we'll take our recipes and we'll do just flour and sugar. Again, you can replace that with your recipe features and do all of them, but we're going to do just flour and sugar, and we're going to convert that to values. We don't need to make a list out of it because it's not string values. These are actual values on there. And we can go ahead and just print ingredients, and you can see what that looks like. And so we have just the amount of flour and sugar, just the 2 sets of plots. And just for fun, let's go ahead and take this over here and take our recipe features. And so if we decided to use all the recipe features, you'll see that it makes a nice column of different data. So it just strips out all the labels and everything, and we just have just the values. But because we want to be able to view this easily in a plot later on, we'll go ahead and take that and just do flour and sugar. And we'll run that and you'll see it's just the 2 columns. So the next step is to go ahead and fit our model. We'll go ahead and just call it model. And it's a SVM. We're using a package called SVC. And in this case, we're going to go ahead and set the kernel equals linear. So it's using a specific setup on there. And if we go to the reference on their website for the SVM, you'll see that there's 8 of them here. 3 of them are for regression. 3 are for classification. The SVC, support vector classification, is probably one of the most commonly used. And then there's also one for detecting outliers, and another one that has to do with something a little bit more specific on the model. But SVC and SVR are the 2 most commonly used, standing for support vector classifier and support vector regression. Remember, regression is an actual value, a float value or whatever you're trying to work on. And SVC is a classifier, so it's a yes, no, true, false. But for this, we want to know 0, 1, muffin, cupcake. We go ahead and create our model. And once we have our model created, we're going to do model.fit. And this is very common, especially in the sklearn. All their models are followed with the fit command. And what we put into the fit, what we're training with it, is we're putting in the ingredients, which in this case we limited to just flour and sugar. And the type label, is it a muffin or a cupcake? Now, in more complicated data science series, you'd want to split into, we won't get into that today, we split it into training data and test data. And they even do something where they split it into thirds, where a third is used for, where you switch between which one's training and test. There's all kinds of things that go into that, and it gets very complicated when you get to the higher end. Not overly complicated, just an extra step which we're not going to do today because this is a very simple set of data. And let's go ahead and run this, and now we have our model fit. And I got an error here, so let me fix that real quick. It's capital SVC, it turns out. I did it lowercase. Support vector classifier. There we go. Let's go ahead and run that. And you'll see it comes up with all this information that it prints out automatically. These are the defaults of the model. You notice that we changed the kernel to linear, and there's our kernel linear on the printout. And there's other different settings you can mess with. We're going to just leave that alone for right now. For this, we don't really need to mess with any of those. So next, we're going to dig a little bit into our newly trained model. And we're going to do this so we can show you on a graph. And let's go ahead and get the separating. And we're going to say we're going to use a W for our variable on here. And we're going to do model.coefficient_0. So what the heck is that? Again, we're digging into the model. So we've already got a prediction and a train. This is the math behind it that we're looking at right now. And so the W is going to represent 2 different coefficients. And if you remember, we had y equals mx plus c. So these coefficients are connected to that, but in 2-dimensional. It's a plane. We don't want to spend too much time on this because you can get lost in the confusion of the math. So if you're a math whiz, this is great. You can go through here and you'll see that we have a equals minus w of 0 over w of 1. Remember, there's 2 different values there. And that's basically the slope that we're generating. And then we're going to build an XX. What is XX? We're going to set it up to a numpy array. There's our np dot line space. So we're creating a line of values between 30 and 60. So it just creates a set of numbers for x. And then if you remember correctly, we have our formula, y equals the slope times x plus the intercept. Well, to make this work, we can do this as yy equals the slope times each value in that array. That's the neat thing about numpy. So when I do a times xx, which is a whole numpy array of values, it multiplies a across all of them. And then it takes those same values and we subtract the model intercept. That's your, remember we had mx plus c, so that'd be the c from the formula, y equals mx plus c. And that's where all these numbers come from. A little bit confusing because it's digging out of these different arrays. And then what we want to do is we're going to take this and we're going to go ahead and plot it. So plot the parallels to separating hyperplane that pass through the support vectors. And so we're going to create B equals a model support vectors, pulling our support vectors out there. Here's our YY, which we now know is a set of data. And we have we're going to create YY down equals A times XX plus B1 minus A times B0. And then model support vector B is going to be set that to a new value, the -1 setup. And YY up equals A times XX plus B1 minus A times B0. And we can go ahead and just run this to load these variables up. If you wanted to understand a little bit more of what's going on, you can see if we print YY, we just run that, you can see it's an array. This is a line. It's going to have, in this case, between 30 and 60, so it's going to be 30 variables in here. And the same thing with YY up, YY down. And we'll plot those in just a minute on a graph so you can see what those look like. You just go ahead and delete that out of here and run that so it loads up the variables. Nice clean slate. I'm just going to copy this from before. Remember this, our SNS, our seaborn plot, LM plot, flour, sugar. And I'll just go ahead and run that real quick so you can see remember what that looks like. It's just a straight graph on there. And then one of the neat things is because seaborn sits on top of PyPlot, we can do the PyPlot for the line going through. And that is simply plt.plot. And that's our XX and YY, our two corresponding values, XY. And then somebody played with this to figure out that the line width equals 2 and the color black would look nice. So let's go ahead and run this whole thing with the PyPlot on there. And you can see when we do this, it's just doing flour and sugar on here. Corresponding line between the sugar and the flour and the muffin versus cupcake. And then we generated the support vectors, the YY down and YY up. So let's take a look and see what that looks like. So we'll do our PL plot. And again, this is all against XX, our X value. But this time we have YY down. And let's do something a little fun with this. We can put in a K dash dash. That just tells it to make it a dotted line. And if we're going to do the down one, we also want to do the up one. So here's our YY up. And when we run that, it adds both sets of line. And so here's our support, and this is what you expect. You expect these two lines to go through the nearest data point. So the dashed lines go through the nearest muffin and the nearest cupcake when it's plotting it. And then your SVM goes right down the middle. So it gives it a nice split in our data. And you can see how easy it is to see, based just on sugar and flour, which one's a muffin or a cupcake. Let's go ahead and create a function to predict muffin or cupcake. I've got my recipes I pulled off the internet, and I want to see the difference between a muffin or a cupcake. And so we need a function to push that through. And we'll create a function with def. And let's call it muffin or cupcake. And remember, we're just doing flour and sugar today. We're not doing all the ingredients. And that actually is a pretty good split. You really don't need all the ingredients to know it's flour and sugar. And let's go ahead and do an if-else statement. So if model predict is of flour and sugar equals 0, so we take our model and we run a predict. That's very common in sklearn where you have a dot predict. You put the data in and it's going to return a value. In this case, if it equals 0, then print you're looking at a muffin recipe. Else, if it's not 0, that means it's 1, then you're looking at a cupcake recipe. That's pretty straightforward for a function, or def for definition. DEF is how you do that in Python. And of course, if you're going to create a function, you should run something in it. And so let's run a cupcake, and we're going to send it values 50 and 20, a muffin or a cupcake. I don't know what it is. And let's run this and just see what it gives us. And it says, oh, it's a muffin. You're looking at a muffin recipe. So it very easily predicts whether we're looking at a muffin or a cupcake recipe. let's plot this. Oops, there we go. Plot this on the graph so we can see what that actually looks like. And I'm just going to copy it and paste it from below where we're plotting all the points in there. So this is nothing different than what we did before. If I run it, you'll see it has all the points and the lines on there. And what we want to do is we want to add another point. And we'll do PLT plot. And if you remember correctly, we did, for our test, we did 50 and 20. And then somebody went in here and decided we'll do YO for yellow, or it's kind of an orangish yellow color is going to come out. Marker size 9. Those are settings you can play with. Somebody else played with them to come up with the right setup so it looks good. And you can see there it is graphed, clearly a muffin. In this case, in cupcakes versus muffins, the muffin has won. And if you'd like to do your own muffin cupcake contender series, you certainly can send a note down below, and the team at Simplilearn will send you over the data they use for the muffin and cupcake. And that's true of any of the data. We didn't actually run a plot on it earlier. We had men versus women. You can also request that information to run it on your data setup so you can test that out. So to go back over our setup, we went ahead for our support vector machine code. We did a predict 40 parts flour, 20 parts sugar. I think it was different than the one we did, whether it's a muffin or a cupcake. Hence, we have built a classifier using SVM, which is able to classify if a recipe is of a cupcake or a muffin.
LLMs. If you ever wondered how machine learning can now understand and generate human-like text, you are in the right place. From chatbots like ChatGPT to AI assistant that power search engines, LLMs are transforming how we interact with technology. One of the most exciting advancements in this space is Google's Gemini or OpenAI ChatGPT, a cutting-edge large language model designed to push the boundaries of what AI can achieve. In this video, we will explore what LLMs are, how they work, and why models like Gemini are critical for the future of AI. Google Gemini is part of a new wave of AI models that are smarter, faster, and more efficient. It is designed to understand context better, offer more accurate responses, and integrate deeply into services like Google Search and Google Assistant, providing more human-like interactions. So we will break down the science behind LLMs, including their massive training datasets, transformer architecture, and how models like Gemini use deep learning innovation to change industries. Plus, we will compare Google Gemini to other popular LLMs such as OpenAI ChatGPT models, showing how each of these technologies is used to power chatbots, virtual assistants, and other AI-driven applications. By the end of this video, you will have a clear understanding of how large language models like Gemini work, their key features, and what they mean for their future AI. Don't forget to like, subscribe, and hit the bell icon to never miss any update from Simplilearn. So what are the large language models? Large language models like ChatGPT 4, Generative Pre-trained Transformer 4, O, and Google Gemini are sophisticated AI systems designed to comprehend and generate human-like text. These models are built using deep learning techniques and are trained on vast datasets collected from the internet. They leverage self-attention mechanism to analyze relationship between words or tokens, allowing them to capture context and produce coherent, relevant responses. LLMs have significant applications, including powering virtual assistant, chatbots, content creation, language translation, and supporting research and decision making. Their ability to generate fluent and contextually appropriate text has advanced natural language processing and improved human-computer interaction. So now let's see what our large language model used for. Large language models are utilized in scenarios with limited or no domain-specific data available for training. These scenarios include both few-shot and zero-shot training approaches, which rely on the model's strong inductive bias and its capability to derive meaningful representation from a small amount of data or even no data at all. So now let's see how our large language model trained. Large language models typically undergo pre-training on a boat, all-encompassing dataset that shares statistical similarities with the dataset specific to the target task. The objective of pre-training is to enable the model to acquire high-level features that can later be applied during the fine-tuning phase for specific tasks. So there are some training processes of LLM which involve several steps. The first one is text pre-processing. The textual data is transformed into a numerical representation that the LLM model can effectively process. This conversion may involve techniques like tokenization, encoding, and creating input sequences. The second one is random parameter initialization. The model's parameters are initialized randomly before the training process begins. The third one is input numerical data. The numerical representation of the text data is fed into the model of processing. The model's architecture, typically based on transformers, allows it to capture the contextual relationship between the words or tokens in the next. The fourth one is loss function calculation. A loss function calculation measures the discrepancy between the model's prediction and the actual next word or token in a syntax. The LLM model aims to minimize this loss during training. The fifth one is parameter optimization. The model's parameters are adjusted through optimization technique. This involves calculating gradient and updating the parameters accordingly, gradually improving the model's performance. The last one is iterative training. The training process is repeated over multiple iterations or epochs until the model's output achieve a satisfactory level of accuracy on that given task or dataset. By following this training process, large language models learn to capture linguistic patterns, understand context, and generate coherent responses, enabling them to excel at various language-related tasks. The next topic is how do large language models work? So large language models leverage deep neural network to generate output based on patterns learned from the training data. Typically, a large language model adopts a transformer architecture which enables the model to identify relationship between words in a sentence irrespective of their position in the sequence. In contrast to RNNs that rely on recurrence to capture token relationship, transformer neural network employs self-attention as their primary mechanism. Self-attention calculates attention scores that determine the importance of each token with respect to the other token in the text sequence, facilitating the modeling of intricate relationships within the data. Next, let's see application of large language models. Large language models have a wide range of applications across various domains. So here are some notable applications. The first one is natural language processing, NLP. Large language models are used to improve natural language understanding tasks such as sentiment analysis, named entity recognition, text classification, and language modeling. The second one is chatbot and virtual assistant. Large language models power conversational agents, chatbots, and virtual assistant, providing more interactive and human-like user interaction. The third one is machine translation. Large language models have been used for automatic language translation, enabling text translation between different languages with improved accuracy. The fourth one is sentiment analysis. LLMs can analyze and classify the sentiment or emotion expressed in a piece of text, which is valuable for market research, brand monitoring, and social media analysis. The fifth one is content recommendation. These models can be employed to provide personalized content recommendations, enhancing user experience and engagement on platforms such as news websites or streaming services. So these applications highlight the potential impact of large language models in various domains for improving language understanding automation.
Today we are diving deep into an exciting AI showdown, Claude 4 versus Gemini 2.5 Pro. I've spent hours testing both the models head to head and the results are absolutely mind-blowing. In this video, we are going beyond the usual articles and benchmarks to see how these models truly perform with real-world applications. We will compare coding abilities, handling real production tasks, features, and pricing. And trust me, you will be surprised by some of the findings. So stick around as we test these two AIs in real projects and tasks. So let's get started. Before we dive into the comparison, let's talk about the real-world testing. While many articles test AI models with just a few selected questions, we will test Claude 4 and Gemini 2.5 Pro with actual production tasks. We are talking about building games, debugging code, and creating features like you would do in a real project. And after all, the true test of an AI model is how well it performs in real-world applications. So at first, we'll start by testing Claude Sonnet 4 and Gemini 2.5 Pro against each other on the SWE benchmark. So you can see right over here, in terms of agentic coding, the SWE bench verified is given 79.4 for Claude Opus 4, and for Sonnet 4 it's around 80.2. And if we compare it with Gemini 2.5 Pro, then obviously it lags a bit behind because it's given 63.2%. Since it's in the preview mode, we can't be expecting much. But then now let's talk about the agentic terminal coding. So again, it has got around 43.2 to around 50%, and Sonnet 4 has got around 35.5 to 41.3%. And again, Gemini 2.5 Pro has got 25.3%. Now, the next we're going to talk about is the graduate level reasoning. I mean, the reasoning questions. So again, you can see here Opus 4 has a good percentage benchmark, which is around 83.3 percentage, and Sonnet 4 has the same, and I think the Opus 4 has a bit higher, which is 79.6. And now Gemini 2.5 Pro doesn't lag behind in this. It's really good at reasoning. So it has been given 83% again, which is almost the similar. Then we have agentic tool use, and again for Opus, it's around 81.4%, and there is no such SWA bench verified percentage for Gemini 2.5 Pro. Then we have multilingual QA, it's not given anything, it's not there, it's blank. And for visual reasoning, we have it actually competes better than the Opus and the Sonnet, the Gemini 2.5, because it stands around at 79.6%, and Claude Opus 4 and Claude Sonnet 4 has around 76.5 and 74.4. Just it lags behind by few numbers, but here I can see that Gemini 2.5 Pro outperforms. And then we have high school math competition. Here we have 75% to 90%, and the Sonnet has 85%, 70% to 85%. Again, this Gemini 2.5 Pro has around 83%, which is quite higher than the Opus 4. And yeah, so in terms of visual reasoning and high school math and graduate level reasoning, I think Gemini 2.5 Pro actually outperforms. So we will be taking this in action, and we'll be testing with some coding prompts and tools and see how it really performs. So here we have Gemini 2.5 Pro, and it is available in the free version. So you just have to try it in the Google AI Studio from here. So now in the chat mode, as you can see, we've got this navigation bar where we have this option of stream, generate media, build history. Now, if you want a complete tutorial on Google AI Studio, you can find a full video I have attached in the card section, so you can just find it from there. So right now, let's give it a prompt. So I've given a prompt to generate a simple HTML and JavaScript game where a character runs endlessly and checks for collisions. So I'll just run from here. Also, you've got this run settings option where you have this thinking mode, set thinking budget, tools, code execution. So yeah, it has a lot of features. So here we have Claude 4. So we'll just compare it parallelly. We'll be running the prompts and commands and see which one actually performs better. So here we have Sonnet 4 and Opus 4 as well. But then the Opus is in the Pro version. For this, you have to pay, which is around yearly $200 and monthly $20 plus tax. So this will be your plan, your Pro plan if you purchase the Opus Pro. So I'll just continue with the Sonnet 4 and check. So here is my prompt given to create a basic HTML and JavaScript game that includes a character running endlessly with a collision detection feature. Alright, so from here you can search with the tools also, web search and all of that. You have this feature. So yeah, we will just hit on this enter plan. So we are using the free plan now, remember. So as you can see, it is creating the code for the game as here. And yeah, it's really fast as compared to Gemini. So here, as you can see, meanwhile, this Gemini 2.5 is also giving us the code faster. So it's written here that you can just copy this code and you can save it as game.html, and then you can open it in your web browser to play this. So we'll just open this, and this is the game which it has generated for us. So you can see from here, press the space bar or click on the jump. And I think it's pretty basic. It doesn't include much. And now you can see Claude has also given us the game, and you can just press the space bar, you can click on jump to check this. And just look at the UI, guys. I think this is much more better, because if we compare it with the Gemini 2.5, then it has given us a simple basic game. Maybe we have to make some changes out there. We'll also check it soon. But then just look at this. The UI and everything, the code it has generated, the control buttons, everything is just so good. So you have the score and high score option as well, and you can just press the space bar, you can click on jump. So I'm really impressed by Claude 4 Sonnet, and I think it really outperforms. So I would rate it 4 out of 5, and if I compare it with the Gemini, it doesn't really perform that well. So I would rate it around maybe 2 out of 5 or 1, because this is pretty simple basic. So now again, I'll be giving a second prompt, which is to create a 3D car simulation game using JavaScript and WebGL. Allow basic car controls like forward, backward, and tuning. You can also modify your prompt, like make the UI really attractive. And so I've given more of the modified prompt here, and I'll just again hit run. So it will take a bit of time to generate. Now in the meanwhile, I'll just head over to Claude from here, and again I'll just give a prompt to create a 3D car simulation game using JavaScript and WebGL. Allow basic car controls like forward, backward, and touring. So you can see it's much more faster compared to the Gemini. And here the Gemini has also created. The code is being given to us with all the stylings and everything. So now I think I've got the code from here, so I'll just download it. So here we have the 3D car simulation of the Gemini 2.5 Pro. And here you have the game option to enable the shadows, camera view is follow. You have top down also. So if you do the top down, it will appear something like this. And yeah, you have plenty. I think this one is pretty good if we compare it with, let's see how actually Claude does this now. But this 3D version is better than the before, the prompt and the game it had generated for us. And for the controls, you have this forward, backward, left and right. Now let's see what Claude has given, and just see, guys, the UI again outperforms here, and it's really amazing. It's really amazing. Just look at the UI features and the game controls as if you're actually, you know, running a game and you're just playing a game in this thing. And yeah, you have plenty of options here. So you have also this car controls features added, and I found it really good. I mean, if we look at the UI wise, so the 3D models look intuitive here in this case of Gemini 2.5 Pro. But then again, in the Claude here, I would say it ranked a lot. And again, if I had to give ranking, then I would give around 5 out of 5. And for Gemini 2.5 Pro, I would give around maybe 3 out of 5. So it's good, but then it lacks a bit of more features and modifications, you know. But in this case, we have a lot of features, and the UI is also very tempting and appealing for any user to play this game. So yeah. I would say that Claude Sonnet 4, the free version is really good. Again, you need to, if you want to try the Opus one, it will be obviously good. So according to me, the Claude 4 really performed well. So next, we'll also check the debugging performance and which one actually fixes the bug faster. So I'm here in my Gemini 2.5, and I've been given a prompt to actually debug my this code. The project was working fine, but there are a few bugs, and I wanted to fix it. So let's see what times and how much time does it actually take to fix these bugs. So it's taking a bit of time, and it's refining the bug dissections. So you have this thinking budget options also from here. So it's taking a bit of time. Meanwhile, we'll just head over to Claude and just check the speed from here. So again, I've given the same prompt to Claude also. The project was working fine, but here are a few bugs and all. So let's see how much time does this take. So you can see the response is really faster as compared to Gemini. And again, Claude here outperformed. Yeah, it is. It takes a bit of time. I mean, comparatively, just a bit slower and lags a bit behind of Claude 4. So yeah, it takes a bit of time now. Talking about the unique features, AI agents and the browser controls. One of the coolest features Claude 4 Sonnet offers is the ability to control your browser and even your laptop using the AI agents. You can ask it to research news, navigate websites, and complete the task. Just from here, you have this option of the search tool. You can use the style also, normal, concise, explanatory. So you can see you have this plenty of unique options here. So I've tested and according to the pricing wise, however, if you want a cheaper, solid option, you can still handle general tasks like debugging, adding features, and understanding the code. And you're not doing hardcore coding tasks, then I think Gemini 2.5 Pro is your best bet. But then if you want some bit of heavy lifting of coding, then I think Claude 4 actually stands out. But then if you really want some basic features and basic coding and everything, then this Gemini 2.5 is better. But then personally, I liked Claude 4. So to sum it up, I would say Claude Sonnet 4 is fantastic for coding, but if you're just looking to get the stuff done without breaking the bank, to Gemini 2.5 Pro also does a great job.
In this tutorial, we will learn about OpenAI's Gen AI agents. So generative AI agents are advanced AI-driven systems designed to autonomously perform tasks, generate content, and assist in decision-making by leveraging large language models, or also known as LLMs, and machine learning algorithms. Imagine an AI agent automating repetitive processes, enhancing productivity, and providing personalized recommendations across various domains, including customer support, marketing, and software development. By understanding context and generating human-like responses, they improve workflows from cost to problem solution and improved efficiency. Such are a few out of many use cases of AI agents. Today, we will cover the OpenAI Gen AI agents and their facts, their challenges, and future implications. That's it. If these are the type of videos you'd like to watch, then hit that like and subscribe buttons and the bell icon to get notified. Also, just that you know, if you want to upskill yourself, master generative AI and artificial intelligence skills, and land your dream job or grow in your career, then you must explore Simplilearn's cohort of various generative AI courses and certifications. Simplilearn offers various certification programs in collaboration with some of the world's leading universities like Purdue, IIT Guwahati, and many more. Through our courses, you will gain knowledge and work-ready expertise in skills like advanced Python, machine learning, generative AI, and over a dozen others. That's not all, you also get the opportunity to work on multiple projects and learn from industry experts working in top-tier data and product companies, and also academics from top universities. After completing these courses, thousands of learners have transitioned into an AI and machine learning role as a fresher or moved on to a higher paying job and profile. If you are passionate about making your career in this field, then make sure to check out the link in the pinned comment and description box below to find a generative AI program that fits your experience and areas of interest. Now, without further delay, let's get started. OpenAI Gen AI agents. So, first, let's get started with the agenda for today's session. We will have a brief introduction to generative AI agents. Followed by that, we will understand the core components of Gen AI agents, then how generative AI agents work, architectures and deployment, enhancing AI agents with external tools, challenges and limitations of Gen AI agents, future trends and advancements in AI agents will be the last one. So I hope I made myself clear with the agenda. Now let's get started with the first part, which is Introduction to Generative AI Agents. So basically, what exactly do you mean by the term generative AI agents? So an AI agent is just an LLM that can take actions, and it can do so autonomously without any human supervision, and now also reason about the tasks. An AI agent is software entity that autonomously interact with environments, make decisions, and execute tasks. Generative AI agents extend by leveraging large language models like OpenAI's GPT to generate intelligent responses and perform tasks beyond rule-based automation. Now, we will also look into the evolution of AI agents. Traditional rule-based AI agents had limited to predefined rules. Like if you define a process and give the steps, it will just perform them and complete it. It will not take a step beyond it. And machine learning based AI agents can learn from data but need structured inputs. And then comes the generative AI agents, which are capable of understanding, reasoning, and generating human like responses autonomously. Like they understand the environment and learn through it and take their steps based on the principle they have been trained for. And also, they will provide the reason for which they have taken a certain step. Now, moving ahead, why generative AI agents matter a lot. So there are three key points to consider. Firstly, efficiency. They automate repetitive tasks with minimal human intervention. Next is high scalability. They handle large volumes of work, example customer support, content generation, and many more. And finally, intelligence. They can adapt to different use cases dynamically. Nobody has to write rules for them. Now let's focus on OpenAI and its latest release of agents. So OpenAI just released two new groundbreaking agents, the Operator Agent and Deep Research Agent. These two releases are absolutely massive for all AI agent developers. So Operator is the first AI agent released by OpenAI, and what it does is it mimics human actions on your browser. So it means it can scroll, type, click, and navigate Google web pages for you just like any other human would. But more importantly, and what many people have missed out is this agent is actually based on a completely new model called CUA, which stands for Computer Using Agent. So this agent, unlike standard GPT models, wasn't trained to just output text. You like write a prompt and expect an output in the text format. Instead of that, it can go beyond it. This agent was actually trained to output mouse and keyboard clicks, which is exactly what makes this agent so powerful in your browser. But not only that, it can also reason about every single action. This is also something that we haven't seen before. This agent doesn't just perform actions in your browser, it actually reasons about every single step and what it should do next. Just like we discussed before about the generic overview of generative AI agents, same as the OpenAI operator here. It takes the step based on the environment, and also it will give you a particular reason for which or based on which it took a certain action, and it also asks you what to do next. Let's say if you want to book a ticket, it'll navigate to all the websites. It can go through some better flight options for you. Let's say the low cost ones, the low hours of flight ones, and best timings, and then finally selects the best one for you based on your recommendations and asks you if it should proceed with booking or not. So that's how it works. Now, of course, there are some limitations as well. The first limitation is it has still a lower bit of accuracy. It's really high compared to other projects that we have seen in the past where people just prompt GPT models to perform actions in the browser that can browse web using GPT-4o vision capabilities, but it often struggles with other models. So whenever there was a model on a web page, like some other random model available working readily on a web page, it would just accidentally pop up and it would not be able to do anything because it would just get confused. It would not be able to close it, and then basically you would have to get involved yourself and close this model manually. And the second limitation is high cost. Right now, this particular operator agent is only available on $200 plus plan. So we can probably guess it's going to be pretty expensive in the API. Also, I do think that if you are focusing on the right thing, then costs are not going to be an issue. Now, let's talk about the second agent that OpenAI deployed. Now, the second agent which was deployed by OpenAI is called as Deep Research. So this second agent released by OpenAI was trained to perform comprehensive research. It can search the web, it can pull up the necessary resources, and then it can compile all that information into a really comprehensive document or maybe a report as well. The groundbreaking thing about this agent is it's powered by the new O3 model. So again, similar to the operator agent, but it doesn't just search the web and provide you with the results. It actually reasons about every single source, and then it thinks about what other information it needs to find out next, and it's really incredibly powerful. Deep research doesn't just output the most average thing on the internet just like some other standard GPT models. It would compile novel insights. Now, let's move on to the real world applications. There are a wide variety of real world applications. First one is customer support AI agents, which helps you in automating help desk responses. Next, powerful AI assistants like co-pilots for professionals. Third one is research and analysis agents for data summarization, literature reviews, and many more. Fourth one is creative writing and content generation, automating social media posts, emails, etc. And lastly, AI-driven code assistants like GitHub Copilot, OpenAI Codex, and many more. Now, let's go through the next part, which is core components of these generative AI agents. Let's begin with the foundation models. So the foundation models are GPT-4, Dolly, and Whisper. GPT-4 for natural language processing, Dolly for image generation, and Whisper for speech to text conversion. The next one would be prompt engineering and context handling. So here, designing effective prompts for AI agents to generate relevant responses, using few shot and zero shot learning for adaptability, and lastly, implementing context-aware AI agents that remember past interactions from the user. Now, next would be the memory and long-term context storage. AI agents typically process short-term prompts, but memory-based approaches, for example, Langchain's memory module, enable long-term reasoning as well. Now, storing and retrieving user-specific data for personal responses is also one of the priority. Next will be the tool use and API integrations. Using external API to fetch real-time data, for example, weather, stock prices, news, etc., and integrating databases for structured information retrieval. And proceeding further, we have autonomous decision making. AI agents evaluate multiple options before making a decision. Planning and reasoning techniques to enhance responses is a priority for them. Proceeding ahead, we will discuss how generative AI agents work. Starting with the first step, input processing and context awareness. AI agents analyze user input, detect intent, and extract entities. For example, in a travel booking AI agent, it identifies destination, date, and budget from user queries. Just like the example we discussed before, right? You provide the point A and point B, the best time for you to fly, and the best number of hours that you focus on flying, and lastly, the destination, right? All these things will be evaluated in real time. The cost, the number of hours, the flight, the options provided, the amenities provided on the flight, and all those things, and also budget as well. And based on that, they take a decision. Now proceeding ahead, generating intelligent responses. So here, RAG, or also known as Retrieval Augmented Generation. AI searches external databases for responding. Next, we have chain of thoughts reasoning, or also known as COT reasoning, and AI breaks down problems into fine steps. And last step is fine-tuning the models, custom trained AI for specific industries. For example, if you're preparing an AI agent for a dedicated sector like healthcare, legal, customer support, based on that, you will fine-tune your AI agent or model. Now, next is decision trees and multi-step reasoning. AI can simulate a thought process, breaking down complex questions into manageable steps. For example, whenever you open DeepSeek or whenever you open OpenAI ChatGPT for the most premium version, you will write a prompt and there will be an option called Think, right? If you just click on that, it will explain you the thought process it is going through and how is it planning on giving a reason for you, right? And followed by that, we have handling uncertainty and error correction. AI self-corrects through confidence scoring and human feedback loops. Last step in this particular stage is fine-tuning and reinforcement learning, or also known as RLHF. Human in the loop training to improve responses, and AI learns from real world interactions and adapts over time. So it's basically called overtime learning, where it adapts to the real world environment and learns things and provides the best feasible solution. Now, the next stage is architecture and deployment of AI agents. So in the first one, we have standalone versus multi-agent systems. So firstly, the standalone AI agents. They perform tasks independently. For example, ChatGPT. Multi-agent systems, on the other hand, work together to achieve complex tasks. For example, one agent for summarization, another for execution. Now, next in this particular stage is agent orchestrator model. A central AI agent coordinates multiple AI sub-agents. For example, in an AI-powered research assistant, one agent gathers all the data that is required, the second agent summarizes all the information collected, and the third agent formats the output. Followed by that, we have cloud-based AI agents and edge-based AI agents. Cloud-based AI agents compute, for example, OpenAI API, Azure AI, and edge-based AI agents run on local devices for faster processing, for example, Tesla's AI in self-driving cars. Followed by that, we have using APIs to build AI agents. OpenAI's API for GPT-4 powered by AI agents, Langchain framework for AI agent orchestration, and Llama Index for document-based AI agents. The next stage, we will discuss about enhancing AI agents with external tools. In that, the first step is integrating with databases. AI agents can query SQL and non-SQL query databases for structured data retrieval. Proceeding ahead, we have connecting with web scrapers and APIs. AI agents can fetch real-time data using tools like Beautiful Soup, Scrappy, and OpenAI plugins. Next ahead, using vector databases for context recall. FAISS ChromaDB store long-term memory for AI agents. For example, legal AI agents retrieve case law from vector embeddings. Lastly, we have autonomous agents and workflows. AutoGPT and Baby AGI are best examples. These AI agents that self-improve by learning from previous tasks, and True AI, which is a set of multiple AI agents collaborating to solve a complex problem. Now, the main part, challenges and limitations of generative AI agents. In that, the first one will be the ethical considerations. AI bias and fairness concerns are the primary ones. Addressing AI hallucinations, which is false information generation, and then we have computational cost and efficiency, which is a major concern amongst all the industries. Large AI models require significant computational power. Strategies to optimize AI agent efficiency will also considered to be expensive to hire many training models or also human programmers. Followed by that, we have security risks and data privacy. Risk of data leaks or data breaches and AI jailbreaking is one of the highest security threat. Implementing secure AI architecture is one of the primary solutions that you need to focus on. And lastly, we have legal and compliance issues. This would majorly be concerned from the enterprise level. GDPR, HIPAA, and AI regulations compliance is mandatory, and AI liability in decision making is also important. And now, the last stage of today's discussion, which is future trends and advancements in AI agents. Starting with the first one, AI agents with emotional intelligence are also known as affective AI. AI is capable of detecting emotions and adapting responses accordingly. For example, if you have designed a therapeutic AI chatbot for mental health. Now, the next one, self-improving AI systems. So meta learning and auto ML are a few examples. AI agents that learn from new data autonomously, for example, AI adjusting marketing campaigns based on customer responses. And now the next one, AGI and roadmap to superintelligence. Well, this always ends up with question. Will AI agents evolve into AGI, or also known as artificial general intelligence? And are the implications of self-learning AI real? This is the major question. And lastly, the role of AI agents in the future of work. Now we can see there are a lot of AI agents like Copilot which will assist humans in their day-to-day tasks, whether it is business, healthcare, or education. And also, you have a lot of automation and transformation happening in the IT industry, which will reduce the work hours and stress on the employees by automating all those mundane tasks by the help of copilots, also the generative AI agents.
Today, we will discuss about booming topic of this era, multimodal AI. Let's understand with an example. Imagine you are showing a friend your vacation photos. You might describe the sight you saw, the sounds you heard, and even your emotions. This is how humans naturally understand the world, by combining information from different sources. Multimodal AI aims to do the same thing. Let's break the modal AI first. Multimodal refers to two different ways of communicating information like text, speech, images, and videos, where AI stands for artificial intelligence, which are systems that can learn and make decisions. So, multimodal AI is a type of AI that can process and understand information from multiple sources, just like you do when you look at your vacation photos. Before delving more into multimodal AI, so here is a just quick info for you.
Craving a career upgrade? Subscribe, like, and comment below. Dive into the link in the description to fast track your ambitions. Whether you're making a switch or aiming higher, Simplilearn has your back.
If you want to switch careers with AI and ML, then try giving Simplilearn's postgraduate program in AI and machine learning from Purdue University in collaboration with IBM. This course teaches in-demand skills such as machine learning, deep learning, NLP, computer vision, reinforcement learning, generative AI, prompt engineering, ChatGPT, and many more. So don't forget to check out the course link from the description box and pin comment. Now that we have understood what is multimodal AI, let's now go a bit further. It is obvious that multimodal AI is not the only AI out there. But what is big deal about multimodal AI that everyone is talking about? That is what we will discuss in this segment. So now let's understand the difference between multimodal AI and the generative AI. While both multimodal AI and generative AI are exciting advancements in AI, they differ in their approach to data and functionality. So generative AI focus creates new data similar to the data it's trained on. And in multimodal AI, focus is to understand and processes information from multiple sources, that is text, speech, images, and videos. Data types of generative AI are primarily works with a single data type like text, writing poems or images, that is generating realistic portraits. Whereas in multimodal AI, data types works with diverse data types, enabling a more comprehensive understanding of the world. The third one is examples like chatbots, text generation models, image editing tools. Whereas multimodal AI example covers virtual assistants, medical diagnosis system, and autonomous vehicles. Strengths are can produce creative and innovative content, automate repetitive tasks, and personalize your experience. Whereas in multimodal AI, strengths are provides a more human-like understanding of the world and improve accuracy. In essence, generative AI excels at creating new data, while multimodal AI excels at understanding and utilizing existing data from diverse sources. They can be complementary, with generative models being used to create new data for multimodal AI systems to learn more from and improve their understanding to the world. Next, let's understand what are the benefits of multimodal AI. The benefits of multimodal AI is that it offers developers and users an AI with more advanced reasoning, problem solving, and generation capabilities. These advancements offers endless possibilities for how next generation application can change the way we work and live. For developers looking to start building, Vortex AI Gemini API offers features such as enterprise security, data residency, performance, and technical support. If your existing Google Cloud customers can start prompting with Gemini AI in Vortex AI right now. Next, let's see what are the multimodal AI big challenges. Multimodal AI is powerful but faces hurdles. The first one is data overload. Managing and storing massive, diverse data is expensive and complex. The second one is meaning mystery. Teaching AI to understand subtle difference in between meaning like sarcasm is tricky. The third one is data alignment. Ensuring data points from different sources staying in tune is challenging. The fourth one is data scarcity. Limited and potentially biased datasets hinder effective training. The fifth one is missing data blues. What happens when data is missing, like distorted audio? The last one is black box blues. Understanding how AI makes decisions can be difficult. So these challenges must be addressed to unlock the full potential of model AI. Next, let's see what is the future of multimodal AI and why is it important. Multimodal AI and multimodals represent a leap forward in how developers build and expand the functionality of AI in the next generation of application. For example, Gemini can understand, explain, and generate high quality code in the world's most popular programming languages like Python, Java, C++, and Go, freeing developers to work on building more featured field applications. Multimodal's AI potential also bring the world closer to AI that's less like smart software and more like an expert helper or assistant.
Have you ever wondered how AI models can understand and process multiple types of inputs, like text, images, and audio simultaneously? Hello, everyone. Welcome to our deep dive into multimodal prompting, a transformative approach that's reshaping the landscape of artificial intelligence. My name is Basil DeClala, and in this video, we'll explore what multimodal prompting is, why it's essential, and how it's applied across various industries. Let's embark on this journey to uncover the future of AI together. Here's our agenda. Introduction to multimodal prompting. Evolution of prompting. Core concepts of multimodal prompting. Tools and platforms that support multimodal prompting. Use cases and applications. Getting started with multimodal tools. And then we'll take a look into simple multimodal prompts in action. And we'll have a deep dive or step-by-step prompt building. Last but not least, we'll look into experimenting with different use cases. You might be wondering, what is multimodal prompting? Multimodal prompting is a technique that allows AI models to interpret and respond to input from more than one modality, like combining text, images, audio, or video. Instead of just reading text, the model can basically analyze visuals, sounds, or other forms of data to generate richer, more context-aware responses. It basically mimics how humans process information. Now, why it matters and where is it used? Multimodal prompting matters because the real world isn't just text-based. We live in a sensory-rich environment, and multimodal AI helps machines understand that. It's used in applications like image captioning, video analysis, interactive chatbots with visual context, and even healthcare diagnostics where images and notes are combined. In addition, multimodal prompting is very useful for content creation and recommendation. Let's talk about the evolution of prompting. Let's learn about the evolution of prompting, from text-only models to multimodal models. Prompting has evolved from simple text inputs to complex multimodal interactions. Today's models can understand and respond to combinations of text, images, audio, and more for deeper context. Prompting began with text-only models like GPT-2, which responded solely to written input. They basically leveraged NLP, which stands for Natural Language Processing. Over time, models evolved to process images, audio, and even video, giving rise to truly multimodal systems that can interpret and connect across different types of information. How models understand and process multiple input types. Modern multimodal models have specialized architectures, such as vision transformers, multimodal neural networks to process different inputs. They are also trained on paired data like images with captions or videos with transcripts. These models learn how different modalities relate to each other, enabling them to take in multiple types of inputs and generate informed outputs that bridge those sensory channels. Cross-model attention helps models link relevant features across inputs, enhancing context and accuracy. At the core, these models use shared embedding spaces to map inputs like text and images into a common understanding. For example, a picture of a dog and the word dog are brought close together in this space, allowing the model to reason across formats in a unified way. Let's talk about core concepts of multimodal prompting. Modalities are different types of information we can give to AI, like text, pictures, sound, or video. They help the model understand things the way humans do, through multiple senses. These senses are text, with written language input like prompts or documents; image, visual content such as photos, charts, or drawings; audio, sound-based input like speech or music; and video, time-based visual and audio content combined. In multimodal prompting, in unimodal prompting, the model receives one type of input, typically text. In contrast, multimodal prompting involves multiple types, like combining a question with an image or a diagram. So, input modalities include one or more types. This requires the model to integrate different streams of information and make connections between them. So let's recap the key difference between unimodal and multimodal prompting. First, we've got the input type. Unimodal prompting has one single type and typically is text. Multimodal prompting has multiple types and it could be text, images, audio, etc. Second, context depth. Unimodal prompting is limited to one form of input. On the other hand, multimodal prompting is richer in context and has combined inputs. 3. Use cases. Unimodal prompting can only be used on text-based tasks, such as writing. Multimodal prompting can be used in multiple tasks and complex ones, like image analysis, and speech to text. 4. Understanding. Unimodal prompting is linear and it's language focused. Multimodal prompting, on the other hand, is cross-modal and human-like. Despite its potential, multimodal prompting comes with challenges. Models can misalign inputs, generate hallucinations, or be biased towards dominant modalities. Input format issues from the model misinterpreting poorly formatted inputs. 2. Limited modal support. Not all models handle every modality. 3. Ambiguity inputs. Unclear inputs can lead to inaccurate responses. 4. High computational load. Multiple modalities require more resources. There's also a lack of standard benchmarks, and combining training data from different formats can be resource intensive. Let's discuss tools and platforms that support multimodal prompting. First, we've got one of the most popular generative AI tools, ChatGPT. Specifically, ChatGPT with Vision. This version of ChatGPT can understand and analyze both text and images. It's useful for tasks like generating captions or answering questions about visual content. If you're not familiar with ChatGPT, it's basically an AI chatbot based on OpenAI's GPT, which stands for Generative Pre-trained Transformer Models. It can understand and generate human-like text for tasks like writing, coding, summarizing, tutoring, and casual conversations. And now it has multimodal capability. It's widely used in education, business, and creative work. ChatGPT can handle multimodal inputs by combining image recognition with text generation, allowing users to ask questions or generate text based on images. It processes the image and merges it with text for a complete response. The second next popular tool is Gemini by Google. Gemini is Google's family of advanced AI models designed to rival GPT. It's multimodal, meaning it can handle text, images, code, and other inputs. Gemini powers tools like Bard and Google Workspace AI, aiming to provide accurate integrated assistance across Google's ecosystem. It helps with complex interactions like visual-based search and multimodal content generation. It's designed for broader, context-aware AI applications. It handles multimodal inputs very quickly and uses advanced fusion models to integrate text, image, and video inputs, understanding relationships between them for more context-aware responses and generation. Next, Claude is a conventional AI developed by Anthropic, focused on safety, helpfulness, and transparency. It's known for its thoughtful responses and is designed to be steerable and aligned with user intentions. It can also integrate text, images, and documents, allowing for in-depth analysis and interaction with various input formats. Claude is a strong competitor to ChatGPT and excels at tasks like PDF creation, Q&A, and content summarization. Claude also does a good job of breaking down each modality for text, images, and documents separately. It processes them and then combines them for tasks like document analysis or multi-source content generation. DALL-E by OpenAI is an AI model that generates high-quality images from text descriptions. It's known for its detailed, creative outputs and is integrated into ChatGPT's interface for users on the Plus plan. It basically accepts textual prompts and translates them into relevant images, seamlessly merging descriptive text with visual output for creative image generation. It's got a lot of tools that help you build a scene and will turn it into an image from realistic to fantastical. Let's talk about use cases and applications in multimodal prompting. We have users that can upload images, such as diagrams and charts, and then ask questions about them, with AI providing context-aware answers. Next, AI creates articles, social media posts, or marketing copy based on both text and image inputs. In terms of content generation applications, AI can create articles, social media posts, and marketing copy based on both text and image inputs. For product tagging, e-commerce platforms use images and descriptions to generate accurate product tags and recommendations. Multimodal prompting can also be effective for interactive education. AI helps in learning by analyzing images, videos, and text to provide interactive educational content. It's also useful for accessibility. It assists visually impaired users by converting visual content, such as photos and infographics, into descriptive text. Let's see how we can access and set up a basic multimodal prompting environment. First, choose a platform. You can sign up for access to platforms like ChatGPT or Gemini. Next, install required tools and install necessary libraries. Then, obtain API keys for the platform and configure your environment. Then, ensure inputs are properly formatted and compatible for the application. Lastly, test with basic prompts or run simple multimodal tasks. Let's talk about the required tools and input formats. First, you need an API access. Second, install some Python libraries and have a Jupyter notebook. Also, you can use cloud platforms, although some of these applications can be done using your local machine. Here's a list of the input formats that you can leverage. You've got text, image, audio, and video. Let's jump into a demo to show how LLMs can be used for multimodal tasks. In this demo, we'll be using ChatGPT to showcase its powerful multimodal capabilities. Keep in mind that most LLM tools like Gemini and Claude can also provide similar capabilities that I'm about to show. For ChatGPT, many of the capabilities we're about to showcase are only available in ChatGPT Pro. It's available for a limited number of prompts in the free version. If you want to leverage the full capabilities, you'll need to subscribe to ChatGPT Pro. First, after you log into ChatGPT, you need to make sure that you have GPT-4 activated. Next, you'll see that there's a plus button that is popping up where I can add media. But before we do this, let's generate media using text prompts. Write a 3-sentence summary of the plot of Inception like you are explaining to a 10-year-old. You can see ChatGPT gave us a response with a concise 3-sentence summary of the plot of Inception. So I'll read the first sentence. Inception is about a man named Cobb who goes into people's dreams to steal their secrets like a spy in their sleep. Let's take things to next step. I'm going to ask ChatGPT to generate a poster based on the description in cartoon style. Let's make sure that it's pointing to the description above. Go ahead and run this, and we'll give it a few seconds to generate the image. Keep in mind that ChatGPT sometimes runs under a heavy load of requests, and sometimes image generation takes time. Image generation is done. You can see ChatGPT generated an output according to my description, a cartoon-like poster of Inception. Next, we'll show ChatGPT's ability to analyze images. I find this task very useful for analyzing complex visuals, such as stock charts. I'll click on the plus sign and then add photos and files. Select your photo and then insert the following prompt. Analyze the support and resistance levels of the attached 4-hour interval chart of Google. You can see that ChatGPT was able to analyze the chart for me in an instance and was able to give me multiple support levels and resistance levels with their description. Let's do another example of image analysis. I'm going to click the plus sign here and upload a hand-drawn chart. And here's my prompt. Explain the attached image of a diagram step by step. For reference, here's the image and here's the explanation. Start the process. The program begins execution. Step 1, input value. Gives me a check for Stack Overflow. And then it explains the rest of the steps according to the diagram. It was also able to analyze the gist of the diagram. It is a standard stack push operation with overflow checking, where it prevents adding data when the stack is full and confirms insertion when space is available. It can also offer an equivalent code in Python or C. That was a good example for visual and text reasoning. Let's increase the level of difficulty of this type of task by giving it a mathematical problem. I'll click on the plus sign again, add photos, and select my image. And I'll use the following prompt. What is the answer to the math problem in the attached image? Here's the image for reference. Find the sum of the series. And you can see that ChatGPT is generating LaTeX or Markdown type of syntax in the background so it can display the mathematical syntax and Greek symbols properly. Not only was it able to solve for these problems, but also was able to give me a step-by-step instructions on how to solve for it. Plus, it recognized that we have 2 problems, not just one, to solve for. In this last example, we're going to do the opposite of multimodal prompting. Instead of providing an image, we're going to ask ChatGPT to generate a complex image based on my description. Provide a detailed process for data science and feature engineering for or the diabetes healthcare dataset. The diabetes healthcare dataset is a popular dataset available online, so ChatGPT will be able to understand exactly what I'm looking for. Here we can see step-by-step instructions of the process, along with Python code on how to run the analysis, such as EDA, outlier detection, multivariate analysis, and then feature engineering as requested, all the way to modeling and providing proper evaluation metrics. After getting the steps in text format, I want ChatGPT to build a visual diagram of those steps.
Why reinforcement learning? Training a machine learning model requires a lot of data, which might not always be available to us. Further, the data provided might not be reliable. Learning from a small subset of actions will not help expand the vast realm of solutions that may work for a particular problem. And you can see here we have the robot learning to walk. Very complicated setup when you're learning how to walk, and you'll start asking questions like, if I'm taking one step forward and left, well, what happens if I pick up a 50-pound object? How does that change how a robot would walk? These things are very difficult to program because there's no actual information on it until it's actually tried out. Learning from a small subset of actions will not help expand the vast realm of solutions that may work for a particular problem. And we'll see here it learned how to walk. This is going to slow the growth that technology is capable of. Machines need to learn to perform actions by themselves and not just learn off humans. And you see the objective climb a mountain. A real interesting point here is that as human beings we can go into a very unknown environment and we can adjust for it and kind of explore and play with it. Most of the models, the non-reinforcement models in computer machine learning, aren't able to do that very well. There's a couple of them that can be used or integrated. To see how it goes is what we're talking about with reinforcement learning. So what is reinforcement learning? Reinforcement learning is a sub-branch of machine learning that trains a model to return an optimum solution for a problem by taking a sequence of decisions by itself. Consider a robot learning to go from one place to another. The robot is given a scenario and must arrive at a solution by itself. The robot can take different paths to reach the destination. It will know the best path by the time taken on each path. It might even come up with a unique solution all by itself. And that's really important as we're looking for unique solutions. We want the best solution, but you can't find it unless you try it. So when we're looking at our different systems, our different model, we have supervised versus unsupervised versus reinforcement learning. And with the supervised learning, that is probably the most controlled environment. We have a lot of different supervised learning models, whether it's linear regression, neural networks, there's all kinds of things in between, decision trees. The data provided is labeled data with output values specified. And this is important because when we talk about supervised learning, you already know the answer for all this information. You already know the picture has a motorcycle in it, so you're supervised learning. You already know that the outcome for tomorrow, for going back a week, you're looking at stock, you can already have like the graph of what the next day looks like, so you have an answer for it. And you have labeled data which is used, you have an external supervision, and solves problems by mapping labeled input to known output. So very controlled. Unsupervised learning, and unsupervised learning is really interesting because it's now taking part in many other models. They start with you can actually insert an unsupervised learning model in almost either supervised or reinforcement learning as part of the system, which is really cool. Data provided is unlabeled data. The outputs are not specified. Machine makes its own predictions. Used to solve association with clustering problems. Unlabeled data is used. No supervision. Solves problems by understanding patterns and discovering output. So you can look at this and you can think some of these things go with each other. They belong together. So it's looking for what connects in different ways. And there's a lot of different algorithms that look at this. When you start getting into those, there's some really cool images that come up of what unsupervised learning is, how it can pick out, say, the area of a donut. One model will see the area of the donut, and the other one will divide it into 3 sections based on its location versus what's next to it. So there's a lot of stuff that goes in with unsupervised learning. And then we're looking at reinforcement learning. Probably the biggest industry in today's market in machine learning, or growing market. It's very infant stage as far as how it works and what it's going to be capable of. The machine learns from its environment using rewards and errors, used to solve reward-based problems. No predefined data is used, no supervision, follows trial and error problem solving approach. So again, we have a random, at first you start with a random, I try this, it works and this is my reward, doesn't work very well maybe, or maybe it doesn't even get you where you're trying to get it to do, and you get your reward back, and then it looks at that and says, well, let's try something else, and it starts to play with these different things, finding the best route. So let's take a look at important terms in today's reinforcement model. And this has become pretty standardized over the last few years, so these are really good to know. We have the agent. Agent is the model that is being trained via reinforcement learning. So this is your actual entity that has, however you're doing it, whether you're using a neural network or a Q table or whatever, combination thereof. This is the actual agent that you're using. This is the model. And you have your environment. The training situation that the model must optimize to is called its environment. And you can see here, I guess we have a robot who's trying to get a chest full of gems or whatever, and that's the output. And then you have your action. This is all possible steps that can be taken by the model, and it picks one action. And you can see here that it's picked 3 different routes to get to the chest of diamonds and gems. We have a state, the current position condition returned by the model. And you could look at this if you're playing like a video game. This is the screen you're looking at. So when you go back here, the environment is a whole game board. So if you're playing one of those Mobius games, you might have the whole game board going on, but then you have your current position. Where are you on that game board? What's around that? What's around you? If you were talking about a robot, the environment might be moving around the yard, where it is in the yard and what it can see, what input it has in that location. That would be the current position condition returned by the model. And then the reward. To help the model move in the right direction, it is rewarded. Points are given to it to appraise some kind of action. So, yeah, you did good, or if didn't do as good, trying to maximize the reward and have the best reward possible. And then policy. Policy determines how an agent will behave at any time. It acts as a mapping between action and present state. This is part of the model. What is your action that you're going to take? What's the policy you're using to have an output from your agent? One of the reasons they separate policy as its own entity is that you usually have a prediction of a different options, and then the policy, well, how am I going to pick the best? Based on those predictions, I'm going to guess at different options. And we'll actually weigh those options in and find the best option we think will work. So it's a little tricky, but the policy thing is actually pretty cool how it works. Let's go ahead and take a look at a reinforcement learning example. And just in looking at this, we're going to take a look, consider what a dog that we want to train. So the dog would be like the agent. So you have your puppy or whatever. And then your environment is going to be the whole house or whatever it is where you're training them. And then you have an action. We want to teach the dog to fetch. So action equals fetching. And then we have a little biscuit, so we can get the dog to perform various actions by offering incentives such as a dog biscuit as a reward. The dog will follow a policy to maximize this reward, and hence will follow every command and might even learn new actions like begging by itself. So you have, so we start off with fetching. It goes, oh, I get a biscuit for that. It tries something else, and you get a handshake or begging or something like that, and it goes, oh, this is also reward based, and so it kind of explores things to find out what will bring it as biscuit. And that's very much like how a reinforced model goes. Is it looks for different rewards. How do I find? Can I try different things and find a reward that works? The dog also will want to run around and play and explore its environment. This quality of model is called exploration. So there's a little randomness going on in exploration. And it explores new parts of the house. Climbing on the sofa doesn't get a reward. In fact, it usually gets kicked off the sofa. So let's talk a little bit about Markov's decision process. Markov's decision process is a reinforcement learning policy used to map a current state to an action where the agent continuously interacts with the environment to produce new solutions and receive rewards. And you'll see here's all of our different vocabulary we just went over. We have a reward, our state, our agent, our environment, and our action. And so even though the environment kind of contains everything, you really, when you're actually writing the program, your environment's going to put out a reward and state that goes into the agent. The agent then looks at this state, or it looks at the reward usually first, and it says, okay, I got rewarded for whatever I just did, or I didn't get rewarded. And then it looks at the state, and then it comes back, and if you remember from policy, the policy comes in, and then we have a reward. The policy is that part that's connected at the bottom. And so it looks at that policy and it says, hey, what's a good action that will probably be similar to what I did, or sometimes they're completely random, but what's a good action that's going to bring me a different reward? So taking the time to just understand these different pieces as they go is pretty important in most of the models today. And so a lot of them actually have templates based on this that you can pull in and start using. Pretty straightforward as far as once you start seeing how it works, you can see your environment says, hey, this is the agent did this. If you're a character in a game, this happened, and it shoots out a reward in a state. The agent looks at the reward, looks at the new state, and then takes a little guess and says, I'm going to try this action. And then that action goes back into the environment. It affects the environment. The environment then changes depending on what the action was, and then it has a new state and a new reward that goes back to the agent. So in the diagram shown, we need to find the shortest path between node A and D. Each path has a reward associated with it, and the path with a maximum reward is what we want to choose. The nodes A, B, C, D denote the nodes to travel from node A to B is an action. Reward is the cost of each path, and policy is each path taken. And you can see here A can go to B, or A can go to C right off the bat, or it can go right to D. And if you explored all three of these, you would find that A going to D was a 0 reward, A going to C and D would generate a different reward, or you could go A, C, B, D. There's a lot of options here. And so when we start looking at this diagram, you start to realize that even though today's reinforced learning models do really good at finding an answer, they end up trying almost all the different directions you see. And so they take up a lot of work or a lot of processing time for reinforcement learning. They're right now in their infant stage, and they're really good at solving simple problems. And we'll take a look at one of those in just a minute in a tic-tac-toe game. But you can see here, once it's gone through these and it's explored, it's going to find the A, C, D is the best reward. It gets a full 30 points for it. So let's go ahead and take a look at a reinforcement learning demo. In this demo, we're going to use reinforcement learning to make a tic-tac-toe game. You will be playing this game against the machine learning model. And we'll go ahead, and we're doing it in Python. So let's go ahead and go through, not always, I actually have a lot of Python tools. Let's go through Anaconda, which will open up a Jupyter notebook. Seems like a lot of steps, but it's worth it to keep all my stuff separate, and it also has a nice display when you're in the Jupyter notebook for doing Python. So here's our Anaconda navigator. I open up the notebook, which is going to take me to a web page, and I've gone in here and created a new Python folder. In this case, I've already done it and enabled it to change the name to tic-tac-toe. And then for this example, we're going to go ahead and import a couple things. We're going to import numpy as np. We'll go ahead and import pickle. Numpy, of course, is our number array, and then pickle is just a nice way sometimes for storing different information, different states that we're going to go through on here. And so we're going to create a class called state. We're going to start with that. And there's a lot of lines of code to this class that we're going to put in here. Don't let that scare you too much. There's not as much here. It looks like there's going to be a lot here, but there really is just a lot of setup going on in our class state. And so we have up here, we're going to initialize it. We have our board. It's a tic-tac-toe board, so we're only dealing with 9 spots on the board. We have player 1, player 2. Is end. We're going to create a board hash. We'll look at that in just a minute. We're just going to store some information in there. Symbol of player equals 1. So there's a few things going on as far as the initialization. Then something simple, we're just going to get the hash of the board. We're going to get the information from the board on there, which is columns and rows. We want to know when a winner occurs. So if you get 3 in a row, that's what this whole section here is for. Let me go ahead and scroll up a little bit. And you can get a copy of this code if you send a note over to Simplilearn. We'll send you over this particular file, and you can play with it yourself and see how it's put together. I don't want to spend a huge amount of time on this because this is just some real general Python coding. But you can see here we're just going through all the rows, and you add them together, and if it equals 3 in a row, same thing with columns. Diagonal, so you got to check the diagonal. That's what all this stuff does here, so it just goes through the different areas. Actually, let me go ahead and put, there we go. And then it comes down here and we do our sum, and it says true, -3, it just says did somebody win, or is it a tie? So you got to add up all the numbers on there anyway, just in case they're all filled up. And next we also need to know available positions. These are ones that no one's ever used before. This way when you try something, or the computer tries something, it's not going to give it an illegal move. That's what the available positions is doing. Then we want to update our state. And so you have your position going in. We're just sending in the position that you just chose. And you'll see there's a little user interface we put in there. You can pick the row and column in there. And again, I mean, this is a lot of code. So really it's kind of a thing you'd want to go through and play with a little bit and just read through it, get a copy of it. A great way to understand how this works. And here is a given reward. So we're going to give a reward, result equals self winner. This is one of the hearts of what's going on here, is we have a result self.winner. So if there's a winner, then we have a result. If the result equals 1, here's our feedback. If it doesn't equal 1, then it gets a 0. So it only gets a reward in this particular case if it wins. And that's important to know because different systems of reinforced learning do rewarding a lot differently depending on what you're trying to do. This is a very simple example with a 3x3 board. Imagine if you're playing a video game, certainly you only have so many actions, but your environment is huge. You have a lot going on in the environment. And suddenly a reward system like this is going to be just, it's going to have to change a little bit. It's going to have different rewards and different setup. And there's all kinds of advanced ways to do that as far as weighing, you add weights to it. And so they can add the weights up depending on where the reward comes in. So it might be that you actually get a reward. In this case, you get the reward at the end of the game. And I'm spending just a little bit of time on this because this is an important thing to note. But there's different ways to add up those rewards. It might have, like if you take a certain path, the first reward is going to be weighed a little bit less than the last reward because the last reward is actually winning the game or scoring or whatever it is. So this reward system gets really complicated in some of the more advanced setups. In this case, though, you can see right here that they give a 0.1 and a 0.5 reward just for picking the right value and something that's actually valid instead of picking an invalid value. So rewards, again, that's like key. It's huge. How do you feed the rewards back in? Then we have a board reset. That's pretty straightforward. It just goes back and resets the board to the beginning because it's going to try out all these different things while it's learning. It's going to do it by trial and error, so you have to keep resetting it. And then, of course, there's the play. We want to go ahead and play rounds equals 100. Depends on what you want to do on here. You can set this different. You can obviously set that to higher level. But this is just going to go through, and you'll see in here that we have player 1 and player 2. This is the computer playing itself. One of the more powerful ways to learn to play a game, or even learn something that isn't a game, is to have two of these models that are basically trying to beat each other. And so they keep explore new things. This one works for this one, so this one tries new things. It beats this. We've seen this in chess, I think was a big one, where they had the two players in chess with reinforcement learning. It was one of the ways they trained one of the top computer chess playing algorithms. So this is just what this is. It's going to choose an action, it's going to try something, and the more it tries stuff, the more we're going to record the hash. We actually have a board hash where they self-get the hash set up on here where it stores all the information. And then once you get to a win, one of them wins, it gets the reward. Then we go back and reset and try again. And then kind of the fun part we actually get down here is we're going to play with a human. So we'll get a chance to come in here and see what that looks like when you put your own information in. And then it just comes in here and does the same thing it did above. It gives it a reward for its things, or sees if it wins or ties, looks at available positions, all that kind of fun stuff. And then finally we want to show the board. So it's going to print the board out each time. Really, as an integration, is not that exciting. What's exciting in here is, one, looking at this reward system. Whoops, play one more up. The reward system is really the heart of this. How do you reward the different setup? And the other one is when it's playing, it's got to take an action. And so what it chooses for an action is also the heart of reinforcement learning. How do we choose that action? And those are really key to right now where reinforcement learning is in today's technology, is figuring this out. How do we reward it, and how do we guess the next best action? So we have our environment, and you can see the environment is or the state, which is kind of like what's going on. We're going to return the state depending on what happens. And we want to go ahead and create our agent, in this case our player. So each one is, let me go and grab that. And so we look at a class player. This is where a lot of the magic is really going on, is how is this player figuring out how to maneuver around the board, and then the board of course returns a state that it can look at and a reward. So we want to take a look at this. We have name, self-state, this is class player, and when we say class player, we're not talking about a human player, we're talking about just the computer players. And this is kind of interesting. So remember I told you, depending on what you're doing, there's going to be a decay gamma, explore rate. These are what I'm talking about, is how do we train it. As you try different moves, it gets to the end, the first move is important, but it's not as important as the last one. And so you could say that the last one has the heaviest weight, and then as you get there, the first one, let's see, the first move gives you a 5 reward, the second gives you a 2 reward, and the third one gives you a 10 reward, because that's the final ending. You got it. The 10's going to count more than the first step. And here's our, we're going to get the board information coming in, and then choose an action. This was the second part that I was talking about that was so important. So once you have your training going on, we have to do a little randomness, and you can see right here is our NP random uniform. So it's picking out a random number. Take a random action. This is going to just pick which row and which column it is. And so choosing the action, this one you can see we're just doing random states, choice, length of positions, action position, and then it skips in there and takes a look at the board for P in positions. And it's actually storing the different boards each time you go through, so it has a record of what it did, so it can properly weigh the values. And this simply just appends a hash state. What's the last state? Append it to the to our states on here. Here's our feedback reward. So the reward comes in, and it's going to take a look at this and say, is it none? What is the reward? And here is that formula. Remember I was telling you about up here that was important because it has decay gamma times the reward. this is where, as it goes through each step, and this is really important. This is kind of the heart of this, of what I was talking about earlier. You have step 1, and this might have a reward of 2. You have step 2. Probably should have done ABC. This has a step 3, step 4, and so on until you get to step N. And this might have a reward of 10. So reward of 10, we're going to add that, but we're not adding, let's say this one right here. Let's say this reward here right before 10 was, let's say it's also 10. That just makes the math easy. So we had 10 and 10. We had 10, this is 10 and 10n, whatever it is, but it's 0.9. So instead of putting a full 10 here, we only do 9. That's 0.9 times 10. And so this formula, as far as the decay times the reward minus the cell state value, it basically adds in, it says here's 1, or here's 2, I'm sorry, I should have done this ABC, it would have been easier. So the first move goes in here and it puts 2 in here. Then we have ourselves set up on here. You can see how this gets pretty complicated in the math, but this is really the key, is how do we train our states? And we want the final state, the win, to get the most points. If you win, you get most points. And the first step gets the least amount of points. So you're really training this almost in reverse. You're training it from the last place where you have, like it says, okay, this is now where I need to sum up my rewards, and I want to sum them up going in reverse, and I want to find the answer in reverse. Kind of an interesting play on the mind when you're trying to figure this stuff out. And of course we want to go ahead and reset the board down here, and save the policy, load policy. These are the different things that are going in between the agent and the state to figure out what's going on. Let's go ahead and load that up. And then finally we want to go ahead and create a human player. And the human player is going to be a little different in that you choose an action, row and column. Here's your action. If action in positions, meaning positions that are available, you return the action. If not, it just keeps asking you until you get the action that actually works. And then we're going to go ahead and append to the hash state, which we don't need to worry about because it returns the action up here, and feed forward. Again, this is because it's a human. At the end of the game, backpropagate and update state values. This part isn't being done because it's not programming the model. The model is getting its own rewards. So we've gone ahead and loaded this in here. So here's all our pieces, and the first thing we want to do is set up P1 player 1, P2 player 2, and then we're going to send our players to our state. So now it has P1, P2, and it's going to play, and it's going to play 50,000 rounds. Now we can probably do a lot less than this, and it's not going to get the full results. In fact, you know what? Let's go ahead and just do 5, just to play with it, because I want to show you something here. Oops, somewhere in there I forgot to load something. There we go. I must have forgot to run this. Run. Oops, forgot a reference there for the board, rows and columns, 3 by 3. There's actually in the state, it references that. We can just tack it on the end. It was supposed to be at the beginning. So now I've only set this up with, let's see, where are we going here? I've only set this up to train 5 times. And the reason I did that is we're going to come in and actually play it, and then I'm going to change that, and we can see how it differs on there. There we go. And it didn't even make it through a run, and we're going to go ahead and save the policy. So now we have our player 1 and our player 2 policy. The way we set it up, it has 2 separate policies loaded up in there. And then we're going to come in here and we're going to do player 1 is going to be the computer, experience rate 0, load policy 1, human player human, and we're going to go ahead and play this. Now remember, I only went through it just one round of training, in fact minimal training, and so it puts an X there, and I'm going to go ahead and do row 0, column 1. You can see this is very basic on here, and so I put in my 0, and then I'm going to go 0, block it, 0, 0, and you can see right here it let me win. Just like that I was able to win. 0, 2, and woo, human wins. So I only trained it 5 times. We're going to run this again, and this time instead of 5, let's do 5,000 or 50,000. I think that's what the guys in the back had. And this takes a while to train it. This is where reinforcement learning really falls apart. Look how simple this game is. We're talking about a 3x3 set of columns. And so for me to train it on this, I could do a Q table which would go much quicker. You could build a quick Q table with almost all the different options on there, and you would probably get the same result much quicker. We're just using this as an example. So when we look at reinforcement learning, you need to be very careful what you apply it to. It sounds like a good deal until you do like a large neural network where you're doing, you set the neural network to a learning increment of 1, so every time it goes through it learns, and then you do your actions. You pick from the learning setup, and you actually try actions on the learning setup until you get what you think is going to be the best action. So you actually feed what you think is right back through the neural network. There's a whole layer there, which is really fun to play with. And then it has an output. Well, think of all those processes. I mean, that is just a huge amount of work it's going to do. Let's go ahead and skip ahead here. Give it a moment. It's going to take a minute or two to go ahead and run. Now, to train it, we went ahead and let it run, and it took a while. This took, I got a pretty powerful processor, and it took about 5 minutes plus to run it. And we'll go ahead and run our player setup on here. Oops, it brought in the last, whoops, it brought in the last round. So give me just a moment to redo the policy save. There we go. I forgot to save the policy back in there. And then go ahead and run our player again. So we've saved the policy, and then we want to go ahead and load the policy for P1 as a computer. And we can see the computer's gone in the bottom right corner. I'm going to go ahead and go 1, 1, which is the center. And it's gone right up the top, and if you have ever played tic-tac-toe, you know the computer has me. But we'll go ahead and play it out. Row 0, column 2. There it is, and then it's gone here, and so I'm going to go ahead and go row 0, 1, 2, no, 0, 1, there we go, and column 0. That's where I wanted. Oh, and it says, okay, your action, there we go, boom. So you can see here, we've got didn't catch the win on this, it said tie. Kind of funny that it didn't catch the win on there. But if we play this a bunch of times, you'll find that it's going to win more and more. The more we train it, the more the reinforcement happens. This lengthy training process is really the stopper on reinforcement learning. As this changes, reinforcement learning will be one of the more powerful packages evolving over the next decade or two. In fact, I would even go as far as to say it is the most important machine learning tool and artificial intelligence tool out there, as it learns not only a simple tic-tac-toe board, but we start learning environments. And the environment would be like in language. If you're translating a language or something from one language to the other, so much of it is lost if you don't know the context it's in, what's the environments it's in. And so being able to attach environment and context and all those things together is going to require reinforcement learning to do. So again, if you want to get a copy of the tic-tac-toe board, it's kind of fun to play with. Run it, you can test it out, you can do test it for different values. You can switch from P1 computer where we loaded the policy 1 to load the policy 2 and just see how it varies. There's all kinds of things you can do on there. So what is Q learning? Q-learning is reinforcement learning policy which will fill the next best action given a current state. It chooses this action at random and aims to maximize the reward. And so you can see here's our standard reinforcement learning graph. By now, if you're doing any reinforcement learning, you should be familiar with this, where you have your agent takes an action, the action affects the environment, and then the environment sends back the reward or the feedback, and the state, it's the new state the agent's in. Where is it at on the chessboard? Where is it at in the video game? If your robot's out there picking trash up off the side of the road, where is it at on the road? Consider an ad recommendation system. Usually when you look up a product online, you get ads which will suggest the same product over and over again. Using Q-learning, we can make an ad recommendation system which will suggest related products to our previous purchase. The reward will be if user clicks on the suggested product. And again, you can see you might have a lot of products on your web advertisement or your pages, but it's still not a float number. It's still a set number, and that's something to be aware of when you're using Q-learning. And you can see here that if you have 100 people clicking on ads and you click on one of the ads, it might go in there and say, okay, this person clicked on this ad. What is the best set of ads based on clicking on this ad or these two ads afterwards based on where they are browsing? So let's go ahead and take a look at some important terms when we talk about Q-learning. We have states. The state S represents the current position of an agent in an environment. The action A is the step taken by the agent when it is a particular state. Rewards. For every action, the agent will get a positive or negative reward. And again, when we talk about states, we're usually not, when you're using a Q table, you're not usually talking about float variables. You're talking about true, false. And we'll take a closer look at that in a second. And episodes, when an agent ends up in a terminating state and can't take a new action. This might be if you're playing a video game, your character stepped in and is now dead or whatever. Q values used to determine how good an action A taken at a particular state S is Q A of S. And temporal difference, a formula used to find the Q value by using the value of the current state and action and previous state and action. And there's Bellman's equation, which basically is the equation that kind of covers what we just looked at in all those different terms. The Bellman equation is used to determine the values of a particular state and deduce how good it is to be in take that state. The optimal state will give us the highest optimal value. Factor influencing Q values, the current state and action, that's your SA, so your current state and your action. Then you have your previous state and action, which is your S, I guess prime, I'm not sure how they reference that, S prime, A prime. So this is what happened before. Then you have a reward for action, so you have your R reward, and you have your maximum expected future reward. And you can see there's also a learning rate put in there and a discount rate. So when we're looking at these, just like any other model, we don't want to have an absolute final value on here. We don't want it to, if you do absolute values instead of taking smaller steps, you don't really have that approach to the solution. You just have a jump, and then pretty soon if you jump one solution out, that's what's going to be the new solution, whichever one jumps up really high first, kind of ruining the whole idea of doing a random selection. I'll go into the random selection in just a second. Steps in Q learning. Step 1, create an initial Q table with all values initialized to 0. Again, we're looking at 0, 1. So here's our action. We start, we're in idle, we took a wrong action, we took a correct action, and end. And then we have our actions, fetching, sitting, and running. And of course, we're just using the dog example. And choose an action and perform it. Update values in the table. And of course, when we're choosing an action, we're going to kind of do something random and just randomly pick one. So you start out and you sit, and you have then depending on that action you took, you can now update the value for sitting after you start, from start to sitting. get the value of the reward, and calculate the value Q value using the Bellman equation. And so now we attach a reward to sitting. And when we attach all those rewards, we continue the same until the table is filled with or an episode ends. And I mentioned I was going to come back to the random side of this. And there's a few different formulas I use for the random setup to pick it. I usually let whatever Q model I'm using do their standard one, because someone's usually gone in and done the math for the optimal spread. But you can look at this. If I have running has a reward of 10, sitting has a reward of 7, fetching has a reward of 5, just kind of without doing like a means, using the bell curve for the means value, and like I said, there's some math you can put in there to pick so that you're more likely, so that running has even a higher chance. But even if you were just going to do an average on this, you could do an average, a random number, by adding them all together. So you get 10 plus 7 plus 5 is 22. You could do 0 to 22, or 0 to 21, but 1 to 22. 1 to 5 would be fetching, and so forth, the last 10. So you can just look at this as what percentage are you going to go for that particular option. And then that gets your random setup in there. And then as you slowly increment these up, you see that if you're idle, where's one? Here we go. Sitting at the end. If you're at the end of wherever you're at, sitting gets a reward of 1. Where's a good one on here? Oh, wrong action. Running for a wrong action gets almost no reward. So that becomes very, very less likely to happen, but it still might happen. It still might have a percentage of coming up. And that's where the random programming and Q-learning comes in. The below table gives us an idea of how many times an action has been taken and how positively correct action or negatively wrong action it is going to affect the next state. So let's go ahead and dive in and pull up a little piece of code and see what this looks like in Python. In this demo, we'll use Q-learning to find the shortest path between two given points.
If getting your learning started is half the battle, what if you could do that for free? Visit Skill Up by Simplilearn. Click on the link in the description to know more.
If you've seen my videos before, I like to do it in the Anaconda Jupyter Notebook setup, just because it's really easy to see and it's a nice demo. And so here's my Anaconda. This one I'm actually using a Python 3.6 environment that I set up in here. And we'll go ahead and launch the Jupyter Notebook on this. And once we're in our Jupyter Notebook, which has the kernel loaded with Python 3, we'll go ahead and create a new Python 3 folder in here. And we'll call this Q Learning. And to start this demo, let's go ahead and import our NumPy array. We'll just run that so it's imported. And like a lot of these model programs, when you're building them, you spend a lot of time putting it all together, and then you end up with this really short answer at the end. And we'll take a look at that as we come into it. So we go ahead and start with our location to state. So we have L1, L2. These are our 9 locations, 1 to 9. And then of course the state is going to be 0, 1, 2, 3, 4. It's just a mapping of our location to a integer on there. And then we have our actions. Our actions are simply moving from one location to another. So I can go to location 0, I can go to location 1, 2, 3, 4, 5, 6, 7, 8. So these are my actions I can choose. These are the locations of our state. And if you remember earlier, I mentioned that the limitation is that you don't want to put in a continually growing table, because you can actually create a dynamic queue table where you continually add in new values as they arise. Because if you have float values, it just becomes infinite, and then your memory in your computer is gone, or it's not going to work. At the same time, you might think, well, that kind of really limits the Q learning setup. But there are ways to use it in conjunction with other systems. And so you might look at, well, I've been doing some work in stock. And one of the questions that comes out is to buy or sell the stock. And the state coming in might be, you might take it and create what we call buckets, where anything that you predict is going to return more than a certain amount of money, the error for that stock that you've had in the past, you put those in buckets, and suddenly as you start creating these buckets, you realize you do have a limited amount of information coming in. You no longer have a float number. You now have bucket 1, 2, 3, and 4. And then you can take those buckets, put them through a Q learning table, and come up with the best action. Which stock should I buy? It's like gambling. Stock is pretty much gambling if you're doing day trading. You're not doing long-term investments. And so you can start looking at it like that. A lot of the current feeds say that the best algorithms used for day traders, where you're doing it on your own, is really to ask the question, do I want to trade the stock? Yes or no? And now you have it in a Q learning table, and now you can take it to that next level, and you can see where that can be a really powerful tool at the end of doing a basic linear regression model or something. What is the best investment? And you start getting the best reward on there. And so if we're going to have rewards, these rewards we just create. It says if you're this should match our Q table, because it's going to be you have your state and you have your action across the top, if you remember from the dog. And so we have whatever state we're in going down, and then the next action and what the reward is for it. And of course, if you were actually doing something more connected, your reward would be based on the actual environment it's in. And then we want to go ahead and create a state to location so we can map the indexes. So just like we defined our rewards, we're going to go ahead and do state to location. And you can see here it's a dictionary setup for location state and location to state with items. And we also need to define what we want for learning rates. You remember we had our two different rates as far as like learning from the past and learning from the current. So we'll go ahead and set those to 0.75 and the alpha set to 0.9. And we'll see that when we do the formula. And of course, any of this code, send a note to our Simplilearn team. They'll get you a copy of this code on here. And let's go ahead and pull. There we go. All the next two sections. Since we're going to keep it short and sweet. Here we go. So let's go ahead and create our agent. So our agent is going to have our initialization where we send it all the information. We'll define our self gamma equals gamma. We could have just set the gamma rate down here instead of submitting it. It's kind of nice to keep them separate because you can play with these numbers. And our self alpha. Then we have our location state. We'll set that in here. We have our choice of actions. We're going to go ahead and just embed the rewards right into the agent. So obviously this would be coming from somewhere else instead of from self-generated. And then a self state to location equals our state to location dictionary. And we go ahead and create a Q learning table. And I went ahead and just set the Q learning table up to 0 to 0. What the setup is, location to state. How many of them are there? And this just creates an array of 0 to 0 setup on there. And then the big part is the training. We have our rewards new equals a copy of self.rewards. Ending state equals the self location state in location. So this is whatever we end up at. Rewards new equals ending state plus ending state equals 999. Just kind of goes to a dead end. And we start going through iterations. And we'll go ahead, let's do this. So this, we're going to come back and we're going to call it on here. Let me just erase that. Switch it to an arrow. There we go. So what we're doing is we're going to send in here to train it. We're going to say, hey, I want to iterate through this 1,000 times and see what happens. Now this part would actually be, instead of iterating, you might have your external environment and they're going back and forth and you iterate through outside of here. But just for ease of use, our agent's going to come in here and iterate through this. Sometimes I'll put this iteration in here and I'll have it call the environment and say, hey, this is what I did, what's the next state? And the environment does its thing right in here as I iterate through it. And then we want to go ahead and pick a random state to start with. That's what's going on here. You have to start somewhere. And then you have your playable actions. We're going to start with just an empty thing for playable actions, and we'll fill that up. So that's what choices I have. And so we're going to iterate through the rewards matrix to get the states, directly reachable from the randomly chosen current state. Assign those states to a list named playable actions. And so you can see here we have range 9. I usually use length of whatever I'm looking at, which is our locations or states as they are. We have a reward, so we want to look at the rewards. The new reward is in our chart here of rewards underscore new current state plus J. J being what is the next state we want to try. And so we go ahead and do our playable actions and we append J. And so what we're doing is we're randomly trying different things in here to see what's going to generate a better reward. And then of course we go ahead and choose our next state. So we have our random choice playable actions. And if you remember, I mentioned on this, let me just go ahead and, let's do a free form. When we were talking about the next state, this right here just does a random selection. Instead of a random selection, you might do something where whatever the best selection is, which might be option 3 here, and then so you can see that it might use a bell curve, and then option 2 over here might have a bell curve like this. Oops. And we start looking at these averages and these spreads, or we can just add them all together and pick the one that kind of goes in all of those. So those are some of the options we have in here. We just go with a random choice. That's usually where you start, play with it. And then we have our reward section down here. And so we want to go ahead and find, well, in this case, the temporal difference. So you have your rewards new plus the self gamma, and this is the formula we were looking at. This is Bellman's equation here. So we have our current value, our learning rate, our discount rate involved in there, the reward system coming in for that, and we can add it all together. This is, of course, our maximum expected future setup in here. So this is all of our Bellman's equation that we're looking at here. And then we come up in here and we update our Q table. That's all this is on this one. And that's right here. We have self Q, current state, next state, and we add in our alpha because we don't want to train all of it at once in case there's slight differentials coming in there. We want to slowly approach the answer. And then we have our route equals the start location, and next location equals start location. So we're just incrementing. We took a step forward. And then finally, remember I was telling you how we're going to do all this and just have some simple thing at the end where it just generates a simple path. We're going to go ahead and get the optimal route. We want to find the best route in here. And so we've created a definition for the optimal route down here. Just scroll down for that. And we get the optimal route. We go ahead and put the information in, including the Q table, self, start location, end location, next location, route, Q. And it says while next location is not equal to end location, so while we can still go, our start location equals self location to state start location. So we already have our best value for the start location. The next state looks at the Q table and says, hey, what's the next one with the best value? And then the next location, we go ahead and pull that in and we just append it. That's what's going on down here. And then our start location equals the next location. And we just go through all the steps. And we'll go ahead and run this. And now that we have our Q table, our Q agent loaded, we're going to go ahead and take our Q agent, load them up with our alpha, gamma that we set up above, along with the location step, action, reward, state to location. And our goal is to plot a course between L9 and L1. And we're going to go through 1,000 iterations on here. And so when I run that, it runs pretty quick. Why is this so fast? If you've been running neural networks and you've been doing all these other models, you sit here and wait a long time. Well, we're a very small amount of data. These are all integers. These aren't float values. The math is not heavy on the processing end, and this is where Q tables are so powerful. If you have a small amount of information coming in, you very quickly get an answer off of this, even though we went through it 1,000 times to train it. And you'll see here we have L9, 8, 5, 2, and 1, and that's based on our reward table we had set up on there. And this is the shortest path going between these different setups in here. And if you remember on our reward table, you can see that if you start here, you can go to here. There's places you can't go. That's how this reward table was set up. So I can only go to certain places. So kind of a little maze set up in there. And you can play with it. This is really fun setup to play with. And you can see how you can take this whole code and you can, like I was saying earlier, you can embed it into another setup and model and predictions where you put things into buckets and you're trying to guess the best investment, the best course of action. As long as you can take that course of action and reduce it down to a yes, no. Or if you're using text, you can use a one-hot encoder, which word is next. There's all kinds of things you can do with a Q table, depending on just how much information you're putting in there. So that wraps up our demo. In this demo, we've found the shortest distance between two paths based on whatever rules or state rewards we have to get from point A to point B and what available actions there are.
Hello and welcome to this tutorial on deep learning. My name is Mohan, and in the next about 1.5 hours I will take you through what is deep learning and into TensorFlow environment to show you an example of deep learning. Now, there are several applications of deep learning, really very interesting and innovative applications, and one of them is identifying the geographic location based on a picture. And how does this work? The way it works is pretty much we train an artificial neural network with millions of images which are tagged, their geolocation is tagged, and then when we feed a new picture, it will be able to identify the geolocation of this new image. For example, you have all these images, especially with maybe some significant monuments or significant locations, and you train with millions of such images, and then when you feed another image, it need not be exactly one of those that you have trained. It can be completely different. That is the whole idea of training. It will be able to recognize, for example, that this is a picture from Paris because it is able to recognize the Eiffel Tower. So the way it works internally, if we have to look a little bit under the hood, is these images are nothing but this is digital information in the form of pixels. So each image could be a certain size. It can be 256 by 256 pixel kind of a resolution, and then each pixel is either having a certain grade of color, and all that is fed into the neural network, and it then gets trained in, and it's able to, based on these pixel information, it is able to get trained and able to recognize the features and extract the features, and thereby it is able to identify these images and the location of these images. And then when you feed a new image, it kind of, based on the training, it will be able to figure out where this image is from. So that's the way, a little bit under the hood, how it works. So what are we going to do in this tutorial? We will see what is deep learning and what do we need for deep learning. And one of the main components of deep learning is neural networks. So we will see what is neural network, what is a perceptron, and how to implement logic gates like AND, OR, NOR, and so on using perceptrons. The different types of neural networks and then applications of deep learning, and we will also see how neural networks works. So how do we do the training of neural networks? And at the end we will end up with a small demo code which will take you through in TensorFlow. Now, in order to implement deep learning code, there are multiple libraries or development environments that are available, and TensorFlow is one of them. So the focus at the end of this would be on how to use TensorFlow to write a piece of code using Python as a programming language. And we will take up an example which is a very common one, which is like the hello world of deep learning. The handwriting number recognition, which is commonly known as MNIST database. So we will take a look at MNIST database and how we can train a neural network to recognize handwritten numbers. So that's what you will see in this particular video. So let's get started. What is deep learning? Deep learning is like a subset of what is known as a high-level concept called artificial intelligence. You must be already familiar, must have heard about this term artificial intelligence. So artificial intelligence is like the high-level concept, if you will. And in order to implement artificial intelligence applications, we use what is known as machine learning. And within machine learning, a subset of machine learning is deep learning. Machine learning is a little bit more generic concept, and deep learning is one type of machine learning, if you will. And we will see a little later in maybe the following slides a little bit more in detail how deep learning is different from traditional machine learning. But to start with, we can mention here that deep learning uses one of the differentiators between deep learning and traditional machine learning is that deep learning uses neural networks. And we will talk about what are neural networks and how we can implement neural networks and so on and so forth as a part of this tutorial. So a little deeper into deep learning. Deep learning primarily involves working with complicated unstructured data compared to traditional machine learning where we normally use structured data. In deep learning, the data would be primarily images or voice or maybe text file. And it is large amount of data as well. And deep learning can handle complex operations. It involves complex operations. And the other difference between traditional machine learning and deep learning is that the feature extraction happens pretty much automatically. In traditional machine learning, feature engineering is done manually. The data scientists, we data scientists have to do feature engineering, feature extraction. But in deep learning, that happens automatically. And of course, deep learning, for large amounts of data, complicated unstructured data, deep learning gives very good performance. Now, as I mentioned, one of the secret sources of deep learning is neural networks. Let's see what neural networks is. Neural networks is based on our biological neurons. The whole concept of deep learning and artificial intelligence is based on human brain, and human brain consists of billions of tiny stuff called neurons, and this is how a biological neuron looks, and this is how an artificial neuron looks. So neural networks is like a simulation of our human brain. Human brain has billions of biological neurons, and we are trying to simulate the human brain using artificial neurons. This is how a biological neuron looks. It has dendrites, and the corresponding component with an artificial neural network is, or an artificial neuron, are the inputs. They receive the inputs through dendrites. And then there is the cell nucleus, which is basically the processing unit in a way. So in artificial neuron also there is a piece which is an equivalent of this cell nucleus, and based on the weights and biases, we will see what exactly weights and biases are as we move. The input gets processed, and that results in an output. In a biological neuron, the output is sent through a synapse, and in an artificial neuron there is an equivalent of that in the form of an output. And biological neurons are also interconnected. So there are billions of neurons which are interconnected. In the same way, artificial neurons are also interconnected. So this output of this neuron will be fed as an input to another neuron and so on. Now, in neural network, one of the very basic units is a perceptron. So what is a perceptron? A perceptron can be considered as one of the fundamental units of neural networks. It can consist at least one neuron, but sometimes it can be more than one neuron. But you can create a perceptron with a single neuron, and it can be used to perform certain functions. It can be used as a basic binary classifier. It can be trained to do some basic binary classification, and this is how a basic perceptron looks like. And this is nothing but a neuron. You have inputs x1, x2, to xn, and there is a summation function, and then there is what is known as an activation function. And based on this input, what is known as the weighted sum, the activation function either gives an output like a 0 or a 1. So we say the neuron is either activated or not. So that's the way it works. So you get the inputs. These inputs are, each of the inputs are multiplied by a weight, and there is a bias that gets added, and that whole thing is fed to an activation function, and then that results in an output. And if the output is correct, it is accepted. If it is wrong, if there is an error, then that error is fed back, and the neuron then adjusts the weights and biases to give a new output, and so on and so forth. So that's what is known as the training process of a neuron or a neural network. There's a concept called perceptron learning. So perceptron learning is again one of the very basic learning processes. The way it works is somewhat like this. So you have all these inputs like x1 to xn, and each of these inputs is multiplied by a weight, and then that sum, this is the formula, the equation. So that sum, wi xi sigma of that, which is the sum of all these product of x and w, is added up, and then a bias is added to that. The bias is not dependent on the input or the input values, but the bias is common for one neuron. However, the bias value keeps changing during the training process. Once the training is completed, the values of these weights, W1, W2, and so on, and the value of the bias gets fixed. So that is basically the whole training process, and that is what is known as the perceptron training. So the weights and biases keep changing till you get the accurate output, and the summation is of course passed through the activation function. As you see here, this wixi summation plus b is passed through activation function, and then the neuron gets either fired or not, and based on that there will be an output. That output is compared with the actual or expected value, which is also known as labeled information. So this is the process of supervised learning. So the output is already known, and that is compared, and thereby we know if there is an error or not. And if there is an error, the error is fed back, and the weights and biases are updated accordingly till the error is reduced to the minimum. So this iterative process is known as perceptron learning or perceptron learning rule, and this error needs to be minimized. So till the error is minimized, this iteratively the weights and biases keep changing, and that is what is the training process. So the whole idea is to update the weights and the bias of the perceptron till the error is minimized. The error need not be 0. The error may not ever reach 0, but the idea is to keep changing these weights and bias so that the error is minimum, the minimum possible that it can have. So this whole process is an iterative process, and the iteration continues till either the error is 0, which is unlikely situation, or it is the minimum possible within these given conditions. Now in 1943, two scientists, Warren McCulloch and Walter Pitts, came up with an experiment where they were able to implement the logical functions like AND, OR, and NOR using neurons. And that was a significant breakthrough in a sense. So they were able to come up with the most common logical gates. They were able to implement some of the most common logical gates, which could take two inputs like A and B and then give a corresponding result. So for example, in case of an AND gate, A and B, and then the output is AB. In case of an OR gate, it is A plus B, and so on and so forth. And they were able to do this using a single layer perceptron. Now, most of these gates, it was possible to use single layer perceptron except for XOR, and we will see why that is in a little bit. So this is how an AND gate works. The inputs A and B, the output should be fired, or the neuron should be fired only when both the inputs are 1. So if you have 0, 0, the output should be 0. For 0, 1, it is again 0, 1, 0 again 0, and 1, 1, the output should be 1. So how do we implement this with a neuron? So it was found that by changing the values of weights, it is possible to achieve this logic. So for example, if we have equal weights like 0.7, 0.7, and then if we take the sum of the weighted product, so for example 0.7 into 0, and then 0.7 into 0 will give you 0, and so on and so forth. And in the last case, when both the inputs are 1, you get a value which is greater than 1, which is the threshold. So only in this case the neuron gets activated and the output is, there is an output. In all the other cases, there is no output because the threshold value is 1. So this is implementation of an AND gate using a single perceptron or a single neuron. Similarly, an OR gate. In order to implement an OR gate, in case of an OR gate, the output will be 1 if either of these inputs is 1. So for example, 0, 1 will result in 1, or rather, in all the cases it is 1 except for 0, 0. So how do we implement this using a perceptron? Once again, if you have a perceptron with weights, for example 1.2, now if you see here, if in the first case when both are 0, the output is 0. In the second case, when it is 0 and 1, 1.2 into 0 is 0, and then 1.2 into 1 is 1. And in the second case, similarly, the output is 1.2. In the last case, when both the inputs are 1, the output is 2.4. So during the training process, these weights will keep changing, and then at one point where the weights are equal to W1 is equal to 1.2 and W2 is equal to 1.2, the system learns that it gives the correct output. So that is implementation of OR gate using a single neuron or a single layer perceptron. Now XOR gate. This was one of the challenging ones. They tried to implement an XOR gate with a single level perceptron, but it was not possible. And therefore, in order to implement an XOR, so this was like a roadblock in the progress of neural network. However, subsequently they realized that this can be implemented, an XOR gate can be implemented using a multi-level perceptron or MLP. So in this case, there are 2 layers instead of a single layer, and this is how you can implement an XOR gate. So you will see that X1 and X2 are the inputs, and there is a hidden layer, and that's why it is denoted as H3 and H4, and then you take the output of that and feed it to the output at O5 and provide a threshold here. So we will see here that this is the numerical calculation. So the weights are, in this case for X1 it is 20 and minus 20, and once again 20 and minus 20. So these inputs are fed into H3 and H4. So you will see here for H3 the input is 0, 1, 1, 1, and for H4 it is 1, 0, 1, 1. And if you now look at the output, final output, where the threshold is taken as 1, if we use a sigmoid with the threshold 1, you will see that in these 2 cases it is 0, and in the last 2 cases it is 1. So this is the implementation of XOR. In case of XOR, only when one of the inputs is 1, you will get an output. So that is what we are seeing here. If we have either both the inputs are 1 or both the inputs are 0, then the output should be 0. So that is what is an exclusive OR gate. So it is exclusive because only one of the inputs should be 1, and then only you will get an output of 1, which is satisfied by this condition. So this is a special implementation. XOR gate is a special implementation of perceptron. Now that we got a good idea about perceptron, let's take a look at what is a neural network. So we have seen what is a perceptron, we have seen what is a neuron, so we will see what exactly is a neural network. So neural network is nothing but a network of these neurons, and they are different types of neural networks. There are about 5 of them. These are artificial neural network, convolutional neural network, then recursive neural network or recurrent neural network, deep neural network, and deep belief network. So, and each of these types of neural networks have a special, they can solve a special kind of problems. For example, convolutional neural networks are very good at performing image processing and image recognition and so on, whereas RNN are very good for speech recognition and also text analysis and so on. So each type has some special characteristics, and they're good at performing certain special kind of tasks. What are some of the applications of deep learning? Deep learning is today used extensively in gaming. You must have heard about AlphaGo, which is a game created by a startup called DeepMind, which got acquired by Google. And AlphaGo is an AI which defeated the human world champion Lee Sedol in this game of Go. So gaming is an area where deep learning is being extensively used, and a lot of research happens in the area of gaming as well. In addition to that, nowadays there are neural networks or special type called generative adversarial networks, which can be used for synthesizing either images or music or text and so on, and they can be used to compose music. So the neural network can be trained to compose a certain kind of music. And autonomous cars, you must be familiar with Google's self-driving car, and today a lot of automotive companies are investing in this space, and deep learning is a core component of this autonomous cars. The cars are trained to recognize, for example, the road, the lane markings on the road, signals, any objects that are in front, any obstruction, and so on and so forth. So all this involves deep learning. So that's another major application. And robots, we have seen several robots, including Sophia. You may be familiar with Sophia, who was given a citizenship by Saudi Arabia. And there are several such robots which are very human-like, and the underlying technology in many of these robots is deep learning. Medical diagnostics and healthcare is another major area where deep learning is being used. And within healthcare diagnostics, again, there are multiple areas where deep learning and image recognition, image processing can be used. For example, for cancer detection, as you may be aware, if cancer is detected early on, it can be cured. And one of the challenges is in the availability of specialists who can diagnose cancer using these diagnostic images and various scans and so on and so forth. So the idea is to train neural network to perform some of these activities so that the load on the cancer specialist doctors or oncologists comes down. And there is a lot of research happening here, and there are already quite a few applications that are claimed to be performing better than human beings in this space. It can be lung cancer, it can be breast cancer, and so on and so forth. So healthcare is a major area where deep learning is being applied. Let's take a look at the inner working of a neural network. So how does an artificial neural network, let's say, can we train a neural network to identify the shapes like squares and circles and triangles when these images are fed? So this is how it works. Any image is nothing but it is a digital information of the pixels. So in this particular case, let's say this is an image of 28 by 28 pixel, and this is an image of a square. There is a certain way in which the pixels are lit up, and so these pixels have a certain value, maybe from 0 to 256, and 0 indicates that it is black or it is dark, and 256 indicates it is white or lit up. So that is like an indication or a measure of how the pixels are lit up. And so this is an image is, let's say, consisting of information of 784 pixels. So all the information, what is inside this image, can be kind of compressed into these 784 pixels. The way each of these pixels is lit up provides information about what exactly is the image. So we can train neural networks to use that information and identify the images. So let's take a look how this works. So each neuron, the value, if it is close to 1, that means it is white, whereas if it is close to 0, that means it is black. Now this is an animation of how this whole thing works. So these pixels one of the ways of doing it is we can flatten this image and take this complete 784 pixels and feed that as input to our neural network. The neural network can consist of probably several layers. There can be a few hidden layers, and then there is an input layer and an output layer. Now the input layer takes these 784 pixels as input, the values of each of these pixels, and then you get an output which can be of three types or three classes. One can be a square, a circle, or a triangle. Now during the training process, there will be initially, obviously you feed this image and it will probably say it's a circle or it will say it's a triangle. So as a part of the training process, we then send that error back, and the weights and the biases of these neurons are adjusted till it correctly identifies that this is a square. That is the whole training mechanism that happens out here. Now let's take a look at a circle. Same way. So you feed these 784 pixels. There is a certain pattern in which the pixels are lit up, and the neural network is trained to identify that pattern. And during the training process, once again, it would probably initially identify it incorrectly, saying this is a square or a triangle, and then that error is fed back and the weights and biases are adjusted finally till it finally gets the image correct. So that is the training process. So now we will take a look at same way a triangle. So now if you feed another image which is consisting of triangles. So this is the training process. Now we have trained our neural network to classify these images into a triangle or a circle and a square. So now this neural network can identify these three types of objects. Now if you feed another image, and it will be able to identify whether it's a square or a triangle or a circle. Now what is important to be observed is that when you feed a new image, it is not necessary that the image or the triangle is exactly in this position. Now the neural network actually identifies the patterns. So even if the triangle is, let's say, positioned here, not exactly in the middle but maybe at the corner or in the side, it would still identify that it is a triangle. And that is the whole idea behind pattern recognition. So how does this training process work? This is a quick view of how the training process works. So we have seen that a neuron consists of inputs. It receives inputs, and then there is a weighted sum, which is nothing but this xi, wi summation of that plus the bias. And this is then fed to the activation function, and that in turn gives us a output. Now during the training process, initially obviously when you feed these images, when you send maybe a square, it will identify it as a triangle, and when you maybe feed a triangle, it will identify as a square, and so on. So that error information is fed back, and initially these weights can be random. Maybe all of them have 0 values, and then it will slowly keep changing. So as a part of the training process, the values of these weights, W1, W2 up to Wn, keep changing in such a way that towards the end of the training process, it should be able to identify these images correctly. So till then, the weights are adjusted, and that is known as the training process. So, and these weights are numeric values. It could be 0.5, 0.25, 0.35, and so on. It could be positive or it could be negative, and the value that is coming here is the pixel value. As we have seen, it can be anything between 0 to 1. You can scale it between 0 to 1 or 0 to 256, whichever way. 0 being black and 256 being white, and then all the other colors in between. So that is the input. So these are numerical values. This multiplication or the product Wixi is a numerical value, and the bias is also a numerical value. We need to keep in mind that the bias is fixed for a neuron. It doesn't change with the inputs, whereas the weights are 1 per input. So that is one important point to be noted. So, but the bias also keeps changing. Initially it will again have a random value, but as a part of the training process, the weights, the values of the weights W1, W2, Wn and the value of B will change, and ultimately once the training process is complete, these values are fixed for this particular neuron, W1, W2 up to Wn, and plus the value of the b is also fixed for this particular neuron. And in this way, there will be multiple neurons, and there may be multiple levels of neurons here, and that's the way the training process works. So this is another example of multi-layer. So there are two hidden layers in between, and then you have the input layer, values coming from the input layer, then it goes through multiple layers, hidden layers, and then there is an output layer. And as you can see, there are weights and biases for each of these neurons in each layer, and all of them keeps changing during the training process. And at the end of the training process, all these weights have a certain value, and that is a trained model, and those values will be fixed once the training is completed. Alright, then there is something known as activation function. Neural networks consists of one of the components in neural networks is activation function, and every neuron has an activation function, and there are different types of activation functions that are used. It could be a ReLU, it could be sigmoid, and so on and so forth. And the activation function is what decides whether a neuron should be fired or not. So whether the output should be 0 or 1 is decided by the activation function. And the activation function in turn takes the input, which is the weighted sum. Remember, we talked about WIXI plus B. That weighted sum is fed as an input to the activation function, and then the output can be either a 0 or a 1. And there are different types of activation functions which are covered in an earlier video you might want to watch. Alright, so as a part of the training process, we feed the inputs, the labeled data or the training data, and then it gives an output, which is the predicted output by the network, which we indicate as y hat. And then there is a labeled data, because for supervised learning, we already know what should be the output. So that is the actual output. And in the initial process, before the training is complete, obviously there will be error. So that is measured by what is known as a cost function. So the difference between the predicted output and the actual output is the error. And the cost function can be defined in different ways. There are different types of cost functions. So in this case, it is like the average of the squares of the error. So, and then all the errors are added, which can sometimes be called as sum of squares, sum of square errors, or SSE. And that is then fed as a feedback in what is known as backward propagation or backpropagation. And that helps in the network adjusting the weights and biases. And so the weights and biases get updated till this value, the error value or the cost function, is minimum. Now there is a optimization technique which is used here called gradient descent optimization, and this algorithm works in a way that the error, which is the cost function, needs to be minimized. So there's a lot of mathematics that goes behind this. For example, they find the local minima and the global minima using the differentiation and so on and so forth. But the idea is this. So as a training process, as the part of training, the whole idea is to bring down the error, which is like, let's say this is the function, the cost function. At certain levels it is very high, the cost value of the cost function, the output of the cost function is very high. So the weights have to be adjusted in such a way, and also the bias of course, that the cost function is minimized. So there is this optimization technique called gradient descent that is used, and this is known as the learning rate. Now gradient descent, you need to specify what should be the learning rate, and the learning rate should be optimal, because if you have a very high learning rate, then the optimization will not converge, because at some point it will cross over to the side. On the other hand, if you have very low learning rate, then it might take forever to convert. So you need to come up with the optimum value of the learning rate, and once that is done, using the gradient descent optimization, the error function is reduced, and that's like the end of the training process. Alright, so this is another view of gradient descent. So this is how it looks. This is your cost function, the output of the cost function, and that has to be minimized using gradient descent algorithm. And these are like the parameters, and weight could be one of them. So initially we start with certain random values, so cost will be high, and then the weights keep changing, and in such a way that the cost function needs to come down, and at some point it may reach the minimum value and then it may increase. So that is where the gradient descent algorithm decides that, okay, it has reached a minimum value and it will kind of try to stay here. This is known as the global minima. Now sometimes these curves may not be, just for explanation purpose, this has been drawn in a nice way, but sometimes these curves can be pretty erratic. There can be some local minima here, and then there is a peak, and so on. So the whole idea of gradient descent optimization is to identify the global minima and to find the weights and the bias at that particular point. So that's what is gradient descent. And then this is another example. So you can have these multiple local minima. So as you can see, at this point when it is coming down, it may appear like this is a minimum value, but then it is not. This is actually the global minimum value, and the gradient descent algorithm will make an effort to reach this level and not get stuck at this point. So the algorithm is already there and it knows how to identify this global minimum, and that's what it does during the training process. Now, in order to implement deep learning, there are multiple platforms and languages that are available, but the most common platform nowadays is TensorFlow, and so that's the reason we have this tutorial. We have created this tutorial for TensorFlow. So we will take you through a quick demo of how to write a TensorFlow code using Python. And TensorFlow is an open source platform created by Google. So let's just take a look at the details of TensorFlow. And so this is a library, a Python library. So you can use Python or any other languages. It's also supported in other languages like Java and R and so on. But Python is the most common language that is used. So it is a library for developing deep learning applications, especially using neural networks. And it consists of primarily two parts, if you will. So one is the tensors, and then the other is the graphs or the flow. That's the way the name, that's the reason for this kind of a name called TensorFlow. So what are tensors? Tensors are like multi-dimensional arrays, if you will. That's one way of looking at it. So usually you have a one-dimensional array. So first of all, you can have what is known as a scalar, which means a number. And then you have a one-dimensional array, something like this, which means this is like a set of numbers. So that is a one-dimensional array. Then you can have a two-dimensional array, which is like a matrix. And beyond that, sometimes it gets difficult. So this is a three-dimensional array, but TensorFlow can handle many more dimensions. So it can have multi-dimensional arrays. That is the strength of TensorFlow, and which makes computation, deep learning computation, much faster. And that's the reason why TensorFlow is used for developing deep learning applications. So TensorFlow is a deep learning tool, and this is the way it works. So the data basically flows in the form of tensors, and the way the programming works as well is that you first create a graph of how to execute it, and then you actually execute that particular graph in the form of what is known as a session. We will see this in the TensorFlow code as we move forward. So all the data is managed or manipulated in tensors, and then the processing happens using these graphs. There are certain terms called, like for example, ranks of a tensor. The rank of a tensor is like a dimensionality in a way. So for example, if it is scalar, so there is just a number, just one number, the rank is supposed to be 0. And then it can be a one-dimensional vector, in which case the rank is supposed to be 1. And then you can have a two-dimensional vector, typically like a matrix. Then in that case, we say the rank is 2. And then if it is a three-dimensional array, then rank is 3, and so on. So it can have more than 3 as well. So it is possible that you can store multi-dimensional arrays in the form of tensors. So what are some of the properties of TensorFlow? I think today it is one of the most popular platform. TensorFlow is the most popular deep learning platform or library. It is open source. It's developed by Google, developed and maintained by Google, but it is open source. One of the most important things about TensorFlow is that it can run on CPUs as well as GPUs. GPU is a graphical processing unit, just like CPU is central processing unit. Now, in earlier days, GPU was used primarily for graphics, and that's how the name has come. And one of the reasons is that it cannot perform generic activities very efficiently like CPU, but it can perform iterative actions or computations extremely fast and much faster than a CPU. So they are really good for computational activities, and in deep learning there is a lot of iterative computation that happens, so in the form of matrix multiplication and so on. So GPUs are very well suited for this kind of computation, and TensorFlow supports both GPU as well as CPU. And there's a certain way of writing code in TensorFlow. We will see as we go into the code. And of course, TensorFlow can be used for traditional machine learning as well, but then that would be an overkill. But just for understanding, it may be a good idea to start writing code for a normal machine learning use case so that you get a hang of how TensorFlow code works, and then you can move into neural networks. So that is just a suggestion, but if you're already familiar with how TensorFlow works, then probably you can go straight into the neural networks part. So in this tutorial, we will take the use case of recognizing handwritten digits. This is like a hello world of deep learning, and this is a nice little MNIST database is a nice little database that has images of handwritten digits nicely formatted, because very often in deep learning and neural networks, we end up spending a lot of time in preparing the data for training. And with MNIST database, we can avoid that. You already have the data in the right format, which can be directly used for training. And MNIST also offers a bunch of built-in utility functions that we can straight away use and call those functions without worrying about writing our own functions. And that's one of the reasons why MNIST database is very popular for training purposes. Initially, when people want to learn about deep learning and TensorFlow, this is the database that is used. And it has a collection of 70,000 handwritten digits, and a large part of them are for training. Then you have test, just like in any machine learning process, and then you have validation, and all of them are labeled. So you have the images and their label, and these images, they look somewhat like this. So they are handwritten images collected from a lot of individuals. People have, these are samples written by human beings. They have handwritten these numbers going from 0 to 9. So people have written these numbers, and then the images of those have been taken and formatted in such a way that it is very easy to handle. So that is MNIST database. And the way we are going to implement this in our TensorFlow is we will feed this data, especially the training data, along with the label information. And the data is basically, these images are stored in the form of the pixel information, as we have seen in one of the previous slides. All the images are nothing but, these are pixels. So an image is nothing but an arrangement of pixels, and the value of the pixel, either it is lit up or it is not, or in somewhere in between. That's how the images are stored, and that is how they are fed into the neural network and for training. Once the network is trained, when you provide a new image, it will be able to identify within a certain error, of course. And for this, we will use one of the simpler neural network configurations called softmax. And for simplicity, what we will do is we will flatten these pixels. So instead of taking them in a two-dimensional arrangement, we just flatten them out. So for example, it starts from here. It is a 28 by 28, so there are 784 pixels. So pixel number 1 starts here, it goes all the way up to 28, then 29 starts here and goes up to 56 and so on. And the pixel number 784 is here. So we take all these pixels, flatten them out, and feed them like one single line into our neural network. And this is what is known as a softmax layer. What it does is, once it is trained, it will be able to identify what digit this is. So there are, in this output layer, there are 10 neurons, each signifying a digit. And at any given point of time, when you feed an image, only one of these 10 neurons gets activated. So for example, if this is trained properly, and if you feed a number 9 like this, then this particular neuron gets activated. So you get an output from this neuron. Let me just use a pen or a laser to show you here. Okay, so you're feeding a number 9. Let's say this has been trained, and now if you're feeding a number 9, this will get activated. Now let's say you feed 1 to the trained network, then this neuron will get activated. If you feed 2, this neuron will get activated, and so on. I hope you get the idea. So this is one type of a neural network or an activation function known as softmax layer. So that's what we will be using here. This is one of the simpler ones for quick and easy understanding. So this is how the code would look. We will go into our lab environment in the cloud, and we will show you there directly. But very quickly, this is how the code looks. And let me run you through briefly here, and then we will go into the Jupyter notebook where the actual code is, and we will run that as well. So as a first step, first of all, we are using Python here, and that's why the syntax of the language is Python. And the first step is to import the TensorFlow library. So, and we do this by using this line of code saying import TensorFlow as TF. TF is just for convenience, so you can give any name. And once you do this, TensorFlow is available as an object in the name of TF, and then you can run its methods and accesses its attributes and so on and so forth. And MNIST database is actually an integral part of TensorFlow, and that's again another reason why we, as a first step, we always use this example, MNIST database example. So you just simply import MNIST database as well using this line of code, and you slightly modify this so that the labels are in this format, what is known as one hot true, which means that the label information is stored like an array. And let me just use the pen to show what exactly it is. So when you do this one hot true, what happens is each label is stored in the form of an array of 10 digits, and let's say the number is 8. Okay, so in this case, all the remaining values, there will be a bunch of zeros. So this is like array at position 0, this is at position 1, position 2, and so on and so forth. Let's say this is position 7, then this is position 8. That will be 1 because our input is 8. And again, position 9 will be 0. Okay, so one hot encoding, this one hot encoding true will kind of load the data in such a way that the labels are in such a way that only one of the digits has a value of 1, and that indicates. So based on which digit is 1, we know what is the label. So in this case, the 8th position is 1, therefore we know this sample data, the value is 8. Similarly, if you have a 2 here, let's say, then the labeled information will be somewhat like this. So you have your labels. So you have this as 0, the 0th position. The first position is also 0. The second position is 1 because this indicates number 2. And then you have third as 0 and so on. Okay, so that is the significance of this one hot true. All right, and then we can check how the data is looking by displaying the data. And as I mentioned earlier, this is pretty much in the form of digital form, like numbers. So all these are like pixel values, so you will not really see an image in this format, but there is a way to visualize that image. I will show you in a bit. And this tells you how many images are there in each set. So the training, there are 55,000 images in training, and in the test set there are 10,000, and then validation there are 5,000. So altogether there are 70,000 images. All right, so let's move on, and we can view the actual image by using the matplotlib library, and this is how you can view. This is the code for viewing the images, and you can view them in color or you can view them in grayscale. So the CMap is what tells in what way we want to view it, and what are the maximum values and the minimum values of the pixel values. So these are the max and minimum values of the pixel values. So maximum is 1 because this is a scaled value. So 1 means it is white, and 0 means it is black, and in between it can be anywhere in between black and white. And the way to train the model, there is a certain way in which you write your TensorFlow code, and the first step is to create some placeholders, and then you create a model. In this case, we will use the softmax model, one of the simplest ones, and placeholders are primarily to get the data from outside into the neural network. So this is a very common mechanism that is used. And then of course you will have variables, which are remember these are your weights and biases. So in our case, there are 10 neurons, and each neuron actually has 784 because each neuron takes all the inputs. If we go back to our slide here, actually every neuron takes all the 784 inputs. Right? This is the first neuron. It receives all the 784. This is the second neuron. This also receives all the 708. So each of these inputs needs to be multiplied with a weight, and that's what we are talking about here. So this is a matrix of 784 values for each of the neurons, and so it is like a 10 by 784 matrix because there are 10 neurons. And similarly, there are biases. Now remember, I mentioned biases only 1 per neuron, so it is not 1 per input, unlike the weights. So therefore there are only 10 biases because there are only 10 neurons in this case. So that is what we are creating a variable for biases. So this is something little new in TensorFlow. You will see, unlike our regular programming languages where everything is a variable, here the variables can be of 3 different types. You have placeholders, which are primarily used for feeding data. You have variables, which can change during the course of computation. And then a third type, which is not shown here, are constants. So these are like fixed numbers. All right. So in a regular programming language, you may have everything as variables or at the most variables and constants. But in TensorFlow, you have 3 different types: placeholders, variables, and constants. And then you create what is known as a graph. So TensorFlow programming consists of graphs and tensors, as I mentioned earlier. So this can be considered ultimately as a tensor. And then the graph tells how to execute the whole implementation, so that the execution is stored in the form of a graph. And in this case, what we are doing is we are doing a multiplication. TF, you remember this TF was created as a TensorFlow object here. One more level, one more. So TF is available here. Now TensorFlow has what is known as a matrix multiplication or matmul function. So that is what is being used here in this case. So we are using the matrix multiplication of TensorFlow so that you multiply your input values x with w, right? This is what we were doing, xw plus b. You're just adding b, and this is very similar to one of the earlier slides where we saw sigma xi wi. So that's what we are doing here. Matrix multiplication is multiplying all the input values with the corresponding weights and then adding the bias. So that is the graph we created. And then we need to define what is our loss function and what is our optimizer. So in this case, we again use the TensorFlow's APIs. So tf.nn softmax cross entropy with logits is the API that we will use, and reduce mean is what is like the mechanism whereby which says that you reduce the error. And optimizer for doing reduction of the error, what optimizer are we using? So we are using gradient descent optimizer. We discussed about this in a couple of slides earlier. And for that, you need to specify the learning rate. You remember we saw that there was a slide somewhat like this, and then you define what should be the learning rate, how fast you need to come down. That is the learning rate. And this again needs to be tested and tried, and to find out the optimum level of this learning rate. It shouldn't be very high, in which case it will not converge, or shouldn't be very low, because it will, in that case, it will take very long. So you define the optimizer, and then you call the method minimize for that optimizer, and that will kickstart the training process. And so far we've been creating the graph, and in order to actually execute that graph, we create what is known as a session, and then we run that session. And once the training is completed, we specify how many times, how many iterations we want it to run. So for example, in this case, we are saying 1000 steps. So that is a exit strategy in a way. So you specify the exit condition. So a training will run for 1000 iterations. And once that is done, we can then evaluate the model using some of the techniques shown here. So let us get into the code quickly and see how it works. So this is our cloud environment. Now you can install TensorFlow on your local machine as well. I'm showing this demo on our existing cloud, but you can also install TensorFlow on your local machine, and there is a separate video on how to set up your TensorFlow environment. You can watch that if you want to install your local environment. Or you can go for any cloud service, like for example Google Cloud, Amazon, or Cloud Labs. Any of these you can use and run and try the code. Okay, so it has got started. We will log in. Alright, so this is our deep learning tutorial code, and this is our TensorFlow environment. And so let's get started. We have seen a little bit of a code walkthrough in the slides as well. Now you will see the actual code in action. So the first thing we need to do is import TensorFlow, and then we will import the data. And we need to adjust the data in such a way that the one hot encoding is set to true, one hot encoding, right? As I explained earlier. So in this case, the label values will be shown appropriately. And if we just check what is the type of the data, so you can see that this is a data sets, Python data sets. And if we check the number of images, the way it looks, so this is how it looks. It is an array of type float 32. Similarly, the number, if you want to see what is the number of training images, there are 55,000, then there are test images 10,000, and then validation images 5,000. Now let's take a quick look at the data itself, visualization. So we will use matplotlib for this. And if we take a look at the shape, now shape gives us like the dimension of the tensors or the arrays, if you will. So in this case, the training data set, if we see the size of the training data set using the method shape, it says there are 55,000 and 55,000 by 784. So remember, this 784 is nothing but the 28 by 28, 28 into 28. So that is equal to 784. So that's what it is showing. Now we can take just one image and just see what is the first image and see what is the shape. So again, size, obviously it is only 784. Similarly, you can look at the image itself, the data of the first image itself. So this is how it shows. So large part of it will probably be zeros, because as you can imagine, in the image only certain areas are written, rest is blank. So that's why you will mostly see zeros, either it is black or white. But then there are these values are, so the values are actually, they are scaled, so their values are between 0 and 1. Okay, so this is what you're seeing. So certain locations there are some values, and then other locations there are zeros. So that is how the data is stored and loaded. If we want to actually see what is the value of the handwritten image, if you want to view it, this is how you view it. So you create, like, do this reshape, and matplotlib has this feature to show you these images. So we will actually use the function called imshow, and then if you pass this parameters appropriately, you will be able to see the different images. Now I can change the values in this position, so which image we are looking at, right? So we can say, if I want to see what is there in maybe 5000, right? So 5000 has 3. Similarly, you can just say 5. What is in 5? 5 has 8. What is in 50? Again 8. So basically, by the way, if you're wondering how I'm executing this code, Shift Enter, in case you're not familiar with Jupyter Notebooks, Shift Enter is how you execute each cell, individual cell. And if you want to execute the entire program, you can go here and say run all. So that is how this code gets executed. And here again we can check what is the maximum value and what is the minimum value of these pixel values. As I mentioned, it is scaled, so therefore it is between, the values lie between 1 and 0. Now this is where we create our model. The first thing is to create the required placeholders and variables, and that's what we are doing here, as we have seen in the slides. So we create one placeholder and we create 2 variables, which is for the weights and biases. These 2 variables are actually matrices, so each variable has 784 by 10 actual values. Okay, so one for this 10 is for each neuron. There are 10 neurons, and 784 is for the pixel values inputs that are given, which is 28 into 28. And the biases, as I mentioned, one for each neuron, so there will be 10 biases. They are stored in a variable by the name B. And this is the graph, which is basically the multiplication of these matrix multiplication of X into W, and then the bias is added for each of the neurons. And the whole idea is to minimize the error. So let me just execute. I think this code is executed. Then we define what is the Y value is basically the label value. So this is another placeholder. We had X as one placeholder and Y underscore true as a second placeholder. And this will have values in the form of 10 digit arrays. And since we said one hot encoded, the position which has a 1 value indicates what is the label for that particular number. All right. Then we have cross entropy, which is nothing but the loss function. And we have the optimizer. We have chosen gradient descent as our optimizer. Then the training process itself. So the training process is nothing but to minimize the cross entropy, which is again nothing but the loss function. So we define all of this in the form of a graph. So up to here, remember what we have done is we have not exactly executed any TensorFlow code till now. We are just preparing the graph, the execution plan. That's how the TensorFlow code works. So the whole structure and format of this code will be completely different from how we normally do programming. So even with people with programming experience may find this a little difficult to understand it, and it needs quite a bit of practice. So you may want to view this video also maybe a couple of times to understand this flow, because the way TensorFlow programming is done is slightly different from the normal programming. Some of you who, let's say, have done maybe Spark programming to some extent will be able to easily understand this. But even in Spark, the programming, the code itself is pretty straightforward. Behind the scenes, the execution happens slightly differently. But in TensorFlow, even the code has to be written in a completely different way. So the code doesn't get executed in the same way as you have written. So that's something you need to understand, and a little bit of practice is needed for this. So far what we have done up to here is creating the variables and feeding the variables, and or rather not feeding but setting up the variables and the graph. That's all. Defining maybe the what kind of a network you want to use. For example, we want to use softmax and so on. So you have created the variables, how to load the data, loaded the data, viewed the data, and prepared everything. But you have not yet executed anything in TensorFlow. Now the next step is the execution in TensorFlow. So the first step for doing any execution in TensorFlow is to initialize the variables. So anytime you have any variables defined in your code, you have to run this piece of code always. So you need to basically create what is known as a node for initializing. So this is a node. You still are not yet executing anything here. You just created a node for the initialization. So let us go ahead and create that. And here onwards is where you will actually execute your code in TensorFlow. And in order to execute the code, what you will need is a session, TensorFlow session. So tf.session will give you a session, and there are a couple of different ways in which you can do this, but one of the most common methods of doing this is with what is known as a with loop. So you have a with tf.session as ses and with a colon here, and this is like a block, starting of the block, and these indentations tell how far this block goes, and this session is valid till this block gets executed. So that is the purpose of creating this with block. This is known as a with block. So with tf.session as ses, you say ses.run init. Now ses.run will execute a node that is specified here. So for example, here we are saying ses.run. Ses is basically an instance of the session, right? So here we are saying tf.session. So an instance of the session gets created and we are calling that ses. And then we run a node within that, one of the nodes in the graph. So one of the nodes here is init. So we say run that particular node, and that is when the initialization of the variables happens. Now what this does is, if you have any variables in your code, in our case we have w is a variable and b is a variable. So any variables that we created, you have to run this code, you have to run the initialization of these variables, otherwise you will get an error. Okay, so that's what this is doing. Then we, within this with block, we specify a for loop, and we are saying we want the system to iterate for 1000 steps and perform the training. That's what this for loop does. Run training for 1000 iterations. And what it is doing basically is it is fetching the data or these images. Remember, there are about 50,000 images, but it cannot get all the images in one shot because it will take up a lot of memory and performance issues will be there. So this is a very common way of performing deep learning training. You always do in batches. So we have maybe 50,000 images, but you always do it in batches of 100 or maybe 500 depending on the size of your system and so on and so forth. So in this case we are saying, okay, get me 100 images at a time and get me only the training images. Remember, we use only the training data for training purpose, and then we use test data for test purpose. You must be familiar with machine learning, so you must be aware of this, but in case you are not, in machine learning also, this is not specific to deep learning, but in machine learning in general, you have what is known as training data set and test data set. Your available data, typically you will be splitting into two parts and using the training data set for training purpose, and then to see how well the model has been trained, you use the test data set to check or test the validity or the accuracy of the model. So that's what we are doing here. And you observe here that we are actually calling an mnest function here. So we are saying mnest train.next batch. Right? So this is the advantage of using MNIST database, because they have provided some very nice helper functions which are readily available. Otherwise, this activity itself, we would have had to write a piece of code to fetch this data in batches. That itself is a lengthy exercise. So we can avoid all that if we are using MNIST database, and that's why we use this for the initial learning phase. Okay, so when we say fetch, what it will do is it will fetch the images into X and the labels into Y, and then you use this batch of 100 images and you run the training. So ses.run, basically what we are doing here is we are running the training mechanism, which is nothing but it passes this through the neural network, passes the images through the neural network, finds out what is the output, and if the output, obviously initially it will be wrong, so all that feedback is given back to the neural network, and thereby all the W's and B's get updated till it reaches 1000 iterations. In this case, the exit criteria is 1000, but you can also specify probably accuracy rate or something like that for the as an exit criteria. So here it just says that, okay, this particular image was wrongly predicted, so you need to update your weights and biases. That's the feedback given to each neuron, and that is run for 1000 iterations. And typically by the end of this 1000 iterations, the model would have learned to recognize these handwritten images. Obviously it will not be 100% accurate. Okay, so once that is done, so this happens for 1000 iterations. Once that is done, you then test the accuracy of these models by using the test data set. Right? So this is what we are trying to do here. The code may appear a little complicated because if you're seeing this for the first time, you need to understand the various methods of TensorFlow and so on. But it is basically comparing the output with what is actually there. That's all it is doing. So you have your test data, and you're trying to find out what is the actual value and what is the predicted value, and seeing whether they are equal or not, tf.equal, right? And how many of them are correct, and so on and so forth. And based on that, the accuracy is calculated as well. So this is the accuracy, and that is what we are trying to see, how accurate the model is in predicting these numbers or these digits. Okay, so let us run this. This entire thing is in one cell, so we will have to just run it in one shot. It may take a little while. Let us see. And not bad. So it has finished the 1000 iterations, and what we see here as an output is the accuracy. So we see that the accuracy of this model is around 91%. Okay, now which is pretty good for such a short exercise. Within such a short time we got 90% accuracy. However, in real life this is probably not sufficient, so there are other ways to increase the accuracy. We will see probably in some of the later tutorials how to improve this accuracy, how to change maybe the hyperparameters like number of neurons or number of layers and so on and so forth, and so that this accuracy can be increased beyond 90%.
Hello and welcome to the TensorFlow Object Detection API tutorial. In this video, I will walk you through the TensorFlow code to perform object detection in a video. So let's get started. This part is basically you're importing all the libraries. We need a lot of these libraries, for example, NumPy, we need image.io, datetime, and pill, and so on and so forth, and of course matplotlib. So we import all these libraries, and then there are a bunch of variables which have some paths for the files and folders. So this is regular stuff. Let's keep moving. Then we import the matplotlib and make it inline, and a few more imports. All right. And then these are some warnings. We can just ignore them. So if I run this code once again, it will go away. All right. And then here onwards, we do the model preparation. Now what we're going to do is we are going to use an existing neural network model. So we are not going to train a new one because that really will take a long time, and it needs a lot of computation resources and so on, and it is really not required. There are already models that have been trained, and in this case it is the SSD with MobileNet. That's the model that we are going to use, and this model is trained to detect objects, and it is readily available as open source, so we can actually use this. And if you want to use other models, there are a few more models available, so you can click on this link here, and let me just take you there. There are a few more models, but we have chosen this particular one because this is faster. It may not be very accurate, but that is one of the faster models. But on this link you will see a lot of other models that are readily available. These are trained models. Some of them would take a little longer, but they may be more accurate and so on. So you can probably play around with these other models. Okay, so we will be using that model. So this piece of code, this line, is basically importing that model, and this is also known as frozen model. The term we use is frozen model. So we import, download and import that, and then we will actually use that model in our code. Alright, so these two cells, we have downloaded and imported the model, and then once it is available locally, we will then load this into our program. Alright, so we are loading this into memory, and you need to perform a couple of additional steps, which is basically we need to map the numbers to text. As you may be aware, when we actually build a model and when we run predictions, the model will not give a text. The output of the model is usually a number. So we need to map that to a text. So for example, if the network predicts that the output is 5, we know that 5 means it is an aeroplane. Things like that. So this mapping is done in this next cell. Alright, so let's keep moving. And then we have a helper code which will basically load the data or load the images and transform into NumPy arrays. This is also used in doing object detection in images. So we are actually going to reuse, because video is nothing but it consists of frames, which in turn are images. So we are going to pretty much reuse the same code which we used for doing object detection in images. So this is where the actual detection starts. So here, this is the path for where the images are stored. So this is, here once again we are reusing the code which we wrote for detecting objects in an image. So this is the path where the images were stored, and this is the extension, and this was done for about 2 or 3 images. So we will continue to use this, and if we go down, I'll skip this section. So this is the cell where we are actually loading the video and converting it into frames, and then using frame by frame we are detecting the objects in the image. So in this code, what we are doing basically is there are a few lines of code. What they do is basically once they find an object, a box will be drawn around those each of those objects, and the input file, the name of the input video file is traffic. It is the extension is MP4, and we have this video reader. It's an excellent object which is basically part of this class called image.io. So we can read and write videos using that, and the video that we are going to use is traffic.mp4. You can use any MP4 file, but in our case I picked up video which has like cars. So let me just show you. So this is in this object detection folder. I have this MP4 file. I'll just quickly play this video. It's a little slow. Yeah, okay. So here we go. This is the video. It's a short one, relatively small video, so that for this particular demo. And what it will do is, once we run our code, it will detect each of these cars and it will annotate them as cars. So in this particular video, we only have cars. We can later on see with another video. I think I have cat here, so we can also try with that. But let's first check with this traffic video. So let me go back. So we will be reading this frame by frame, and no, actually we will be reading the video file, but then we will be analyzing it frame by frame, and we will be reading them at 10 frames per second. That is the rate we are mentioning here, and analyzing it and then annotating and then writing it back. So you will see that we will have a video file named something like this, traffic_annotated, and we will see the annotated video. So let's go back and run through this piece of code, and then we will come back and see the annotated video. This might take a little while, so I will pause the video after running this particular cell and then come back to show you the results. Alright, so let's go ahead and run it. So it is running now, and it is also important that at the end you close the video writer, so that it is similar to a file pointer. When you open a file, you should also make sure you close it so that it doesn't hog the resources. So it's very similar. So at the end of it, the last piece or last line of code should be video_writer.close. Alright, so I'll pause and then I'll come back. Okay, so I will see you in a little bit. Alright, so now as you can see here, the processing is done. The hourglass has disappeared. That means the video has been processed. So let's go back and check the annotated video. We'll go back to my file manager. So this was the original traffic.mp4, and now you have here traffic underscore annotated mp4. So let's go and run this and see how it looks. You see here, it has got each of these cars are getting detected. Let me pause and show you. So we pause here. It says car 70%. Let us allow it to go a little further. It detects something on top. What is that? Truck. Okay. So I think because of the board on top, it somehow thinks there is a truck. Let's play some more and see if it detects anything else. So this is again a car, looks like. So let us, yeah. So this is a car, and it has confidence level of 69%. Okay, this is again a car. Alright, so basically till the end it goes and detects each and every car that is passing by. Now we can quickly repeat this process for another video. Let me just show you the other video, which is a cat. Again, there is this cat is not really moving or anything, but it is just standing there staring and moving a little slowly, and our application will, our network will detect that this is a cat, and even when the cat moves a little bit in the other direction, it will continue to detect and show that it is a cat. Okay, so yeah, so this is how the original video is. Let's go ahead and change our code to analyze this one and see if it detects, our network detects this cat. Close this, here we go, and I'll go back to my code. All we need to do is change this traffic to cat. The extension, it will automatically up because it is given here, and then it will run through. So very quickly, once again, what it is doing is this video reader, video underscore reader, has a neat little feature or interface whereby you can say for frame in video underscore reader. So it will basically provide frame by frame. So you're in a loop frame by frame, and then you take that each frame that is given to you, you take it and analyze it as if it is an image, individual image. So that's the way it works. So it is very easy to handle this. Alright, so now let's once again run just this cell. The rest of the stuff remains the same. So I will run this cell again. It will take a little while, so the hourglasses come back. I will pause and then come back in a little while. Alright, so the processing is done. Let's go and check the annotated video. Go here. So we have cat annotated.mp4. Let's play this. Alright, so you can see here it is detecting the cat, and in the beginning you also saw it detected something else here. There looks like it detected one more object. So let's just go back and see what it has detected here. Let's see. Yes. So what is it trying to show here? It's too small, not able to see, but it is trying to detect something. I think it is saying it is a car. I don't know. Alright, okay, so in this video there's pretty much only one object, which is a cat, and let's wait for some time and see if it continues to detect it when the cat turns around and moves as well. Just in a little bit that's going to happen, and we will see. There we go. And in spite of turning the other way, I think our network is able to detect that it is a cat. So let me freeze and then show here. It is actually still continues to detect it as a cat. Alright, so that's pretty much it. I think that's the only object that it detects in this particular video. Okay, so close this. So that's pretty much it. Thank you very much for watching this video. You have a great day, and in case you have any questions, please put them below the video here, and we will be more than happy to get back to you. And make sure you put your email ID so that we can contact you in case you have any questions. Thank you once again. Bye-bye.
Today we're going to be covering the convolutional neural network tutorial. Do you know how deep learning recognizes the objects in an image? And really, this particular neural network is how image recognition works. It's very central, one of the biggest building blocks for image recognition. It does it using convolution neural network. And over here we have the basic picture of a hummingbird. Pixels of an image fed as input. You have your input layer coming in, so it takes that graphic and puts it into the input layer. You have all your hidden layers. And then you have your output layer, and your output layer, one of those is going to light up and say, oh, it's a bird. We're going to go into depth. We're going to actually go back and forth on this a number of times today. So if you're not catching all the image, don't worry, we're going to get into the details. So we have our input layer accepts the pixels of the image as input in the form of arrays. And you can see up here where they've actually labeled each block of the bird in different arrays. So we'll dive into deep as to how that looks like and how those matrices are set up. Your hidden layer carry out feature extraction by performing certain calculations and manipulations. So this is the part that kind of reorganizes that picture multiple ways until we get some data that's easy to read for the neural network. This layer uses a matrix filter and performs convolution operation to detect patterns in the image. And if you remember that convolution means to coil or to twist, so we're going to twist the data around and alter it and use that operation to detect a new pattern. There are multiple hidden layers like convolution layer, ReLU is how that is pronounced, and that's the rectified linear unit. That has to do with the activation function that's used. Pooling layer also uses multiple filters to detect edges, corners, eyes, feathers, beak, etc. And just like the term says, pooling is pooling information together. And we'll look into that a lot closer here. So if it's a little confusing now, we'll dig in deep and try to get you squared away with that. And then finally, there is a fully connected layer that identifies the object in the image. So we have these different layers coming through in the hidden layers, and they come into the final area, and that's where we have, say, one node or one neural network entity that lights up that says it's a bird. What's in it for you? We're going to cover an introduction to the CNN, what is convolution neural network, how CNN recognizes images. We're going to dig deeper into that and really look at the individual layers in the convolutional neural network. And finally, we do a use case implementation using the CNN. We'll begin our introduction to the CNN by introducing the pioneer of convolutional neural network, Yann LeCun. He was the director of Facebook AI Research Group. Built the first convolutional neural network called LeNet in 1988. So these have been around for a while and have had a chance to mature over the years. It was used for character recognition tasks like reading zip code digits. Imagine processing mail and automating that process. CNN is a feed-forward neural network that is generally used to analyze visual images by producing data with a grid-like topology. A CNN is also known as a convnet. And very key to this is we are looking at images. That was what this was designed for, and you'll see the different layers as we dig in mirror some of them are actually now used since we're using TensorFlow and Keras in our code later on. You'll see that some of those layers appear in a lot of your other neural network frameworks. But in this case, this is very central to processing images and doing so in a variety that captures multiple images and really drills down into their different features. In this example here, you see flowers of two varieties, orchid and a rose. I think the orchid is much more dainty and beautiful, and the rose smells quite beautiful. I have a couple rose bushes in my yard. They go into the input layer. That data is then sent to all the different nodes in the next layer, one of the hidden layers, based on its different weights and its setup. It then comes out and gives those a new value. Those values then are multiplied by their weights and go to the next hidden layer, and so on. And then you have the output layer, and one of those nodes comes out and says it's an orchid, and the other one comes out and says it's a rose, depending on how well it was trained. What separates the CNN, or the convolutional neural network, from other neural networks is a convolutional operation. Forms the basis of any convolutional neural network. In a CNN, every image is represented in the form of arrays of pixel values. So here we have a real image of the digit 8. That then gets put onto its pixel values, represented in the form of an array. In this case, you have a two-dimensional array. And then you can see in the final end form, we transform the digit 8 into its representational form of pixels of zeros and ones, where the ones represent, in this case, the black part of the 8, and the zeros represent the white background. To understand the convolution neural network, or how that convolutional operation works, we're going to take a sidestep and look at matrices. In this case, we're going to simplify it, and we're going to take two matrices, A and B, of one dimension. Now, kind of separate this from your thinking as we learn that you want to focus just on the matrix aspect of this. And then we'll bring that back together and see what that looks like when we put the pieces for the convolutional operation. Here we've set up two arrays. We have, in this case, they're a single dimension matrix. And we have A equals 5, 3, 7, 5, 9, 7. And we have B equals 1, 2, 3. So in the convolution, as it comes in there, it's going to look at these two, and we're going to start by multiplying them, A times B. And so we multiply the arrays element-wise, and we get 5, 6, 6, where 5 is the 5 times 1, 6 is 3 times 2, and then the other 6 is 2 times 3. And since the two arrays aren't the same size, they're not the same setup, we're going to just truncate the first one, and we're going to look at the second array multiplied just by the first 3 elements of the first array. Now that's going to be a little confusing. Remember, a computer gets to repeat these processes hundreds of times. So we're not going to just forget those other numbers later on. We'll bring those back in. And then we have the sum of the product. In this case, 5 plus 6 equals 17. So in our A times B, our very first digit in that matrix of A times B is 17. And if you remember, I said we're not going to forget the other digits. So we now have 3, 2, 5. We move one set over, and we take 3, 2, 5, and we multiply that times B. And you'll see that 3 times 1 is 3, 2 times 2 is 4, and so on and so on. We sum it up, so now we have the second digit of our A times B product in the matrix. And we continue on with that same thing, so on and so on. So then we would go from 375 to 759 to 597. This short matrix that we have for A, we've now covered all the different entities in A that match 3 different levels of B. Now, in a little bit, we're going to cover where we use this math at, this multiplying of matrices and how that works. But it's important to understand that we're going through the matrix and multiplying the different parts to it to match the smaller matrix with the larger matrix. I know a lot of people get lost at is, what's going on here with these matrices? Ooh, scary math. Not really that scary when you break it down. We're looking at a section of A and we're comparing it to B. So when you break that down in your mind like that, you realize, okay, so I'm just taking these two matrices and comparing them, and I'm bringing the value down into one matrix, A times B. We're reducing that information in a way that will help the computer see different aspects. Let's go ahead and flip over again back to our images. Here we are back to our images. Talking about going to the most basic two-dimensional image you can get to. Consider the following two images. The image for the symbol backslash. When you press the backslash, the above image is processed. And you can see there for the image for the forward slash is the opposite. So when we click the forward slash button, that flips. Very basic. We have 4 pixels going in. Can't get any more basic than that. Here we have a little bit more complicated picture. We take a real image of a smiley face. Then we represent that in the form of black and white pixels. So if this was an image in the computer, it's black and white. And like we saw before, we convert this into the zeros and ones. So where the other one would have just been a matrix of just 4 dots, now we have a significantly larger image coming in. So don't worry, we're going to bring this all together here in just a little bit. Layers in convolutional neural network. When we're looking at this, we have our convolution layer. And that really is the central aspect of processing images in the convolutional neural network. That's why we have it. And then that's going to be feeding in. And you have your ReLU layer, which is, as we talked about, the rectified linear unit. We'll talk about that a little bit later. The ReLU is how that layer is activated, is the math behind it, what makes the neurons fire. You'll see that in a lot of other neural networks. When you're using it just by itself, it's for processing smaller amounts of data, where you use the atom activation feature for large data coming in. Now, because we're processing small amounts of data in each image, the ReLU layer works great. You have your pooling layer. That's where you're pooling the data together. Pooling is a neural network term. It's very commonly used. I like to use the term reduce. So if you're coming from the map and reduce side, you'll see that we're mapping all this data through all these networks, and then we're going to reduce it. We're going to pool it together. And then finally we have the fully connected layer. That's where our output's going to come out. So we have started to look at matrices. We've started to look at the convolutional layer and where it fits in and everything. We've taken a look at images. So we're going to focus more on the convolution layer, since this is a convolutional neural network. A convolution layer has a number of filters and perform convolution operation. Every image is considered as a matrix of pixel values. Consider the following 5x5 image whose pixel values are only 0 and 1. Now, obviously, when we're dealing with color, there's all kinds of things that come in on color processing, but we want to keep it simple and just keep it black and white. And so we have our image pixels, so we're sliding the filter matrix over the image and computing the dot product to detect the patterns. And right here, you're going to ask, where does this filter come from? This is a bit confusing because the filter is going to be derived later on. We build the filters when we program or train our model. So you don't need to worry what the filter actually is, but you do need to understand how a convolution layer works, is what is the filter doing. Filter, and you'll have many filters. You don't have just one filter. You'll have lots of filters that are going to look for different aspects. And so the filter might be looking for just edges, it might be looking for different parts. We'll cover that a little bit more detail in a minute. Right now we're just focusing on how the filter works as a matrix. Remember earlier we talked about multiplying matrices together? And here we have our two-dimensional matrix. And you can see we take the filter and we multiply it in the upper left image, and you can see right here 1 times 1, 1 times 0, 1 times 1. We multiply those all together, then sum them, and we end up with a convolved feature of 4. We're going to take that and sliding the filter matrix over the image and computing the dot product to detect patterns. So we're just going to slide this over. We're going to predict the first one and slide it over 1 notch, predict the second one, and so on all the way through until we have a new matrix. And this matrix, which is the same size as the filter, has reduced the image, and whatever filter, whatever that's filtering out, is going to be looking at just those features reduced down to a smaller matrix. So once the feature maps are extracted, the next step is to move them to the ReLU layer. So the ReLU layer, the next step, first is going to perform an element-wise operation. So each of those maps coming in, if there's negative pixels, so it sets all the negative pixels to 0. And you can see this nice graph where it just zeroes out the negatives, and then you have a value that goes from 0 up to whatever value is coming out of the matrix. This introduces nonlinearity to the network. So up until now, we have when we say linearity, we're talking about the fact that the feature has a value. So it's a linear feature. This feature came up and it has, let's say the feature is the edge of the beak. It's like, or that backslash that we saw. It'll look at that and say, okay, this feature has a value from -10 to 10 in this case. If it was 1, it'd say, yeah, this might be a beak. It might not. It might be an edge right there. A -5 means, no, we're not even going to look at it. It's a 0. And so we end up with an output, and the output takes all these filtered features. Remember, we're not just running one filter on this, we're running a number of filters on this image. And so we end up with a rectified feature map that is looking at just the features coming through and how they weigh in from our filters. So here we have an input of it looks like a toucan bird. Very exotic looking. Real image is scanned in multiple convolution and the ReLU layers for locating features. And you can see up here is turn it into a black and white image. And in this case, we're looking in the upper right-hand corner for a feature, and that box scans over. A lot of times it doesn't scan 1 pixel at a time. A lot of times it will skip by 2 or 3 or 4 pixels to speed up the process. That's one of the ways you can compensate if you don't have enough resources on your computation for large images. And it's not just one filter that slowly goes across the image. You have multiple filters that have been programmed in there. So you're looking at a lot of different filters going over the different aspects of the image and just sliding across there and forming a new matrix. One more aspect to note about the ReLU layer is we're not just having one ReLU coming in. So not only do we have multiple features going through, but we're generating multiple ReLU layers for locating the features. That's very important to note. So we have quite a bundle. We have multiple filters, multiple ReLU, which brings us to the next step, forward propagation. Now we're going to look at the pooling layer. The rectified feature map now goes through a pooling layer. Pooling is a downsampling operation that reduces the dimensionality of the feature map. That's all we're trying to do. We're trying to take a huge amount of information and reduce it down to a single answer. This is a specific kind of bird. This is an iris. This is a rose. So you have a rectified feature map. And you see here we have a rectified feature map coming in. We set the max pooling with a 2x2 filters and a stride of 2. And if you remember correctly, I talked about not going 1 pixel at a time. Well, that's where the stride comes in. We end up with a 2x2 pooled feature map, but instead of moving 1 over each time and looking at every possible combination, we skip a few there. We go by 2. We skip every other pixel. We just do every other one. And this reduces our rectified feature map, which, as you can see over here, 16 by 16 to a 4 by 4. So we're continually trying to filter and reduce our data so that we can get to something we can manage. And over here you see that we have the max 3, 4, 1, and 2. And in the max pooling, we're looking for the max value, a little bit different than what we were looking at before. So coming from the rectified feature, we're now finding the max value, and then we're pooling those features together. So instead of thinking of this as image of the map, think of this as how valuable is a feature in that area? How much of a feature value do we have? And we just want to find the best or the maximum feature for that area. They might have that one piece of the filter of the beak said, oh, I see a 1 in this beak in this image, and then it skips over and says, I see a 3 in this image, and it says, oh, this one is rated as a 4. We don't want to sum it together, because then you might have like 5 1s, and it'll say 5, but you might have 4 zeros and 1 10, and that 10 says, well, this is definitely a beak, where the 1s will say probably not a beak. A little strange analogy since we're looking at a bird, but you can see how that pooled feature map comes down, and we're just looking for the max value in each one of those matrices. Pooling layer uses different filters to identify different parts of the image, like edges, corners, body, feathers, eyes, beak, etc. I know I focus mainly on the beak, but obviously each feature could be a different part of the bird coming in. So let's take a look at what that looks like. Structure of a convolution neural network so far. This is where we're at right now. We have our input image coming in, and then we use our filters, and there's multiple filters on there that are being developed to kind of twist and change that data. And so we multiply the matrices. We take that little filter, maybe it's a 2 by 2, we multiply it by each piece of the image. And if we step 2, then it's every other piece of the image. That generates multiple convolution layers. So we have a number of convolution layers we have set up in there just looking at that data. We then take those convolution layers, we run them through the ReLU setup, and then once we've done through the ReLU setup, and we have multiple ReLUs going on, multiple layers that are ReLU, then we're going to take those multiple layers and we're going to be pooling them. So now we have the pooling layers, or multiple poolings going on. Up until this point, we're dealing with, sometimes it's multiple dimensions. You can have 3 dimensions, some strange data setups that aren't doing images but looking at other things. They can have 4, 5, 6, 7 dimensions. So right now we're looking at 2D image dimensions coming into the pooling layer. So the next step is we want to reduce those dimensions, or flatten them. So flattening. Flattening is a process of converting all of the resultant 2-dimensional arrays from pooled feature map into a single long continuous linear vector. So over here you see where we have a pooled feature map. Maybe that's the bird wing, and it has values 6, 8, 4, 7. And we want to just flatten this out and turn it into 6, 8, 4, 7, or a single linear vector. And we find out that not only do we do each of the pooled feature maps, we do all of them into one long linear vector. So now we've gone through our convolutional neural network part, and we have the input layer into the next setup. All we've done is taken all those different pooling layers and we've flattened them out and combined them into a single linear vector going in. So after we've done the flattening, we have just a quick recap because we've covered so much, so it's important to go back and take a look at each of the steps we've gone through. The structure of the network so far is we have our convolution where we twist it and we filter it and multiply the matrices. We end up with our convolutional layer, which uses the ReLU to figure out the values going out into the pooling. As you have numerous convolution layers that then create numerous pooling layers, pooling that data together, which is the max value. Which one we want to send forward. We want to send the best value. And then we're going to take all of that from each of the pooling layers and we're going to flatten it. And we're going to combine them into a single input going into the final layer. Once you get to that step, you might be looking at that going, boy, that looks like the normal input to most neural network. And you're correct, it is. So once we have the flattened matrix from the pooling layer, that becomes our input. So the pooling layer is fed as an input to the fully connected layer to classify the image. And so you can see as our flattened matrix comes in this case we have the pixels from the flattened matrix fed as an input back to our toucan, or whatever that kind of bird that is. I need one of these to identify what kind of bird that is. It comes into our forward propagation network. And that will then have the different weights coming down across. And then finally it selects that that's a bird and that it's not a dog or a cat in this case. Even though it's not labeled, the final layer there in red is our output layer, our final output layer that says bird, cat, or dog. So quick recap of everything we've covered so far. We have our input image, which is twisted and multiplied. The filters are multiplied times the two matrices multiplied all the filters to create our convolution layer. Our convolution layers, there's multiple layers in there because it's all building multiple layers off the different filters. Then goes through the ReLU as its activation, and that creates our pooling. And so once we get into the pooling layer, we then on the pooling look for who's the best, what's the max value coming in from our convolution. And then we take that layer and we flatten it, and then it goes into a fully connected layer, our fully connected neural network, and then to the output. And here we can see the entire process, how the CNN recognizes a bird. This is kind of nice because it's showing the little pixels and where they're going. You can see the filter is generating this convolution network, and that filter shows up in the bottom part of the convolution network. And then based on that, it uses the ReLU for the pooling. The pooling then find out which one's the best, and so on, all the way to the fully connected layer at the end, or the classification in the output layer. So that'd be a classification neural network at the end. So we covered a lot of theory up till now, and you can imagine each one of these steps has to be broken down in code. So putting that together can be a little complicated. Not that each step of the process is overly complicated, but because we have so many steps. We have 1, 2, 3, 4, 5 different steps going on here with sub-steps in there. We're going to break that down and walk through that in code. So in our use case implementation using the CNN, we'll be using the CFAR10 dataset from Canadian Institute for Advanced Research for classifying images across 10 categories. Unfortunately, they don't let me know whether it's going to be a toucan or some other kind of bird, but we do get to find out whether it can categorize between a ship, a frog, deer, bird, airplane, automobile, cat, dog, horse, truck. So that's a lot of fun. And if you're looking anything in the news at all of our automated cars and everything else, you can see where this kind of processing is so important in today's world and very cutting edge as far as what's coming out in the commercial deployment. I mean, this is really cool stuff. We're starting to see this just about everywhere in industry. So a great time to be playing with this and figuring it all out. Let's go ahead and dive into the code and see what that looks like when we're actually writing our script. Before we go on, let's do one more quick look at what we have here. Let's just take a look at data batch 1 keys. And remember, in Jupyter Notebook, I can get by with not doing the print statement. If I put a variable down there, it'll just display the variable. And you can see under data batch 1 for the keys, since this is a dictionary, we have the batch 1 label, data, and file names. So you can actually see how it's broken up in our data set. So for the next step, or step 4 as we're calling it, we want to display the images using Matplotlib. There's many ways to display the images. You could even, well, there's other ways to drill into it, but Matplotlib is really good for this. And we'll also look at our first reshape setup, or shaping the data, so you can have a little glimpse into what that means. So we're going to start by importing our matplot, and of course, since I am doing Jupyter Notebook, I need to do the matplot inline command, so it shows up on my page. So here we go. We're going to import matplotlib.pyplot as PLT. And if you remember Matplotlib, the pyplot is like a canvas that we paint stuff onto. And there's my %sign matplotlib inline, so it's going to show up in my notebook. And then of course we're going to import numpy as np for our numbers Python array setup. And let's go ahead and set x equals to data batch 1. So this will pull in all the data going into the x value. And then, because this is just a long stream of binary data, we need to go a little bit of reshaping. So in here we have to go ahead and reshape the data. We have 10,000 images. Okay, that looks correct. And this is kind of an interesting thing. It took me a little bit I had to go research this myself to figure out what's going on with this data. And what it is it's a 32 by 32 picture. And let me do this. Let me go ahead and do a drawing pad on here. So we have 32 bits by 32 bits, and it's in color. So there's 3 bits of color. Now, I don't know why the data is particularly like this. It probably has to do with how they originally encoded it. But most pictures put the 3 afterward. So what we're doing here is we're going to take the shape. We're going to take the data, which is just a long stream of information, and we're going to break it up into 10,000 pieces, and those 10,000 pieces then are broken into 3 pieces each, and those 3 pieces then are 32 by 32. You can look at this like an old-fashioned projector where they have the red screen, or the red projector, the blue projector, and the green projector, and they add them all together, and each one of those is a 32 by 32 bit. So that's probably how this was originally formatted, was in that kind of ideal. Things have changed, so we're going to transpose it, and we're going to take the 3, which was here, and we're going to put it at the end. So the first part is reshaping the data from a single line of bit data, or whatever format it is, into 10,000 by 3 by 32 by 32, and then we're going to transpose the color factor to the last place. So it's the image, then the 32 by 32 in the middle, that's this part right here, and then finally we're going to take this, which is 3 bits of data, and put it at the end. So it's more like we process images now. And then as type, this is really important that we're going to use an integer 8. You can come in here and you'll see a lot of these, they'll try to do this with a float or a float 64. What you got to remember though is a float uses a lot of memory. So once you switch this into something that's not integer 8, which goes up to 128, you are just going to, the amount of RAM, let's just put that in here, is going to go way up. The amount of RAM that it loads. So you want to go ahead and use this. You can try the other ones and see what happens if you have a lot of RAM on your computer. But for this exercise, this will work just fine. And let's go ahead and take that and run this. So now our X variable is all loaded and it has all the images in it from the batch 1, data batch 1. And just to show what we were talking about with the as type on there, if we go ahead and take X0 and just look for its max value, let me go ahead and run that. You'll see it doesn't, oops, I said 128, it's 255. You'll see it doesn't go over 255 because it's basically an ASCII character is what we're keeping that down to. We're keeping those values down. So they're only 255, 0 to 255 versus a float value, which would bring this up exponentially in size. And since we're using the matplot library, we can do, oops, that's not what I wanted. Since we're using the matplot library, we can take our canvas and just do a plt.im for image show, and let's just take a look at what X0 looks like. And it comes in, I'm not sure what that is, but you can see it's a very low grade image broken down to the minimal pixels on there. And if we did the same thing, let's see what 1 looks like. Hopefully it's a little easier to see. Run on there, not enter. Let's hit the run on that. And we can see this is probably a semi-truck. That's a good guess on there. And I can just go back up here instead of typing the same line in over and over. And we'll look at 3. That looks like a dump truck unloading, and so on. You can do any of the 10,000 images. We can just jump to 55. Looks like some kind of animal looking at us there, probably a dog. And just for fun, let's do just one more run on there, and we can see a nice car for our image number 4. So you can see we paste through all the different images. It's very easy to look at them, and they've been reshaped to fit our view and what the matplot library uses for its format. So the next step is we're going to start creating some helper functions. We'll start by a one-hot encoder to help us when we're processing the data. Remember that your labels, they can't just be words. They have to switch it, and we use the one-hot encoder to do that. And then we'll also create a class CFAR helper, so it's going to have an init and a setup for the images. And then finally we'll go ahead and run that code so you can see what that looks like. And then we get into the fun part where we're actually going to start creating our model, our actual neural network model. So let's start by creating our one-hot encoder. We're going to create our own here, and it's going to return an out. And we'll have our vector coming in and our values equal 10. What this means is that we have the 10 values, the 10 possible labels. And remember, we don't look at the labels as a number, because a car isn't one more than a horse. That'd be just kind of bizarre to have horse equals 0, car equals 1, plane equals 2, cat equals 3. So a cat plus a car equals what? So instead, we create a numpy array of zeros. And there's going to be 10 values, so we have 10 different values in there. So you have 0 or 1. 1 means it's a cat, 0 means it's not a cat. In the next line it might be that 1 means it's a car, 0 means it's not a car. So instead of having one output with a value of 0 to 10, you have 10 outputs with the values of 0 to 1. That's what the one-hot encoder is doing here. And we're going to utilize this in code in just a minute. So let's go ahead and take a look at the next helpers. We have a few of these helper functions we're going to build. And when you're working with a very complicated Python project, dividing it up into separate definitions and classes is very important. Otherwise, it just becomes really ungainly to work with. So let's go ahead and put in our next helper, which is a class. And there's a lot in this class, so we'll break it down here. And let's just start, oops, we can put a space right in there. There we go. Now this is a little bit more readable. Add a second space. So we're going to create our class, the Cipher Helper, and we'll start by initializing it. Now there's a lot going on in here. So let's start with the init part. Self.I equals 0. That'll come in a little bit. We'll come back to that in the lower part. We want to initialize our training batches. So when we went through this, there was like a meta batch. We don't need the meta batch, but we do need the data batch 1, 2, 3, 4, 5, and we do not want the testing batch in here. This is just the self all train batches. So we're going to make an array of all those different images. And then of course we left the test batch out, so we have our self.test batch. We're going to initialize the training images and the training labels, and also the test images and the test labels. So this is just to initialize these variables in here. Then we create another definition down here, and this is going to set up the images. And let's just take a look and see what's going on in there. Now we could have all just put this as part of the init part, since this is all just helper stuff, but breaking it up again makes it easier to read. It also makes it easier when we start executing the different pieces to see what's going on. So that way we have a nice print statement to say, hey, we're now running this and this is what's going on in here. We're going to set up the self-training images at this point, and that's going to go to a NumPy array VStack. And in there we're going to load up, in this case, the data for D and self all train batches. Again, that points right up to here. So we're going to go through each one of these files, or each one of these data sets, because they're not a file anymore. We've brought them in. Data batch 1 points to the actual data. And so our self-training images is going to stack them all into a NumPy array. And then it's always nice to get the training length, and that's just the total number of self-training images in there. And then we're going to take the self-training images. And let me switch marker colors, because I am getting a little too much on the markers up here. Oops, there we go. Bring down our marker change so we can see it a little better. And at this point, this should look familiar. Where did we see this? Well, when we wanted to look at this above, and we wanted to look at the images in the Matplot library, we had to reshape it. So we're doing the same thing here. We're taking our self-training images, and based on the training length, total number of images, because we stacked them all together, so now it's just one large file of images, we're going to take and look at it as our 3 video cameras that are each displaying 32 by 32, and we're going to switch that around so that now we have each of our images that stays the same place, and then we have our 32 by 32, and then by our 3. Our 3 different values for the color. And of course we want to go ahead and they run this where you say divide by 255. That was from earlier. It just brings all the data into 0 to 1. That's what this is doing. So we're turning this into a 0 to 1 array, which is all the pictures 32 by 32 by 3. And then we're going to take the self-training labels, and we're going to pump those through our one-hot encoder we just made, and we're going to stack them together. And again, we're converting this into an array that goes from, instead of having horse equals 1, dog equals 2, and then horse plus dog would equal 3, which would be cat. No, it's going to be an array of 10 where each one is 0 to 1. Then we want to go ahead and set up our test images and labels. And when we're doing this, you're going to see it's the same thing we just did with the rest of them. We just changed colors right here. This is no different than what we were doing up here with our training set. We're going to stack the different images. We're going to get the length of them so we know how many images are in there. You certainly could add them by hand, but it's nice to let the computer do it, especially if it ever changes on the other end and you're using other data. And again, we reshape them and transpose them, and we also do the one-hot encoder. Same thing we just did on our training images. So now our test images are in the same format. So now we have a definition which sets up all our images in there. And then the next step is to go ahead and batch them, or next batch. And let's do another breakout here for batches, because this is really important to understand. It tends to throw me for a little loop when I'm working with TensorFlow or Keras or a lot of these. We have our data coming in. If you remember, we had like 10,000 photos. Let me just put 10,000 down here. We don't want to run all 10,000 at once, so we want to break this up into batch sizes. And you also remember that we had the number of photos, in this case length of test or whatever number is in there. We also have 32 by 32 by 3. So when we're looking at the batch size, we want to change this from 10,000 to a batch of, in this case, I think we're going to do batches of 100. So we want to look at just 100, the first 100 of the photos. And if you remember, we set self-I equal to 0. So what we're looking at here is we're going to create X. We're going to get the next batch from the very initialized. We've already initialized it for 0. So we're going to look at X from 0 to batch size, which we've set to 100. So just the first 100 images. And then we're going to reshape that into, and this is important to let the data know, that we're looking at 100 by 32 by 32 by 3. Now, we've already formatted it to the 32 by 32 by 3. This just sets everything up correctly so that X has the data in there in the correct order and the correct shape. And then the Y, just like the X, is our labels. So our training labels, again, they go from 0 to batch size. In this case, they do self-I plus batch size because the self-I is going to keep changing. And then finally, we increment the self-I because we have 0. So the next time we call it, we're going to get the next batch size. And so basically, we have X and Y. X being the photograph data coming in and Y being the label. And that, of course, is labeled through one hot encoder. So if you remember correctly, if it was, say, horse is equal to 0, it would be 1 for the 0 position, since this is the horse, and then everything else would be 0 in here. Let me just put lines through there. There we go. There's our array. Hard to see that array. So let's go ahead and take that, and we're going to finish loading it, since this is our class. And now we're armed with all this, our setup over here. Let's go ahead and load that up. And so we're going to create a variable ch with the CFAR helper in it. And then we're going to do ch.setupImages. Now we could have just put all of the setup images under the init, but by breaking this up into 2 parts, it makes it much more readable. And also, if you're doing other work, there's reasons to do that as far as the setup. Let's go ahead and run that. And you can see where it says setting up training images and labels, setting up test images. And that's one of the reasons we broke it up, is so that if you're testing this out, you can actually have print statements in there telling you what's going on, which is really nice. They did a good job with this setup. I like the way that it was broken up in the back. And then one quick note, you want to remember that batch, to set up the next batch, since we have to run batch equals ch next batch of 100, because we're going to use the 100 size. But we'll come back to that. We're going to use that. Just remember that that's part of our code we're going to be using in a minute from the definition we just made. So now we're ready to create our model. First thing we want to do is we want to import our TensorFlow as TF. I'll just go ahead and run that so it's loaded up. And you can see we got a warning here. That's because they're making some changes. It's always growing, and they're going to be depreciating one of the values from float64 to float type, or is treated as an NP float64. Nothing to really worry about, because this doesn't even affect what we're working on, because we've set all of our stuff to a 255 value, or 0 to 1. And do keep in mind that 0 to 1 value that we converted to 255 is still a float value, but it'll easily work with either the NumPy float64 or the NumPy D-type float. It doesn't matter which one it goes through, so the depreciation would not affect our code as we have it. And in our TensorFlow, we'll go ahead, let me just increase the size in there just a moment so you can get a better view of the what we're typing in. We're going to set a couple placeholders here. And so we're going to set x equals tf placeholder tf float32. We just talked about the float64 versus the NumPy float. We're actually just going to keep this at float32. More than significant number of decimals for what we're working with. And since it's a placeholder, we're going to set the shape equal to, and we've set it equal to none, because at this point we're just holding the place on there. We'll be setting up as we run the batches. That's what that first value is. And then 32 by 32 by 3, that's what we reshaped our data to fit in. And then we have our y true equals placeholder tf float 32, and the shape equals none, comma 10. 10 is the 10 different labels we have, so it's an array of 10. And then let's create one more placeholder. We'll call this hold prob, or hold probability. And we're going to use this. We don't have to have a shape or anything for this. This placeholder is for what we call dropout. If you remember from our theory before, we drop out so many nodes is looking at, or the different values going through, which helps decrease bias. So we need to go ahead and put a a placeholder for that also. And we'll run this. So it's all loaded up in there. So we have our 3 different placeholders. And since we're in TensorFlow, when you use Keras, it does some of this automatically, but we're in TensorFlow direct. Keras sits on TensorFlow. We're going to go ahead and create some more helper functions. We're going to create something to help us initialize the weights, initialize our bias. If you remember that each layer has to have a bias going in. We're going to go ahead and work on our convolutional 2D, our max pool. So we have our pooling layer, our convolutional layer, and then our normal full layer. So we're going to go ahead and put those all into definitions. And let's see what that looks like in code. And you can also grab some of these helper functions from the MNIST, the NIST setup. Let me just put that in there if you're under the TensorFlow. So a lot of these are already in there, but we're going to go ahead and do our own. And we're going to create our init weights. And one of the reasons we're doing this is so that you can actually start thinking about what's going on in the back end. So even though there's ways to do this with an automation, sometimes these have to be tweaked and you have to put in your own setup in here. Now we're not going to be doing that. We're just going to recreate them for our code. And let's take a look at this. We have our weights, and so what comes in is going to be the shape, and what comes out is going to be random numbers. So we're going to go ahead and just init some random numbers based on the shape with a standard deviation of 0.1. Kind of a fun way to do that. And then the TF variable, init random distribution. So we're just creating a random distribution on there. That's all that is for the weights. Now, you might change that. You might have a higher standard deviation. In some cases, you actually load preset weights. That's pretty rare. Usually you're testing that against another model or something like that, and you want to see how those weights configure with each other. Now remember, we have our bias, so we need to go ahead and initialize the bias with a constant. In this case, we're using 0.1. A lot of times the bias is just put in as 1, and then you have your weights to add on to that. But we're going to set this as 0.1. So we want to return a convolutional 2D, in this case a neural network. This is would be a layer on here. What's going on with the conv2D is we're taking our data coming in, we're going to filter it. Strides, if you remember correctly, strides came from, here's our image, and then we only look at this picture here, and then maybe we have a stride of 1, so we look at this picture here, and we continue to look at the different filters going on there. The other thing this does is that we have our data coming in as 32 by 32 by 3. And we want to change this so that it's just, this is 3 dimensions, and it's going to reformat this as just 2 dimensions. So it's going to take this number here and combine it with the 32 by 32. So this is a very important layer here because it's reducing our data down using different means. And it connects down, I'm just going to jump down one here. It goes with the convolutional layer. So you have your kind of your pre-formatting and the setup, and then you have your actual convolution layer that goes through on there. And you can see here we have init weights by the shape, init bias, shape of 3, because we have the 3 different, here's our 3 again. And then we return the TFNN ReLU with the convention 2D, so this convolutional has this feeding into it. Right there, it's using that as part of it, and of course the input is the XY plus B, the bias. So that's quite a mouthful, but these two are the keys here to creating the convolutional layers there. The convolutional 2D coming in, and then the convolutional layer, which then steps through and creates all those filters we saw. Then of course we have our pooling. So after each time we run it through the conventional layer, we want to pool the data. If you remember correctly on the pool side, and let me just get rid of all my marks, it's getting a little crazy there. And in fact, let's go ahead and jump back to that slide. Let's just take a look at that slide over here. So we have our image coming in. We create our convolutional layer with all the filters. Remember, the filters go, the filters coming in here, and it looks at these 4 boxes. And then if it's a step, let's say step 2, it then goes to these 4 boxes, and then the next step, and so on. So we have our convolutional layer that we generate, or convolutional layers. They use the ReLU function. There's other functions out there. For this, though, the ReLU is the the one that works the best, at least so far. I'm sure that will change. And then we have our pooling. Now, if you remember correctly, the pooling was max. So if we had the filter coming in, and they did the multiplication on there, and we have a 1, and maybe a 2 here, and another 1 here, and a 3 here, 3 is the max. And so out of all of these, you then create an array that would be 3, and if the max is over here 2, or whatever it is, that's what goes into the pooling, of what's going on in our pooling. So again, we're reducing that data down. We're reducing it down as small as we can, and then finally, we're going to flatten it out into a single array, and that goes into our fully connected layer. And you can see that here in the code. Right here we're going to create our normal full layer. So at some point we're going to take from our pooling layer, this will go into some kind of flattening process, and then that will be fed into the different layers going in down here. And so we have our input size. You'll see our input layer get shape, which is just going to get the shape for whatever's coming in. And then input size, initial weights is also based on the input layer coming in. And the input size down here is based on the input layer shape. So we're just going to already use the shape and already have our size coming in. And of course, you have to make sure you init the bias. Always put your bias on there. And we'll do that based on the size. So this will return tf.matmul input layer W plus B. This is just a normal full layer. That's what this means right down here. That's what we're going to return. So that was a lot of steps we went through. Let's go ahead and run that. So those are all loaded in there. And let's go ahead and create the layers. Let's see what that looks like. Now that we've done all the heavy lifting and everything, we get to do all the easy part. Let's go ahead and create our layers. We'll create a convolution layer 1 and 2 different convolutional layers, and then we'll take that and we'll flatten that out, create a reshape pooling in there for our reshape, and then we'll have our full layer at the end. So let's start by creating our first convolutional layer. Then we come in here, and let me just run that real quick. And I want you to notice on here the 3 and the 32. This is important because coming into this convolutional layer, we have 3 different channels and 32 pixels each. So that has to be in there. The 4 and 4 you can play with. This is your filter size. So if you remember, you have a filter and you have your image, and the filter slowly steps over and filters out this image depending on what your step is. For this particular setup, 4 is just fine. That should work pretty good for what we're doing and for the size of the image. And then of course at the end, once you have your convolutional layer set up, you also need to pool it, and you'll see that the pooling is automatically set up so that it would see the different shape based on what's coming in. So here we have max 2 by 2, and we put in the convolutional one that we just created, the convolutional layer we just created goes right back into it. And that right up here, as you can see, is the X. It's coming in from here, so notice to look at the first model and set the data accordingly. Set that up so it matches. And we went ahead and ran this already. I think I ran it. Let me go and run it again. And if we're going to do one layer, let's go ahead and do a second layer down here. And it's we'll call it Convo 2. It's also a convolutional layer on this. And you'll see that we're feeding convolutional 1 in, the pooling. So it goes from convolutional 1 into convolutional 1 pooling, from convolutional 1 pooling into convolutional 2, and then from convolutional 2 into convolutional 2 pooling. And we'll go ahead and take this and run this. So these variables are all loaded into memory. And for our flattened layer, let's go ahead and we'll do, since we have 64 coming out of here and we have 4 by 4 going in, let's do 8 by 8 by 64. So let's do 4096. This is going to be the flat layer. So that's how many bits are coming through on the flat layer. And we'll reshape this. So we'll reshape our Convo 2 pooling, and that will feed into here, the Convo 2 pooling. And then we're going to set it up as a single layer that's 4096 in size. That's what that means there. We'll go ahead and run this. So we've now created this variable, the Convo 2 flat. And then we have our first full layer. This is the final neural network where we have the flat layer going in. And we're going to again use the ReLU for our setup on there in a neural network for evaluation. And you'll notice that we're going to create our first full layer. Our normal full layer, that's our definition. So we created that. That's creating the normal full layer. And our input for the data comes right here from this goes right into it. The Convo 2 flat. So this tells it how big the data is. And we're going to have it come out. It's going to have 1024. That's how big the layer is coming out. We'll go ahead and run this. So now we have our full layer 1. And with the full layer 1, we want to also define the full 1 dropout to go with that. So our full layer 1 comes in, keep probability equals hold probability. Remember we created that earlier. And the full layer 1 is what's coming into it. And this is going backwards and training the data. We're not training every weight. We're only training a percentage of them each time, which helps get rid of the bias. So let me go ahead and run that. And finally, we'll go ahead and create a Y-predict, which is going to equal the normal full 1 dropout and 10 because we have 10 labels in there. Now, in this neural network, we could have added additional layers. That would be another option to play with. You can also play with, instead of 1024, you can use other numbers for the way that sets up on what's coming out and going into the next one. We're only going to do just the 1 layer and the 1 layer dropout. And you can see if we did another layer, it'd be real easy just to feed in the full 1 dropout into full layer 2. And then full layer 2 dropout would have full layer 2 feed into it. And then you'd switch that here for the Y prediction. For right now, this is great. This particular data set is tried and true, and we know that this will work on it. And if we just type in Y predict and we run that, we'll see that this is a tensor object, shape $10, D-type 32. A quick way to double check what we're working on. So now we've got all of our, we've done a setup all the way to the Y predict, which we just did. We want to go ahead and apply the loss function and make sure that's set up in there. Create the optimizer. And then train our optimizer and create a variable to initialize all the global TF variables. So before we dive into the loss function, let me point out one quick thing, or just kind of a rehab over a couple things. And that is, when we're playing with these setups, we pointed out up here we can change the 4-4 and use different numbers there. They change your outcome. So depending on what numbers you use here will have a huge impact on how well your model fits. And that's the same here with the 1024 also. This is also another number that if you continue to raise that number, you'll get possibly a better fit. You might overfit. And if you lower that number, you'll use less resources. And generally, you want to use this in the exponential growth. An exponential being 2, 4, 8, 16. And in this case, the next one down would be 5, 12. You can use any number there, but those would be the ideal numbers when you look at this data. So the next step in all this is we need to also create a way of tracking how good our model is. And we're going to call this a loss function. And so we're going to create a cross-entropy loss function. And so before we discuss exactly what that is, let's take a look and see what we're feeding it. We're going to feed it our labels, and we have our true labels and our prediction labels. So coming in here is the two different variables we're sending in, or the two different probability distributions, is one that we know is true and what we think it's going to be. Now this function right here, when they talk about cross-entropy, in information theory, the cross-entropy between two probability distributions over the same underlying set of events measures the average number of bits needed to identify an event drawn from the set. That's a mouthful. Really, we're just looking at the amount of error in here. How many of these are correct and how many of these are incorrect? So how much of it matches? And we're going to look at that. We're just going to look at the average. That's what the reduced to the mean means here. So we're looking at the average error on this. And so the next step is we're going to take the error. We want to know our cross entropy, or our loss function, how much loss we have. That's going to be part of how we train the model. So when you know what the loss is and we're training it, you feed that back into the back propagation setup. And so we want to go ahead and optimize that. Here's our optimizer. We're going to create the optimizer using an atom optimizer. Remember, there's a lot of different ways of optimizing the data. Atom's the most popular used. So our optimizer is going to equal the TF train atom optimizer. If you don't remember what the learning rate is, let me just pop this back into here. Here's our learning rate. When you have your weights, you have all your weights in your different nodes that are coming out. Here's our node coming out, and it has all its weights. And then the error is being sent back through in reverse on our neural network. So we take this error and we adjust these weights based on the different formulas. In this case, the atom formula is what we're using. We don't want to just adjust them completely. We don't want to change this weight so it exactly fits the data coming through. Because if we made that kind of adjustment, it's going to be biased to whatever the last data we sent through is. Instead, we're going to multiply that by 0.001 and make a very small shift in this weight. So our delta W is only 0.001 of the actual delta W of the full change we're going to compute from the atom. And then we want to go ahead and train it. So our training, or set up a training variable or function. And this is going to equal our optimizer minimize cross entropy. And we make sure we go ahead and run this. So it's loaded in there. And then we're almost ready to train our model. But before we do that, we need to create one more variable in here, and we're going to create a variable to initialize all the global TF variables. And when we look at this, the TF global variable initializer, this is a TensorFlow object. It goes through there and it looks at all our different setup that we have going under our TensorFlow, and then initializes those variables. So it's kind of like a magic wand because it's all hidden in the back end of TensorFlow. All you need to know about this is that you have to have the initialization on there, which is an operation, and you have to run that once you have your setup going. So we'll go ahead and run this piece of code, and then we're going to go ahead and train our data. So let me run this so it's loaded up there. And so now we're going to go ahead and run the model by creating a graph session. Graph session is a TensorFlow term. So you'll see that coming up. It's one of the things that throws me because I always think of GraphX and Spark and Graph as just general graphing. But they talk about a graph session. So we're going to go ahead and run the model. And let's go ahead and walk through this, what's going on here. And let's paste this data in here. And here we go. So we're going to start off with a TF session as ses. So that's our actual TF session that we've created. So we're right here with the TF session. Our session we're creating, we're going to run TF global variable initializer. So right off the bat, we're initializing our variables here. And then we have for I in range 500. So what's going on here, remember 500, we're going to break the data up and we're going to batch it in at 500 points each. We've created our session run. So we're going to do with TF session as session right here. We've created our variable session. And then we're going to run and we're going to go ahead and initialize it. So we have our TF global variables initializer that we created. That initializes our session in here. The next thing we're going to do is we're going to go for I in range of 500, batch equals ch.next batch. So if you remember correctly, this is loading up 100 pictures at a time. And this is going to loop through that 500 times. So we are literally doing, 500 times 100 is 50,000. So that's 50,000 pictures we're going to process right there. And the first process is we're going to do a session run. We're going to take our train. We created our train variable or optimizer in there. We're going to feed it the dictionary. We had our feed dictionary that we created. And we have x equals batch 0 coming in, y true, batch 1, hold the probability, 0.5. And then just so that we can keep track of what's going on, we're going to, every 100 steps, we're going to run a print. So currently on step, format, accuracy is, and we're going to look at matches equals tf argument y prediction 1, tf.arg max y true, comma 1. So we're going to look at this as how many matches it has. And here our ACC, all we're doing here is we're going to take the matches, how many matches they have, it generates a chart. We're going to convert that to float. That's what the TF cast does. And then we just want to know the average. We just want to know the average of the accuracy. And then we'll go ahead and print that out, print session run accuracy feed dictionary. So it takes all this and it prints out our accuracy on there. So let's go ahead and take this. Oops, flip screens there. Let's go ahead and take this and let's run it. And this is going to take a little bit to run. So let's see what happens on my old laptop. And we'll see here that we have our current, we're currently on step 0. It takes a little bit to get through the accuracy. And this will take just a moment to run. We can see that on our step 0, it has an accuracy of 0.1 or 0.1028. And as it's running, we'll go ahead, you don't need to watch it run all the way, but this accuracy is going to change a little bit up and down. So we've actually lost some accuracy during our step 2. But we'll see how that comes out. Let's come back after we run it all the way through and see how the different steps come out. I was actually reading that backwards. The way this works is the closer we get to 1, the more accuracy we have. So you can see here we've gone from a 0.1 to a 0.39, and we'll go ahead and pause this and come back and see what happens when we're done with the full run. Alright, now that we've prepared the meal, got it in the oven, and pulled out my finished dish here, if you've ever watched any of the old cooking shows, let's discuss a little bit about this accuracy going on here, and how do you interpret that? We've done a couple things. first, we've defined accuracy. The reason I got it backwards before is you have loss or accuracy. And with loss, you'll get a graph that looks like this. It goes, oops, that's an S, by the way. There we go. You get a graph that curves down like this. And with accuracy, you get a graph that curves up. This is how good it's doing. Now, in this case, 1 is supposed to be really good accuracy. That means it gets close to 1, but it never crosses 1. So if you have an accuracy of 1, that is phenomenal. In fact, that's pretty much unheard of. And the same thing with loss. If you have a loss of 0, that's also unheard of. And the 0 is actually on this axis right here as we go in there. So how do we interpret that? Because, if I was looking at this and I go, oh, 0.51, that's 51%. You're doing 50-50. No, this is not percentage. Let me just put that in there. It is not percentage. This is logarithmic. What that means is that 0.2 is twice as good as 0.1. And when we see 0.4, that's twice as good as 0.2. Real way to convert this into a percentage. You really can't say this is a direct percentage conversion. What you can do, though, is in your head, if we were to give this a percentage, we might look at this as 50%, we're just guessing, equals 0.1. And if 50% roughly equals 0.1, that's where we started up here at the top. Remember at the top here, here's our 0.1028. The accuracy of 50%, then 75% is about 0.2, and so on and so on. Don't quote those numbers because that doesn't work that way. They say that if you have 0.95, that's pretty much saying 100%. And if you have anywhere between, you'd have to go look this up. Let me go ahead and remove all my drawings there. So the magic number is 0.5. We really want to be over a 0.5 in this whole thing. And we have both 0.5004. Remember, this is accuracy. If we were looking at loss, then we would be looking the other way. But 0.0, instead of how high it is, we want how low it is. But with accuracy, being over a 0.5 is pretty valid. That means this is pretty solid. And if you get to a 0.95, then it's a direct correlation. That's what we're looking for here in these numbers. You can see we finished with this model at 0.5135, so still good. And if we look at when they ran this in the other end, remember there's a lot of randomness that goes into it when we see the weights. They got 0.5251, so a little better than ours. But that's fine. You'll find your own comes up a little bit better or worse depending on just that randomness. And so we've gone through the whole model. We've trained the model, and we've also gone through on every 100th run to test the model to see how accurate it is.
Deep learning is a subset of machine learning, which itself is a branch of artificial intelligence. Unlike traditional machine learning models, which require manual feature extraction, deep learning models automatically discovers representation from raw data. So this is made possible through neural networks, particularly deep neural networks, which consist of multiple layers of interconnected nodes. So these neural networks are inspired by the structure and the function of human brain. Each layer in the network transforms the input data into more abstract and composite representation. For instance, in image recognition, the initial layer might detect simple features like edges and textures, while the deeper layer recognizes more complex structure like shapes and objects. So one of the key advantages of deep learning is its ability to handle large amount of unstructured data, such as images, audios, and text, making it extremely powerful for various applications. So stay tuned as we delve deeper into how these neural networks are trained, the types of deep learning models, and some exciting applications that are shaping our future. Types of deep learning. Deep learning AI can be applied supervised, unsupervised, and reinforcement machine learning, using various methods for each. The first one, supervised machine learning. In supervised learning, the neural network learns to make prediction or classify that data using labeled datasets. Both input features and target variables are provided, and the network learns by minimizing the error between its prediction and the actual targets. A process called backpropagation. CNN and RNN are the common deep learning algorithms used for tasks like image classification, sentiment analysis, and language translation. The second one, unsupervised machine learning. In unsupervised machine learning, the neural network discovers patterns or clusters in unlabeled datasets without target variables. It identifies hidden pattern or relationship within the data. Algorithms like autoencoders and generative models are used for tasks such as clustering, dimensionality reduction, and anomaly detection. The third one, reinforcement machine learning. In this, an agent learns to make decisions in an environment to maximize a reward signal. The agent takes action, observes the records, and learns policies to maximize cumulative rewards over time. Deep reinforcement learning algorithms like deep Q networks and deep deterministic polygradient are used for tasks such as robotics and gameplay. Moving forward, let's see what are the artificial neural networks. Artificial neural networks, ANNs, inspired by the structure and the function of human neurons, consist of interconnected layers of artificial neurals or units. The input layer receives data from the external resources and it passes to one or more hidden layers. Each neuron in these layers computes a weighted sum of inputs and transfers the result to the next layer. During training, the weight of these connections are adjusted to optimize the network's performance. A fully connected artificial neural network includes an input layer or more hidden layers and an output layer. Each neuron in a hidden layer receives input from the previous layer and sends its output to the next layer. So this process continues until the final output layer produces a network response. So moving forward, let's see types of neural networks. So deep learning models can automatically learn features from data, making them ideal to tasks like image recognition, speech recognition, and natural language processing. So the most common architecture in deep learnings are the first one, feed-forward neural network, FNNs. So these are the simplest type of neural network where information flows linearly from the input to the output. They are widely used for tasks such as image classification, speech recognition, and natural language processing, NLP. The second one, convolutional neural network, designed specifically for image and video recognition. CNNs automatically learn features from images, making them ideal for image classification, object detection, and image segmentation. The third one, recurrent neural networks, RNNs, are specialized for processing sequential data time series and natural language. They maintain an internal state to capture information from previous input, making them suitable for tasks such as speech recognition, NLP, and language translation. So now let's move forward and see some deep learning application. The first one is autonomous vehicle. Deep learning is changing the development of self-driving car. Algorithms like CNNs process data from sensors and cameras to detect objects, recognize traffic signs, and make driving decisions in real time, enhancing safety and efficiency on the road. The second one is healthcare diagnostic. Deep learning models are being used to analyze medical images such as X-rays, MRIs, and CT scans with high accuracy. They help in early detection and diagnosis of diseases like cancer, improving treatment outcomes and saving lives. The third one is NLP. Recent advancement in NLP powered by deep learning models like Transformer, ChatGPT have led to more sophisticated and human-like text generation, translation, and sentiment analysis. So applications include virtual assistant, chatbots, and automated customer service. The fourth one, deepfake technology. So deep learning techniques are used to create highly realistic synthetic media known as deepfakes. While this technology has entertainment and creative application, it also raises ethical concern regarding misinformation and digital manipulation. The fifth one, predictive maintenance. In industries like manufacturing and aviation, deep learning models predict equipment failures before they occur by analyzing sensor data. Their proactive approach reduces downtime, lowers maintenance costs, and improves operational efficiency. So now let's move forward and see some advantages and disadvantages of deep learning. So first one is high computational requirements. So deep learning requires significant data and computational resources for training, whereas advantage is high accuracy, achieves state-of-the-art performance in tasks like image recognition and natural language processing. Whereas deep learning needs large labeled datasets, often require extensive labeled dataset for training, which can be costly and time-consuming together. So second advantage of deep learning is automated feature engineering. Automatically discovers and learns relevant features from data without manual intervention. The third disadvantage is overfitting. So deep learning can overfit to training data, leading to poor performance on new unseen data. Whereas the third deep learning advantage is scalability. So deep learning can handle large complex dataset and learn from massive amount of data. So in conclusion, deep learning is a transformative leap in AI, mimicking human neural networks. It has changed healthcare, finance, autonomous vehicles, and NLP.
I'm going to show you how to create highly realistic digital clone of anyone using Hygiene. This tool is an incredible way to generate lifelike avatars and unlock endless creative possibilities for content creators, businesses, and anyone looking to produce realistic digital representation. So whether you want to create training videos, personalize content, or even bring someone's likeness into your project, this tutorial will walk you through the process step by step. So guys, watch this video till the end if you want to learn more about it. But before we move on, let us first understand what exactly is digital clone. A digital clone is essentially a digital version of a person that mimics their appearance or voice and even behaviors. These clones can be used for a wide variety of purposes, from creating virtual assistant avatars for training videos or personalized messages, to even crafting content for marketing campaigns. The key is that these clones are powered by artificial intelligence, which allows them to mimic the unique trait and characteristics of a real person. Digital clones are created by combining video footage, voice recording, advanced machine learning techniques to produce digital representation that can speak, move, and interact just like the original person. And with tools like HeyGen, this process has become much more easier and accessible. So you can see I'm at the official website of HeyGen. Okay, you can access this website if you go all over here, type HeyGen, and you can also go with type HeyGen digital clone. It will redirect you all over here. Clone yourself AI. So this is the official website. Now the next step is you have to sign up. So you can see all over here there's an option sign up for free. Just click on this. Now there will be various plans that will be there for you. Like for example, there would be the free version where you don't have to pay anything. Then you have the creator plan. Okay. Once you have signed up, it is going to show you the given plan. So first one is the free version. You can try this plan if you are beginner and want to learn about this tool. For most of the users, they can go with the creator plan. You can create up to 5 minutes video long. You can export it at, and you have also amazing features like utilizing language translation. Then you have team, where minimum 2 seats are there, and you could see it is billed $720 yearly. There are unlimited videos. You can create videos up to 30 minutes, 4K video export, faster video processing, and there is 5 minutes of avatar 4 videos per month. So these are the things. And for larger scale projects, you can also go with the enterprise level plan. It has additional features and scalability options. Now, once you have chosen your plan, you are ready to go. The next step is creating the avatar. So let us click on the free plan, and let's say I'm creating my personal project. Let's right click. You can just click content creator. Let's say we are creating a marketing video. Okay. Now, all over here, we have to create our avatar. So let's try avatar 4. Let's see what it has.
Avatar 4 allows you to turn a...
Now, you can try any sample photo all over here. So you can click on this and you can create an avatar. So like I have selected this avatar, and you could write your script all over here, or you could upload or record audio also. So let's take the help of ChatGPT to create a script. Okay. So let's ask GPT. Okay. So guys, I've taken the help of ChatGPT and I have instantly added a script all over here. Now, let's say custom motion also. So for custom motion, you can again take the help of ChatGPT. Let's ask add. Okay. Now, what I've done is I have taken the help of ChatGPT, and also I have added in the custom motion also to give much more idea like how my avatar is going to do. Now you could choose the given resolution. Let's say it's 180p, and we cannot do that since I'm on a free tier. So go with the 720p and let's click on generating the video. So guys, for the best result, you can select the motion option. This allows you to actually give much more description about the motion of your avatar. Now, make sure the avatar you are using is well lit, centered, and expressive. This will help make avatar appear more natural and lifelike. The more natural the expression, the better the final avatar will look. Now, the third step, we have to record and train. Now, it's time to actually record your subject. The footage does not need to be shot in a professional studio setting. It could be done at home, outdoors, or in any well-lit environment. The key here is to make sure subject speaks clearly and directly into the camera. But for this instance, we are actually using the avatar which is already given by Hagen. Okay, but for the other purpose, if you are creating your own avatar, and also make sure that there is pause between sentences when you are creating a video. For example, you could say something like, hello, my name is your name, and today we are going to show you how to create a digital clone. So add some brief pauses between the sentence, because this is going to help Hagen process the footage more effectively and gives the avatar more human-like cadence. Now let's see how video is created. Let's look into this. Let's select the portrait version. So guys, initially we added this script for our digital clone and we selected this random image and we have given certain script. Now we have used the motion feature of Hagen and let us see how this comes out.
Hey there, I'm your digital assistant, here to show you how our amazing software is revolutionizing the way you edit photos, videos, and more, all powered by cutting-edge AI.
Wow, it sounds so amazing. Just looks like, repeat, it just looks like a real person. For somewhat, it's still recognizable that it's an AI clone, but you can create your own avatars like that. So for section of creating your own avatar, what you need to do is just go all over here, click on create new avatar. Then you could either go with hyper realistic avatar or custom photo, or you could click on generate. So let us try this feature. Let's say name is me and gender is man. So let's take a prompt from ChatGPT. So we could add up all over here and let's select till personality only and paste this. Okay, delete the behavior part and let us try to see the preview, how our avatar looks like based on our text prompts. Now, it has already generated certain a photo for our avatar. Let's select this, click on save. And in this way, you could generate an avatar also by giving the description. So this is a very amazing tool, guys. There's a lot of things you could do all over here. Now you could see you can also add a voice. So let's add this voice, okay? And let us try to see this. And now there is also option to train this model, but this will take some time and also certain credits. Now, if you're someone who is a content creator or you're creating tutorial videos, then this tool, you must check it out. And you can buy the creator plan. That is the most ideal plan for most of the users. And then you could access all these features. So this is our photo. Let us see how our avatar looks like. So now here you could upload the audio also, or you could add a script, and it will take certain time. So let us ask ChatGPT for the same. Now, after this, what you need to do is just add the given script. Okay, you can add the script all over here. Let's say, let's add the name. And after this, just click on generate. And let's say, now just add the title and click on submit. It is going to take some time to generate the video. Let us see. Okay, so it's still in line for processing. It might take some time. But apart from that, there is also amazing feature for brand. You could do the branding kit also. So let us explore a bit. So you could see, you could create your own branding logos, or you could create your product images with the help of this tool. Very amazing tool. And it also has amazing integration, like it has HubSpot integration, Adobe Express plugin, Canva app, ChatGPT plugin, and there's a lot of other applications through which this tool can be integrated. And this is Labs. Labs is also a new feature. So someone who is into podcasting, you could also try this amazing feature. Now URL to video is also there. Amazing features like instant highlights, interactive avatar. So as you can see all over here, the video is still in the processing line and you don't have to wait for this. What you can do is you can explore this platform and create your own avatar. And that's it guys. We have successfully created our one avatar today using Hygiene. This technology is still evolving, and as it improves, we can expect more lifelike and interactive avatars. Hygiene has incredible potential. Whether you are creating personalized video messages, training content, or just exploring new ways to express yourself digitally, digital clones have potential to revolutionize the way we create content and communicate. Imagine the possibilities: personalized customer support bots, training videos where presenter is always available, virtual brand ambassadors, or even educational tools that feature instructors who can be physically present.
LLM benchmarks, tools used to test and measure how well large language models like GPT and Google Gemini performs. If you have ever wondered how AI models are evaluated, this video will explain it in simple terms. LLM benchmarks are used to check how good these models are at tasks like coding, answering questions, and translating languages or summarizing text. These tests use sample data and specific measurement to see how well the model performs. For example, the model might be tested with a few examples, like few short learning, or none at all, like zero short learning, to see how it handles new tasks. So now the question arises, why are these benchmarks important? They help developers understand where a model is strong and where it needs improvement. They also make it easier to compare different models, helping people choose the best one for their needs. However, LLM benchmarks do have some limits. They don't always predict how well a model will work in real-world situations, and sometimes model can overfit, meaning they perform well on test data but struggle in practical use. We will also cover how LLM leaderboards rank different models based on their benchmark scores, giving us a clear picture of which models are performing the best. So stay tuned as we dive into how LLM benchmarks work and why they are so important for advancing AI.
Craving a career upgrade? Subscribe, like, and comment below. Dive into the link in the description to fast-track your ambitions. Whether you're making a switch or aiming higher, Simplilearn has your back.
But before we start, here is a quick info for you. Dive into the future of AI with our Generative AI and Machine Learning course in collaboration with ENICT Academy, IIT Guwahati. Learn tools like ChatGPT, OpenAI, Hugging Face, Python, and more. Join masterclass led by IIT Guwahati faculty, engage in hands-on projects, and earn executive alumni status. This Generative AI and Machine Learning course enriches your career journey with comprehensive coverage of machine learning, deep learning, NLP, generative AI, reinforcement learning, computer vision, and many more. So don't forget to find the course link from the description box below and the pinned comment. So without any further ado, let's get started. So what are LLM benchmarks? LLM benchmarks are standardized tools used to evaluate the performance of large language models. They provide a structured way to test LLMs on a specific task or question, using sample data and predefined metrics to measure their capabilities. These benchmarks assess various skills such as coding, common sense reasoning, and NLP tasks like machine translation, question answering, and text summarization. The importance of LLM benchmark lies in their role in advancing model development. They track the progress of an LLM, offering quantitative insights into where the model performs well and where improvement is needed. This feedback is crucial for guiding the fine-tuning process, allowing researchers and developers to enhance model performance. Additionally, benchmarks offers an objective comparison between different LLMs, helping developers and organizations choose the best model for their needs. So how LLM benchmarks work? LLM benchmarks follow a clear and systematic process. They present a task for LLM to complete, evaluate its performance using specific metrics, and assign a score based on how well the model performs. So here is a breakdown of how this process works. The first one is setup. LLM benchmark come with pre-prepared sample data, including coding challenges, long documents, math problems, and real-world conversation. The task span various areas like common sense reasoning, problem solving, question answering, summary generation, and translation, all present to the model at the start of testing. The second step is testing. The model is tested on one of the three ways. Few shot, the LLM is provided with a few examples before being prompted to complete a task, demonstrating its ability to learn from limited data. The second one is zero shot. The model is asked to perform a task without any prior examples, testing its ability to understand new concepts and adapt to unfamiliar scenarios. The third one is fine-tune. The model is trained on a dataset similar to the one used in the benchmark, aiming to enhance its performance on the specific task involved. The third step is scoring. So after completing the task, the benchmark compares the model's output with the expected answer and generates a score, typically ranging from 0 to 100, reflecting how accurately the LLM performed. So now moving forward, let's see key metrics for benchmarking LLMs. So LLM's benchmark uses various metrics to assess the performance of large language model. So here are some commonly used metrics. The first one is accuracy or precision. Measure the percentage of correct prediction made by the model. The second one is recall, also known as sensitivity. Measure the number of true positive reflecting the correct prediction made by the model. The third one is F1 score. Combines both accuracy and recall into a single metric, weighing them equally to address any false positive or negatives. F1 score ranging from 0 to 1, where 1 indicates perfect precision and recall. The fourth one is exact match. Tracks the percentage of predictions that exactly match the correct answer, which is especially used for the tasks like translation and question answering. The fifth one is perplexity gauges. Here it will tell you how well a model predicts the next word or token. A lower perplexity score indicates better task comprehension by the model. The sixth one is BLUE, bilingual evaluation understudy. Is used for evaluating machine translation by comparing n-grams, sequence of adjacent text element, between the model's output and the human produced translation. So these quantitative metrics are often combined for more through evaluation. So in addition, human evaluation introduces qualitatively factors like coherence, relevance, and semantic meaning, provide a nuanced assessment. However, human evaluation can be time-consuming and subjective, making a balance between quantitative and qualitative measures important for comprehensive evaluation. So now let's moving forward see some limitation of LLM benchmarking. While LLM benchmarking are valuable for assessing model performance, they have several limitations that prevents them from the fully predicting real-world effectiveness. So here are some few. The first one is bounded scoring. Once a model achieves the highest possible scores on the benchmark, that benchmark loses its utility and must be updated with more challenging tasks to remain a meaningful assessment tool. The second one is broad dataset. LLM benchmark often rely on sample data from diverse subjects and tasks. So this wide scope may not effectively evaluate a model's performance in edge cases, specialized fields, or specific use cases where more tailored data would be needed. The third one is finite assessment. Benchmark only tests a model's current skills, and as LLMs evolve and new capabilities emerge, new benchmarks must be created to measure these advancements. The fourth one is overfitting. So if an LLM is trained on the same data used for benchmarking, it can be lead to overfitting, where the model performs well on the test data but struggles with the real task. So this result is scores that don't truly represent the model's broader capabilities. So now what are LLM leaderboards? So LLM leaderboards publish a ranking of LLMs based on the variety of benchmarks. Leaderboards provide a way to keep track to the myriad LLMs and compare their performance. LLM leaderboards are especially beneficial in making decisions on which models to use. So here are some. So in this you can see here OpenAI is leading and GPT-4o second and the Lama third with 405 parameter B and 3.5 Sonnet is there. So this is best in multitask reasoning. What about the best in coding? So here OpenAI O1 is leading. I guess this is the Orion one, and the second one is 3.5 Sonnet, and after that in the third position there is GPT-4o. So this is in best in coding. So next comes fastest and most affordable models. So fastest models are Lama 8B parameter, and the second one is LLAMA Lama 70B. And the third one is 1.5 Flash. This is Gemini 1. And lowest latency. And here it is leading Lama again. In cheapest models, again Lama 8B is leading. And in the second number, we have Gemini Flash 1.5. And in third, we have GPT-4o Mini. Moving forward, let's see standard benchmarks between Claude 3 Opus and GPT-4. So in general, they are equal. In reasoning, Claude 3 Opus is leading. And in coding, GPT-4 is leading. In math, again GPT-4o is leading. In tool use, Claude 3 Opus is leading. And in multilingual, Claude 3 Opus is leading.
Think about this. You're about to create something amazing. An AI that can think, learn, and grow in ways we only dreamed of. And here's the best part. You don't need to be an AI expert to make it happen. What if you could use Langchain, a tool that connects most advanced language models to real-time data, allowing you to build AI applications that are both smart and flexible? It sounds like something out of science fiction, but with Langchain, it's real. As large language models quickly become the backbone of many applications, Langchain has emerged as a game-changing tool, transforming the way we use these powerful technologies. Today, we are diving into Langchain, the ultimate framework that makes AI development easier for everyone. Whether you want to understand user questions with one LLM, create human-like responses with another, or pull in data insights, Langchain makes it all happen. But Langchain is more than just making AI easy to use. It's about getting these models to work together seamlessly. Langchain simplifies what could be a complex process into a simple, powerful system. From smart chatbots to enhancing data for machine learning, the possibilities with Langchain are endless. So why has Langchain become one of the fastest growing open source projects ever? And how you can use Langchain to get ahead in the world of AI. So let's first start by understanding what is Langchain. Langchain is an open source framework designed to help developers build AI-powered applications using large language models or LLMs, just like GPT-4. But what really sets Langchain apart is its ability to link these powerful models with external data sources and other components. So this allows you to create sophisticated natural language processing NLP applications that can do much more than just understand and generate text. They can interact with live data, databases, and other software tools. Now you might be asking, is Langchain a Python library? Yes, it is. Langchain is available as a Python library, which means you can easily integrate into your existing Python projects. But it doesn't stop there. Langchain is also available in JavaScript and TypeScript, making it accessible to a wide range of developers. Whether you're working on a web app or backend system or a standalone tool, Langchain fits right in. So why should we use Langchain? So why is Langchain such a big deal? Developing AI applications typically requires using multiple tools and writing a lot of complex code. You need to manage data retrieval, processing, integration with language models, and many more. This can be time-consuming and complicated, especially if you're not deeply familiar with AI. Langchain simplifies the entire process, allowing you to develop and deploy and even manage AI applications more easily and efficiently. Let's break down this with an example. Imagine you're building a chatbot that needs to provide real-time weather updates. Without Langchain, you would need to manually connect your AI to a weather API, fetch data, process it, and then format the response. But with Langchain, the process becomes much more straightforward. You can focus on what matters the most, building the features and functionalities of your application, while Langchain handles the complex integrations behind the scenes. So let's discuss the key features of Langchain. Langchain is packed with features that make it incredibly powerful and flexible. Let's take a closer look at some of the key components. At first, we have model interaction. Langchain allows you to interact with any language model seamlessly. It manages the inputs and outputs to these data models, ensuring that you can integrate them into your application without a hitch. For example, if you want to use GPT-4 to generate responses to customer inquiries, Langchain makes it easy to plug that model into your workflow. Next, we have data connection and retrieval. One of the Langchain strengths is its ability to connect to external data sources. So whether you need to pull data from a database or web API or even a file system, Langchain simplifies this process. You can retrieve, transform, and use data from almost any source, making your AI applications more robust and versatile. Next, we have chains. Langchain introduces the concept of chains, where you can link multiple models and components together to perform complex tasks. For example, you might have a chain where one component retrieves data and another processes it, and a third generates a human-like response. This chaining ability allows you to build workflows that would otherwise require extensive coding. Next, we have agents. Agents are like the decision makers in Langchain. They can create commands deciding the best course of action based on the input they receive. For example, an agent Claude determines which language model to use based on the type of query it's handling, making your application smarter and more adaptive. Then we have memory. Langchain supports both short-term and long-term memory, making that your AI can remember past interactions. This is particularly useful for applications like chatbots, where maintaining context over multiple interactions are significantly improve the user experience. Imagine you're building a virtual assistant. The assistant needs to remember previous interactions to provide relevant responses. Now, with the help of Langchain, you can easily implement memory so that the assistant knows what you have talked before, making the conversation more natural and engaging. So, what are the integrations supported by Langchain? Well, Langchain is designed to work seamlessly with a wide variety of integrations, making it extremely versatile for different use cases. LLM providers. Langchain supports integration with major LLM providers like OpenAI, Hugging Face, and Cohort. This means you can easily incorporate the latest and most powerful language models into your applications. Then we have data sources. Langchain can connect to a variety of data sources such as Google Search, Wikipedia, and cloud platforms like AWS, Google Cloud, and Azure. This makes it easy to retrieve and use the most up-to-date information in your applications. Vector databases are used for handling large volumes of complex data such as images or long text. So Langchain integrates with vector databases like Pinecone, and these databases store data as high-dimensional vectors, which helps in allowing for efficient and accurate retrieval. So this is particularly useful for applications that require searching through large data sets quickly. For example, let's say you're building an application that needs to analyze thousands of documents to find relevant information. With Langchain, you can integrate a vector database like Pinecone, store your documents as vectors, and quickly search through using them powerful language models. This capability can save you a lot of time and make your application much more effective. Now the question arises how to create prompts in Langchain. Creating prompts in Langchain is much easier with something called a prompt template. A prompt template acts as a set of instructions for language model, and these templates can be customized to varying levels of customizations. For example, you might design a prompt template to ask simple questions, or you could create more detailed instructions that guide the language model to produce high-quality responses. Let's walk through how you can create a prompt using Langchain in Python. Step 1 is installing Langchain. First, you'll need to have Python installed in your system. Once that's set up, you can install Langchain by opening your Python shell or terminal and running the following command: pip install Langchain. The next step is adding integrations to Langchain. This often requires at least one integration to function properly. A common choice is OpenAI's Language Model API. To use OpenAI's API, you'll need to create an account on the OpenAI website and obtain your API key. After that, install OpenAI's Python package and input your API key like this. So this is the following command which is inserted below. You can look into that. Next step is importing and using a prompt template. Now that you have Langchain and the necessary integration set up, you can start creating your prompts. Langchain offers a pre-made prompt template that allows you to structure your text in a way that the language model can easily understand. Here's how you can do it through this particular prompt given below. So in this example, the prompt template asks two variables, which is an adjective and a content subject, and uses them to generate a prompt. The output might be something like, tell me an interesting fact about zebras. The language model would then take this prompt and return a relevant fact about zebras based on the given adjective. This is a simple but powerful way to generate dynamic prompt that can be adapted to a wide range of tasks, from answering questions to generating creative content. Let's now talk about how to develop applications with Langchain. So building applications with Langchain is straightforward and involves a few key steps. First, define your application, know exactly what problem it's solving, and identify the necessary components like language models, data sources, and user interaction. The next step is to build the functionality using Langchain's components such as prompt, chains, and agents. This is where you can create the logic that drives your application, like processing user input or retrieving data. Then we have customizing your application to meet specific needs. Langchain's flexibility allows you to tweak prompts, integrate additional data sources, and fine-tune models for optimal performance. Before going live, it's crucial to test and deploy your application. Testing helps catch any issues, and Langchain makes debugging easy, so you can deploy your application with confidence. For example, let's build a chatbot using Langchain. First, we have to define it is a chatbot that answers questions about technology trends. We then create a functionality by setting a prompt and a chain to process input. Next, we have customization. We customize it by integrating a new API to pull in the latest information. And finally, we test and deploy the chatbot to ensure it responds accurately to users. So Langchain offers endless possibilities across various industries. Let's now look into the examples and use cases of Langchain. Langchain offers endless possibilities across various industries. You can create customer service chatbots that manage queries and transaction or coding assistants that suggest code snippets and debug issues. In healthcare, Langchain can assist doctors with diagnosis and patient data management. Then we have marketing and e-commerce. It can analyze consumer behavior, generate product recommendations, and craft compelling product descriptions. So with the help of this AI assistant, it helps doctors make quicker, more informed decisions. So Langchain is a powerful framework that makes AI development accessible and efficient. Did you know that you can easily build a website for free using AI? And that's not a trick. It's completely true. Thanks to the amazing new AI tools, anyone can create a website even without writing a single line of code. Even if you have no technical experience, you can set up a professional website quickly and easily. In this video, I'm going to show you how you can build a website without even writing a single line of code, using the power of AI and no-code tools. In today's video, we have split this video into two parts to make it more simple and easy to follow. So whether you are a complete beginner or a business owner or even a student, this is something anyone can do. In the first part, I'll guide you through how to build a website using Pantheon and WordPress. You don't need any coding skills for this. Plus, we will use Gravity Write, an AI tool that helps you generate content for your website, like About Us page or blog post. AI will take care of everything from writing to saving your time and also giving the maximum effort. In the second part, we look at some of the best AI website builders like Durable, Cleap AI, and Pineapple AI. These tools are actually free of cost and can build your website for you just in few seconds. You don't even have to worry about the design or content. AI will handle everything. It's fast, easy, and perfect for anyone who needs a website but doesn't want to struggle with coding. So if you're looking to create a website quickly and for free, you're in the right place. Stick around and I'll show you step by step how to get your website live using these top-notch code and AI-powered platforms. So let's get started and see how AI is making web design easier than ever. So let's move on to the demo part. Alright, so now that we know what we're going to cover, let's jump into the first part, which is building a website using Pantheon. And this is the Pantheon website we have logged in. And for this, you have to just click on Get Started. And then we will move on to the WordPress part. So here, as you can see, you have to just simply fill up your details. So I've filled up my details here and just click on Continue. Wait for a few seconds till the dashboard is being loaded, and then you have to just simply click on Create a Site. And then we will be selecting WordPress. So now, as you can see, we have successfully logged into our Pantheon account and we have also created our account. Now the next step will be installing this WordPress account and then deploying our website in Pantheon in WordPress. So we will just simply click on WordPress here. Okay, you have to enter your Pantheon site name. Suppose I want to keep my name as Urban Threads India, and then just click on Continue here. So as you can see, the site name already exists, so we have to just change our name. We'll just put new over here. Let's see what it shows. New Urban Threads, and just click on Continue. So if this website name is not registered, it will successfully create my website using this particular name. So now the dashboard is being loaded. We just have to wait for a few seconds till it deploys our WordPress. Okay, so now that our WordPress is successfully deployed, we just have to click on Visit Your Pantheon Site Dashboard. And then it will load the dashboard. So now you have to click on Visit Development Site. And here you have to select the preferred language which you'll be using. So I've already selected my language, which is English here, and just click on Continue. And now as you can see that our WordPress installation is successfully done. So now I'll be just writing my title name, which is New Urban Threads, and write the username here, provide your name, and yeah, this password you can copy it or you can change your password accordingly. Just provide your email address here and click on Discourage search engines from indexing the site. and just select on install WordPress. So now that our installation is completely done, we can log into our WordPress account, and here you have to provide your username and the email address which you have used in order to create this account. Copy paste the password here and just click on login. So this is the WordPress interface here. Now, so this is the WordPress installation we have done, and now the next step will be building our website. So as you can see, we have successfully installed our WordPress, and this is the dashboard being shown. Now you have to click on plugins and just select add new plugin. And from here you have to select plugin which is a starter template and just select enter. So this is the template which we will be using to create our website. So you have to install this template here, wait for a few seconds and then click on activate. So there are two ways of building our website here. The first one is using the AI website builder, which will be using features like Zip WP to help to build a website faster. And the second step, which is quite old and traditional, which is using the classic starter template. So using this method, you have to create a website, professionally designed templates to meet the requirements. I mean, you have to just select a template, already made website template, and from there you can customize and edit accordingly. But for the first step, I'll be showing you how to make using the AI website builder. So just simply click on build with AI. Okay, and here you have to select let's get started. So as you can see, we are building our website using Zip WP, which is an AI tool that can automatically create our website content and layout, and it makes our work super easy. So now, as you can see, we are connecting our Zip WP account with this website, Pantheon website, and then we will click on continue here. Okay, so as now you can see, we have logged into our Zip WP account, and from here you can select as per as your use. So for now, we will be going with the free version and just click on get started here. So this is the verification code it has sent to my email. We'll just wait for a few minutes. So now you have to give the name of your website which you're building, which was New Urban Threads, and you just have to provide the detail. What is this website used for? Is it for clothing, spa, gym, local business, non-profit, entrepreneur, agency? So here we will just click on entrepreneur and just click on next. So it's written describe your new urban threads in few words. So here you have to describe what your website, what your business is about in a few words. Or also here's an option like you can also write using the AI. So you can just simply click here, write using AI, and now you can see it has created a description for your Urban Threads website account. So it has already written what your website will be about. See, it's written it's an innovative fashion brand in San Francisco. Since we are in India, you can all modify here as per as your needs. So just provide Bengaluru and I'll just give your India. Okay, and whatever customization you have to do, you can do it. So it was founded 2001. I'll just put it 2024 and just click on next. So as you can see, it has already given a description for your website here, and now you have to provide your email address. You can also add your social media account if you want to, and just click on next here. Okay, so these are the images you want to pick. So just select on the images. Since it's my clothing online store, you can just select few images from here. You can select this. You can also just simply search here fashion or street style fashion. Okay, so as you can see, these are few images it has shown for us. I'll just select this also. You can also upload your images if you want to, and then we will click on next. So now since we have described our website and given our contact details and address and also uploaded the image here, the next step is choosing the design. So here from this templates given, you can choose your design, whatever you want your website to be displayed as. So these designs are actually premium. You can select, since we are using the free trial here, you can select the free version here. So whatever style it's looking good, you can just select that accordingly. Since I like this more, I'll just select this. And this is just a sneak peek of how our actual website will be. So just take a look, how will it look like? Alright, and from here you can actually upload your logo. So just click on select files. So this is our logo here, new urban threads. And you can also decrease the logo width accordingly. You can also change the font pair, whatever you want your website font to be in. So since I like this more, I'll just keep it this. You can change the color palette also. So I'll be selecting this as my color palette and I'll select continue. So also you can add features in your website, what features you want. Blog, contact form, automation integrations, video player, page builder, e-commerce, that cart, donations, free live chat. So I will just simply click on free live chat as I want this to be displayed as a feature in my website, and I'll just select start building. So we are preparing your website. You just have to wait for a few seconds till it prepares our website. So as you can see, our website is now ready and you can just click on this option. Okay, and now the next step will be editing our layout and the content in our website according to. Just simply click on edit page here. So from here you can just edit the home page, sustainable. Okay, so this is the description here. You can add it accordingly, or you can also ask the AI to write it or make it more shorter here. You can also change the layout of this button, and from here click on content and the image icon you want it to be. So if you want this icon to be enabled, you have to just click on select here, and what style you want in your title plus your description. You can just change it accordingly. Since I want to keep it in white color, I'll just go with it. And okay, Alex turns journey to some sustainable fashion. These are the demo post 1 reviews. You can just simply click here and change if you want to. These are the testimonials of what our customers say here. And now if you want to stay in touch, you have to just enter your email address. To continue reading, you can just select here. So see, you can just customize it accordingly and edit your layout if you want to. And the best way I do it is using an AI tool known as Gravity Write. So you can just search your Gravity Write. This AI tool will help you to generate content for your website. I'll just show you how. So you have to just enter your email address here. Okay, so as you can see, it has got bundles and plenty of option here to provide you content for any of your thing, for booking management, course creator, music, website content. So since I want content for my website, see, you can even get some domain name ideas and create homepage, service page content using this AI tool, which is really amazing. So let's go back to our web page and we will just simply save this. So now we have finally viewed our page here. So this is how our actual page will look like. Our actual website, how it looks like. Isn't it really amazing? Just within few seconds, following few steps, you are now able to create an amazing website. Also, just a quick info for you, if you want to make your career in machine learning and AI, you can unlock your potential in machine learning with Simplilearn's professional certificate course in generative AI and machine learning, which is in collaboration with IIT Kanpur, which is designed for aspiring AI professionals. This program will offer hands-on experience with machine learning algorithms, deep learning, NLP, and many more. A year of experience is preferred. So you can hurry up now and enroll in this course and start your step forward in the future of AI and machine learning. You can find the course link in the description box and in the pinned comment. So now that we have created a website, the next step is purchasing a domain name. For this, you can use one website which is called Web Space Kit or Hostinger. So I'll be showing you here. Just simply type Web Space Kit. And if you think you can buy a free domain, I don't think so it is possible to buy a free domain. It's obviously paid, but then you can use this website to actually buy a domain in lesser price, which is only 139 rupees per month. And you can just view the plans and simply buy. And the next website is Hostinger. So these services will let you buy a domain and host your website in a very small fee. So all the links will be added in the description box if you want to check out these websites and create and buy your domain for publishing it online in the internet. You can use either Hostinger or WebSpaceKit. Also, one more thing. Now that we have decided to move our website for WebSpaceKit for hosting, you need to install a plugin on your Pantheon website, which is known as Migrate Guru. And using this plugin, you can actually, wait, I'll show you the plugin here. So you have to just simply click on add new plugin, and the plugin name is Migrate Guru. So we'll just search for Migrate Guru here. And using this, you have to just simply click on this. Now, why do we have to do it? I've already explained you. This will help you just have to install it on both your Pantheon site as well as your WebSpace, and it will help you to move everything over just within a few clicks. So we have now created a fully functional website using our AI. The second step was using the template version. You can also use the template version if you want to. So now that we have covered how to build a website using Pantheon, WordPress, so now we will discuss quickly the free AI tools which you can use to make your website even more faster. The first one on the list is Hookos AI. So you just have to simply click on Hookos AI Builder and it will create your website within just 5 minutes. So you have to just simply enter your email address and just click on Get Your AI Website here. As you can see, within just few steps, you have to just provide the details and the description of your website purpose. So suppose it's for travel, just simply write travel here and select categories like travel agent, equipment store. So it's a travel blog, so I'll just simply click on travel blog here. So you just can provide it accordingly what features you want to be included in your website here. So if I want to create a blog website for travel, just simply click on write a blog and just create a website. So as you can see, these are the steps here involved. So it's for my online business only. You can just simply provide business name here. Wander with me is my website name. So now you can see we're almost finished. So select the 3 unique aspects of your business, which is affordable prices, friendly, easy navigation, and just select on continue here. Just one more step and we will be done building our website. The second step is you can either what website visitors, how you want your website visitors to connect with you. So if you want your website visitors to connect via phone or contact form, I want them to connect via contact form and I'll just simply click on continue. So this is the layout they have generated for us for my travel blog website. Select the template you wanted. I like this one, so I'll just quickly click on this and select continue. So see, this is the website it has created for me here. And it's really good. So I really like the layout it has generated for me here. And also the font. You can just change, customize and edit your blog accordingly. If you want to keep it in pink color, you can also choose that. And also edit the images if you want to. See, you can add your touch here. And I like it in this font. If you like it in this font, you can just simply click here and create my website. So as you can see, our site is now created here. And this is really amazing. I mean, within just a few steps, you can create a fully functional website using this AI tool. Now let's discuss the second AI tool on the list, which is Leia AI. Just search your LEIA AI website builder. And this is also one of the amazing website builder you can create within just few seconds. You have to just click on get started here and just type, suppose I want a yoga studio website, and just click on next here. Just build my site and click on continue. So it will not take even a minute to build this website. Just click on view it. And now you can see that a yoga studio website is functionally built here. Like just within, and this is way more, I guess, faster than the previous AI website we have discussed before. I mean, you do not have to even provide description and it will just generate website for you. So from here, you can just simply replace the image, delete the element you want to, and add the content accordingly. So this was way more faster than the previous website, AI website we have generated. Now let's quickly dive into the third website tool, which is Pineapple AI. Just simply type Pineapple AI website builder and see. This is the website's interface. And here also you can just simply write your website you want. For example, you want a website for kindergarten school. You want to create a website for kindergarten school offering best education in town with all the modern technologies used to educate students. And just simply click on generate here. So see, you have to train your AI and just provide the business details you want to, and just simply click on next option to generate your website. So you can just simply click on the website template you want to. So if I like this one, I'll just simply click here and just click on AI customize and see, it will generate a website for you. And from here, you can add details to start generation. And like this, you can create a website. I mean, it is good, but I like the previous two AI tools more, which could create really amazing website within just a few seconds. This was the template we had selected. And from here, you have to just simply click on each of the content you want to edit and just pick your design here. All right. So let's move on to the next website, which is Cleep AI. Just simply search Cleep AI website builder and let's see how this website is. So you can just simply click on try for free option here and search for business. If your business is related to health and beauty, just select that. If you're an entrepreneur, select entrepreneur. What name it should be? Fit India. What's your goal to make money online? Location you can set accordingly. With AI, add some information. For information, you can use either ChatGPT or your Gravity, right, to generate content. So just copy paste the content here from either ChatGPT or your this. You can also provide your logo and the picture of your choice and just simply click on next here. You can choose any of the style you want. And now you can see that your AI is building your content. So as you can see, this website is being created using the Cleep AI tool. So this is a website you can Just click on the site settings and just change the template or the style you want, however you want to be. So let's talk about the final AI website builder, which is my personal favorite, which is Durable AI. So we just click on Durable AI and let's check how this AI will create content for us. We'll just select generate your website here. So what type of website are you building? It's we will use the same fashion online clothing store. Name of your business is Trendy Collections. Just click on generate websites. So you just have to wait for a few seconds and our website will be generated. So since I had provided my location, Bangalore, so it has created my website called Bangaluru's latest collection website. You can check it now. So as you can see, our website is now ready and you can also edit your website accordingly. This tool creates websites in a matter of seconds. Just give some basic details and Durable AI generates a complete website including content, images and layout. If you're in a hurry, this is the perfect solution for you. I would highly recommend using this tool. And now you can see the pricing label and everything mentioned here. It's superb. I mean, the quality and the layout it has provided is really good. So now you can just click on edit section and edit accordingly.
Welcome to the RNN tutorial. That's the recurrent neural network. So we talk about a feed-forward neural network. In a feed-forward neural network, information flows only in the forward direction, from the input nodes through the hidden layers, if any, and to the output nodes. There are no cycles or loops in the network. And so you can see here we have our input layer. I was talking about how it just goes straight forward into the hidden layers. So each one of those connects and then connects to the next hidden layer, connects to the output layer. And of course we have a nice simplified version where it has a predicted output and they refer to the input as X a lot of times and the output as Y. Decisions are based on current input, no memory about the past, no future scope. Why recurrent neural network? Issues in feed-forward neural network. So one of the biggest issues is because it doesn't have a scope of memory or time, a feed-forward neural network doesn't know how to handle sequential data. It only considers only the current input. So if you have a series of things and because 3 points back affects what's happening now and what your output affects what's happening, that's very important. So whatever I put as an output is going to affect the next one. A feed forward doesn't look at any of that. It just looks at this is what's coming in. And it cannot memorize previous inputs. So it doesn't have that list of inputs coming in. Solution to feed forward neural network. You'll see here where it says recurrent neural network, and we have our X on the bottom going to H, going to Y. That's your feed forward. But right in the middle, it has a value C, so it's a whole other process. So it's memorizing what's going on in the hidden layers, and the hidden layers, as they produce data, feed into the next one. So your hidden layer might have an output that goes off to Y, but that output goes back into the next prediction coming in. What this does is this allows it to handle sequential data. It considers the current input and also the previously received inputs. And if we're going to look at general drawings and solutions, we should also look at applications of the RNN. Image captioning. RNN is used to caption an image by analyzing the activities present in it. A dog catching a ball in midair. That's very tough. I mean, we have a lot of stuff that analyzes images of a dog and the image of a ball, but it's able to add one more feature in there that's actually catching the ball in midair. Time series prediction. Any time series problem like predicting the prices of stocks in a particular month can be solved using RNN. And we'll dive into that in our use case and actually take a look at some stock. One of the things you should know about analyzing stock today is that it is very difficult. And if you're analyzing the whole stock, the stock market at the New York Stock Exchange in the U.S. produces somewhere in the neighborhood, if you count all the individual trades and fluctuations by the second, it's like 3 terabytes a day of data. So we're only going to look at one stock. Just analyzing one stock is really tricky. In here, we'll give you a little jump on that, so that's exciting, but don't expect to get rich off of it immediately. Another application of the RNN is natural language processing. Text mining and sentiment analysis can be carried out using RNN for natural language processing. And you can see right here the term natural language processing, when you stream those three words together, is very different than if I said processing language naturally. So the time series is very important when we're analyzing sentiments. It can change the whole value of a sentence just by switching the words around. Or if you're just counting the words, you might get one sentiment where if you actually look at the order they're in, you get a completely different sentiment. When it rains, look for rainbows. When it's dark, look for stars. Both of these are positive sentiments, and they're based upon the order of which the sentence is going in. Machine translation. Given an input in one language, RNN can be used to translate the input into a different languages as output. I myself am very linguistically challenged. But if you study languages and you're good with languages, you know right away that if you're speaking English, you would say big cat. And if you're speaking Spanish, you would say cat big. So that translation is really important to get the right order, to get, there's all kinds of parts of speech that are important to know by the order of the words. Here this person is speaking in English and getting translated. And you can see here a person is speaking in English in this little diagram. I guess that's denoted by the flags. I have a flag. I own it. No. But they're speaking in English and it's getting translated into Chinese, Italian, French, German, and Spanish languages. Some of the tools coming out are just so cool. So somebody like myself who's very linguistically challenged, I can now travel into worlds I would never think of, because I can have something translate my English back and forth readily, and I'm not stuck with a communication gap. So let's dive into what is a recurrent neural network. Recurrent neural network works on the principle of saving the output of a layer and feeding this back to the input in order to predict the output of the layer. Sounds a little confusing. When we start breaking it down, it'll make more sense. And usually we have a propagation forward neural network with the input layers, the hidden layers, the output layer. With the recurrent neural network, we turn that on its side. So here it is, and now our X comes up from the bottom into the hidden layers into Y, and they usually draw it very simplified, X to H, with C as a loop, A to Y, where A, B, and C are the perimeters. A lot of times you'll see this kind of drawing in here, digging closer and closer into the H and how it works. Going from left to right, you'll see that the C goes in, and then the X goes in. So the X is going upward bound, and C is going to the right. A is going out. And C is also going out. That's where it gets a little confusing. So here we have X in, C in, and then we have Y out and C out. And C is based on HT minus 1. So our value is based on the Y and the H value are connected to each other. They're not necessarily the same value because H can be its own thing. And usually we draw this, or we represent it as a function. H of T equals a function of C, where H of T minus 1, that's the last H output, and X of T going in. So it's the last output of H combined with the new input of X, where HT is the new state, FC is a function with the parameters C, that's a common way of denoting it, HT minus 1 is the old state coming out, and then X of T is an input vector at time of step T. Well, we need to cover types of recurrent neural networks. And so the first one is the most common one, which is a one-to-one single output. One-to-one neural network is usually known as a vanilla neural network, used for regular machine learning problems. Why? Because vanilla is usually considered kind of just a real basic flavor. But because it's very basic, a lot of times they'll call it the vanilla neural network, which is not the common term, but it is, like kind of a slang term. People will know what you're talking about usually if you say that. Then we run one-to-many, so you have a single input, and you might have multiple outputs. In this case, image captioning, as we looked at earlier, where we have not just looking at it as a dog, but a dog catching a ball in the air. And then you have many-to-one network, takes in a sequence of inputs. Examples, sentiment analysis, where a given sentence can be classified as expressing positive or negative sentiments. And we looked at that as we were discussing, if it rains, look for a rainbow. So positive sentiment, where rain might be a negative sentiment if you were just adding up the words in there. And then, of course, if you're going to do a one-to-one, many-to-one, one-to-many, there's many-to-many networks, takes in a sequence of inputs and generates a sequence of outputs. Example, machine translation. So we have a lengthy sentence coming in English and then going out in all the different languages. Just a wonderful tool. Very complicated set of computations. If you're a translator, you realize just how difficult it is to translate into different languages. One of the biggest things you need to understand when we're working with this neural network is what's called the vanishing gradient problem. While training an RNN, your slope can be either too small or very large, and this makes training difficult. When the slope is too small, the problem is known as vanishing gradient. And you'll see here they have a nice image, loss of information through time. So if you're pushing not enough information forward, that information is lost, and then when you go to train it, you start losing the third word in the sentence or something like that, or it doesn't quite follow the full logic of what you're working on. Exploding gradient problem. Oh, this is one that runs into everybody. When you're working with this particular neural network, when the slope tends to grow exponentially instead of decaying, this problem is called exploding gradient. Issues in gradient problem: long training time, poor performance, bad accuracy. And I'll add one more in there. Your computer, if you're on a lower end computer testing out a model, will lock up and give you the memory error. Explaining gradient problem. Consider the following two examples to understand what should be the next word in the sequence. The person who took my bike and blank, a thief. The students who got into engineering with blank from Asia. And you can see in here we have our x value going in, we have the previous value going forward, and then you back propagate the error like you do with any neural network. And as we're looking for that missing word, maybe we'll have the person took my bike and blank was a thief. And the student who got into engineering with a blank were from Asia. Consider the following example, the person who took the bike. So we'll go back to the person who took the bike was blank a thief. In order to understand what would be the next word in the sequence, the RNN must memorize the previous context, whether the subject was singular noun or a plural noun. So was a thief is singular. The student who got into engineering, well, in order to understand what would be the next word in the sequence, the RNN must memorize the previous context, whether the subject was singular noun or a plural noun. And so you can see here the students who got into engineering with blank were from Asia. It might be sometimes difficult for the error to back propagate to the beginning of the sequence to predict what should be the output. So when you run into the gradient problem, we need a solution, the solution to the gradient problem. First, we're going to look at exploding gradient, where we have three different solutions depending on what's going on. One is identity initialization. So the first thing we want to do is see if we can find a way to minimize the identities coming in instead of having it identify everything, just the important information we're looking at. Next is to truncate the back propagation. So instead of having whatever information it's sending to the next series, we can truncate what it's sending. We can lower that particular set of layers, make those smaller. And finally is a gradient clipping. So when we're training it, we can clip what that gradient looks like and narrow the training model that we're using. When you have a vanishing gradient, the option problem, we can take a look at weight initialization, very similar to the identity, but we're going to add more weights in there so it can identify different aspects of what's coming in better. Choosing the right activation function. That's huge. So we might be activating based on one thing and we need to limit that. We haven't talked too much about activation functions, so we'll look at that just minimally. There's a lot of choices out there. And then finally there's long short-term memory networks, the LSTMS. And we can make adjustments to that. So just like we can clip the gradient as it comes out, we can also expand on that. We can increase the memory network, the size of it, so it handles more information. And one of the most common problems in today's setup is what they call long-term dependencies. Suppose we try to predict the last word in the text. The clouds are in the, and you probably said sky. Here we do not need any further context. It's pretty clear that the last word is going to be sky. Suppose we try to predict the last word in the text. I have been staying in Spain for the last 10 years. I can speak fluent. Maybe you said Portuguese or French. No, you probably said Spanish. The word we predict will depend on the previous few words in context. Here we need the context of Spain to predict the last word in the text. It's possible that the gap between the relevant information and the point where it is needed to become very large. LSTMs help us solve this problem. So the LSTMs are a special kind of recurrent neural network capable of learning long-term dependencies. Remembering information for long periods of time is their default behavior. All recurrent neural networks have the form of a chain of repeating modules, of neural network connections. In standard RNNs, this repeating module will have a very simple structure such as a single tangent H layer. LSTMSs also have a chain-like structure, but the repeating module has a different structure. Instead of having a single neural network layer, there are 4 interacting layers communicating in a very special way. LSTMS are a special kind of recurrent neural network, capable of learning long-term dependencies. Remembering information for long periods of time is their default behavior. LSTMSs also have a chain-like structure, but the repeating module has a different structure. Instead of having a single neural network layer, there are 4 interacting layers communicating in a very special way. As you can see, the deeper we dig into this, the more complicated the graphs get. In here, I want you to note that you have x at t minus 1 coming in, you have x at t coming in, and you have x at t plus 1. And you have h at t minus 1, and h at t coming in, and h at t plus 1 going out. And of course, on the other side is the output A. In the middle, we have our tangent H, but it occurs in 2 different places. So not only when we're computing the x at t plus 1 are we getting the tangent H from x at t, but we're also getting that value coming in from the x at t minus 1. So the short of it is that as you look at these layers, not only does the propagate through the first layer, goes into the second layer and back into itself, but it's also going into the third layer. So now we're kind of stacking those up. And this can get very complicated as you grow that in size. It also grows in memory too, and in the amount of resources it takes. But it's a very powerful tool to help us address the problem of complicated, long sequential information coming in, like we were just looking at in the sentence. And when we're looking at our long, short-term memory network, there's 3 steps of processing in the LSTMS that we look at. The first one is we want to forget irrelevant parts of the previous state. A lot of times, like, is, as, in, a, unless we're trying to look at whether it's a plural noun or not, they don't really play a huge part in the language, so we want to get rid of them. Then selectively update cell state values. So we only want to update the cell state values that reflect what we're working on. And finally, we want to only output certain parts of the cell state. So whatever's coming out, we want to limit what's going out too. And let's dig a little deeper into this. Let's just see what this really looks like. So step 1 decides how much of the past it should remember. First step in the LSTM is to decide which information to be omitted from the cell in that particular time step. It is decided by the sigmoid function. It looks at the previous state, h at t minus 1, and the current input, x at t, and computes the function. So you can see over here we have a function of t equals the sigmoid function of the weight of f, the h at t minus 1, and then x at t, plus, of course you have a bias in there with any of your neural networks, so we have a bias function. So f at t equals forget gate, decides which information to delete that is not important from the previous time step. Considering an LSTM is fed with the following inputs from the previous and present time step. Alice is good in physics. John, on the other hand, is good in chemistry. So, previous output. John plays football well. He told me yesterday over the phone that he had served as a captain of his college football team. That's our current input. So as we look at this, the first step is the forget gate realizes there might be a change in context after encountering the first full stop. Compares with the current input sentence of x at t. So we're looking at that full stop and then compares it with the input of the new sentence. The next sentence talks about John, so the information on Alice is deleted. Okay, that's important to know. So we have this input coming in, and if we're going to continue on with John, then that's going to be the primary information we're looking at. The position of the subject is vacated and is assigned to John. And so in this one, we've seen that we've weeded out a whole bunch of information, and we're only passing information on John, since that's now the new topic. So step 2 is then to decide how much should this unit add to the current state. In the second layer, there are 2 parts. One is the sigmoid function, and the other is the tangent h. In the sigmoid function, it decides which values to let through, 0 or 1. Tangent h function gives the weightage to the values which are passed, deciding their level of importance, -1 to 1. And you can see the 2 formulas that come up. The I of t equals the sigmoid of the weight of I, h at t minus 1, x at t plus the bias of I. And the c of t equals the tangent of h of the weight of c of h at t minus 1, x at t plus the bias of c. So our I of t equals the input gate, determines which information to let through based on its significance in the current time step. If this seems a little complicated, don't worry, because a lot of the programming is already done when we get to the case study. Understanding, though, that this is part of the program is important when you're trying to figure out what to set your settings at. You should also note when you're looking at this, it should have some semblance to your forward propagation neural networks, where we have a value assigned to a weight plus a bias. Very important steps in any of the neural network layers, whether we're propagating into them the information from one to the next, or we're just doing a straightforward neural network propagation. Let's take a quick look at this, what it looks like from the human standpoint as I step out of my suit again. Consider the current input at X of t. John plays football well. He told me yesterday over the phone that he had served as a captain of his college football team. That's our input. Input gate analyzes the important information. John plays football and he was a captain of his college team is important. He told me over the phone yesterday is less important, hence it is forgotten. This process of adding some new information can be done via the input gate. Now this example is as a human form, and we'll look at training this stuff in just a minute. But as a human being, if I wanted to get this information from a conversation, maybe it's a Google Voice listening in on you or something like that, how do we weed out the information that he was talking to me on the phone yesterday? Well, I don't want to memorize that he talked to me on the phone yesterday, or maybe that is important. But in this case, it's not. I want to know that he was the captain of the football team. I want to know that he served. I want to know that John plays football and he was the captain of the college football team. Those are the two things that I want to take away as a human being. Again, we measure a lot of this from the human viewpoint, and that's also how we try to train them so we can understand these neural networks. Finally, we get to step 3, decides what part of the current cell state makes it to the output. The third step is to decide what will be our output. First we run a sigmoid layer, which decides what parts of the cell state make it to the output. Then we put the cell state through the tangent h to push the values to be between -1 and 1, and multiply it by the output of the sigmoid gate. So when we talk about the output of t, we set that equal to the sigmoid of the weight of 0 of the h of t minus 1, back one step in time, by the x of t, plus of course the bias. The h of t equals the out of t times the tangent h of c of t. So our O of t equals the output gate, allows the passed in information to impact the output in the current time step. Let's consider the example to predicting the next word in the sentence. John played tremendously well against the opponent and won for his team. For his contributions, Brave blank was awarded player of the match. There could be a lot of choices for the empty space. Current input, Brave, is an adjective. Adjectives describe a noun. John could be the best output after Brave. Thumbs up for John, awarded player of the match. And if you were to pull just the nouns out of the sentence, team doesn't look right because that's not really the subject we're talking about. Contributions, brave contributions, or brave team, brave player, brave match. So you look at this and you can start to train this neural network. So it starts looking at it and goes, oh no, John is what we're talking about. So brave is an adjective. John's going to be the best output. And we give John a big thumbs up. And then of course we jump into my favorite part, the case study. Use case implementation of LSTM. Let's predict the prices of stocks using the LSTM network based on the stock price data between 2012 and 2016. We're going to try to predict the stock prices of 2017. And this will be a narrow set of data. We're not going to do the whole stock market. It turns out that the New York Stock Exchange generates roughly 3 terabytes of data per day. That's all the different trades up and down of all the different stocks going on. And each individual one second to second or nanosecond to nanosecond. But we're going to limit that to just some very basic fundamental information. So don't think you're going to get rich off this today. But at least you can give a step forward in how to start processing something like stock prices, a very valid use for machine learning in today's markets. Use case implementation of LSTM. Let's dive in. We're going to import our libraries. We're going to import the training set and get the scaling going. Now, if you watch any of our other tutorials, a lot of these pieces just start to look very familiar because it's a very similar setup. But let's take a look at that. And just a reminder, we're going to be using Anaconda, the Jupyter Notebook. So here I have my Anaconda Navigator. When we go under environments, I've actually set up a Keras Python 3.6. I'm in Python 3.6. And nice thing about Anaconda, especially the newer version, I remember a year ago messing with Anaconda in different versions of Python and different environments. Anaconda now has a nice interface And I have this installed both on a Ubuntu Linux machine and on Windows, so it works fine on there. You can go in here and open a terminal window, and then in here, once you're in the terminal window, this is where you're going to start installing using pip to install your different modules and everything. Now we've already pre-installed them, so we don't need to do that in here. But if you don't have them installed in your particular environment, you'll need to do that. And of course, you don't need to use the Anaconda or the Jupyter. You can use whatever favorite Python IDE you like. I'm just a big fan of this because it keeps all my stuff separate. You can see on this machine I have specifically installed one for Keras, since we're going to be working with Keras under TensorFlow. When we go back to home, I've gone up here to application, and that's the environment I've loaded on here, and then we'll click on the Launch Jupyter Notebook. Now I've already, in my Jupyter Notebook, have set up a lot of stuff so that we're ready to go. Kind of like Martha Stewart's in the old cooking shows. We want to make sure we have all our tools for you so you're not waiting for them to load. And if we go up here to where it says New, you can see where you can create a new Python 3. That's what we did here underneath the setup, so it already has all the modules installed on it. And I'm actually renamed this. If you go under File, you can rename it. I'm calling it RNN Stock. And let's just take a look and start diving into the code. Let's get into the exciting part. Now we've looked at the tool, and of course you might be using a different tool, which is fine. Let's start putting that code in there and seeing what those imports and uploading everything looks like. Now, first half is kind of boring when we hit the Run button, because we're going to be importing NumPy as NP. That's the number Python, which is your NumPy array, and the matplot library, because we're going to do some plotting at the end, and our pandas for our data set. Our pandas as PD. And when I hit Run, it really doesn't do anything except for load those modules. Just a quick note, let me just do a quick draw here. Oops, Shift-Alt, there we go. You'll notice when we're doing this setup, if I was to divide this up, oops, I'm going to actually, let's overlap these, here we go. This first part that we're going to do is our data prep. A lot of prepping involved. In fact, depending on what your system is, since we're using Keras, I put an overlap here, but you'll find that almost maybe even half of the code we do is all about the data prep. And the reason I overlap this with Keras, let me just put that down because that's what we're working in, is because Keras has like their own preset stuff, so it's already pre-built in, which is really nice. So there's a couple steps a lot of times that are in the Keras setup. We'll take a look at that to see what comes up in our code as we go through and look at stock. And then the last part is to evaluate. And if you're working with shareholders or classroom, whatever it is you're working with, the evaluate is the next biggest piece. So the actual code here, Keras is a little bit more, but when you're working with some of the other packages, you might have like 3 lines. That might be it. All your stuff is in your pre-processing and your data. Since Keras is cutting edge and you load the individual layers, you'll see that there's a few more lines here and Keras is a little bit more robust. And then you spend a lot of times, like I said, with the evaluate, you want to have something you present to everybody else and say, hey, this is what I did, this is what it looks like. So let's go through those steps. This is like a kind of just general overview. And let's just take a look and see what the next set of code looks like. And in here we have a dataset train, and it's going to be read using the PD, or pandas.readCSV, and it's the Google stock price train.csv. And so under this we have training set equals dataset train.iLocation, and we've kind of sorted out part of that. So what's going on here? Let's just take a look at it. Let's look at the actual file and see what's going on there. Now if we look at this, ignore all the extra files on this, I already have a train and a test set where it's sorted out. This is important to notice because a lot of times we do that as part of the pre-processing of the data. We take 20% of the data out so we can test it, and then we train the rest of it. That's what we use to create our neural network. That way we can find out how good it is. But let's go ahead and just take a look and see what that looks like as far as the file itself. And I went ahead and just opened this up in a basic WordPad and text editor just so we can take a look at it. Certainly you can open up an Excel or any other kind of spreadsheet. And we note that this is a comma-separated variables. We have a date, open, high, low, close, volume. This is the standard stuff that we import into our stock, and we're the most basic set of information you can look at in stock. It's all free to download. In this case, we downloaded it from Google. That's why we call it the Google stock price. And it specifically is Google. This is the Google stock values from, as you can see here, we started off at 1/3/2012. So when we look at this first setup up here, we have a data set train equals PD underscore CSV. And if you noticed on the original frame, let me just go back there. They had it set to home Ubuntu downloads Google stock price train. I went ahead and changed that because we're in the same file where I'm running the code. So I've saved this particular Python code and I don't need to go through any special paths or have the full path on there. And then of course we want to take out certain values in here. And you're going to notice that we're using our data set, and we're now in pandas. So pandas, basically it looks like a spreadsheet. And in this case, we're going to do iLocation, which is going to get specific locations. The first value is going to show us that we're pulling all the rows in the data. And the second one is we're only going to look at columns 1 and 2. And if you remember here from our data, as we switch back on over, columns, we always start with 0, which is the date. And we're going to be looking at open and high, which would be 1 and 2. We'll just label that right there so you can see. Now, when you go back and do this, you certainly can extrapolate and do this on all the columns. But for the example, let's just limit a little bit here so that we can focus on just some key aspects of stock. And then we'll go up here and run the code. And again, I said the first half is very boring. Whenever you hit the run button, it doesn't do anything because we're still just loading the data and setting it up. Now that we've loaded our data, we want to go ahead and scale it. We want to do what they call feature scaling. And in here we're going to pull it up from the sklearn or the skKit pre-processing import min-max scaler. And when you look at this, you got to remember that biases in our data, we want to get rid of that. So if you have something that's like a really high value, let's just draw a quick graph. And I have something here like maybe the stock has a value, one stock has a value of 100, and another stock has a value of 5. You start to get a bias between different stocks. And so when we do this, we go ahead and say, okay, 100 is going to be the max, and 5 is going to be the min, and then everything else goes, and then we change this, so we just squish it down. I like the word squish. So it's between 1 and 0. So 100 equals 1. Or 1 equals 100, and 0 equals 5. And you can just multiply. It's usually just a simple multiplication we're using. Multiplication. So it's going to be minus 5 and then 100 divided, or 95 divided by 1. So, or whatever value is divided by 95. And once we've actually created our scale, we're telling us it's going to be from 0 to 1. We want to take our training set, and we're going to create a training set scaled. And we're going to use our scaler, SC, and we're going to fit. We're going to fit and transform the training set. So we can now use the SC, this particular object, we'll use it later on our testing set. Because remember, we have to also scale that when we go to test our model and see how it works. And we'll go ahead and click on the run. Again, it's not going to have any output yet because we're just setting up all the variables. Okay, so we paste the data in here, and we're going to create the data structure with the 60 time steps and output. First note, we're running 60 time steps, and that is where this value here also comes in. So the first thing we do is we create our xtrain and ytrain variables, and we set them to an empty Python array. Very important to remember what kind of array we're in and what we're working with. And then we're going to come in here, we're going to go for I in range 60 to 1258. There's our 60 time steps. And the reason we want to do this is as we're adding the data in, there's nothing below the 60. So if we're going to use 60 time steps, we have to start at point 60 because it includes everything underneath of it. Otherwise, you'll get a pointer error. And then we're going to take our xtrain, and we're going to append training set scaled. This is the scaled value between 0 and 1. And then as I is equal to 60, this value is going to be 60 minus 60 is 0. So this actually is 0 to I. So it's going to be 0 to 60, 1 to 61. Let me just circle this part right here. 1 to 61, 2 to 62, and so on and so on. And if you remember, I said 0 to 60. That's incorrect because it does not count. Remember, it starts at 0, so this is a count of 60. So it's actually 59. Important to remember that as we're looking at this. And then the second part of this that we're looking at, so if you remember correctly, here we go from 0 to 59 of I, and then we have a comma, a 0 right here. And so finally, we're just going to look at the open value. Now, I know we did put it in there for 1 to 2. If you remember correctly, it doesn't count the second one, so it's just the open value we're looking at, just open. And then finally, we have ytrain.append training set I to 0. And if you remember correctly, I comma 0. If you remember correctly, this is 0 to 59, so there's 60 values in it. So when we do I down here, this is number 60. So what we're going to do this is we're creating an array, and we have 0 to 59. And over here we have number 60, which is going into the Y train. It's being appended on there. And then this just goes all the way up. So this is down here is 0 to 59, and we'll call it 60, since that's the value over here. And it goes all the way up to 1258. That's where this value here comes in. That's the length of the data we're loading. So we've loaded 2 arrays. We've loaded one array that has, which is filled with arrays from 0 to 59, and we loaded one array which is just the value. And what we're looking at, you want to think about this as a time sequence. Here's my open. What's the next one in the series? So we're looking at the Google stock, and each time it opens, we want to know what the next one, 0 through 59, what's 60? 1 through 60, what's 61? 2 through 62, what's 62? And so on going up. And then once we've loaded those in our for loop, we go ahead and take xtrain and ytrain equals np.array xtrain.nparray ytrain. We're just converting this back into a numpy array. That way we can use all the cool tools that we get with numpy array, including reshaping. So if we take a look and see what's going on here, we're going to take our xtrain, we're going to reshape it. Wow, what the heck does reshape mean? That means we have an array, if you remember correctly, so many numbers by 60. That's how wide it is. And so when you do xtrain.shape, that gets one of the shapes. And you get xtrain.shape of 1 gets the other shape. And we're just making sure the data is formatted correctly. And so you use this to pull the fact that it's 60 by, in this case, where's that value? 60 by 1199, 1258 minus 60, 1199, and we're making sure that that is shaped correctly, so the data is grouped into 1199 by 60 different arrays. And then the 1 on the end just means at the end, because when you're dealing with shapes and NumPy, they look at this as layers, and so the end layer needs to be 1 value. That's like the leaf of a tree, where this is the branch, and then it branches out some more, and then you get the leaf. np.reshape comes from and using the existing shapes to form it. We'll go ahead and run this piece of code. Again, there's no real output. And then we'll import our different Keras modules that we need. So from Keras models, we're going to import the sequential model. We're dealing with sequential data. We have our dense layers. We have actually 3 layers we're going to bring in. Our dense, our LSTM, which is what we're focusing on, and our dropout. And we'll discuss these 3 layers more in just a moment. But you do need with the LSTM, you do need the dropout, and then the final layer will be the dense. But let's go ahead and run this, and that'll import our modules. And you'll see we get an error on here. And if you read it closer, it's not actually an error, it's a warning. What does this warning mean? These things come up all the time when you're working with such cutting edge modules that are completely being updated all the time. We're not going to worry too much about the warning. All it's saying is that the H5PY module, which is part of Keras, is going to be updated at some point. And if you're running new stuff on Keras and you start updating your Keras system, you better make sure that your H5Pi is updated too, otherwise you're going to have an error later on. And you can actually just run an update on the H5Pi now if you wanted to. Not a big deal. We're not going to worry about that today. And I said we were going to jump in and start looking at what those layers mean. I meant that. And we're going to start off with initializing the RNN, and then we'll start adding those layers in, and you'll see that we have the LSTM and then the dropout. LSTM, then dropout. LSTM, then dropout. What the heck is that doing? So let's explore that. We'll start by initializing the RNN, regressor equals sequential, because we're using the sequential model, and we'll run that and load that up. And then we're going to start adding our LSTM layer and some dropout regularization. And right there should be the Q, dropout regularization. And if we go back here and remember our exploding gradient, well, that's what we're talking about. The dropout drops out unnecessary data, so we're not just shifting huge amounts of data through the network. So we go in here. Let's just go ahead and add this in. I'll go ahead and run this. And we had 3 of them. So let me go ahead and put all 3 of them in, and then we can go back over them. Here's the second one, and let's put 1 more in. So let's put that in, and we'll go ahead and put 2 more in. I said 1 more in, but it's actually 2 more in. And then let's add 1 more after that. And as you can see, each time I run these, they don't actually have an output. So let's take a closer look and see what's going on here. So we're going to add our first LSTM layer in here. We're going to have units 50. The units is the positive integer, and it's the dimensionality of the output space. This is what's going out into the next layer. So we might have 60 coming in, but we have 50 going out. We have a return sequence, because it is a sequence data, so we want to keep that true. And then you have to tell it what shape it's in. Well, we already know the shape by just going in here and looking at xtrain shape. So input shape equals the xtrain shape of 1, 1. It makes it real easy. You don't have to remember all the numbers that put in 60 or whatever else is in there. You just let it tell the regressor what model to use. And so we follow our STM with a dropout layer. Now, understanding the dropout layer is kind of exciting because one of the things that happens is we can overtrain our network. That means that our neural network will memorize such specific data that it has trouble predicting anything that's not in that specific realm. To fix for that, each time we run through the training mode, we're going to take 0.2 or 20% of our neurons and just turn them off. So we're only going to train on the other ones. And it's going to be random. That way, each time we pass through this, we don't overtrain. These nodes come back in the next training cycle. We randomly pick a different 20. And finally, I see a big difference as we go from the first to the second and third and fourth. The first thing is we don't have to input the shape. Because the shape's already, the output units is 50 here, the next step automatically knows this layer is putting out 50, and because it's the next layer, it automatically sets that and says, oh, 50 is coming out from our last layer. It's coming out, goes into the regressor, and of course we have our dropout. And that's what's coming into this one, and so on, and so on. And so the next 3 layers, we don't have to let it know what the shape is. It automatically understands that. And we're going to keep the units the same. We're still going to do 50 units. It's still a sequence coming through, 50 units and a sequence. Now, the next piece of code is what brings it all together. Let's go ahead and take a look at that. And we come in here, we put the output layer, the dense layer. And if you remember up here, we had the 3 layers. We had LSTM, dropout, and dense. Dense just says we're going to bring this all down into one output. Instead of putting out a sequence, we just want to know the answer at this point. And let's go ahead and run that. And so in here, you notice all we're doing is setting things up, one step at a time. So far, we've brought in our, way up here, we brought in our data, we brought in our different modules, we formatted the data for training it, we set it up, we have our X train and our Y train. We have our source of data and the answers we know so far that we're going to put in there. We've reshaped that. We've come in and built our Keras. We've imported our different layers. And we have in here, if you look, we have 5 total layers. Now, Keras is a little different than a lot of other systems because a lot of other systems put this all in one line and do it automatic, but they don't give you the options of how those layers interface, and they don't give you the options of how the data comes in. Keras is cutting edge for this reason. So even though there's a lot of extra steps in building the model, this has a huge impact on the output and what we can do with these new models from Keras. So we brought in our dense, we have our full model put together, our regressor. So we need to go ahead and compile it, and then we're going to go ahead and fit the data. We're going to compile the pieces so they all come together, and then we're going to run our training data on there and actually recreate our regressor so it's ready to be used. So let's go ahead and compile that, and I can go ahead and run that. And if you've been looking at any of our other tutorials on neural networks, you'll see we're going to use the optimizer Atom. Atom is optimized for big data. There's a couple other optimizers out there beyond the scope of this tutorial, but certainly Atom will work pretty good for this. And loss equals mean squared value. So when we're training it, this is what we want to base the loss on. How bad is our error? Well, we're going to use the mean squared value for our error and the Atom optimizer for its differential equations. You don't have to know the math behind them, but certainly it helps to know what they're doing and where they fit into the bigger models. And then finally we're going to do our fit, fitting the RN into the training set. We have the regressor.fit, xtrain, ytrain, epochs, and batch size. So we know where this is. This is our data coming in for the xtrain. Our ytrain is the answer we're looking for of our data, our sequential input. Epochs is how many times we're going to go over the whole data set. We created a whole data set of xtrain. So this is each of those rows, which includes a time sequence of 60. And batch size, another one of those things where Keras really shines, is if you were pulling this, say, from a large file, instead of trying to load it all into RAM, it can now pick smaller batches up and load those indirectly. We're not worried about pulling them off a file today because this isn't big enough to cause the computer too much of a problem to run, not too straining on the resources. But as we run this, you can imagine what would happen if I was doing a lot more than just one column in one set of stock, in this case Google stock. Imagine if I was doing this across all the stocks and I had, instead of just the open, I had open, close, high, low, and you can actually find yourself with about 13 different variables times 60 because it's a time sequence. Suddenly you find yourself with a gig of memory you're loading into your RAM, which will just completely, if you're not on multiple computers or cluster, you're going to start running into resource problems. But for this, we don't have to worry about that. So let's go ahead and run this, and this will actually take a little bit on my computer because it's an older laptop. And give it a second to kick in there. There we go. Alright, so we have Epic. So this is going to tell me it's running the first run through all the data. And as it's going through, it's batching them in 32 pieces. So 32 lines each time. And there's 1198. I think I said 1199 earlier, but it's 1198. I was off by 1. And each one of these is 13 seconds. So you can imagine this is roughly 20 to 30 minutes runtime on this computer. Like I said, it's an older laptop running at 0.9 gigahertz on a dual processor. And that's fine. What we'll do is I'll go ahead and stop, go get a drink of coffee, and come back, and let's see what happens at the end and where this takes us. And like any good cooking show, I've gotten my latte. I also had some other stuff running in the background, so you'll see these numbers jumped up to like 19 seconds, 15 seconds. But you can scroll through, and you can see we've run it through 100 steps, or 100 epics. So the question is, what does all this mean? One of the first things you'll notice is that our loss is over here. It kind of stopped at 0.0014, but you can see it kind of goes down until we hit about 0.014 3 times in a row. So we guessed our epic pretty close since our loss has remained the same on there. So to find out what we're looking at, we're going to go ahead and load up our test data, the test data that we didn't process yet. And a real stock price, data set, test allocation. This is the same thing we did when we prepped the data in the first place. So let's go ahead and go through this code. And we can see we've labeled it Part 3, Making the Predictions and Visualizing the Results. So the first thing we need to do is go ahead and read the data in from our test CSV. And you see I've changed the path on it for my computer. And then we'll call it the real stock price. And again, we're doing just the one column here and the values from iLocation. So it's all the rows and just the values from that one location. That's the open. Stock open. Let's go ahead and run that. So that's loaded in there. And then let's go ahead and we have our inputs. We're going to create inputs here. And this should all look familiar because this is the same thing we did before. We're going to take our data set total. We're going to do a little pandas concat from the data set train. Now remember, the end of the data set train is part of the data going in. And let's just visualize that just a little bit. Here's our train data. Let me just put TR for train. And it went up to this value here. But each one of these values generated a bunch of columns. So it was 60 across, and this value here equals this one, and this value here equals this one, and this value here equals this one. And so we need these top 60 to go into our new data. So to find out what we're looking at, we're going to go ahead and load up our test data, the test data that we didn't process yet. And a real stock price, data set, test allocation. This is the same thing we did when we prepped the data in the first place. So let's go ahead and go through this code. And we can see we've labeled it Part 3, Making the Predictions and Visualizing the Results. So the first thing we need to do is go ahead and read the data in from our test CSV. And you see I've changed the path on it for my computer. And then we'll call it the real stock price. And again, we're doing just the one column here and the values from iLocation. So it's all the rows and just the values from that one location. That's the open. Stock open. Let's go ahead and run that. So that's loaded in there. And then let's go ahead and we have our inputs. We're going to create inputs here. And this should all look familiar because this is the same thing we did before. We're going to take our data set total. We're going to do a little pandas concat from the data set train. Now remember, the end of the data set train is part of the data going in. And let's just visualize that just a little bit. Here's our train data. Let me just put TR for train. And it went up to this value here. But each one of these values generated a bunch of columns. So it was 60 across, and this value here equals this one, and this value here equals this one, and this value here equals this one. And so we need these top 60 to go into our new data, because that's part of the next data, or it's actually the top 59. So that's what this first setup is over here, is where we're going in, we're doing the real stock price, and we're going to just take the data set test, and we're going to load that in, and then the real stock price is our data test location. So we're just looking at that first column, the open price. And then our data set total, we're going to take pandas and we're going to concat, and we're going to take our data set train for the open and our data set test open. And this is one way you can reference these columns. We've referenced them a couple different ways. We've referenced them up here with the 1, 2, but we know it's labeled as a panda set as open. So pandas is great that way. Lots of versatility there. And we'll go ahead and go back up here and run this. There we go. And you'll notice this is the same as what we did before. We have our open data set. We appended our two different, or concatenated our two data sets together. We have our inputs equals data set total length, data set total minus length of data set minus test minus 60 values. So we're going to run this over all of them, and you'll see why this works, because normally when you're running your test set versus your training set, you run them completely separate. But when we graph this, you'll see that we'll be looking at the part that we didn't train it with to see how well it graphs. And we have our inputs equals inputs dot reshapes, or reshaping like we did before. We're transforming our inputs. So if you remember from the transform between 0 and 1, and finally we want to go ahead and take our x test, and we're going to create that x test, and for I in range 60 to 80. So here's our x test, and we're appending our inputs I to 60, which remember is 0 to 59, and I comma 0 on the other side. So it's just the first column, which is our open column. And once again, we take our x test, we convert it to a numpy array, we do the same reshape we did before, and then we get down to the final two lines, and here we have something new. Right here on these last two lines, let me just highlight those or mark them. Predicted stock price equals regressor.predicts x test. So we're predicting all the stock, including both the training and the testing model here. And then we want to take this prediction and we want to inverse the transform. So remember, we put them between 0 and 1. Well, that's not going to mean very much to me to look at a float number between 0 and 1. I want the dollar amounts. I want to know what the cash value is. And we'll go ahead and run this, and you'll see it runs much quicker than the training. That's what's so wonderful about these neural networks. Once you put them together, it takes just a second to run the same neural network that took us, what, a half hour to train? Head and plot the data. We're going to plot what we think it's going to be, and we're going to plot it against the real data, what the Google stock actually did. So let's go ahead and take a look at that in code. And let's pull this code up. So we have our PLT. That's our, if you remember from the very beginning, let me just go back up to the top. We have our matplotlibary.pyplot as PLT. That's where that comes in. And we come down here, we're going to plot, and let me get my drawing thing out again. We're going to go ahead, and PLT is basically kind of like an object. It's one of the things that always threw me when I'm doing graphs in Python, because I always think you have to create an object, and then it loads that class in there. Well, in this case, PLT is like a canvas you're putting stuff on. So if you've done HTML5, you'll have the canvas object. This is the canvas. So we're going to plot the real stock price. That's what it actually is. And we're going to give that color red. So it's going to be in bright red, and we're going to label it real Google stock price. And then we're going to do our predicted stock, and we're going to do it in blue, and it's going to be labeled predicted. And we'll give it a title, because it's always nice to give a title to your graph, especially if you're going to present this to somebody, to your shareholders in the office. And the X label is going to be time, because it's a time series. And we didn't actually put the actual date and times on here, but that's fine. We just know they're incremented by time. And then, of course, the Y label is the actual stock price. PLT.legend tells us to build the legend on here so that the color red and real Google stock price show up on there. And then the plot shows us that actual graph. So let's go ahead and run this and see what that looks like. And you can see here we have a nice graph, and let's talk just a little bit about this graph before we wrap it up. Here's our legend I was telling you about. That's why we have the legend to show the prices. We have our title and everything. And you'll notice on the bottom we have a time sequence. We didn't put the actual time in here. Now we could have. We could have gone ahead and plotted the X, since we know what the dates are, and plotted this to dates. But we also know that it's only the last piece of data that we're looking at. So last piece of data, which ends somewhere probably around here on the graph. I think it's like about 20% of the data, probably less than that. We have the Google price, and the Google price has this little up jump and then down, and you'll see that the actual Google, instead of a turn down here, just didn't go up as high and didn't go down. So our prediction has the same pattern, but the overall value is pretty far off as far as stock. But then again, we're only looking at one column. We're only looking at the open price. We're not looking at how many volumes were traded. And like I was pointing out earlier, when we talk about stock, just right off the bat, there's 6 columns. There's open, high, low, close, volume. Then there's whether how many volume shares. Then there's the adjusted open, adjusted high, adjusted low, adjusted close. They have a special formula to predict exactly what it would really be worth based on the value of the stock. And then from there's all kinds of other stuff you can put in here. So we're only looking at one small aspect, the opening price of the stock. And as you can see here, we did a pretty good job. This curve follows the curve pretty well. It has like little jumps on it, bends. They don't quite match up. So this bend here does not quite match up with that bend there, but it's pretty darn close. We have the basic shape of it, and the prediction isn't too far off. And you can imagine that as we add more data in and look at different aspects in the specific domain of stock, we should be able to get a better representation each time we drill in deeper. Of course, this took a half hour for my computer to train, so you can imagine that if I was running it across all those different variables, it might take a little bit longer to train the data. Not so good for doing a quick tutorial like this. So we're going to dive right into what is Keras. We'll also go all the way through this into a couple of tutorials, because that's where you really learn a lot, is when you roll up your sleeves. So when we talk about what is Keras, Keras is a high-level deep learning API written in Python for easy implementation of neural networks. It uses deep learning frameworks such as TensorFlow, PyTorch, etc. as backend to make computation faster. And this is really nice because as a programmer, there is so much stuff out there and it's evolving so fast, it can get confusing. And having some kind of high-level order in there where you can actually view it and easily program these different neural networks is really powerful. It's really powerful to have something out really quick and also be able to start testing your models and seeing where you're going. So Keras works by using complex deep learning frameworks such as TensorFlow, PyTorch, MLPlayed. It's provided easy front end. And you can see here we have the Keras API specifications, and under that you'd have like TF Keras for TensorFlow, Thano Keras, and so on. And then you have your TensorFlow workflow that this is all sitting on top of. And this is, like I said, it organizes everything. The heavy lifting is still done by TensorFlow or whatever underlying package you put in there. And this is really nice because you don't have to dig as deeply into the heavy end stuff while still having a very robust package you can get up and running rather quickly. And it doesn't distract from the processing time because all the heavy lifting is done by packages like TensorFlow. This is the organization on top of it. So the working principle of Keras. The working principle of Keras is Keras uses computational graphs to express and evaluate mathematical expressions. And you can see here we put them in blue. They have the expression expressing complex problems as a combination of simple mathematical operators, where we have like the percentage, or in this case in Python that's usually your remainder, or multiplication. You might have the operator of x to the power of 0.3. And it is useful for calculating derivatives by using back propagation. So if we're doing with neural networks, when we send the error back up to figure out how to change it, this makes it really easy to do that without really not banging your head and having to handwrite everything. It's easier to implement distributed computation, and for solving complex problems, specify input and outputs and make sure all nodes are connected. And so this is really nice as you come in through, is that as your layers are going in there, you can get some very complicated different setups nowadays, which we'll look at in just a second. And this just makes it really easy to start spinning this stuff up and trying out the different models. So when we look at Keras models, Keras model, we have a sequential model. Sequential model is a linear stack of layers where the previous layer leads into the next layer. And this, if you've done anything else, even like the sklearn with their neural networks and propagation and any of these setups, this should look familiar. You should have your input layer, it goes into your layer 1, layer 2, and then to the output layer. And it's useful for simple classifier or decoder models. And you can see down here we have the model equals across sequential, and this is the actual code. You can see how easy it is. We have a layer that's dense, your layer 1. As an activation, they're using the ReLU in this particular example. And then you have your name layer 1, layer dense ReLU, name layer 2, and so forth. And they just feed right into each other. So it's really easy just to stack them, as you can see here, and it automatically takes care of everything else for you. And then there's a functional model. And this is really where things are at. This is new. Make sure you update your Keras, or you'll find yourself running this, doing the functional model. You'll run into an error code because this is a fairly new release. And it uses multi-input and multi-output model. The complex model which forks into 2 or more branches. And you can see here we have our image inputs equals your Keras input shape equals 32 by 32 by 3. You have your dense layers, dense 64 activation ReLU. This should look similar to what you already saw before, but if you look at the graph on the right, it's going to be a lot easier to see what's going on. You have 2 different inputs. And one way you could think of this is maybe one of those is a small image and one of those is a full-sized image. And that feedback goes into, you might feed both of them into one node because it's looking for one thing, and then only into one node for the other one. And so you can start to get kind of an idea that there's a lot of use for this kind of split and this kind of setup. Where you have multiple information coming in, but the information's very different even though it overlaps. And you don't want it to send it through the same neural network. And they're finding that this trains faster and also has a better result depending on how you split the data up and how you fork the models coming down. And so in here we do have the 2 complex models coming in. We have our image inputs, which is a 32 by 32 by 3, or 3 channels, or 4 if you're having an alpha channel. You have your dense, your layers, dense is 64 activation using the ReLU, very common. X equals dense inputs, X layers dense X64 activation equals ReLU, X outputs equals layers dense 10X, model equals Keras, model inputs equals inputs, outputs equals outputs, name equals minced model. So we add a little name on there. And again, this is this kind of split here. This is setting us up to have the input go into different areas. So if you're already looking at Keras, you probably already have this answer. What are neural networks? But it's always good to get on the same page, and for those people who don't fully understand neural networks, to dive into them a little bit or do a quick overview. Neural networks are deep learning algorithms modeled after the human brain. They use multiple neurons, which are mathematical operations, to break down and solve complex mathematical problems. And so just like the neuron, one neuron fires in and it fires out to all these other neurons, or nodes as we call them, and eventually they all come down to your output layer. And you can see here we have the really standard graph: input layer, a hidden layer, and an output layer. One of the biggest parts of any data processing is your data pre-processing. So we always have to touch base on that. With a neural network, like many of these models, they're kind of, when you first start using them, they're like a black box. You put your data in, you train it, and you test it and see how good it was. And you have to pre-process that data because bad data in is bad outputs. So in data pre-processing, we will create our own data examples set with Keras. The data consists of a clinical trial conducted on 2,100 patients, ranging from ages 13 to 100, with the patients under 65 and the other half over 65 years of age. We want to find the possibility of a patient experiencing side effects due to their age. And you can think of this in today's world with COVID, what's going to happen on there. And we're going to go ahead and do an example of that in our live hands-on. Like I said, most of this you really need to have hands-on to understand. So let's go ahead and bring up our Anaconda and open that up and open up a Jupyter notebook for doing the Python code in. Now, if you're not familiar with those, you can use pretty much any of your setups. I just like those for doing demos and showing people, especially shareholders. It really helps because it's a nice visual. So let me go ahead and flip over to our Anaconda. And the Anaconda has a lot of cool tools. They just added Datalore and IBM Watson Studio Cloud into the Anaconda framework. But we'll be in the Jupyter Lab or Jupyter Notebook. I'm going to do Jupyter Notebook for this because I use the lab for like large projects with multiple pieces because it has multiple tabs, where the notebook will work fine for what we're doing. And this opens up in our browser window because that's how Jupyter Notebook is set to run. And we'll go under New, create a new Python 3, and it creates an untitled Python. We'll go ahead and give this a title, and we'll just call this cross tutorial. And let's change that to capital. There we go. We'll go ahead and just rename that. And the first thing we want to go ahead and do is get some pre-processing tools involved. And so we need to go ahead and import some stuff for that, like our NumPy, do some random number generation. I mentioned sklearn or your scikit. If you're installing sklearn, the sklearn stuff, it's scikit you want to look up. That should be a tool of anybody who is doing data science. If you're not familiar with the sklearn toolkit, it's huge, but there's so many things in there that we always go back to. And we want to go ahead and create some train labels and train samples for training our data. And then just a note of what we're actually doing in here. Let me go ahead and change this. This is kind of a fun thing you can do. We can change the code to Markdown. And then Markdown code is nice for doing examples once you've already built this. Our example data, we're going to do experimental. There we go. Experimental drug was tested on 2,100 individuals between 13 to 100 years of age. Half the participants are under 65, and 95% of participants are under 65. Experienced no side effects, while 95% of participants over 65 experienced side effects. So that's kind of where we're starting at. And this is just a real quick example, because we're going to do another one with a little bit more complicated information. And so we want to go ahead and generate our setup. So we want to do for I and range, and we want to go ahead and create, if you look here, we have random integers, train the labels, append. So we're just creating some random data. And let me go ahead and just run that. And so once we've created our random data, and you can certainly ask for a copy of the code from Simplilearn. They'll send you a copy of this, or you can zoom in on the video and see how we went ahead and did our train samples append. And we're just using this. I do this kind of stuff all the time. I was running a thing on that had to do with errors following a bell-shaped curve on a standard distribution error. And so what do? I generate the data on a standard distribution error to see what it looks like and how my code processes it, since that was the baseline I was looking for. In this, we're just doing generating random data for our setup on here. And we could actually go in, print some of the data up. Let's just do this, print. We'll do train samples, and we'll just do the first 5 pieces of data in there to see what that looks like. And you can see the first 5 pieces of data in our train samples is 49, 85, 41, 68, 19. Just random numbers generated in there. That's all that is. And we generated significantly more than that. Let's see, 50 up here, 1,000. Yeah, so there's 1,000 here. 1,000 numbers we generated. And we could also, if we wanted to find that out, we could do a quick print the length of it. And so, or you could do a shape kind of thing, and if you're using NumPy, although the link for this is just fine. And there we go, it's actually 2,100, like we said in the demo setup in there. And then we want to go ahead and take our labels. Oh, that was our train labels. We also did samples, didn't we? So we could also print, do the same thing. Oh, labels. And let's change this to labels. And labels. And run that just to double check, and sure enough we have 2,100, and they're labeled 10, 10, 10. I guess that's if they have symptoms or not. 1 symptoms, 0 none. And so we want to go ahead and take our train labels and we'll convert it into a NumPy array, and the same thing with our samples. And let's go ahead and run that. And we also shuffle. This is just a neat feature you can do in NumPy right here. Put my drawing thing on, which I didn't have on earlier. I can take the data and I can shuffle it. So we have our, it just randomizes it. That's all that's doing. We've already randomized it, so it's kind of an overkill. It's not really necessary. But if you're doing a larger package where the data is coming in, and a lot of times it's organized somehow, and you want to randomize it just to make sure that the input doesn't follow a certain pattern that might create a bias in your model. And we go ahead and create a scalar. The scalar range, minimum max scalar, feature range 0 to 1. And then we go ahead and scale the scaled trained samples. So we're going to go ahead and fit and transform the data so it's nice and scaled. And that is the age. So you can see up here we have 49, 85, 41. We're just moving that so it's going to be between 0 and 1. And so this is true with any of your neural networks. You really want to convert the data to 0 and 1, otherwise you create a bias. So if you have like 100 creates a bias versus the math behind it gets really complicated. If you actually start multiplying stuff, because there's a lot of multiplication and addition going on in there, that higher end value will eventually multiply down, and it will have a huge bias as to how the model fits it, and then it will not fit as well. And then one of the fun things we can do in Jupyter Notebook is that if you have a variable and you're not doing anything with it, and it's the last one on the line, it will automatically print. And we're just going to look at the first 5 samples on here. And so it's going to print the first 5 samples. And you can see, here we go, 0.195, 0.791. So everything's between 0 and 1. And that just shows us that we scaled it properly and it looks good. It really helps a lot to do these kind of print-ups halfway through. You never know what's going to go on there. I don't know how many times I've gotten down and found out that the data sent to me that I thought was scaled was not. And then I have to go back and track it down and figure it out on there. So let's go ahead and create our artificial neural network. And for doing that, this is where we start diving into TensorFlow and Keras. TensorFlow, if you don't know the history of TensorFlow, it helps to jump into, we'll just use Wikipedia. Be careful, don't quote Wikipedia on these things because you get in trouble. But it's a good place to start. Back in 2011, Google Brain built Disbelief as a proprietary machine learning setup. TensorFlow became the open source for it. So TensorFlow was a Google product, and then it became open sourced, and now it's just become probably one of the de factos when it comes for neural networks as far as where we're at. So when you see the TensorFlow setup, it's got like a huge following. There are some other setups like the Scikit under the sklearn has their own little neural network, but the TensorFlow is the most robust one out there right now. And Keras sitting on top of it makes it a very powerful tool, so we can leverage both the Keras easiness in which we can build a sequential setup on top of TensorFlow. And so in here we're going to go ahead and do our input of TensorFlow, and then we have the rest of this is all Keras here from number 2 down. We're going to import from TensorFlow the Keras connection. And then you have your TensorFlow Keras models, import sequential. It's a specific kind of model. We'll look at that in just a second. If you remember from the files, that means it goes from one layer to the next layer to the next layer. There's no funky splits or anything like that. And then we have from TensorFlow Keras layers, we're going to import our activation and our dense layer. And we have our optimizer Atom. This is a big thing to be aware of, how you optimize your data. When you first do it, Atom's as good as any. Atom is usually, there's a number of optimizer out there. There's a couple of main ones, but Atom is usually assigned to bigger data. It works fine. Usually the lower data does it just fine, but Atom is probably the mostly used. But there are some more out there, and depending on what you're doing with your layers, your different layers might have different activations on them. And then finally down here you'll see our setup where we want to go ahead and use the metrics. And we're going to use the TensorFlow cross metrics for categorical cross entropy. So we can see how everything performs when we're done. That's all that is. A lot of times you'll see us go back and forth between TensorFlow, and then Scikit has a lot of really good metrics also for measuring these things. Again, it's the end of the at the end of the story. How good does your model do? And we'll go ahead and load all that, and then comes the fun part. I actually like to spend hours messing with these things. And 4 lines of code. You're like, you're going to spend hours on 4 lines of code? No, we don't spend hours on 4 lines of code. That's not what we're talking about when I say spend hours on 4 lines of code. What we have here, I'm going to explain that in just a second. We have a model, and it's a sequential model. If you remember correctly, we mentioned the sequential up here where it goes from one layer to the next. And our first layer is going to be your input. It's going to be what they call dense, which is usually it's just dense, and then you have your input and your activation. How many units are coming in? We have 16. What's the shape? What's the activation? And this is where it gets interesting, because we have in here ReLU on 2 of these and softmax activation on 1 of these. There are so many different options for what these mean and how they function. How does the ReLU, how does the softmax function? And they do a lot of different things. We're not going to go into the activations in here. That is what really you spend hours doing, is looking at these different activations. And just some of it is just almost like you're playing with it. Like an artist, you start getting a feel for like a inverse tangent activation, or the tan-H activation. Takes up a huge processing amount. So you don't see it a lot. Yet it comes up with a better solution, especially when you're doing when you're analyzing Word documents and you're tokenizing the words. And so you'll see this shift from one to the other because you're both trying to build a better model. And if you're working on a huge data set, it'll crash the system. It'll just take too long to process. And then you see things like softmax. Softmax generates an interesting setup where a lot of these, when you talk about ReLU, oops, let me do this. ReLU, there we go. ReLU has a setup where if it's less than 0, it's 0, and then it goes up. And then you might have what they call lazy setup, where it has a slight negative to it so that the errors can translate better. Same thing with softmax. It has a slight laziness to it so that errors translate better. All these little details make a huge difference on your model. So one of the really cool things about data science that I like is you build your what they call you build to fail. And it's an interesting design setup. Oops, I forgot the end of my code here. The concept of build to fail is you want the model as a whole to work, so you can test your model out, so that you can do you can get to the end and you can do your, let's see, where was it? Overshot down here. You can test out the quality of your setup on there. And see, where did I do my TensorFlow? Oh, here we go. It was right above me. There we go. We start doing your cross entropy and stuff like that. Is you need a full functional set of code so that when you run it, you can then test your model out and say, hey, it's either this model works better than this model, and this is why. And then you can start swapping in these models. And so when I say I spend a huge amount of time on pre-processing data, it's probably 80% of your programming time. Well, between those two, it's like 80-20. You'll spend a lot of time on the models. Once you get the model down, once you get the whole code and the flow down set, depending on your data, your models get more and more robust as you start experimenting with different inputs, different data streams, and all kinds of things. And we can do a simple model summary here. Here's our sequential, here's our layer, our output, a parameter. This is one of the nice things about Keras is you can see right here, here's our sequential 1 model. Boom, 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 boom. Everything's set and clear and easy to read. So once we have our model built, the next thing we're going to want to do is we're going to go ahead and train that model. And so the next step is, of course, model training. And when we come in here, this a lot of times is just paired with the model because it's so straightforward. It's nice to print out the model setup so you can have a tracking. But here's our model. The keyword in Keras is compile, optimizer atom, learning rate, another term right there that we're just skipping right over that really becomes the meat of the setup is your learning rate. So whoops, I forgot that I had an arrow, but I'll just underline it. A lot of times the learning rate set to 0.01. Depending on what you're doing, this learning rate can overfit and underfit. So you'd want to look up. I know we have a number of tutorials out on overfitting and underfitting that are really worth reading once you get to that point and understanding. And we have our loss, sparse categorical cross entropy. So this is going to tell Keras how far to go until it stops. And then we're looking for metrics of accuracy. So we'll go ahead and run that. And now that we've compiled our model, we want to go ahead and run it, fit it. So here's our model fit. We have our scale to train samples, our train labels, our validation split. In this case, we're going to use 10% of the data for validation. Batch size, another number you kind of play with. Not a huge difference as far as how it works, but it does affect how long it takes to run, and it can also affect the bias a little bit. Most of the time, though, a batch size is between 10 to 100, depending on just how much data you're processing in there. We want to go ahead and shuffle it. We're going to go through 30 epochs and put a verbose of 2. Let me just go ahead and run this. And you can see right here, here's our epoch, here's our training, here's our loss. Now, if you remember correctly up here, we set the loss. Let's see, where was it? Compiled our data. There we go, loss. So it's looking at the sparse categorical cross entropy. This tells us that as it goes, how much does the error go down? Is the best way to look at that. And you can see here, the lower the number, the better. It just keeps going down. And vice versa, accuracy we want, let's see, where's my accuracy? Value accuracy at the end. And you can see 0.619, 0.69, 0.74, it's going up. We want the accuracy, would be ideal if it made it all the way to 1. But we also, the loss is more important because it's a balance. You can have 100% accuracy and your model doesn't work because it's overfitted. Again, you want to look up overfitting and underfitting models. And we went ahead and went through 30 epochs. It's always fun to kind of watch your code going. To be honest, I usually the first time I run it, I'm like, oh, that's cool, I get to see what it does. And after the second time of running it, I'm like, I'd like to just not see that. And you can repress those, of course, in your code. Repress the warnings in the printing. And so the next step is going to be building a test set and predicting it now. So here we go. We want to go ahead and build our test set. And we have, just like we did our training set, a lot of times you just split your initial set up. But we'll go ahead and do a separate set on here. And this is just what we did above. There's no difference as far as the randomness that we're using to build this set on here. The only difference is that we already did our scalar up here. Well, that doesn't matter because the data is going to be across the same thing. But this should just be transform down here instead of fit transform. Because you don't want to refit your data on your testing data. There we go. And now we're just transforming it because you never want to transform the test data. Easy mistake to make, especially on an example like this where we're not doing You know, we're randomizing the data anyway, so it doesn't matter too much because we're not expecting something weird. And then we want to go ahead and do our predictions. The whole reason we built the model is we take our model, we predict, and we're going to do, here's our X-scale data, batch size 10, verbose, and now we have our predictions in here, and we could go ahead and do a, we'll print predictions, and then I guess I could just put down predictions in 5 so we can look at the first 5 of the predictions. And what we have here is we have our age and the prediction on this age versus what we think it's going to be, what we think is going to have symptoms or not. And the first thing we notice is that's hard to read because we really want a yes/no answer. So we'll go ahead and just round off the predictions using the argmax, the NumPy argmax for predictions. So it just goes to a 0, 1, and if you remember, this is a Jupyter Notebook, so I don't have to put the print. I can just put in rounded predictions, and we'll just do the first 5. And you can see here 0, 1, 0, 0, 0. So that's what the predictions are that we have coming out of this, is no symptoms, symptoms, no symptoms, symptoms, no symptoms. And just as we were talking about at the beginning, we want to go ahead and take a look at this. There we go. Confusion matrices for accuracy check. Most important part when you get down to the end of the story, how accurate is your model before you go and play with the model and see if you can get a better accuracy out of it. And for this, we'll go ahead and use the scikit, the sklearn metrics, scikit being where that comes from. Import confusion matrix, some iteration tools, and of course a nice matplot library. That makes a big difference, so it's always nice to have a nice graph to look at. Picture's worth 1,000 words. And then we'll go ahead and call it CM for confusion matrix, y true equals test labels, y predict rounded predictions. And we'll go ahead and load in our CM. And I'm not going to spend too much time on the plotting, going over the different plotting code. You can spend we have whole tutorials on how to do your different plotting on there. But we do have here is we're going to do a plot confusion matrix. There's our CM, our classes, normalized false, title, confusion matrix. CMAP is going to be in blues. And you can see here we have to the nearest CMAP, titles, all the different pieces, whether you put tick marks or not, the marks, the classes, the color bar. So a lot of different information on here as far as how we're doing the printing of the confusion matrix. You can also just dump the confusion matrix into a Seaborn and real quick get an output. It's worth knowing how to do all this when you're doing a presentation to the shareholders. You don't want to do this on the fly. You want to take the time to make it look really nice, like our guys in the back did. And let's go ahead and do this. Forgot to put together our CM plot labels. We'll go ahead and run that. And then we'll go ahead and call the definition for our mapping. And you can see here plot confusion matrix. That's the little script we just wrote. And we're going to dump our data into it. So our confusion matrix, our classes, title confusion matrix, and let's just go ahead and run that. And you can see here we have our basic setup. No side effects 195, had side effects 200, no side effects that had side effects. So we predicted the 10 of them who actually had side effects, and that's pretty good. I mean, I don't know about you, but you know, that's 5% error on this, and this is because there's 200 here. That's where I get 5% is divide these both by 2 and you get 5 out of 100. You can do the same kind of math up here. Not as quick on the fly because it's 15 and 195, not an easily rounded number. But you can see here where they have 15 people who predicted to have with the no side effects but had side effects kind of set up on there. And these confusion matrix are so important at the end of the day. This is really where you show whatever you're working on comes up, and you can actually show them, hey, this is how good we are or not, how messed up it is. So this was I spent a lot of time on some of the parts, but you can see here is really simple. We did the random generation of data, but when we actually built the model coming up here, here's our model summary, and we just have the layers on here that we built with our model on this, and then we went ahead and trained it and ran the prediction. Now we can get a lot more complicated. Let me flip back on over here because we're going to do another demo. So that was our basic introduction to it. We talked about the oops, here we go. Okay, so implementing a neural network with Keras. After creating our samples and labels, we need to create our Keras neural network model. We will be working with a sequential model which has 3 layers. And this is what we did. We had our input layer, our hidden layers, and our output layers. And you can see the input layer coming in was the age factor. We had our hidden layer, and then we had the output. Are you going to have symptoms or not? So we're going to go ahead and go with something a little bit more complicated. Training our model is a 2-step process. We first compile our model, and then we train it in our training data set. So we have compiling. Compiling converts the code into a form of understandable by machine. We use the atom in the last example, a gradient descent algorithm, to optimize the model, and then we trained our model, which means it let it learn on training data. And I actually had a little backwards there, but this is what we just did. Is if you remember from our code we just had, oops, let me go back here. Here's our model that we created, summarized. We come down here and we compile it. So it tells it, hey, we're ready to build this model and use it. And then we train it. And this is the part where we go ahead and fit our model and put that information in here, and it goes through the training on there. And of course we scaled the data, which was really important to do. And then you saw we did the creating a confusion matrix with Keras. As we are performing classifications on our data, we need a confusion matrix to check the results. A confusion matrix breaks down the various misclassifications as well as correct classifications to get the accuracy. And so you can see here, this is what we did with a true positive, false positive, true negative, false negative. And that is what we went over. Let me just scroll down here. On the end, we printed it out, and you can see we have a nice printout of our confusion matrix with the true positive, false negative, true negative. And so the blue ones, we want those to be the biggest numbers because those are the better side. And then we have our false predictions on here as far as this one. So it had no side effects, but we predicted, let's see, no side effects predicting side effects and vice versa.
If getting your learning started is half the battle, what if you could do that for free? Visit SkillUp by Simplilearn. Click on the link in the description to know more.
Now, saving and loading models with Keras. We're going to dive into a more complicated demo. And you're going to say, oh, well, that was a lot of complication before. Well, if you broke it down, we randomized some data, we created the Keras setup, we compiled it, we trained it, we predicted, and we ran our matrix. So we're going to dive into something a little bit more fun. Is we're going to do a face mask detection with Keras. So we're going to build a Keras model to check if a person is wearing a mask or not in real time. And this might be important if you're at the front of a store. This is something today which is might be very useful as far as some of our, making sure people are safe. And so we're going to look at mask and no mask. And let's start with a little bit on the data. And so in my data I have with a mask. You can see they just have a number of images showing the people in masks. And again, if you want some of this information, contact Simplilearn, and they can send you some of the information as far as people with and without masks, so you can try it on your own. And this is just such a wonderful example of this setup on here. So before I dive into the mask detection, talking about being in the current with COVID and seeing if people are wearing masks, this particular example I had to go ahead and update to a Python 3.8 version. It might run in a 3.7, I'm not sure. I kind of skipped 3.7 and installed 3.8. So I'll be running in a Python 3.8, and then you also want to make sure your TensorFlow is up to date, because they call functional layers, that's where they split, if you remember correctly from back. Let's take a look at this. Remember from here, the functional model, And a functional layer allows us to feed in the different layers into different nodes into different layers and split them. Very powerful tool, very popular right now in the edge of where things are with neural networks and creating a better model. So I've upgraded to Python 3.8, and let's go ahead and open that up and go through our next example, which includes multiple layers, programming it to recognize whether someone wears a mask or not, and then saving that model so we can use it in real time. So we're actually almost a full end-to-end development of a product here. Of course, this is a very simplified version, and there'd be a lot more to it. You'd also have to do like recognizing whether it's someone's face or not. All kinds of other things go into this. So let's go ahead and jump into that code, and we'll open up a new Python 3. Oops, Python 3. It's working on it. There we go. And then we want to go ahead and train our mask. We'll just call this train mask. And we want to go ahead and train mask and save it. So it's save mask, train mask detection, not to be confused with masking data. A little bit different. We're actually talking about a physical mask on your face. And then from the cross standpoint, we got a lot of imports to do here. And I'm not going to dig too deep on the imports. We're just going to go ahead and notice a few of them. So we have in here, oops, let me go Alt-D, there we go. Have something to draw with a little bit here. We have our image processing, and the image processing right here, let me underline that, deals with how do we bring images in, because most images are like a square grid, and then each value in there has 3 values for the 3 different colors. Keras and TensorFlow do a really good job of working with that, so you don't have to do all the heavy listening and figuring out what's going to go on. We have the mobile net average pooling 2D. This again is how do we deal with the images and pulling them. Dropout's a cool thing worth looking up. If you haven't, as you get more and more into Keras and TensorFlow, it'll auto drop out certain nodes. That way you'll get a better, the nodes just kind of die. They find that they actually create more of a bias than a help, and they also add processing time, so they remove them. And then we have our flatten. That's where you take that huge array with the 3 different colors and you find a way to flatten it so it's just a one-dimensional array instead of a 2 by 2 by 3. Dense input, we did that in the other one, so that should look a little familiar. Oops, there we go. Our input, our model, again, these are things we had on the last one. Here's our optimizer with our atom. We have some pre-processing on the input that goes along with bringing in the data in. More pre-processing with image to array, loading the image. This stuff is so nice. It looks like a lot of work, so you have to import all these different modules in here. But the truth is it does everything for you. You're not doing a lot of pre-processing. You're letting the software do the pre-processing. And we're going to be working with the setting something to categorical. Again, that's just a conversion from a number to a category. 0, 1 doesn't really mean anything. It's like true, false. Label binarizer, the same thing. We're changing our labels around. And then there's our train test split classification report. Our IM utilities, let me just go ahead and scroll down here a notch for these. This is something a little different going on down here. This is not part of the TensorFlow or the sklearn. This is the scikit setup in TensorFlow above. The paths, this is part of OpenCV, and we'll actually have another tutorial going out with the OpenCV. So if you want to know more about OpenCV, you'll get a glance on it in this software, especially the second piece when we reload up the data and hook it up to a video camera. We're going to do that on this round. But this is part of the OpenCV thing, and you'll see CV2 is usually how that's referenced. But the IM utilities has to do with how do you rotate pictures around and stuff like that, and resize them. And then the matplot library for plotting, because it's nice to have a graph, tells us how good we're doing, and then of course our numpy numbers array and just a straight OS access. Wow. So that was a lot of imports. Like I said, I'm not going to spend, I spent a little time going through them, but we didn't want to go too much into them. And then I'm going to create some variables that we need to go ahead and initialize. We have the learning rate, number of epochs to train for, and the batch size. And if you remember correctly, we talked about the learning rate to the negative 4.00001. A lot of times it's 0.001 or 0.001. Usually it's in that variation depending on what you're doing and how many epochs, and they kind of play with the epochs. The epochs is how many times we're going to go through all the data. And now I have it as 2. The actual setup is for 20, and 20 works great. The reason I have it for 2 is it takes a long time to process. One of the downsides of Jupyter is that Jupyter isolates it to a single kernel. So even though I'm on an 8-core processor with 16 dedicated threads, only one thread is running on this, no matter what. So it doesn't matter. So it takes a lot longer to run, even though TensorFlow really scales up nicely. And the batch size is how many pictures do we load at once and process. Again, those are numbers you have to learn to play with depending on your data and what's coming in. And the last thing we want to go ahead and do is there's a directory with a data set we're going to run. And this just has images of masks and not masks. And if we go in here, you'll see data set. And then you have pictures with masks. They're just images of people with masks on their face. And then we have the opposite. Let me go back up here. Without masks. So it's pretty straightforward. They look kind of askew because they tried to format them into very similar setup on there. So they're mostly squares. You'll see some that are slightly different on here. And that's kind of an important thing to do on a lot of these data sets. Get them as close as you can to each other. And we actually will run in this processing of images up here and the cross layers and importing and dealing with images. It does such a wonderful job of converting these that a lot of it we don't have to do a whole lot with. So you have a couple things going on there. And so we're now going to be, this is now loading the images. And let me see. And we'll go ahead and create data and labels. Here's our here's the features going in, which is going to be our pictures, and our labels going out. And then for categories in our list directory, and if you remember, I just flashed that at you. It had face mask or no face mask. Those are the two options. And we're just going to load into that. We're going to append the image itself and the labels. So we're just going to create a huge array. And you can see right now this could be an issue if you had more data. At some point, thankfully I have a 32 gig hard drive or RAM. Even that, you could do with a lot less of that. Probably under 16 or even 8 gigs would easily load all this stuff. And there's a conversion going on in here. I told you about how we are going to convert the size of the image so it resizes all the images. And that way our data is all identical the way it comes in. And you can see here with our labels, we have without mask, without mask, without mask. The other one would be with mask. Those are the two that we have going in there. And then we need to change it to the one-hot encoding. And this is going to take our, up here we had, what was it, labels and data. We want the labels to be categorical. So we're going to take labels and change it to categorical, and our labels then equal a categorical list. We'll run that. And again, if we do labels and we just do the last or the first 10, let's do the last 10 just because minus 10 to the end. There we go. Just so we can see what the other side looks like. We now have 1. That means they have a mask. 1, 0, 1, 0, so on. 1 being they have a mask and 0 no mask. And if we did this in reverse, I just realized that this might not make sense if you've never done this before. Let me run this. 0, 1. So 0 is, do they have a mask on? 0. Do they not have a mask on? 1. So this is the same as what we saw up here without mask. 1 equals, the second value is without mask. So with mask, without mask. And that's just with any of your data processing, we can't really, if you have a 0, 1 output, it causes issues as far as training and setting it up. So we always want to use a one-hot encoder if the values are not actual linear value or regression values, are not actual numbers, if they represent a thing. And so now we need to go ahead and do our train X, test X, train Y, test Y, train, split, test data. And we'll go ahead and make sure it's going to be random, and we'll take 20% of it for testing and the rest for setting it up as far as training their model. This is something that's become so cool. When they're training these sets, they realize we can augment the data. What does augment mean? Well, if I rotate the data around and I zoom in, I zoom out, I rotate it, shear it a little bit, flip it horizontally, fill mode, as I do all these different things to the data, it is able to, it's kind of like increasing the number of samples I have. So if I have all these perfect samples, what happens when we only have part of the face, or the face is tilted sideways, or all those little shifts cause a problem if you're doing just a standard set of data. So we're going to create an augment in our image data generator, which is going to rotate, zoom, and do all kinds of cool things. And this is worth looking up, this image data generator and all the different features it has. A lot of times, the first time through my models, I'll leave that out because I want to make sure there's a thing what we call build to fail, which is just cool to know. You build the whole process, and then you start adding these different things in so that you can better train your model. And so we go and run this, and then we're going to load. And then we need to go ahead, and you probably would have gotten an error if you hadn't put this piece in right here. I haven't run it myself because the guys in the back did this. But we take our base model, and one of the things we want to do is we want to do a MobileNet v2. And this is a big thing right here. Include the top equals false. A lot of data comes in with a label on the top row. So we want to make sure that that is not the case. And then the construction of the head of the model that will be placed on the top of the base model. We want to go ahead and set that up. And you'll see a warning here. I'm kind of ignoring the warning because it has to do with the size of the pictures and the weights for input shape. So it'll switch things to defaults, just saying, hey, we're going to auto shape some of this stuff for you. You should be aware that with this kind of imagery, we're already augmenting it by moving it around and flipping it and doing all kinds of things to it. So that's not a bad thing in this. But in other data, it might be if you're working in a different domain. And so we're going to go back here, and we're going to have, we have our base model. We're going to do our head model equals our base model output. And what we got here is we have an average pooling 2D, pool size 7.7 head model. Head model flatten, so we're flattening the data. So this is all processing and flattening the images. And the pooling has to do with some of the ways it can process some of the data. We'll look at that a little bit when we get down to the lower level and just processing it. And then we have our dense. We've already talked a little bit about a dense, just what you think about. And then the head model has a dropout of 0.5. What we can do with a dropout, the dropout says that we're going to drop out a certain amount of nodes while training. So when you actually use the model, it will use all the nodes. But this drops certain ones out, and it helps stop biases from forming. So it's really a cool feature in here. They discovered this a while back. We have another dense mode, and this time we're using softmax activation. Lots of different activation options here. Softmax is a real popular one for a lot of things, and so is the ReLU. And you know, we could do a whole talk on activation formulas and what their different uses are and how they work. When you first start out, you'll use mostly the ReLU and the softmax for a lot of them, just because they're some of the basic setups. It's a good place to start. And then we have our model equals model, inputs equals base model dot input, outputs equals head model. So again, we're still building our model here. We'll go ahead and run that. And then we're going to loop over all the layers in the base model and freeze them so they will not be updated during the first training process. So for layer and base model layers, layers.trainable equals false. A lot of times when you go through your data, you want to kind of jump in partway through. I'm not sure why in the back they did this for this particular example, but I do this a lot when I'm working with series and specifically in stock data. I want it to iterate through the first set of 30 data before it does anything. I would have to look deeper to see why they froze it on this particular one. And then we're going to compile our model. So compiling the model, atom, init, layer, decay, initial learning rate over epochs, and we go ahead and compile. Our loss is going to be the binary cross entropy, which will have that print out. Optimizer for opt, metrics is accuracy. Same thing we had before, not a huge jump as far as the previous code. And then we go ahead and we've gone through all this, and now we need to go ahead and fit our model. So train the head of the network, print info training head, run. Now I skipped a little time because you'll see the run time here is at 80 seconds per epoch. It takes a couple minutes for it to get through on a single kernel. One of the things I want you to notice on here while it's finishing the processing is that we have up here our augment going on. So anytime the train X and train Y go in, there's some randomness going on there and is jiggling it around what's going into our setup. Of course, we're batch sizing it, so it's going through whatever we set for the batch values, how many we process at a time. And then we have the steps per epoch, the train X, the batch size, validation data. Here's our test X and test Y where we're sending that in. And this, again, it's validation. One of the important things to know about validation is when both our training data and our test data have about the same accuracy, that's when you want to stop. That means that our model isn't biased. If you have a higher accuracy on your testing, you've trained it, and your accuracy is higher on your actual test data, then something in there is probably has a bias and it's overfitted. So that's what this is really about right here with the validation data and validation steps. So it looks like let me go ahead and see if it's done processing. It looks like we've gone ahead and gone through 2 epochs. Again, you could run this through about 20 with this amount of data, and it would give you a nice refined model at the end. We're going to stop at 2 because I really don't want to sit around all afternoon, and I'm running this on a single thread. So now that we've done this, we're going to need to evaluate our model and see how good it is. And to do that, we need to go ahead and make our predictions. These are our predictions on our test X to see what it thinks are going to be. So now it's going to be evaluating the network, and then we'll go ahead and go down here, and we will need to turn the indexing, because remember it's either 0 or 1. It's 0, 1, 0, 1. So you have 2 outputs: not wearing a mask, not wearing a mask. And so we need to go ahead and take that argument at the end and change those predictions to a 0 or 1 coming out. And then to finish that off, we want to go ahead and let me just put this right in here and do it all in one shot. We want to show a nicely formatted classification report so we can see what that looks like on here. And there we have it. We have our precision. It's 97% with a mask. There's our F1 score, support without a mask, 97%. So that's pretty high setup on there. You 3 people are going to sneak into this store who are without a mask and thinks they have a mask, and there's going to be 3 people with a mask that's going to flag the person at the front to go, oh, hey, look at this person, he might not have a mask. That's I guess if it's a setup in front of a store. So there you have it. And of course, one of the other cool things about this is if someone's walking into the store and you take multiple pictures of them, this is just it would be a way of flagging, and then you can take that average of those pictures and make sure they match or don't match if you're on the back end. And this is an important step because this is just cool. I love doing this stuff. So we're going to go ahead and take our model and we're going to save it. So model save maskdetector.model. We're going to give it a name. We're going to save the format. In this case, we're going to use the H5 format. And so this model we just programmed has just been saved. So now I can load it up in model. Now they can use it for whatever. And then if I get more information and we start working with that, at some point I might want to update this model, make a better model. And this is true of so many things, where I take this model and maybe I'm running a prediction on making money for a company, and as my model gets better, I want to keep updating it, and then it's real easy just to push that out to the actual end user. And here we have a nice graph. You can see the training loss and accuracy as we go through the epochs. We only did the, only shows just the one epoch coming in here, but you can see right here as the value loss, train accuracy, and value accuracy start switching and they start converging. And you'll hear converging. This is a convergence they're talking about when they say I know when I work in the scikit with sklearn neural networks, this is what they're talking about, a convergence, is our loss and our accuracy come together, and also up here, and this is why I'd run it more than just 2 epochs. As you can see, they still haven't converged all the way. So that would be a cue for me to keep going. But what we want to do is we want to go ahead and create a new Python 3 program. And we just did our train mask. So now we're going to go ahead and import that and use it and show you in a live action. Get a view of both myself in the afternoon along with my background of an office, which is in the middle still of reconstruction for another month. And we'll call this mask detector. And then we're going to grab a bunch of a few items coming in. We have our MobileNet v2 import preprocessing input, so we're still going to need that. We still have our TensorFlow image to array. We have our load model. That's where most of the stuff's going on. This is our CV2 or OpenCV. Again, I'm not going to dig too deep into that. We're going to flash a little OpenCV code at you, and we actually have a tutorial on that coming out. Our NumPy array, our IM utilities, which is part of the OpenCV or CV2 setup. And then we have, of course, time and just our operating system. So those are the things we're going to go ahead and set up on here. And then we're going to create, this takes just a moment. Our module here, which is going to do all the heavy lifting. So we're going to detect and predict a mask. We have frame, FaceNet, MaskNet. These are going to be generated by our OpenCV. We have our frame coming in, and then we want to go ahead and create a mask around the face. So it's going to try to detect the face and then set that up so we know what we're going to be processing through our model. And then there's a frame shape here. This is just our height versus width. That's all HW stands for. They've called it blob, which is a CV2 DNN blob form image frame. So this is reformatting this frame that's going to be coming in literally from my camera. And we'll show you that in a minute, that little piece of code that shoots that in here. And we're going to pass the blob through the network and obtain the face detections. So FaceNet.setImport blob, detections FaceNet forward, print detections shape. So this is what's going on here. This is that model we just created. We're going to send that in there, and I'll show you in a second where that is, but it's going to be under FaceNet. And then we go ahead and initialize our list of faces, their corresponding locations, and the list of predictions from our face mask network. We're going to loop over the detections, and this is a little bit more work than you think as far as looking for different faces. What happens if you have a crowd of faces? So we're looping through the detections and the shapes going through here. And probability associated with the detection. Here's our confidence of detections. We're going to filter out weak detection by ensuring the confidence is greater than the minimum confidence. So we've set it, remember, 0 to 1. So 0.5 would be our minimal confidence, probably is pretty good. And then we're going to put in compute bounding boxes for the object. If I'm zipping through this, it's because we're going to do an OpenCV, and I really want to stick to just the Keras part. And so I'm just kind of jumping through all this code. You can get a copy of this code from Simplilearn and take it apart, or look for the OpenCV coming out. And we'll create a box. The box sets it around the image. Ensure the bounding boxes fall within the dimensions of the frame. So we create a box around what we hope is going to be the face. Extract the face, ROI, convert it from BGR to RGB channel. Again, this is an OpenCV issue. Not really an issue, but it has to do with the order. I don't know how many times I've forgotten to check the order colors when working with OpenCV. Causes all kinds of fun things when red becomes blue and blue becomes red. And we're going to go ahead and resize it, process it, frame it, face frame, setup. Again, the face, the CVT color, we're going to convert it. We're going to resize it, image to array, pre-process the input, pin the face, locate face, start X, start Y, and X. Boy, that was just a huge amount, and I skipped over a ton of it, but the bottom line is we're building a box around the face, and that box, because the OpenCV does a decent job of finding the face, and that box is going to go in there and see, hey, does this person have a mask on it? And so that's what all this is doing on here. And then finally we get down to this where it says predictions equals masknet.predict faces batch size 32. So these different images of where we're guessing where the face is are then going to go through and generate an array of faces, if you will. And we're going to look through and say, does this face have a mask on it? And that's what's going right here is our prediction. That's the big thing that we're working for. And then we return the locations and the predictions. The location just tells where on the picture it is, and then the prediction tells us what it is. Is it a mask or is it not a mask? Alright, so we've loaded that all up. So we're going to load our serialized face detector model from disk. And we have the path that it was saved in. Obviously, you're going to put it in a different path depending on where you have it or however you want to do it and how you saved it on the last one where we trained it. And then we have our weights path. And so finally our facenet, here it is, equals cv2.dnn.readnet prototext path weights path. And we're going to load that up on here. So let me go ahead and run that. And then we also need to, I'll just put it right down here. I always hate separating these things in there. And then we're going to load the actual mask detector model from disk. This is the model that we saved. So let's go ahead and run that on there also. So this is pulling in all the different pieces we need for our model. And then the next part is we're going to open up our video. And this is just kind of fun because it's all part of the OpenCV video setup. And let me just put this all in as one. There we go. So we're going to go ahead and open up our video. We're going to start it and we're going to run it until we're done. And this is where we get some real kind of live action stuff, which is fun. This is what I like working about with images and videos, is that when you start working with images and videos, it's all right there in front of you. It's visual and you can see what's going on. So we're going to start our video streaming. This is grabbing our video stream source 0 start. That means it's grabbing my main camera I have hooked up. And then, starting video, you're going to print it out. Here's our video source equals 0 start. Loop over the frames from the video stream. Oops, a little redundancy there. Let me close. I'll just leave it. That's how they had it in the code. So while true, we're going to grab the frame from the threaded video stream and resize it to have the maximum width of 400 pixels. So here's our frame. We're going to read it from our visual stream. We're going to resize it. And then we're returning. Remember, we returned from our procedure the location and the prediction. So detect and predict mask. We're sending it the frame. We're sending it the face net and the mask net. So we're sending all the different pieces that say this is what's going through on here. And then it returns our location and predictions, and then for our box and predictions in the location and predictions. And the box is again, this is an OpenCV set that says, hey, this is a box coming in from the location. Because you have the two different points on there. And then we're going to unpack the box and predictions, and we're going to go ahead and do mask without a mask equals prediction. We're going to create our label. No mask, we're going to create color. If the label equals mask, L00225. And you know, this is going to make a lot more sense when I hit the run button here. But we have the probability of the label. We're going to display the label in bounding box rectangle in the output frame. And then we're going to go ahead and show the output from the frame, CV2 IM show frame. And then the key equals CV2 wait key 1. We're just going to wait till the next one comes through from our feed. And we're going to do this until we hit the stop button pretty much. So are you ready for this? Let's see if it works. We've distributed our model. We've loaded it up into our distributed code here. We've got it hooked into our camera, and we're going to go ahead and run it. And there it goes. It's going to be running, and we can see the data coming down here, and we're waiting for the pop-up. And there I am in my office with my funky headset on. And you can see in the background my unfinished wall, and it says up here, no mask. Oh no, I don't have a mask on. I wonder if I cover my mouth, what would happen? You can see my no mask goes down a little bit. I wish I'd brought a mask into my office. It's up at the house. But you can see here that this says, you know, there's a 95, 98% chance that I don't have a mask on. And it's true, I don't have a mask on right now. And this could be distributed. This is actually an excellent little piece of script that you could start, you install somewhere on a video feed on a security camera or something, and then you'd have this really neat setup saying, hey, do you have a mask on when you enter a store or public transportation or whatever it is where they're required to wear a mask? Let me go ahead and stop that. Now, if you want a copy of this code, definitely give us a holler. We will be going into OpenCV in another one, so I skipped a lot of the OpenCV code in here as far as going into detail. Really focusing on the Keras, saving the model, uploading the model, and then processing a streaming video through it so you can see that the model works. We actually have this working model that hooks into the video camera, which is just pretty cool and a lot of fun. So I told you we're going to dive in and really roll up our sleeve and do a lot of coding today. We did the basic demo up above for just pulling in a Keras, and then we went into a Keras model where we pulled in data to see whether someone was wearing a mask or not. So very useful in today's world as far as a fully running application.
Artificial intelligence or AI is transforming our world, making things faster and more efficient. But what happens when AI makes mistakes? When AI is biased? It can have serious consequences for companies and people's lives. Imagine missing out on a job, being wrongly identified in a photo, or being unfairly treated, all because a computer program made a bad decision. These mistakes don't just harm individuals, they can affect entire communities without realizing it. So AI bias is also called algorithmic bias. Happens when AI systems unintentionally favor one group over another. Take healthcare. For example, if the data used to train an AI system doesn't include enough women or people from minority groups, the system might not work as well for them. This can lead to incorrect medical prediction, like giving black patients less accurate results than white patients. In job hiring, AI can unintentionally promote certain stereotypes, like when job ads use terms like ninja, which may attract more men than women, even though the term isn't a requirement for the job. Even in creative areas like image generation, AI can reinforce biases. When asked to create pictures of CEOs, AI systems often show mostly white men, leaving out women and people of color. In law enforcement, AI tools sometimes rely on biased data, which can unfairly target minority communities. So in this video, we will explore some well-known examples of AI bias and how these mistakes are impacting people and society, from healthcare to hiring and even criminal justice. AI bias is something we need to understand and fix. So let's dive in and learn how these biases happen and what can be done to stop them.
Craving a career upgrade? Subscribe, like, and comment below. Dive into the link in the description to fast-track your ambitions. Whether you're making a switch or aiming higher, Simplilearn has your back.
But before we start, here is a quick info for you. Dive into the future of AI with our generative AI and machine learning course in collaboration with ENICT, Academy IIT Guwahati. Learn tools like ChatGPT, OpenAI, Hugging Face, Python, and more. Join masterclass led by IITG faculty, engage in hands-on project, and earn executive alumni status. So find the course link from the description box below and the pinned comment. So without any further ado, let's get started. So what is AI bias? AI bias, also called machine learning bias, happens when human biases affect the data used to train AI system, causing unfair or inaccurate results. When AI bias isn't fixed, it can hurt a business success and prevent some people from fully participating in the economy or society. Biases makes AI less accurate, which reduce its effectiveness. Businesses may struggle to benefit from systems that give unfair results, and scandals from AI bias can lead to loss of trust, especially among groups like people of color, women, people with disabilities, and the LGBTQ community. AI models often learn from the data that reflects society biases. This can lead to unfair treatment of marginalized groups in the areas like hiring, policing, and credit scoring. As the Wall Street Journal notes, businesses still find it challenging to address these widespread biases as the AI use grows. So moving forward, let's see some sources of AI bias. Distorted outcomes can negatively affect both organization and society as a whole. So here are some common forms of AI bias. The first one is algorithm bias. If the problem or question is not well defined or the feedback provided to the machine learning algorithm is inadequate, the result may be inaccurate or misleading. The second one is cognitive bias. Since AI systems rely on a human input, they can be affected by unconscious human biases, which may influence either the dataset or the model's behavior. The third one, confirmation bias. This occurs when the AI overly depends on existing beliefs or trends in the data, reinforcing prior biases and failing to detect new patterns or trends. The fourth one, execution bias. When important data is omitted from the dataset, often due to the developer overlooking new or crucial factors, this type of bias arises. The fifth one, measurement biases. So this bias stems from incomplete data, such as when a dataset fails to represent the entire population. For instance, if a college analyzes only graduates to determine success factors, it would overlook reasons why others drop out. So moving forward, let's see how to avoid bias. So here are checklists of 6 process steps that can keep AI programs free of bias. The first one is choose the right model. Ensure diverse stakeholders select training data in supervised model and integrate bias detection tools in unsupervised models. The second one, use accurate data. Train AI with complete balanced data that reflects the true demographics. The third one, build a diverse team. A varied team helps spot bias, including innovators, creators, implementers, and end users. The next one, watch data processing. Bias can appear during any phase of processing, so stay vigilant throughout. The fifth one, monitor regularly. So continuously test models and have independent assessment to detect and fix biases. And the last one, check infrastructure. Ensure technological tools and sensors are functioning properly to avoid hidden biases. So conclusion is AI biases poses serious challenges by amplifying existing societal biases, affecting individuals and businesses. From healthcare to hiring, AI system can unintentionally reinforce stereotypes and inequalities.
Welcome to the Retrieval Augmented Generation for Beginners course by Simplilearn. So in this course, we will understand initially the introduction to RAG, and then we will get into the components of RAG, and after that, we will dive deep into the data loading as well as text splitting, and then we will see storing the chunks in vector stores and embeddings, and then we will see how to retrieve the data. The most importantly, we will build a multi-document agent, and finally, we will conclude the course. So let us begin with the first chapter, that is Introduction to Retrieval Augmented Generation. So let us begin with the first chapter, that is the Introduction to Retrieval Augmented Generation. So imagine you are chatting with an AI and you ask it a question. Who won the FIFA World Cup in 2022? The AI can't just guess. It needs real information. But most language models like the ChatGPT are only trained up to a certain point in time. So if something happened after their training, they wouldn't know about it. Then their RAG comes. The short for Retrieval Augmented Generation solves this problem. So let us now understand what is RAG. RAG is like giving your AI a powerful search engine buddy. So instead of depending only on what it remembers from its training, it also retrieves the latest and the most relevant information from a connected source, like a document, knowledge base, or even the web, and then uses the information to generate a better response. So, RAG is equal to retrieval, that is find information, plus generation, that is writing answers. Think of it as a student taking an open book test. First, they look up the question and then they explain it in their own words. So, the question arises, why does it even matter? So, here's the thing. Most traditional language models have a knowledge cutoff. That means they don't know anything that happened after a specific date. So, RAG helps fix these problems. It improves accuracy by pooling the real information when needed. Then it provides the up-to-date responses, even if the AI was trained years ago. Then it reduces hallucination because it uses facts instead of making educated guesses. Then it makes AI more trustworthy in the critical tasks like the legal, healthcare, or even enterprise search. Now let us move and see what are its use cases. So RAG is super useful in many real-world situations, especially when accuracy and up-to-date knowledge are important. So here are a few examples. The first example we have is customer support bots. They can pull answers from the help docs, facts, or internal knowledge bases to give the relevant and the accurate responses. Then we have enterprise search. So employees can ask questions and get answers from the company documents, manuals, or the HR policies. Then we have healthcare. Doctors can ask about treatment guidelines and RAG pulls information from the recent medical research papers. Then we have legal. The law firms can use RAG to find and summarize the case laws from a massive legal document repository. Then we have education. And students can ask questions and then AI finds the best answer from the textbooks or notes. So now let's move on and see how does RAG work. So let's break it down into the simple steps. The first step is the user asks a question. Then you type something like, what are the side effects of aspirin? And then step 2 is retrieve. So instead of only relying on its memory, the AI first searches a connected database like medical documents, articles, or PDFs. So this is done using something called a retriever model like the BM25 or dense vector search. Then we have the third step as augment. The most relevant documents or snippets are selected and combined with your question. And then we have our fourth step, that is generate. Now the language model like the GPT or the BERT takes this context and generates a final answer based on the real information it just retrieved. It's like asking a librarian a question and that is compared with AI. The librarian doesn't just answer from the memory. They first find the right book, that is the retriever here, and then read the right page, that is the augmentation, and then explain the answer to you in simple language, and that is generation. Then let's move on to the next chapter and see the core components of RAG pipeline. In this chapter, we will understand about the core components of the RAG pipeline. So to understand how retrieval augmented generation works, we first need to meet its core building blocks. The RAG pipeline is not a single model. It's a smart system made up of multiple documents, each playing a unique role. So here's a quick overview of the 6 major components. So what are the components of the RAG pipeline? The first component we have is query encoder. Then we have retriever. The third one is the knowledge base, also known as the document store. Then we have the re-ranker. The fifth one is the generator, that is a language model. And then finally we have the last one as feedback logo. Now let's break down each one to see what it does and how it helps the RAG system. The first we have query encoder. So what it does? The query encoder takes the user's question like what are the benefits of green tea, and it turns into a mathematical formula called a vector. So this makes the question searchable by the machines. Now, how it helps RAG? So without encoding, the system can't compare your question to the information in the knowledge base. The encoder makes sure that your query is in a format the retriever can understand and match with the relevant content. Then let's move on to the second one. We have retriever. So what it does, the retriever uses the encoded query to search through the knowledge base and fetch the top matching documents or passages. So how it helps the RAG? This is where the RAG starts becoming powerful. So instead of relying on the model's memory, it now brings in fresh, real-world data from the trusted sources. Now, this also boosts the accuracy and reduces hallucinations. Then let's move on to the third one. We have knowledge base, that is the document store. So the knowledge base is the library that holds all your searchable content, like the PDFs, support documents, manuals, research papers, and etc. So how it helps RAG? This is where the truth lives. A well-structured, regularly updated knowledge base ensures your AI assistant can retrieve the current and the reliable information. Then let's move on to the fourth one. We have re-rank. So after the retriever pulls the top end documents, the re-ranker re-evaluates and reorders them based on the relevance to the question. Then how it helps RAG? So sometimes the retriever brings okay results, but not in the best order. So the re-ranker acts as a quality checker, pushing the most useful documents to the top before the generator even sees them. Now let's move on to the next one. We have generator, that is the language model. So this is your AI's voice. The generator, like the GPT, takes a question plus top documents and crafts a human-like informative answer. So this is where the magic happens. Instead of guessing based on training data, the model now uses retrieved facts to generate the grounded, accurate responses. Now moving on to the sixth one, we have feedback loop. So the feedback loop collects user reactions like the upvotes, downvotes, or clicks and feeds that back into the system. So the feedback loop collects user actions like upvotes, downvotes, or clicks and feeds that back into the system. So how it helps RAG? So this loop helps the RAG system learn over time. So if users consistently like certain responses or sources, the system adjusts to prioritize them next time. It also helps to retain or fine-tune the retriever and re-ranker. Now let's move on to the next and see the results. In this chapter, we will learn about the document loading and splitting. So in order to create an application where you can have a conversation with your data, you first have to load your data into a format where it can be worked with. That's when Langchain document loaders come into play. We have over 80 different types of document loaders, and in this lesson, we will cover a few to get comfortable with the concept in general. So let's jump in. So let's understand what are loaders. So loaders deal with the specifics of accessing and converting data from a variety of different formats and sources into the standardized format. There can be various places where we can load our data from, like the websites, databases, and YouTube, and many more. And these documents become converted into the data types like PDFs, HTML, JSON, Word, PowerPoint, and more. And so the purpose of different data loaders is to take this variety of data sources and load them into a standard document object, which consists of the content and then associated metadata. So there are various types of document loaders in Langchain. It's not possible to cover them all, but here we have a rough. The first one is public unstructured. So the data that is freely available to everyone, but doesn't have a fixed format. For example, the social media post, blogs, articles, and YouTube videos. Then we have public structured. So here, the freely accessible data that is organized in a clear format. For example, the government census data, stock market data, weather reports, and more. Then we have proprietary unstructured data. That is the private data owned by the companies, but it's unorganized. For example, the customer service mails, internal company reports, recorded phone calls. And then we have this proprietary structured, so the private, well-organized data owned by the companies. A bank's customer transaction records, there is a Netflix user watch history, Amazon sales database, and more. So let's now jump into the fun part where we actually see how actually using document loaders work. So regarding the OpenAI API pricing, you can go directly to this openai.com API pricing wala website, and then when you scroll down, you will see and explore the detailed pricing, and you go there and you will basically find all the latest models with the input, the cached input, and the output as well. So in this course, we are using the GPT 3.5 Turbo, and its input is $3 and the training is $8. And if you contact the pricing, you will see it cost $0.5 and the output is $1.50. You can basically take up any API that suits well in your project. So initially, we are going to import some environment variables that we need, like the OpenAPI key. The first type of documents we're going to use would be PDFs. So let's see this. So we have downloaded the relevant document loader from the Langchain, and we're going to use the PyPDF loader. We have loaded a bunch of PDFs into the documents folder in the workspace. And so let's choose one and put it in the folder. So let's load the document just by calling the load method, and we will run this. Now let's take a look on the length of the pages we have downloaded, and we can see that we have 22 different pages in the PDF. So each one is a unique one. So let's look at the first one. So let's run this. So let's see the first content of the page. You can see the instructor is Andrew. Okay, good morning. Welcome to CS2229, the machine learning class. So this is the first page. So now here you will basically get a piece of information, that is the metadata, and we'll run this. And basically we can see there are two parts, the source. So till that .pdf, basically it is the name of the file we have loaded it from. The other is a page field, and it corresponds to the page of the PDF. So the next type of document we are going to look is at the YouTube content. There's a lot of fun content in YouTube. So a lot of people use document loader to ask questions about the content, lectures, or anything like that. So let's see. So here we have imported certain things. The key parts are YouTube audio loader, which loads an audio file from a YouTube video. The other key part is OpenAI Whisper Parser. This will use the OpenAI's Whisper model, a speech-to-text model that converts the YouTube audio to text format that we can work with. So after the output, we can now specify the URL. So let's see that. So we can now specify the URL, specify a directory in which we save the audio files, and then create a generic loader as a combination of this YouTube audio loader combined with the OpenAI Whisper Parser. And then we can load the documents by calling the loader.load corresponding to YouTube. Take a few minutes to load. So after this, we'll see the next. You can now see that it has generated the first output, and after that, we can actually take a look on the page content. And this is the first part of the transcript from the YouTube video. You can see this. So the next set of documents we are going to go with is how to load the URLs from the internet. So there is a bunch of educational content on the internet, and it will be pretty cool to actually just chat with it. So we are going to enable that by importing the web-based loader from the Langchain. And here basically we can choose any URL. And here I have chosen one markdown file from the GitHub page and created a folder. So let's then call the loader class. So we have called the loader class. Then we can even just take a look at the content. And we can see a lot of blank space over here. And when I scroll down, then you can see some content over here. And then again blank, and then again content. And this is pretty interesting. So finally, we will cover how we can load data from the Notion. You have to follow certain steps from the Notion side to duplicate the page into your own Notion space and export them as Markdown or CSV file. Then unzip it and save it as a folder that contains the Markdown file for the Notion page. So then here, we have a specific format, and we can use the Notion directory loader to load the data and get documents that we can work with. Now let's take a look at the first page of the content. And you can see this is a living document with everything we have learned working with people while running a startup. And of course, we continue to learn, therefore it's a document that. So it's basically the part. We can clearly see that it is a markdown handbook, that is a Blendis employee handbook. And I'm aware that a lot of people has worked with Notion and has a Notion's database. So it's a great opportunity to export that data and bring it here and start working with this. And then finally we see the metadata over here, Blendis employee handbook. So now after we have loaded the data successfully, we will now get into and see the splitting of the data. So here we just went over on how to load the documents into a standard format. Now we are going to talk about how to split them up in a standard format. So it may sound easy, but there are a lot of subtitles over here. So document splitting happens after you have loaded your data into the document format, but before it goes into the vector store, and this may appear really simple. You can basically skip the chunks according to the length of each character or something like that. For example, we have a sentence that the Honda Accord boasts an impressive 192 HP engine paired with a seamless 10-speed automatic transmission, delivering a smooth yet powerful ride that will leave a lasting impression. So we can split this document into two chunks. So the chunk 1 would be the Honda boosts, and then the chunk 2 will be the rest part. An impressive 192 HP engine paired with a seamless 10-speed automatic transmission, delivering a smooth yet powerful ride that will leave a lasting impression. And we are trying to answer one question, that is, what are the specifications of Honda? But here is the tricky part. None of the chunk alone can answer the question. So how you split one information, that is very important to get the relevant chunks of information. So the basis of all text splitters in Langchain involves splitting chunks in some chunk size with some chunk overlap also. So there are various types of splitters in Langchain. So the first one, we have the character text splitter. So it basically splits the text based on a specific character. For example, /n with a chunk size and overlap. And then we have markdown header text splitter. It splits markdown documents while preserving the headers and structures. And then we have the token text splitter. That is, it splits the text based on the token count, ensuring the compatibility with LLMs like GPT. And then we have the sentence transformers token text splitter. And it uses the sentence transformers to split the text intelligently based on the semantic meaning. And then we have recursive character text splitter, and it splits text hierarchically, first by large units and then by the smaller ones, that is the sentences and the words. Then we have language, that is used for the language aware text splitting based on the linguistic rules. And then we have NLTK text splitter. It utilizes the NLTK to split the text into meaningful sentence-based chunks. And then we have the Spacy text splitter. It uses the Spacy's NLP models to split the text while preserving the grammatical structure. Now let's see how to split the documents for real. So from here, we have imported OS, OpenAI and systems, and then from the .env, we have imported the load.env and the find.env, and we have set up our OpenAPI key. And then we have imported the recursive character text splitter and the character text splitter from the Langchain text splitter. So we will run this, and over here we are mentioning the chunk size to be 26 and the chunk overlap to be 4 beforehand. And over here, we are initializing the art splitter with the recursive character text splitter, and we are initializing the chunk size and the chunk overlap. Then we are again initializing the C splitter as the character text splitter and chunk size to be the chunk size, and chunk overlap we have done before also. So we will run this, and here we have the first text and we will pass this. Then we have this R splitter for splitting this text one. So we'll see this. So you can basically see there is no difference. So for this we have a different example, and we will pass this, and now we will see the result. And now you can see basically it has splitted the text, but the fact is we have a chunk overlap of 4, but it looks like 3. So let's see more examples. We are again passing this text number 3, and we will text split it with the use of R splitter, and you can basically see it has created A, B, C, D, E, F, G, H, I, J, K, L, M, L, M, N, O, P, Q, R, S, T, U, V, W, X, the W, X, Y, Z. Now let's apply the C splitter on the same example, and you can basically see it has again joined the whole text. This is nice. So here in the C splitter, we are adding a separator to be as the inverted commas. So we can see we have already got the result before, but here it is just separated with the inverted commas for more understanding. Here now it is the best time to actually pause and try out your own examples like this. But then we have a different example, and this time we have a paragraph. And let's now see the length of the text. It's 496 words. So we will now see the C splitter and the R splitter once again, and we will initialize it. This time we have the chunk size is equal to 450, and chunk overlap we don't have any, and we have a separator for the C splitter as the inverted commas. And in the R splitter we have chunk size as the same, no overlaps, and the separator should be a new line, 2 new lines, or a new line, or a double inverted commas, and everything. So let's just pass this. Now it's time to actually apply the C splitter over the some text we have generated. So you can basically see it is separated with the inverted commas. And here now in the R splitter, we will then apply it over the same text, and you can basically see the double inverted commas. So here what we have done is we have reduced the chunk size, and we have added period to the separators. So let's now see. Now you can basically see the difference. And let's now see we have made a difference of, we have added this operators. And let's now see the difference. We have now loaded one PDF from the machine learning lecture 1, and we have called the loader class from pages. So here we are importing the character text splitter from the Langchain text splitter, and we have a separator of /n, and then we have a chunk size of 1000 and chunk overlap of 150. So let's run this, and then we can basically call the text splitter.split documents pages, and we will run this. Let's now see the length of the document, that is 77. And then we have a length of the pages, that is 22. And now we are importing the Notion directory loader, and then we are passing one Notion database, and then we'll load this. And then we are using this text splitter in the Notion database, and let's see the Notion DB length. And you can see it is 52. And then basically you can see the length of the documents, and then we'll see it is 353. Now basically we can actually split on the basis of token count explicitly only if we want. So let's now see that. So we are importing the token text splitter from the Langchain. Here now we are actually keeping the chunk size to be 1 and the chunk overlap to be 0, and we are passing it under the token text splitter. So here we again came with a one text, and it doesn't make any sense, but it's okay. And then we are going to pass this text 1 through this text splitter.split, and we'll run this. And then you can basically see it has splitted the whole text, and it has also separated with the inverted commas. And then we are applying this to the pages, And let's now see the first document. And then you can basically see it is filled with page content, metadata that is containing the source, the lectures, the page we have. This is basically the field as I have already discussed. And then let's move on. And lastly, for the token-wise splitting, let's see the metadata of the page. And you can see it is the machine learning lecture 1 PDF, page and fidelity. Now let's see the context-aware splitting. So here we have imported the Notion directory loader and we have imported the markdown header text splitter. So here we have one markdown document and let's run this. And then basically we have these headers to split. That is first hash and then we have header 1, double hash we have header 2 and triple hash we have header 3. And here now we have this markdown splitter. And we can basically see we have MD header splits equal to markdown splitter dot split text markdown documents. And then now let's see the MD header splits 0 that refers to the first document. And now you can basically see, hi, this is Jim, this is Joe, metadata header, title, header 2, chapter 1. And let's now see the second one we have. And this is Lance. Chapter 1, Header 3 section. Let's now see this on the new Notion database. Here basically we have this headers to split, header 1 and header 2. Then similarly we have this markdown header text splitter and we are using those headers to split on headers to split on. This is basically we are initializing it. So let's run this. And let's now pass this first text and a markdown splitter split text. And let's see. And let's now see the first document. And this is basically what we can see. Now guys, let's move on to the next chapter. So in this chapter, we will talk about the storing, the chunks, and vector stores and embeddings. So imagine you are reading a 200-page book and you want to remember the most important ideas. So instead of just memorizing every word, you highlight the key sentences and write them on the sticky notes. So these sticky notes are your chunks. So in the world of AI and large language models, especially in the retrieval augmented generation systems, we do something similar. We split the large documents into the small meaningful chunks or text. So this helps the model retrieve only the parts it needs to instead of reading the whole thing again and again. Now let us see why storing in chunks is important. So you might ask, why can't we just store the full document? And that is a valid question. So LLMs can only process a limited amount of text at a time. So giving them a whole book can overwhelm them or cause important parts to be ignored. And so storing information in the smaller chunks makes it easier for the model to find the relevant content quickly. And then the smaller chunks improve accuracy by helping the model focus on the specific details instead of giving vague answers. So let us now see what are embeddings. So now here's the cool part. How do we find the right chunk later? That's where embeddings come in. So embeddings are like the turning words into numbers that capture meaning. Think of them as GPS coordinates for ideas. For example, the words dog and puppy might be close together in the embedding space because they have similar meanings. So let's say we have a chunk. Python is a programming language used for the data science. So we convert this into a list of numbers or embedding like 0.12, 0.98, minus 0.34 and more. So this vector represents the meaning of that sentence, but not in words. So now let's move on and see what are vector stores. So we have turned our chunks into embeddings, but where do we keep all these meaning vectors? In a vector store. So think of a vector store as a smart library. So instead of organizing books by titles, it organizes chunks by meaning. So when you ask a question, it compares your query's embedding with all the stored embeddings and pulls out the most relevant chunks. For example, you ask, what is Python used for? The system converts your question into an embedding and searches the vector store for the closest match, which might be the chunk we saved earlier. So, the answer is Python is a programming language used for data science, and boom, that's your answer. Let's now see how are they helping together, or why storing in chunks is so important. So putting it all together, you split the document into chunks. Then you generate embeddings for those chunks as well. And then you store the embeddings in a vector store. So when a question comes in, you generate its embedding. The vector store finds the most relevant chunks. And finally, the LLM uses those chunks to generate an accurate response. So this is how the RAG system works. They're not just smart, they're efficient. They don't try to memorize everything. Instead, they store what matters in the right format and retrieve it when needed. So let's now see everything in action.
So to start, we will once again set the appropriate environment variables. So here we have already discussed how to load a document and how to split them just now. So now here we will be working on with the same set of documents. So let's run this. So here now, after loading the PDF and all the documents, we are now planning to split them. So here basically we are importing the recursive character text splitter. So text splitter is equal to recursive character text splitter. We are initializing the text splitter. Then we have mentioned the chunk size as 1500 and chunk overlap equal to 150. So let's run this. So once again, if I have missed a point in the loading PDF, so there are a set of CS229 lectures, and if you look closely, you will see we have duplicated the lecture 1 2 times because of simulating dirty data. So that we can now see that we will initialize this text splitter. Now we can say this, we have created more than 200 chunks, 209. Now time to move on to the embeddings. Let's take our splits and embed them. We will use the OpenAI to create these embeddings. So we'll run this. Now before trying with the real world examples, let's try out some other examples too. So we are planning to pass these 3 sentences over here. Sentence 1 is I like dogs. Sentence 2 is I like canines. Sentence 3 is the weather is ugly outside. So we'll pass this. And now here we can actually see that we have created 3 embeddings for 3 respective classes for the 3 sentences we have. So we'll run this. So we can now create an embedding class for each sentence. So we can import the NumPy to import them. We'll expect the first 2 sentences will be very similar. So we'll check that. And now we will be using this dot product to compare them. So the dot product in here multiplies the corresponding elements of the 2 vectors and then adds them up, giving a single number. It helps measure similarity between embeddings. Higher value means more similarity and lower value means less similarity. So we will run this. Now basically you can see that the dot product of the first and the second was quite higher respect to the first sentence and the third. So we can get a significant lower value. So now let's read the dot product between 2 and 3. And if you run this, we can see that it's almost the same. Now I will suggest you to pause the video and try out a few different examples and their dot products. So let's move on to the real world examples. It's time to create embeddings for all the chunks of the PDFs and store them in a vector store. So the vector store we will use here is Chroma. So let's import that first. So here we are importing Chroma database and we are importing Chroma from the Langchain vector stores. And before we run this, Langchain has integration with lots of vector stores. We are using Chroma here because it's lightweight and in memory, which makes it very easy to get up and start with. There are other vector stores that offer the hosted solutions which can be useful when you are trying to persist large documents of data or persist it in the cloud storage somewhere. So then we are going to save this in the vector store so that we can use it for the future lessons. So let's create a variable called persist directory, which we will use later on at docs/chroma. So here, let's also make sure that nothing is there already. So here basically we have created the vector store. So we'll call the chroma from documents, then passing on the splits that we created earlier. So passing through embeddings, now this is the OpenAI embedding, and finally passing through a directory. And the directory is persist directory that we have created to store for the future use. So we will run this. Now we will take a look at the collection count. We can see that this is the same as that of the split that we did previously. So let's now start using it. Think of a question that we can ask. We know that this is a class lecture, so we can ask. So if there's any email address we can ask for regarding the class or anything. So the question we're gonna pass over here is there any email I can ask for help? So we are going to use the similarity search method over here, passing the question, and even k is equal to 3, which specifies the number of the documents that we want to return. So we will run this. And let's then check the length of the docs. Now that we will see the length, and it's 3 as we have specified. Now let's take a look at the content of the first document. It's in fact about an email address and is obviously an email we can send queries to. So now you can see that there is an email. This goes to the account that's read by all the TAs and me. So this is nice. So after doing this, let's be sure to persist the database for future use. So we'll persist it. So basically similarity search will give you 80% of the great results. But there are some edge cases, and now we are gonna discuss that only. Now let's ask a question. What did they say about the MATLAB? And we'll pass this. And we are trying that similarity search over here, and we're passing the k is equal to 5. Now let's see the first document, and then we'll look at the second one. And notice that we are getting duplicate chunks. So because of the duplicate machine learning lecture 1 PDF in the index, semantic search fetches all the similar documents, but does not enforce diversity. So docs 0 and docs 1 are identical. We can see a new ferial mode now. Let's pass one question. What did they say about the regression in the third lecture? So we'll pass this. We can check this because we have information about metadata about what lectures they came from. So we are using the similarity search, passing through this vector DB, and we are keeping the case values equal to 5. So let's loop over this document and print the metadata. So we can see a combination of results, some from the lecture 3 and some from 2 and 1. The reason it is failing is that the third lecture and the fact that we want documents from the third lecture is a piece of structured information, but we are doing a semantic lookup based on the embeddings, where it creates an embedding for the whole sentence and is probably a bit more focused on the regression. So let's now look at the fifth document, the one that comes from the first lecture. It does refer to the regression. So if it is picking up on that, but not on the fact that it's supposed to be querying documents only related to the third document, because again it is a piece of structured document. So it is a good time to pause and truly figuring out some more questions and try changing the value of k. So in this lecture we have seen the basics of semantic search and also the failure modes. Let's move forward in the next part and try to address those failures and retrieval too. In this lesson, we will dive deep into the retrieval and few more advanced methods for overcoming the edge cases. So let us understand what is retrieval in RAG. So in RAG, retrieval refers to fetching the relevant documents or data from a knowledge base like a vector database, or the local files to answer the user queries. It helps in searching, filtering, and retrieving information efficiently. Now let us move and see where retrieval is used. So it is used in the chatbots with memory. For example, retrieving the past conversations. Then we have question answering system. That is, for example, retrieving the FAQ answers. Then it can be used in the AI powered search engines. That is for the semantic search. So the techniques we will be talking about today are new to the market.
The first one we will be talking about is maximum marginal relevance. That is, the MMR is a smart way to select the diverse and the relevant information from a large set of documents. So instead of just picking the most similar results, it balances the relevance and diversity, ensuring that the retrieved results are not too repetitive. So MMR is used in the retrieval augmented generation, that is the RAG, to improve the search results by selecting both the relevant and the diverse documents. So imagine searching for the best AI tools. So without MMR, you get the 5 results about ChatGPT, too similar. But with MMR, you get the results about ChatGPT, Gemini, Claude, Midjourney, and Copilot. So let's now move on to the second one we will be talking about is LLM aided retrieval. LLM aided retrieval is a smart way to improve the search results by using a large language model to refine or guide the retrieval process. So instead of just fetching documents based on the keyword similarity, the LLM helps in the better query understanding, ranking, and selecting the relevant information. For example, without LLM-aided retrieval, a search for the AI in marketing may retrieve random AI articles. So with LLM-aided retrieval, the LLM understands the intent and retrieves the specific articles on AI tools for marketing. So let's now move on and see the demo. So let's see all the techniques in action. So we will start with loading the environment variables as we always do, and then we'll run this. So let's then import Chroma from Langchain vectors. We will also import OpenAI embeddings, and we will also create this purpose directory we have created before, the docs Chroma, and we will run this. We will now create embeddings. Embeddings equal to OpenAI embedding, vector Chroma, and then pass this purpose directory and embedding function. So we will run this. So now we'll try to print vector db dot collection dot count, and we'll run this. So after looking at the collection counts, we can see this is 209 documents that we loaded before. So let's now begin with maximum marginal relevance MMR. So we have all this text that got loaded and all are about mushrooms. So we'll create a small database equal to Chroma dot from text, and we'll pass text comma embeddings equal to embedding. So this is type of a toy example, and we will run this. So I have a different question. Tell me about all the white mushrooms with the large fruiting bodies. So I'll run this, and we'll create plugin called this small db dot max marginal relevance search. We will pass the question, then k is equal to 2, comma fetch. Make sure you give the correct code, and we'll run this. So here, if you see, we have still k value as 2, but fetch k is equal to 3 to fetch all the 3 documents originally. So now let's go back to a question, a previous lesson where we asked about MATLAB. So the question is, what did they say about MATLAB? And we have the vector similarity search over here, and the k value is 3. So now we'll basically compare docs ss 0 dot page content and we will run this. And we will again, basically I'll copy this and I will change 2 to 1. Now we can actually see that both are the same. Now we will use MMR to actually find out the difference. So let's write docs MMR first document dot page content and we will copy this, paste it here, and we'll make it as 1. Now the second one is different. It's getting some diversity in the environment. Let's now move on to the next part. We have a different question again and we'll try to run this. So we are here again using the vector DB similarity search, and if you see, it is the third lecture over here. So we'll try to run this. Now if you see this, that you will understand that it got retrieved, that is exactly like the initial. So now we are going to use self-query retriever. So I'm importing OpenAPI and self-query retriever and attribute info. Let's run this. So here again we are specifying the metadata attributes like the name, the description and the type, and if you see the difference, the page from the lecture, and here in the description it is the lecture, the chunk is from should be one of the documents from this. So let's run this. We will now specify it more and use LLM as OpenAPI model, and we will give retriever as self-query retriever from LLM and vector DB and everything, and we will also here verbose is equal to true. So we will run this. So here we are basically retrieving the relevant documents and passing the question, and it is okay, and we'll print the metadata. This can be ignored and you can actually find out the metadata. So there are some additional tricks over here for compression. That is another approach for improving the quality of the retrieved documents is compression. So information most relevant to a query may be buried in a document with a lot of irrelevant text as well. So passing that full document through your application can lead to more expensive LLM calls and poorer responses. So contextual compression is meant to fix this. So I'll import contextual compression retriever and we'll run this. Here we are passing this pretty print documents through the documents, and we are even giving all the specifications of the double new line, page content and everything, and we will run this. So here we will wrap our vectors stored. So we'll run this. We can now create a compressor with the LLM chain extractor as well. So we'll run this. We can now create the contextual repression retriever and then the best retriever from the vector store. And now we are passing the question and we'll run this. Now we are passing the question. Seeing the output, you can find out that the documents are shorter than the normal one, and they have some repeated stuffs as well. So it's not worth nothing that vector DB is not the only kind of tool to retrieve documents. The Langchain retriever abstraction includes other ways to retrieve documents such as TF, IDF or SVM. So let's see. We will begin with loading the environment variables like we always do, and we will run this, and then we will see loading the PDF, and then we are using the recursive character text splitter to split the text, and we are specifying the chunk size, the chunk overlap, and finally splitting it. So after splitting is done, we will be using the retrievers SVM retriever and TF-IDF retriever, and we will run this. And then finally, we will ask this question, what are the major topics for this class? And we will basically run this. Now you can see the page content. Let me just check about what questions you have right now. So if there are no questions, I will just, it has given it. So now we are using the TF-IDF retriever, and let's run this. So this is the right time to pause and try your own examples.
And now, down the line in the next lecture, we will see how we can ask questions and get the relevant answers. So, in this lesson, we will learn how to extend the normal agent to handle multiple documents and increasing the degrees of complexity. So now, initially we'll begin with setting up the OpenAPI key. And secondly, we will import the Nest Essentio. And then the first task is to set up our function calling agent over 3 papers. So we do this by combining the vector summary tools by each document into a list and passing it to the agent so that the agent actually has 6 tools in total. So here we have downloaded 3 papers from the Clear. So this includes the MetaGPT for the last time, and this also includes the long LoRa as well as the self-RAG. So next we will convert each paper into a tool. So this is basically a helper function. That is the gap doc tools, which automatically builds both a vector and index tool as well as a summary index tool over a given paper. And the vector tool performs the vector search and the summary tool performs the summarization of the entire document. So for each paper, we are getting back both vector tools and the summary tools. So here we'll run this. So then we will define the 3.5 Turbo from the OpenAI as the large language model of our choice. And now, if we run this, it is basically the GPT 3.5 Turbo. So if we really take a quick look at the number of tools that are going to be passed to the agent, we will get 6. Because we have 3 papers and 2 tools for each paper, a factory and a summary tool. And the next step is to construct our overall agent worker. And it includes all the 6 tools as well as the large language model that we pass out. And we are able to ask questions across these 3 documents or within a single document. For now, let's ask a question. Tell me about the evaluation dataset used in the long LoRa and then tell me about the evaluation results. And we have got the answer that one of the evil datasets uses the feature of 19 test split. We are able to look at the evil results for our long haul models. The next question is, give me a summary of both the self-RAG and the long LoRa. So this will basically allow us to do the summarization of the 2 papers. So first, we call the summary tool for the self-RAG with the inputs of its name. So we will run this. And you can basically see added user memory. You can basically see added user message to the memory. Then we have the calling function. Then we have the output. Then again we are calling function and then we have the output. And this code defines the 2 lists, URLs and the papers. So the URLs list contains 11 links to research papers in the PDF format from the Open Review website, while the papers list consists of the corresponding file names that likely represent the downloaded versions of these papers. So here each URL in the URLs list maps to a specific file name in the papers list, suggesting that these names might be used to save the downloaded files. So this setup can be useful for automating the downloading process, keeping track of the files or referencing papers by their assigned names. So this code basically processes a list of the research papers by extracting the specific tools for each document using the getDocTools function. So it begins by importing the getDocTools from the utils module and path from the pathlib for handling the file names. An empty dictionary paper to tools dictionary is initialized to store the mapping of each paper to its respective tools. The code then iterates through the papers list, printing a message to indicate which paper is being processed. For each paper, it calls the getDocTools, passing the paper's file name and its same file name without the .pdf function. So this function returns the 2 tools, that is the vector tool likely for converting the text into embeddings for the NLP task, and summary tool which might generate the summaries of the paper. So these tools are then stored in the dictionary with the paper file name as the key and the tools as the value. So this setup enables efficient document processing, allowing for easy access to vectorized representations and summaries for the research paper. Now basically you can see the output. So this code creates a list called the all tools that collects of the tools from the paper to tools dictionary for every paper in the papers list. So it uses a nested list comprehension, which means it goes through each paper in the papers, retrieves its associated tools, a list of the two tools stored in the paper to tools dictionary, and adds each tool to all the tools. So as a result, all the tools become a single list containing all the vector and the summary tools for every paper rather than keeping them grouped by paper. So this approach makes it easy to access and process all tools together instead of dealing with them paper by paper. So here this code creates an object-based index and retriever for the tools stored in all the tools using the vector stored index from the Lama index.core library. So the object index from the objects function takes all the tools and organizes them into a searchable index. So the index CLS is equal to vector stored index argument specifies that the indexing method should use a vector-based retrieval, meaning each tool will be converted into a vector representation for the efficient searching. So this setup allows the quick retrieval of the relevant tools based on the similarity searches, making it useful for the tasks like finding related tools based on the user queries. Now this code object retriever is equal to object index dot as retriever is creating a retriever object from the object index, which likely represents as index collection of data such as documents or embeddings. The as retriever method converts this index into a retriever, following it to fetch the relevant results based on the similarity. The parameter similarity top k equal to 3 ensures that when a query is made, the retrieval will return the top 3 most similar results based on their relevance. So this is useful in applications like search engines, chatbots, or recommendation systems where retrieving the most relevant information is important. So here the core tools equal to object retriever is asking the retriever to find the relevant information related to the given query. The retriever searches through the index data and retrieves the most relevant results based on the similarity. Since object retriever was configured to return the top 3 similar matches, it will return up to the 3 pieces of relevant information. The retrieved results are then stored in the tools variable, which can be used for further processing, such as displaying the information to the user or using it in an AI model. So this process is commonly used in the AI-driven search systems, chatbots, and question answering application to fetch the relevant data efficiently. So here the core tools2.metadata is accessing the metadata of the third retrieved result from the tools list. Since the tool stores the results returned by the object retriever.retrieve, each item in the tool contains both the retrieved content and the additional metadata. So metadata typically includes the extra information, such as the source, timestamp, author, document ID, or other attributes, and that describe the retrieved data. So by using tools.metadata, you are specifically extracting the metadata of the third result, which can be useful for understanding whether the retrieved data came from the adding context to the results or not. So the given code over here is setting up an AI-powered agent that can answer questions based on the retrieved information from a collection of papers. So first it imports the function calling agent worker and the agent runner from the Lama index code.agent. Then it creates an agent worker using the function calling agent worker, which takes the object retriever as the tool for retrieving the relevant information and LLM to process and generate responses. So the system prompt ensures that the agent always relies on the retrieved data instead of the prior knowledge. So finally, agent is equal to agent runner wraps the worker inside the agent runner, making it easier to manage and execute the agent's task. So this setup allows the agent to intelligently retrieve and generate answers based on the predefined knowledge base, making it useful for the research, document analysis, and question answering applications. So this code is making the AI agent answer a query about the evaluation dataset used in the MetaGPT and how it compares to the SWB bench. The query function sends this question to the agent, which then retrieves the relevant information using the object retriever and processes the response using the language model. The retrieved and the generated response is stored in the response variable. So finally, the print str response converts the response into a string and displays it. So this allows the AI agent to provide a well-structured answer based on the available documents, ensuring an informed comparison between the two datasets. So this last but not the least code AI agent analyze and compare the two research papers, Long Laura and the Loft Q. The query function sends a detailed question asking the agent to first analyze the approach used in each paper and then compare and contrast them. The agent retrieves relevant information using the object retriever and processes the response using the language model. So the generated response is stored in the response variable. Finally, the retrieved and the analyzed answer is stored in the response variable. This setup helps in extracting the insights from the research papers efficiently, making it useful for the academic research, technical analysis, and AI-driven summarization. Now you can see that it has generated the output. In the next lesson, let's conclude this whole course. So lastly and finally, we have a conclusion over here. And the conclusion basically focuses on the future of RAG. So as powerful as RAG is today, its future looks even more promising. So in the upcoming years, we can expect the smarter retrieval, that is, the more accurate retrievers that consider the semantic nuances, user preferences, and intent, not just keywords. Then we have multimodal RAG, that is integration of not just text but also images, audio and video into the retrieval and generation process. Then we can even expect the personalized agents, that is the systems that learn from the user feedback loops in real time, delivering more relevant and personalized answers. Then we can even expect the memory augmented RAG, that is incorporating the long-term memory into agents so they can retain the context across sessions. Then we can expect the low latency, that is scalable RAG, that is optimizations in storage and retrieval that allow the RAG to work seamlessly even at the massive scale and speed. So RAG is evolving fast, from powering search engines to enhancing the customer support, healthcare, finance, and education. So as these systems become more fine-tuned and grounded in the accurate and the real-world knowledge, they will bridge the gap between the static data and dynamic, intelligent responses, paving the way for the next generation of AI. So guys, congratulations on completing the RAG for the Beginners course. You have now built a strong foundation in the retrieval augmented generation by learning what RAG is, why it matters, and how it powers the real-world applications. From understanding the core components like the query encoder, retriever, re-ranker, knowledge base, and generator to hands-on demos in the document loading, chunking, storing with embeddings and vector stores, and building a multi-document agent, you have gained the practical skills to apply RAG effectively. So as you move forward, continue experimenting with your datasets and refining your pipeline to unlock the full potential of RAG in creating the smarter, context-aware AI systems.
Welcome to our video about transformers in AI. And no, we don't mean the robot toys from the movies. We are diving into something even cooler in the world of computers and AI. Have you ever wondered how your phone knows what word you might type next, or how Google Translate works so well? That's where transformers come in. They are like super smart computer brains that can understand and create human-like text. Here's a fun example. I asked a transformer to tell me a joke and it said, "Why did the computer go to the art school?" Because it wanted to improve its draw speed. Okay, that's a bit cheesy, but it shows how these computer programs can come up with new ideas on their own. Transformers are changing how we use technology every day. They help us with things like translating languages, summarizing long articles, writing emails and stories, and even playing games like chess. In this video, we will explore how transformers work, why they are so special, and what cool things they might do in the future. So let's talk about what exactly are transformers. Transformers are an artificial intelligence model used to process and generate natural languages. They can read and understand huge amount of text and then use that knowledge to answer questions, translate languages, summarize information, and even create stories or write code. The magic behind transformers is their ability to focus on different text paths with attention mechanisms. This means that they can understand context better than older models, making their outputs more accurate and natural sounding. The basic structure of a transformer includes two main parts, the encoder and the decoder. Think of the encoder as a translator that understands and processes the input, and the decoder as the one that takes the processed information and turns it into the output. For example, if we are translating a sentence from English to French, the encoder reads the English sentence and converts it into a form that AI can understand. The decoder then takes this form and generates the French sentence. A great example of a transformer in action is ChatGPT. ChatGPT uses transformers to understand and generate human-like text. When you ask a question, it processes your input with its encoder and generates a response with its decoder. This lets it have conversations, write essays, and even tell jokes. For instance, if you ask ChatGPT what's the weather like today, it uses its transformer model to understand your question and respond it with it's sunny with a chance of rain in the afternoon. This ability to understand and generate text makes transformers incredibly powerful. So let's talk about how transformers work. Transformers are especially good at sequence-to-sequence learning tasks like translating a sentence from one language to another. Here's how they work. First, there's the attention mechanism. This allows the transformer to focus on different parts of input data. For example, if it's translating the sentence, the cat sat on the mat, it can pay attention to each word's context to understand the meaning better. So it knows cat is related to sat and mat, helping it produce an accurate translation in another language. Transformers also use something called positional encoding. Since they process all words at once, they need a way to understand the order of the words. Positional encoding adds information about the position of each word to the input, helping the transformers understand the sequence. Another key feature is like parallel processing. Unlike older models like Recurrent Neural Network, which is RNNs, the process text words by word. Transformers can process the entire sentence at once. This makes them much faster and more efficient. Let's compare transformers with recurrent neural networks. But first, let's understand what are RNNs. So RNNs is a type of neural network designed to handle sequential data. They process data one step at a time, maintaining a memory of previous steps. This makes them good for tasks where order matters, like speech recognition or time series prediction. However, RNNs have a problem called the vanishing gradient, which means that they can forget information from earlier in the sequence. Imagine trying to understand the sentence, Alice went to the park and then to the store. And RNN might struggle to remember Alice by the time it gets to the store, but a transformer can easily keep track of Alice throughout the sentence. So why are transformers better? Unlike RNNs, transformers process the entire sentence at once, keeping the context intact. This solves the vanishing gradient problem and makes transformers faster and more accurate to tasks like language translation and text generation. So let's talk about the applications of transformers. At first, we have language translation. They are used by services like Google Translate to convert text from one language to another. For example, translating hello, how are you to Spanish as hola. Then we have document summarization. They can take long articles and summarize them into shorter, more concise versions. For instance, summarizing a 10-page report into a few key points, making it easier to understand the main ideas without reading the whole document. Then we have content generation. Transformers can write articles, stories, and even code. They can create new content based on what they have learned. For example, you could ask a transformer to write a short story about a space adventure, and then it would come up with a unique narrative. Then we have game playing. Transformers can learn and play complex games like chess, making strategic decisions just like a human player. They analyze the entire board and make moves considering all possible outcomes. Let's talk about image processing. They are used in tasks like image classification and object detection, helping computers understand visual data. For example, identifying objects in a photo, like recognizing a cat, tree, or a car. Now let's understand the training process. The training transformers involves two main steps. Semi-supervised learning. They can learn from both labeled data where the answer is known and unlabeled data where the answer is not provided. This makes them very versatile. For example, a transformer could be trained on a mix of articles with and without summaries to learn how to summarize text effectively. Pre-training and fine-tuning. Transformers are pre-trained on a large data set to learn general patterns. Then they are fine-tuned with specific tasks, making them highly versatile. For instance, a transformer might be pre-trained on a large collection of books to understand language and then fine-tuned to generate marketing copy for a specific brand. The future potential of transformers is huge. Researchers are continuously improving them, making them even more powerful. We can expect more advanced applications in areas like healthcare, finance, and more sophisticated AI systems that interact with humans in more natural ways. Imagine having an AI that can provide personalized medical advice or one that can help you write a novel. In conclusion, we can say that transformers are a revolutionary architecture in AI. They offer speed, efficiency, and versatility, changing how we interact with the technology. The future looks bright for transformers, and we can't wait to see what they'll do next.
Hello everyone, I am Mayank and welcome to this video where I will show you how to run Llama 3.1 on your systems, all while keeping your data private. If you are curious about AI and want to use it on your own PC without relying on online services, you are in the right place. Llama 3.1 is a powerful AI tool that can help with tasks like text generation, but instead of using it in the cloud, you can run it directly on your computer. So in this video, I will guide you through everything from setting up your system to installing and running Llama 3.1 step by step. It's a great way to experiment with AI while keeping your work private. So by the end of this video, you will have Llama 3.1 up and running on your own systems. And you won't need to worry about sharing your data with anyone else. Whether you are just learning about AI or planning to use it for bigger projects, this tutorial will make it easy for you to get started. So let's dive in, follow along, and by the end, you will have your own private AI setup. Don't forget to like, subscribe, and let's start running Llama 3.1. Welcome to this demo part of this Llama. How to install Llama 3.1 in your system. So I'm using Windows right now. It is available for Mac OS, Linux, and Windows. So first what we will do, we will install this Llama. Just type ollama.com and I will provide this link in the description as well. Then here you have to press the download. Here you can choose your system, your OS, Mac OS, Linux, Windows. Just follow the steps later. So I will download for the Windows. So the application will get download. It is like 625 MB. So it is downloading. Till then there is no official documentation for this Llama. So here in GitHub there is one. So Llama. This is Windows for here, Windows, Mac OS, Linux, you can download. And these are some models. See Llama 3.1, Llama 3.1, Llama 3.1, and 5, Gemma, and Mistral is there, Moondream is there, and so on. And see, these are some parameters. 8B is 4.7 GB, 70B is 40 GB, and for 05B is 231 GB. So here note, you should have at least 8 GB of RAM available to run 7B models. 16 GB RAM to run 13B models and 32 GB RAMs to run 32B models. So here we will install this 8B parameters. You can choose anyone as per your specification of your system, your OS. So still it's downloading. I have already installed in this, but again I will reinstall it. Fine. So now we have Llama setup. Just double click on this and install. See why it is showing this error. And why it is showing this error? Why? Because the following applications are using files that need to be updated by setup. It is recommended that you allow setups to automatically. It is automatically installed. See, it's a simple steps. There are 3-4 steps that you have to do. So yeah, the setup is done. And now what you can do, I am using PowerShell. You can use your command prompt as well. So here I will write Llama. So here you can see these are some available command I can do. Okay, so to run a model you have to just write run and this. Okay, now if you will see here, to download Llama 3.1 8B parameter 1 4.7 GB will be the size. So this is the command, just copy it and paste it here. Okay, and enter. So why it is coming like this? Because it is already installed on my system. Fine. So now Llama 3.1 is installed. Okay, so here you can write your questions. Okay, what is Llama 3.1? So see, it is start generating the output. So this is how you can privately run or install Llama into your large language models applications into your system. See, it is like ChatGPT. If you are looking for more details, can you please provide context or more background about why you are interested in Llama 3.1? That would be me try to find more relevant information for you. Okay, so here what I will write what is ChatGPT. Okay, so it will give you the answer. See, ChatGPT is a conversational AI model developed by OpenAI, a leading artificial intelligence research laboratory. Okay, what you have to note, you have to note what's the size of your RAM. Okay, I have 16 GB of RAM, that's why I installed this 8B one. Okay, and if you have 8 GB RAM, there is no model of 7B. 7B we have Lava, and we have Code Llama, and we have Mistral. So if you have 16 GB of RAM and this one Llama 3.1, the latest one, is enough. Okay, so let's check. Yeah, see, ChatGPT stands for Conversational Generative Pre-trained Transformer. It is an AI chatbot designed to understand and respond to human-like language input. And some key features are this. So this is how you can be protected from your data as well, and you can ask anything to this. Okay, and there is one more thing. If you will go here, this API section. Okay, yeah, so there is one thing, I guess here is a thing. So yeah, if you type this localhost 11434, so this is an API for the Llama. See, here you can see Llama is running. Fine. So this is how you can do this, perform or install your Llama 3.1 in your local system. See, it is now asking me, how is that? Did I cover what you wanted to know about ChatGPT? Okay, and you can give your prompt, and again you can do something. So okay, I will write what is hello world. See, hello world is a simple phrase that has become iconic in the world of computer programming. Everyone know to print hello world, I guess so. So this is how you can install Llama 3.1 in your local system. Okay, just you have to install Llama first, then search this Llama run 3.1, or if you want to explore more thing, you can write version, so the version, server, create, and all this thing. Okay, today we are talking about must-have Python AI projects and how to build them so that can really help you sharpen your skills and stand out in the growing field of artificial intelligence. So let's quickly see what is Python. Python is one of the most popular programming languages for AI because of its simplicity and the powerful libraries it offers, like TensorFlow, Keras, and PyTorch. Building projects using Python is a great way to get started if you want to break into the AI industry. Whereas artificial intelligence is transforming industries like healthcare, finance, and even entertainment. Companies are now looking for experts who know how to apply AI to real-world problems. In this video, we will explore beginner level to advanced level projects. So these projects are designed to give you hands-on experience in building intelligent systems, analyzing data, and even automating tasks. So without any further ado, let's get started. So let's start with beginner level projects. So number one, we have fake news detection using machine learning. So in today's world, fake news is a major concern, causing misinformation to spread rapidly across social media and news platforms. Detecting fake news is crucial to maintaining the integrity of the information we consume. So these projects aim to build a machine learning model that can identify fake news articles by analyzing their textual content, by learning from existing datasets of real and fake news. The model will be able to classify articles into these two categories, thus assisting media outlets and social media platforms in reducing the spread of misinformation. This project is perfect introduction to natural language processing (NLP) as it involves text data manipulation, feature extraction, and supervised learning. It can also be adapted for real-time use on website or social media platforms to flag suspicious articles and provide more reliable information to users. So now let's see how to build this. In this, first step is data collection. Use dataset like LIAR or fake news net that can contain label, real, and fake news articles. You can find dataset from the Kaggle. The second step is pre-processing. Clean the text by removing stop words, punctuation, and special characters. Tokenize and stem words using NLTK or spacing. The third step is feature extraction. Use TF, IDF, or bag of words to convert the text into numerical data for machine learning models. The fourth step is model training. Train a classifier like logistic regression, naive Bayes, or random forest on the dataset. The fifth step is evaluation. Evaluate the model using accuracy, precision, recall, and F1 score metrics to determine how well it classifies fake and real news. Tools you can use is NLTK, Scikit-learn, and Pandas. Skills you will gain from this are text preprocessing, NLP, classification models. And if you want to make us video on this project, please comment down below. In number 2, we have image recognition using CNN. Image recognition is one of the core applications of deep learning and computer vision, used in a variety of industries ranging from healthcare to autonomous vehicles. This project will guide you through building an image classifier using CNNs, a deep learning architecture designed specifically for image recognition tasks. The goal is to create a model that can accurately classify images, such as differentiating between cats and dogs. By working on this project, you will gain a solid understanding of the fundamental concepts of CNNs, such as convolutional layers, pooling, and activation functions. This project not only introduces you to the basics of CNNs, but also teaches essential skills like image preprocessing, dataset handling, and model evaluation, which can be applied to more advanced computer vision projects in the future. So now let's see how to build this project. In this project, first you have to import dataset. So use a dataset like CIFAR10 or Kaggle cats versus dogs with labeled images. The second step is pre-processing. Resize, normalize, and augmented images using libraries like OpenCV or PIL to prepare the dataset. The third step is model architecture. Design a basic CNN model with convolutional, pooling, and fully connected layers using Keras or TensorFlow. The fourth step is training. Split the dataset into training and validation sets and train the CNN model to classify images. The fifth step is model evaluation. Use accuracy, precision, and confusion metrics to evaluate how well the model predicts the correct class label. Tools you will use in this project are Keras, TensorFlow, OpenCV, Pandas. Skills you will gain after doing these projects are image preprocessing, CNN architecture, model evaluation. And if you want to make us video on image recognition using CNN, please comment down below. Second, we have intermediate level projects. In this first, we have AI-based recipe recommendation system. Recommendation systems have become an integral part of modern digital platforms. From e-commerce websites suggesting product to users to streamlined services recommending shows and movies. So in this project, you will build a recipe recommendation system that suggests dishes based on the ingredients a user has on hand. This project demonstrates how recommendation algorithms such as content-based filtering and collaborative filtering can be used to provide personalized suggestions. You will also learn how to pre-process data and clean textual data, such as ingredient lists, and implement a machine learning algorithm to match user inputs with recipe databases. This is an excellent project for understanding how recommendation systems work and how they can be applied in various industries, from food tech to personalized content recommendations. So now let's see how to build this. In this project, first step is data collection. Use web scraping tools like Beautiful Soup to scrape recipes from websites, or use datasets like Recipe1M. The second step is pre-processing. Normalize and clean ingredient data by standardizing ingredient names and handling missing values. The third step is recommendation algorithms. Implement content-based filtering and collaborative filtering to recommend recipes. Content-based filtering matches ingredient list, while collaborative filtering uses user preferences model. Fourth step is model training. Use cosine similarity to match user-provided ingredients with recipe ingredient in the dataset. And the next step is interface and tools. So create a simple web interface using Flask where users can input ingredients and receive recipe recommendation. Tools you will use: Beautiful Soup, Pandas, Scikit-learn, and Flask. So you will gain skills like web scraping, data cleaning, recommendation systems using this project, by doing this project. And if you want to make us video on this project, please comment down below. Number 4, we have chatbot with sentiment analysis. Chatbots have transformed how businesses and services interact with users, providing 24/7 support and personalized responses. In this project, you will build a conversational chatbot that can analyze the sentiment behind user inputs and respond accordingly. By incorporating sentiment analysis, the chatbot will not only understand the content of the user's messages, but also the emotional tone, such as whether the user is happy, frustrated, or neutral. This allows the chatbot to adjust its tone and responses to improve user satisfaction. For example, a chatbot could offer a more empathetic response if it detects a negative sentiment. This project will give you hands-on experience in building a conversational AI system while learning how to integrate machine learning techniques like sentiment analysis. The skills you develop in this project can be applied to customer service, healthcare, education, and more. So now let's see how to build this project. So before jumping to advanced level projects, here is a quick info for you. Dive into the future of AI with our generative AI and machine learning course in collaboration with and ICT Academy, IIT Guwahati. Learn tools like ChatGPT, OpenAI, Hugging Face, Python, and more. Join masterclass led by IITG faculty, engage in hands-on projects, and earn executive alumni status. This generative AI and machine learning course enriches your career journey with comprehensive coverage of machine learning, deep learning, NLP, generative AI, reinforcement learning, computer vision, and more. Combining theory with hands-on practice, it offers live virtual sessions, projects with integrated labs, and masterclasses by IIT Guwahati faculty. So find the course link from the description box below and the pinned comment. In this project, the first step is chatbot framework. Use tools like Dialogflow or Rasa to build a conversational chatbot capable of handling various user intents. The second step is sentiment analysis. Integrate a sentiment analysis model using pre-trained models like Veda or BERT. The third step is conversational flow. Adjust the chatbot's responses based on the sentiment, positive, negative, or neutral, detected in the user's input. The fourth step is integration and deployment. So build an interface, website, or messaging platform where users can interact with the chatbot in real time, and deploy the chatbot on a website or app, allowing user to engage with it and receive sentiment-aware responses. So you will use tools in this are Dialogflow, Rasa, Vader, Transformers, Flask, and you will gain skills like sentiment analysis, chatbot deployment, conversational AI. And if you want to make us video on this project, please comment down below. So now let's see some advanced level projects. In this we have AI-powered image colorization. Image colorization is a fascinating application of deep learning that transforms black and white images into color by predicting and applying realistic colors to grayscale images. This project explores how CNN and GANs can be used to learn mapping between grayscale and colored images. You will gather dataset of colored images, convert them into grayscale, and train the model generate color versions. This project is especially useful in areas such as film restoration, photography, and artistic creation, where colorization can breathe new life into old black and white images. Moreover, it highlights the power of deep learning in understanding and generating complex visual data, giving you insight into how these models work for tasks like image generation, video prediction, and beyond. The skills you learn in this project will also be useful for other creative AI applications like style transfer and image synthesis. So now let's see how to build this project. So in this project, first step is data collection. Use dataset of colored image, convert them into grayscale, and use the grayscale images as inputs while training the model to output colorized version. The second step is pre-processing. Normalize images pixel values and resize them for training. The third step is model architecture. Implement a UNet model or generative adversarial network (GANs), which are well suited for image generation tasks like colorization. Fourth step is training and evaluation. Train the model on grayscale images as input and colored images as output using mean squared error method for guidance. Evaluate with visual inspection and peak signal to noise ratio. The last step is deployment. So create a web interface where user can upload black and white images and get them colorized. So you will use tools like TensorFlow, Keras, OpenCV, and Flask. So we'll gain skills like deep learning, CNNs, JNs, and image preprocessing. And if you want to make a video on AI-powered image colorization project, so please comment down below. And the last we have object detection using YOLO. You only look once. Object detection is one of the most popular computer vision applications, allowing machine to recognize and locate multiple objects within an image or video stream in real time. YOLO is a state-of-the-art object detection algorithm known for its speed and accuracy. This project involves building a real-time object detection system capable of identifying multiple objects in images or videos feeds by drawing bounding boxes around them. Object detection has widespread use in fields such as security surveillance, autonomous driving, and augmented reality, where systems need to understand and interact with their surroundings in real time. By working on this project, you will learn how to pre-process image data, format bounding box labels, and train a YOLO model using a dataset like Coco or Pascal. You will also gain a valuable experience in deploying object detection systems that process video streams, giving you the skills to build application in dynamic environment, from traffic monitoring to industrial robotics. So now let's see how to build these projects. So in this project, we will first import dataset. So use a dataset like Coco or Pascal VOC, which contains label objects in images with bounding boxes. The second step is pre-processing. Resize image and normalize pixel values, ensuring bounding box labels are appropriately formatted. The third step is model architecture. Use the YOLO, you only look once architecture, which splits images into a grid and predicts bounding boxes and class probabilities for each object. The fourth step is training and evaluation. Train the YOLO model on labeled data using a framework like Darknet. Evaluate the model using metrics like intersection over union and mean average precision. The last step is deployment. Develop a system that can process video streams in real time, detecting objects and drawing bounding boxes around them. Tool you will use OpenCV, TensorFlow, and Darknet. You will gain skills like object detection, YOLO architecture, real-time video processing. And if you want to make videos on this project, please comment down below. So in conclusion, these Python AI projects not only help you build hands-on skills, but also provide a solid foundation for advancing your career in artificial intelligence. Whether you are working on fake news detection, image recognition, or developing advanced tools like chatbots and object detection systems, these projects offer real-world applications that companies are looking for. Start small, keep learning, and as you complete each project, you will get better prepared to take on the challenges in the growing AI field.
Imagine waking up in the morning, checking your phone and seeing that your AI agent has already applied to 50 jobs for you, automated your business operations, generated YouTube videos, and even invested in stocks, all while you were sleeping. It sounds futuristic, right? Think again. The AI gold rush is here, and those who take advantage of it right now will be the ones profiting the most in the next few years. AI agents and DeepSeek AI are transforming how people earn money, build businesses, and also create passive incomes. And the best part is, you don't need to be a tech genius to take advantage of this opportunity. So whether you're a freelancer, entrepreneur, or content creator, or even investor, or someone looking for passive income, this guide will walk you through step by step on how to make money using AI agents and DeepSeek AI, even if you have zero experience with AI. So in today's video, we are diving deep into AI agents, what they are and why they are the future, how they work in real-world scenarios. You learn how to spot profitable AI agent opportunities before they go mainstream and also explore multiple ways to make money with AI. So whether you have coding skills or not, we'll break down 6 proven methods to earn using DeepSeek AI and discuss smart investment strategies to help you back AI projects while avoiding scams. I'll walk you through building an AI-powered passive income business and creating AI video avatars to monetize YouTube using DeepSeek AI. Finally, we will cover the strategies to scale your AI business and maximize your profits in this growing industry. Make sure to watch till the end. These live demos could be your game changer. You need to start earning with AI today. So let's get started. Before we talk about how to make money using AI, let's first understand what AI agents are and why they are such a game changing. So if you have used ChatGPT, Google Assistant, or Siri, you already know that AI can generate text, answer questions, and assist with tasks. But AI agents can take it a step further. They don't need to just provide answers, they take real-world actions on your behalf. AI models are the brain versus AI agents are the brain plus body. To break it down, here's the difference. AI model which acts as the brain, these include ChatGPT, Claude, and DeepSeek AI. They generate text, answer questions, and provide insights but do not take real-world actions. AI agents are the brain plus body. AI agents go beyond just thinking. They click, type, automate workflows, and make decisions. They act just like a human assistant would, but 100x faster and more efficiently. So let's get started. Okay, so now let's look at a real-world example of an AI agent at work. Let's say you're looking for a job, but you don't have the time to apply to multiple positions manually. Here's what an AI agent could do for you. It will automatically log into your job portals like LinkedIn, Indeed, ZipRecruiter, and it will find the job listing matching your skills and experience, and then it will automatically apply to all the related jobs. So let's look at one such tool over here, which is auto apply. Let's see how it does it. Alright, so here as you can just simply write your description over here, whatever job description you want to, and then you can just select on this click resume. So it will create a resume in such a way that you can apply in different job posting, autofill application, submit them automatically. So, okay. So this is how autoapply.com works actually. Let's look at the another tool on our list, which is aiapply.com. Okay, so this is another tool known as AI Apply Dashboard. From here, you can just simply upload your resume. So as you can see, I have just uploaded my resume here, and it will actually analyze my resume and it will create a base template. And then you can just simply provide all the essential information you want to. And see, here we are redirected to this page over here, and you can also create your customized cover letters for each job posting. You can also track responses from recruiters and notify them for interviews. See, here is an option known as auto apply. So it will also maintain a track. Okay, for this you have to actually pay by subscription. So we're looking for the free tool over here. So I haven't saved anything, and you can also save your job. We have another option as Interview Buddy, which is a Chrome extension which will help you answer questions confidently. So this is why AI agents are the future. They save time, effort, and money, making them a powerful tool for earning income. So now let's talk about how to spot the next big AI agent opportunities before everyone else. So now that you understood what AI agents are, the next step is to find profitable AI agent opportunities before they go mainstream. Many people miss out on early stage opportunities simply because they don't know where to look. So basically, you can just go on Google Trends, and from there, you can actually search for terms such as, let's suppose you're searching for AI agents from here. And we will just see what is the situation of this particular term, how many people are searching for this for the past 12 months, or maybe for the past 7 days. Let's check the graph. Okay, so this is the graph for the past 7 days. As you can see, it is at all-time high here, February 17. See, this is at 9:30 a.m. All right, this is February 13. Okay, let's suppose we are checking for the past 30 days. So this is the graph for this thing and how many people are searching for this thing. Alright, so terms such as AI agents, autonomous AI automation on Google Trends, Twitter, this topic is growing rapidly. That means this is a very hot topic and you can get started with all of these new technologies. Second of all, we're talking about is using AI agent tracking platforms. You can use tools such as Waifu, Cookie.fun, Sentiment Market to see which AI agent projects are gaining traction. So let's suppose we have one website which is Cookie.fun. So let's see what this web page will do. So basically it has all the new AI agents listed on this page over here. See, as you can see, the agents listed, top AI agents by mindshare for the last 24 hours. And these are the top AI agents we have today. So basically, you can use this to create AI agent projects. You know how many people are investing in this thing. You can just get a track of all these particular AI agents. Also, GitHub and white papers, real AI projects have publicly source code and frequent updates. So if you see an AI project with 0 updates, that means it's a red flag. Alright, so you can just simply check for a particular project if you want to. Let's suppose you're searching on Google on AI agents project. So let's suppose this is our AI agent project. and we'll just copy paste it from here. And then you can just simply ask ChatGPT whether this project is really running or not, whether this is true or fake or just uploaded in the internet. So just check, is this project really working? And then ChatGPT will just check if this project have the actual public source code or not, or frequent update. So let's see. That curates a comprehensive list of AI autonomous agents and agent building framework. So it means that, yeah, this code is really working, so we can get along with this thing. So once you find a promising AI agent project, the next step is to turn into a money-making business. So now let's look into how you can make money with AI agents. So now we have come to the most exciting part, which is how you can turn AI agents into a money-making machine. There are multiple ways to make money with AI agents, and I'm going to break down the best strategies step by step. So the first strategy is build and sell AI agents as a SaaS business, which is software as a service business, which is your passive income model. So one of the most profitable ways of making money is by creating an AI-powered automation tool and selling it on subscription model. How it works is basically it will identify a problem business face. Example, let's suppose a customer support or lead generation or resume application. So it will identify this particular business problem, and then it will build an AI agent that automates this particular task. And then it will access the AI agent as a monthly subscription. For example, imagine a company that receives 500 customer emails daily. So instead of hiring a customer support team, they can use your AI agent to reply instantly. For this, you can charge them for like around $100 a month per user. So if 50 businesses sign up, you can make around $5,000 per month passively. So building an AI agent that can automate customer support is a good way to go. So the best platforms where you can build AI agents would be Crew AI, Agency Form, or OpenAI API. Also, we have one more video on this, how you can leverage ChatGPT for customer support, how we are creating an agent to that. So we have a separate video for that. It's mentioned in the link there. So you can just check it. All right. So let's talk about the second strategy, which is you can tokenize your AI agent and then you can monetize it. That is the crypto model. So this is another innovative way to profit by attaching a cryptocurrency token to your AI agent. So how it works is basically you can create an AI-powered platform. Users will pay with crypto tokens to access your AI services, and then you can earn a percentage of every transaction. For example, an AI-powered trading bot that buys and sells stocks or crypto based on market trends. So users pay in tokens for AI-powered trades. You can also earn a percentage of every particular trade. So as we have already discussed, see, these are the top AI agents: Virtual Protocol, Chain, Humans.ai, and I think we have gone through this Cookie.fun. So basically, Cookie.fun, as I have already told you before, is a platform which will track and rank AI agents using metrics like market capitalization, social engagement, token holder growth, and also impressions. Now moving on to our third strategy, which is you can invest in AI agent projects, the venture capitalist strategy. So just like a venture capitalist, how they invest in early stage startup, you can also invest in an AI agent project before they go mainstream. So what are the steps how you can invest in AI agent tokens? The first step would be you have to find early stage AI agent projects. The second step would be you have to research their legitimacy. You have to check GitHub, white papers, social activity. And then the third step would be investing before they gain mainstream transaction. And the fourth step would be sell when demand and price will increase. So the best platform for such AI agent investments would be the first one on the list is Dex Screener. So just simply click on this link, Dex Screener, and here it will, it's a website that will track trending AI agent coins. As you can see, these are the trending Grok 3 AI, the agent coins, and these are the volume makers, how many people are making money by investing on these coins. So basically, Dex Screener is a popular analytical tool, once again, just like Cookie.fun, for decentralized exchanges, and it will help users to track trending AI-related cryptocurrencies, including AI agent coins, and it will also provide real-time data on price movements, trading volume, and liquidity across various blockchain networks. So basically, this platform is especially useful for investors and developers looking to identify emerging AI agent tokens in the crypto space. Okay, so next on the list, we also have Sentient Market, which will measure the AI agent projects over here. See, we have the agents. And so this is a platform that will analyze the engagement and adoption levels of AI agent projects. And it will evaluate user activity, interactions, real world usage to determine how well these AI systems perform. So by tracking engagement metrics, Sentient Market help investors, researchers, and also enthusiasts gauge the potential and credibility of AI-driven projects. So now let's understand whether you have to be really a tech coder to make money for AI agents or not. So even if you're not from a technical background, you still can earn money by making AI agents. You don't need to be a coder to profit from AI agents. So first of all, you can also sell AI automation services. So instead of just building AI agents, you can sell AI automation solution to businesses. For example, you can automate social media marketing, customer service, or email responses for small businesses. So as you can see, you can use AI in customer service automation also, machine learning for customer experience, multilingual queries. We have so many options from here. The second step is you can start an AI consulting business. So businesses need guidance on how to integrate AI. You can charge for AI strategy sessions and consulting services. You can also create AI content and monetize it. This is very important because content creators are making thousands of rupees per month just by educating people about AI agents. You can start a YouTube channel, review AI tools, you can sell AI tutorials and courses, you can monetize AI content with sponsorships and also affiliate marketing. Now let's look how DeepSeek can help to make money. DeepSeek AI is another powerful tool for making money online. Here's how you can earn profit. First of all, you can create AI-generated video avatars for YouTube. So you can use DeepSeek to generate video scripts, use platforms like HeyGen to create AI avatars that present your content. You can also monetize videos through YouTube ads and affiliate marketing. So here we have this DeepSeek model, and we'll just see how whether it is good for content creation or not. So we'll just simply write me a video script on topic generative, let's suppose generative AI in 2025, and let's see what type of content does DeepSeek actually generates for us, since it is very efficient in creating content, building and monetizing websites also as well. So as you can see, the script is designed to be engaging, informative, and visually dynamic. So I've just given one prompt, and then here it has already, given me all the script. It knows how to make a script that I don't have to again write, making it engaging or informative. So I think it's really cool. Second is you can also build and monetize AI-generated websites using DeepSeek. So DeepSeek AI can generate SEO-optimized content, monetize your site using Google AdSense, and affiliate marketing as well. Websites created with AI have earned around $21,000 plus in passive income. So you can proceed doing these things. Third is leveraging social media for AI-generated content. You can create AI-generated Instagram Reels, TikTok, Twitter threads. You can also monetize social media accounts through brand deals and sponsorships. Fourth one is you can also sell AI-generated services on Fiverr as well as on Upwork. This offers AI-powered copywriting, marketing, or business automation services. AI freelancers can charge around $500,000 plus per project. It can offer AI automation for small businesses. You can also help business automate content creation, customer support, and email marketing. You can charge monthly retainers for AI automation. The sixth one on the list is you can combine SEO with AI-generated video content. You can rank both on YouTube and Google by using DeepSeek for blog content plus AI video scripts. Double traffic will give you double income. So as you can see how AI agents and DeepSeek are the future. AI agents and DeepSeek are changing the way people make money online. So whether you want to build and sell AI agents, invest in AI agent projects, use AI to automate and scale your income, or leverage DeepSeek for content and marketing, this is now your time to start.
By 2025, if you are not using AI to code, you might be falling behind. That might sound extreme, but the truth is, AI is changing how we develop software at lightning speed. Whether you are a beginner or an experienced programmer, AI tools are opening up new opportunities you might not have thought possible. In this video, I will show you the top AI coding tools that will make you feel like you have got a full team of developers at your disposal. No matter if you're working on web apps, mobile projects, or data science, AI coding assistant can seriously boost your productivity. Before we get into the list, let me quickly explain what AI coding tools actually are. These tools use advanced machine learning to enhance your coding experience. They can suggest smart code completion, generate full code snippets, and handle repetitive tasks for you. Think of them as a helpful assistant, always there to make coding faster and easier. So now let's check out the best AI coding tools used in 2025. Before jumping to the demo part, here is a quick info for you. Dive into the future of AI with a generative AI and machine learning course in collaboration with ENICT Academy IIT Guwahati. Learn tools like ChatGPT, OpenAI, Hugging Face, Python, and more. Join masterclasses led by IITG faculty, engage in hands-on projects, and earn executive alumni status. This generative AI and machine learning course enriches your career journey with comprehensive coverage of machine learning, deep learning, NLP, generative AI, reinforcement learning, computer vision, and more. Combining theory with hands-on practice, it offers live virtual session, project with integrative labs, and masterclasses by IIT Guwahati faculty. So find the course link from the description box below and the pin comment. So welcome to the demo part of best AI coding tools for 2025. So in this, I will show you top 5 coding AI tools, right? First, we will start with ChatGPT. So I'm not talking about the simple one because simple one is everyone know, but recently ChatGPT launched GPT-4o with Canvas. So we'll open this. Here I will write, give me login page code using HTML, CSS and CSS. Okay. See the magic. See, like this. So right now it's in beta version. Okay. So I guess those who have paid version, so they can, use this. So now, see here. What if I want to change this background color? Only particular background color. I don't want to change all the code, but I just want to change this color, H2 color, or you can say display it will block or something else. Okay, I want to change the padding of this particular class, right? So here what I will do, I will select this and one pop-up will come, ask ChatGPT. So now you can just here you can write, please change background color to blue. I don't know which color is that, but again I want to change it to blue. See, it will change only the background color. See, rest will be the same, right? See here, edited. So this is the best upgrade I can see with ChatGPT with coding for coding. Okay, so let's see one more. Okay, so here what I will do. Let's change the padding. Okay, here I will write increase. What is this? Border radius. Border radius. Okay, see here is 8. It will increase. See, it did 16, and the rest all is same. So this is one tool. Okay, ChatGPT 4o with Canvas. The second is Gemini. Okay, I'm not going to use Gemini into Gemini prompt, but I will open one thing, Google Colab. Okay, so here is Google Colab, and I will open new notebook. So here you will get Gemini inbuilt. Here you can see Gemini inbuilt. But first you have to log in. See, start coding or generate with AI. If I'll click on generate with AI, so it will ask me like this. So I will write, give me code to find odd and even in C++. Okay, you can write anything. So I will write enter. See, it's generating and code is here in minute of seconds. Okay, if I will write in Java, the code is here in minute of seconds. Okay, in seconds it will give you. So this is the second. You can use Gemini as well in the while giving prompt here, or you can open Gemini, right? You can open Gemini as well, but it's better if you are using Gemini for code, so use in Google Colab. Why? Because you can use or you can run code directly. Okay, let's try to run it. Let me run it. See, it's running. Wait. Okay, some error is there. Invalid syntax. Why? Okay, why it's giving error? Because I opened this, it's notebook only. Okay, this is the Python notebook, right? That's why it's giving error. Okay, let me run this in Python. Oh my god. See, it's running nicely in Python because it's Python notebook. Okay, so these are the odd numbers and these are the even numbers, and numbers are already given here, right? So this is the second one, and the third one is Claude. Okay, I have to log in it first. So here, so in Claude as well, we have many models. You can say Claude 3.5 Sonnet and Haiku is there, and some more things are there. Okay, and here I will write. Okay, please give me code to make snake game in Python. Okay, so see, now it's generating. So some tools are to generate code from the scratch, and some tools are the suggestions tools. Okay, we will see the next one, the suggestion tool, what I am talking about. Okay, so here all the details for this particular code, and yeah, so third model is Claude. So this is how you can use Claude. So there are many models of Claude, like I told you already, 3.5 Sonnet is there, Haiku is there, and there is one more. Okay, where I can't see. Okay, but again, it's it's paid thing. Okay, and the next is Codium. Okay, so I will show you Codium. This is the Codium, right? This Codium is this. So I have already installed this Codium into my VS Code. Okay, see, Codium generate control plus I. See, this is the command. Just write. This is again Python one. Okay, give me code to find the prime numbers in Python. Okay, just submit, and the code will be here. See, okay, code will be here. Or if you write here, find the prime numbers. See, it will give you suggestion. Okay, if I will write def, define prime, and then see, again suggestion. If I will write this, again suggestion, then yeah, the code is complete. Okay, so it will give you suggestions as well. Okay, this is a Codium. So just like Codium, so this is our fourth tool, Codium, and just like Codium, there is one amazing tool which is called AWS Q Developer, Amazon Q Developer. This is the amazing tool. Okay, so recently they jumped into this thing, AI coding, and you can install it to Visual Code directly as well. Okay, you can go here, and from where the extensions are there, you can write Amazon Q here. Okay, this thing you can install. Okay, it's like this Codium only. Yeah, let me show you some videos. Where are the videos? Okay, so how Codium works. Okay, not here. I will show you in this. See, this is how Codium works. Again, same thing. See, if you write this, again the suggestions will come. Okay, lambda function to publish user, like Codium. Okay, so the fifth one is our Amazon Q. Okay, so there are many models like Copilot. This GitHub Copilot is there. Copilot is there. GitHub Copilot is there for this AI coding, AI developer tool. And if you are curious to make a website within a second, so there is one more app called, not app, this tool, you can say, WebSim. Okay, see what you like to create today. I will write here Amazon, but okay, let me first, yeah. So, but they use Sonnet 3.5, means Claude. They are using Claude. So I will write here, I want to create Amazon.in. See, it will create website for you. No coding, nothing, all. Directly it will give you website. Okay, it's loading, I guess. So this is how you can use WebSim. Right? See, OnePlus Node, this came. Okay. I just gave Amazon.in and the website is here within a second. Okay. So these are some, important tools to learn or how to use them in 2025, for 2025. Using AI tools for coding is essential to be in the race.
So that's a wrap up on this full course. If you have any doubts or questions, you can ask them in the comment section below. Our team of experts will reply you as soon as possible. Thank you and keep learning with Simplilearn.
Staying ahead in your career requires continuous learning and upskilling. Whether you're a student aiming to learn today's top skills or a working professional looking to advance your career, we've got you covered. Explore our impressive catalog of certification programs in cutting-edge domains, including data science, cloud computing, cybersecurity, AI, machine learning, or digital marketing. Designed in collaboration with leading universities and top corporations, and delivered by industry experts, choose any of our programs and set yourself on the path to career success. Click the link in the description to know more.
Hi there, if you like this video, subscribe to the Simplilearn YouTube channel and click here to watch similar videos. To nerd up and get certified, click here.